11 cu. Ids of concrete amounts to 57 cts per cu yd. It will be noted that 2 mixers were kept busy. Their average output was 100 cu. Ids, each per day, which is the same as for the mixers on Section 14. The total cost of concrete on Section 15 was as follows. Per cu yd. Labor quarrying, crushing, and mixing $0. 991 explosives 0. 083 Utica cement at $0, 60 per BBL, 0. 930 Portland cement at $2, 25 per BBL, 0. 180 sand at $1, 35 per cu yd, 0. 476. Total $2,660 first cost of plant $0. 567. It is not strictly correct to charge the full first cost of the plant to the work as it possessed considerable salvage value at the end. Comparison. For the purpose of comparing sections 14 and 15, the following summary is given of the cost per cubic yard of concrete. Sec. 14. Sec. 15. General Foss $0. 078 $0. 082 Wall Foss 0. 108 0. 116 Mixing Foss 0. 121 0. 250 Timbering Foss 0. 150 0. 140 Hauling Foss 0. 142 0. 081 Crushing Foss 0. 073 0. 128 Quarry Foss 0. 303 0. 275 Cement Natural 0. 863 0. 930 Cement Portland 0. 305 0. 180 Sand 0. 465 0. 476 Plant Full Cost 0. 407 0. 567. Total $3. 015 $3. 225. It should be remembered that on Section 14 there was no drilling and blasting of the rock, but that the quarry foss not only loaded but hauled the stone to the crusher. The cost of mixing on Section 15 is higher than on Section 14 because the materials were dumped on platforms and shoveled into the mixer, instead of being discharged from bins into the mixer as on Section 14. Fig. 108. Cross-section of retaining wall, New York Central Terminal work. Fig. 109. Portable concrete mixing tower N.Y. Central Terminal work. Grand Central Terminal, New York N.Y. In building a retaining wall of the cross-section shown in Fig. 108, a traveling tower moving on tracks parallel to the wall contained the concrete mixing plant. The construction of the tower is shown in Fig. 109. The tower had 2 platforms, one at the top carrying 2 10 cu yd bins for sand and stone, and the other directly below carrying 40 cu ft. 4 cu ft cement, 12 cu ft sand, and 24 cu ft stone. Ransom mixer driven by a 30 HP motor and a Lidgerwood motor hoist. The elevator tower carried 240 cu ft. Ransom dumping buckets traveling in guides and dumping automatically into the bins. These buckets were operated by the Lidgerwood motor hoist on the mixer platform. Sand and broken stone on flat cars were brought alongside the tower. The sand was shoveled direct from the car into the sand bucket, but the broken stone was shoveled into wheelbarrows, which were wheeled over a light bridging from car to bucket and dumped. Wheelbarrows were used for handling the stone chiefly because the capacity of the plant was so great that enough men could not be worked in the limited space around the bucket to keep up the supply by shoveling. The wheelbarrow work added materially to the cost. Cement was carried from the cars to the sand bucket, hoisted and stored on the mixer platform, which provided storage room for 100 bags. A 1 to 3 to 6 mixture was used. The sand and stone were chuted directly from the bins to the charging hopper, and the cement was charged by hand. The mixed concrete was delivered to 2-1 Coup, YD, dump cars running on a 2FT, gauge track laid in sections on Thecros pieces connecting the uprights of the forms. The track had no switches, so that one car had to wait for the other. 4 men were required to push each car, and 2 more men assisted in dumping the car and kept the track clear. The wall was built in sections 51 FT, long, each containing 250 Coup. IDs. One of these sections was filled in 8 hours with ease, and by a little hustling a section was filled in 6 3/4 hours, which is at the rate of 37 Coup. IDs of concrete per hour. Working 8 hours per day, the cost of mixing, transporting, and placing concrete with this mixing plant, with wages for common labor of $1.50 per day, was as follows total, per Coup, YD. 2 men carrying cement $3.000, $0.12. 6 men shoveling sand $9.000. 0.36. 17 men shoveling stone $25.000. 111 men wheeling stone $16.000. 0.64. 2 men at stone and sand bins $3.000. 0.12. 2 men opening cement bags $3.000. 0.12. 1 man dumping hopper $1.50. 0.006. 1 man dumping mixer $1.50. 0.006. 1 man cleaning chute, mixer, etc. $1.50. 0.006. 1 motorman or engineer $3.000. 0.12. Total labor mixing $66.50. 266. 8 men pushing 2 cars $12.000. 0.48. 2 men cleaning track, etc. $3.000. 0.12. 7 men spading concrete $10.50. 0.42. Total labor transporting, placing $25.50. 102. 1 foreman $5.000. 0.20. Electricity estimated $7.000. 0.28. Total general $12.000. 0.48. Grand total $104.000. 416. It will be noted that the cost of shoveling and wheeling the broken stone amounts to 16.4 CTS per Coup, YD, or nearly 40% of the total cost of mixing and placing. The cost of spading the concrete is also high for a sloppy mixture, but is probably accounted for by the fact that the concrete had to be spaded so as to have 2 or 3 ins of clear mortar next the forms. The forms used in constructing the wall are shown by Figs 110 and 111. They were made in panels 51 FT. Long, and a locomotive crane was used to shift the panels. This crane worked handling forms only a small part of the time, but a form gang of 10 carpenters was kept busy all of the time moving and reassembling. Assuming the work of the crane to amount to $5 per day, and the wages of the carpenter gang to amount to $25, we get a cost of 12 CTS. Per cubic yard of concrete for shifting forms. It should be noted carefully that the costs given for this work do not include cost of materials, interest on plant, superintendents, and other items. Fig. 110. End view of forms for retaining wall, New York Central Terminal work, wall for railway yard. For building a retaining wall 7 FT, high forms were made and placed by a carpenter and helper at $8 per m. wages being 35 CTS and 20 CTS an hour, respectively. Concrete materials were dumped from wagons alongside the mixing board. Ramming was unusually thorough. Foreman expense was high due to small number in gang, 2 coup. IDs were laid per hour by the gang. Fig. 111. Corner detail of retaining wall forms, New York Central Terminal work. Per day, per coup, YD. 7 mixes, 15 CTS, per hour $10, $50, 53 2 rammers, 15 CTS, per hour 3,000. 15 1 foreman 30 CTS, per 8 Shah, 1 waterboy 5 CTS, 3,50. 17. Total labor $17. $000. 85. The total cost was as follows per cubic yard. Per coup, YD, 0. 8 BBLS, Portland cement at $2 $1. 60 sand 0, 30 gravel 0, 70 labor mixing and placing 0, 85 lumber for forms at $16 per M, 0, 56 labor on forms at $8 per M, 0, 28 total per cubic yard $4. 29 The sheathing plank for the forms was 2 in. Hemlock concrete footing for rubble masonry retaining wall. In constructing a footing for a retaining wall at Grand Rapids, Mich. A 1:2 of 5 natural cement concrete was used. It was found that 1 coup, YD of concrete was equivalent to 29, 8 coup FT of material composed of 3, 6 coup FT, or 1 BBLS of cement 8, 4 coup FT or 2, 7 BBLS of sand and 17, 8 coup FT, or 5 BBL of broken stone. The labor cost of 15, 5 coup IDs of concrete was as follows. Item, total, per coup, YD, foreman 14 hours at 40 CTS, $5, $60, 36 13 foreman 20 hours at 22, 5 CTS, $450, 2903 laborers 49 hours at 12, 5 CTS, 6, 11 0, 3942 mason 2 hours at 35 CTS, 0, 70 0, 0451, total labor $16, 91 $1, 0909 all material was furnished by the railway company, the contractor furnishing labor only. His contract price for this was $1 per coup. YD. Track elevation, Allegheny Pa. The wall was 6,100 FT, long and 75%, was on curves. The first wall built had a top width of 2.5 FT and a bottom width of 0, for the height with the back on a smooth batter. Later the back was stepped and last the wall was proportioned as follows, calling the height from top of foundation to under coping, then width of base was 0. 45 H plus 3, the top measuring 2.5 FT. The back was arranged in steps 24 ins, 30 ins, and 36 ins. High and the thickness of wall at each step was, calling H equal to height of step from base 0, 45 H plus 3. Several forms of expansion joints were tried. The first was tarred paper extending through the wall every 50 FT. The second was a half-in, boards running through the wall every 50 FT. The third was a half-in, board extending 2 FT, into the wall with a quarter-in, cove at the angles every 25 FT. The third construction gave perfect satisfaction. A 1:2 to 5 natural cement and a 1:3 to 6 Portland cement concrete mixed fairly wet were used. The concrete was laid in 8 tin, courses and faced with a 1:2 mortar. The forms were 2 in. White pine faced and jack planed on the edges. Upon removal of the forms, board marks and other defects were removed and a wash of neat cement was applied. One contractor used hand mixing. The sand and gravel were measured in wheelbarrows and wheeled onto the platform. The sand and cement were spread in thin layers, one over the other, and thoroughly mixed dry. The gravel was then spread over the mixture. The whole was shoveled into barrows or the pit again shoveled into place and rammed. The other contractor used a cubical mixer, a charging box holding 1/4 cu ids, and graduated to show the correct proportions of sand and gravel was filled by shoveling. Cement was placed on top, and the box hoisted and dumped into the mixer. A barrel holding the correct amount of water was emptied into the mixer, which was turned 10 or 15 times, and discharged into cars. The costs of mixing by hand and by machine were as follows. Hand mixing, total per cu yd. A half foreman at $3 $1, $50 0.25 3 men wheeling barrows at $1, 54 50 0.75 10 men wheeling materials at $1, 50 15 0.00 253 men mixing sand and gravel at $1, 54 50 0.75 6 men mixing concrete at $1, 59 0.00 151 man sprinkling at $1, 51 50 0.25 total $36 0.00 600. The output of the hand mixing gang was 60 cu ids per day. Machine mixing total per cu yd. One foreman at $3, $50 3 $50 0.35 one stationary engineer at $3 3 0.00 0.30 a half foreman at $1, 75 87 0.09 15 men loading charging bucket at $1, 50 22 50 225 2 men dumping charging bucket at $1, 75 3 50 0.35 2 tagmen at $2 a half time 2 0.00 0.21 man at trap at $2 a half time 1 0.00 0.10 total $36 37 $0 364. The output of the cubicle mixer was 100 cu ids per day. The costs of placing concrete in the forms above the foundation by hand below 12 ft and by cars and derricks any height were as follows. By hand barrows below 12 ft, total per cu yd. 4 men loading concrete at $1, $50 6 0.00 101 foreman a half time at $3 1, 50 0.25 10 men wheeling at $1, 50 15 0.00 251 man scraping barrows at $1, 51 50 0.25 2 men placing concrete at $1, 53 0.00 0.51 man placing mortar face at $1, 51 50 0.25 2 men mixing and carrying mortar at $1, 53 0.00 0.50 total $31 50 0 525 by cars and derricks, 1 horse and driver at $3 $3 0.00 0.32 men dumping concrete a half time at $1, 51 50 0.15 1 fireman a half time at $1, 75 88 0.009 tagmen at $1, 54 50 0.45 8 men placing and ramming conch at $1, 50 12 0.00 122 men mixing mortar at $1, 53 0.00 0.32 men placing mortar at $1, 53 32 men carrying mortar at $1. 53, 31 foremen at $3. 31 stationary engineer at $3. 32 men attending hook at $1. 53, 30, total $39. 88 $0. 399 The costs of placing concrete in the foundations were as follows. By hand, total, per coup, YD, 1 foreman a half time at $3, $1, $50 0.25 4 men shoveling concrete at $1, 56 0.00 101 man placing concrete at $1, 51 50 0.25 1 man ramming concrete at $1, 51 50 0.25 total $10, $50 175 by machine 1 horse and driver at $3, 3 $0.33 men pushing and unloading car at $1, 54 50 0.45 5 men placing and ramming at $1, 57 50 0.75 1 foreman at $3, 3 0.32 men dumping mixer at $1, 53 0.30 total $21, $0.00 210 cost of retaining wall. The following figures of the cost of a concrete retaining wall are given by C. Williams cost of material. Kind and amount of material, unit price. Cost, stone 441 tons, $7,308, 70 sand 182, 5 ids 55 100, 37 cement 536 BBLS, 85 453, 60 total $862. 67 lumber 3/4 value $205. 33 wheelbarrows 3/4 value 6 at $3. 50-15. 75 total $221. 08 excavation labor 4,002 hours at 15 CTS. $600. 30 carts 800 hours at 12.5 CTS. 100. 00 foreman 460 hours at 35 CTS. 171. 00 waterboy 240 hours at 10 CTS. 24. 00 total $895. 30 concrete labor 2,398 hours at 15 CTS. $359. 70 foreman 224 hours at 35 CTS. 77. 40 total $437. 10 handling material, unloading cars 380 hours at 15 CTS. $57. 00 foreman 40 hours at 35 CTS. 14. 00 total $71. 00 forms carpenters 997 hours at 22.5 CTS. $224. 33 work to support bridge carpenters 542 hours at 22.5 CTS. $121. 95 labor 458 hours at 15 CTS. 68. 70 total $190. 65 superintendents and office superintendent 30 hours at 50 CTS. $15. 00 office 20. 00 total $35. 00 grand total $2,937. 13 proportional costs item cost per yard of concrete percent of total cost Concrete materials $862. 67 $2, 0246. 7 laying concrete 437. 10 1, 0323. 4 lumber 205 33 48 11. 3 building forms 224 33 53 12. 3 handling material 71 00 1703. 8 wheelbarrows 15 75 0401 0 supt etc 35 00 0701. 5 total $1,851 $18 34 100 00 work on bridge 190 65 excavation 895 30 $2,937. 13. Chapter 42. Contractor's skill or want of skill in systematizing and managing labor counts as high in street work as in any class of concrete construction. As previously demonstrated, the cost of mixing is a very small portion of the labor cost of concrete in place. The costs of getting the materials to the mixer and the mixed concrete to the work are the big items, and in street work the opportunity for increasing the cost of these items through mismanagement is magnified by the large area of operations involved per cubic yard of concrete placed. 1 cubic yard of concrete makes 6 SQ, IDs of 6 in. Pavement foundations and 100 cu. IDs of concrete make a 6 in. Foundation for 300 FT of 30 FT street while 4 to 5 cu. IDs will build 100 FT of ordinary curb and gutter. Thus the haulage per cubic yard is considerable at best, and lack of plan in distributing stockpiles and handling the concrete can easily result in such increased haulage expenses as to change a possible profit into a certain loss. A little thought and skill in planning street work pays a good profit. Mixtures employed. A comparatively lean concrete will serve for pavement foundations. Mixtures of 1 to 4 to 8 Portland cement or 1 to 2 to 5 natural cement are amply good, and it is folly ordinarily to employ richer mixtures. Until recently, natural cement has been used almost exclusively. A 1 to 2 to 5 natural cement mixture requires about 1.15 BBLS of cement per cubic yard of concrete. A 1 to 4 to 8 Portland cement mixture requires about 0.7 BBL of cement per cubic yard. In the opinion of the authors, a considerably leaner mixture of Portland concrete is sufficiently good when it is well mixed in machine mixers for a 6 in. Foundation 0.5 BBL per cu. YD. The mixtures actually employed are proportioned about as stated, and their cost, or that of any other common mixture, may easily be computed from tables Roman 12 and Roman 13. Giving for different mixtures the quantities of cement, sand, and stone per cubic yard of concrete. The product of these quantities and the local prices of materials in the stockpiles gives the cost. When the concrete is mixed by hand, the ordinary labor cost of foundations is 0.4 to 0.5 of a 10-hour day's wages per cubic yard of concrete. Occasionally, it may be as low as 0.3 of a day's wages where 2 mixing gangs are worked side by side under different foremen and with an exacting contractor. Data for machine mixing are too few to permit a similar general statement for machine work, but in one case coming under the author's observation, the cost figured out to a little less than 0.2 of a day's wages per cubic yard. Distribution of stockpiles. Assuming a 30 FT street and a 1 to 3 to 5 concrete laid 6 ins. Thick, the quantities of concrete materials required per lineal foot of street are cement 0, 60 bbl, sand 0, 27 ku, yd, stone 0, 44 ku, yd. The stockpiles should be so distributed that each supplies enough materials for a section of foundation reaching halfway to the next adjacent stockpile on each side. And they should not contain more or less material. Otherwise, a surplus remains to be cleaned up or a deficiency to be supplied by borrowing from another pile. A little care will ensure the proper distribution, and it is well paid for in money saved by not rehandling surplus or borrowed materials. For a given mixture and a given width and thickness of foundation, the sizes of the stockpiles are determined by their distance apart, and this will depend upon whether hand or machine mixing is employed, and upon the means adopted for hauling the raw materials and the mixed concrete. It is worthwhile always in stockpiles of any size to lay a flooring of plank particularly under the stone pile. If dumped directly on the ground, it costs half as much again to handle stone. Current practice warrants everything from a continuous bank to piles from 1,000 to 1,500 ft, apart in the spacing of stockpiles. Hints on hand mixing. All but a small percentage of the concrete annually laid in street work is hand mixed. The authors are confident that this condition will disappear as contractors learn more of the advantages of machine mixing, but it prevails at present. The general economics of hand mixing are discussed in Chapter II. In street work, as before stated, the big items of labor cost are the costs of handling materials, and the data in Chapter II on these processes deserve special attention. It is particularly worth noting that it is seldom economical to handle materials in shovels where carrying is necessary. It is a common thing in street work to see an attempt to get the stockpiles so close to the mixing board that the material can be handled with shovels, and this is nearly always an economic error. Street work is readily measured. In fact, its progress can be seen at a glance, and advantage can often be taken of this fact to profit by the rivalry of separate gangs. The authors have known of the labor costs being reduced as much as 25%, due to pitting one gang against another where each could see the progress made by the other. Methods of machine mixing. Concrete mixers have been slow to replace handwork in laying pavement foundations. In explanation of this fact, it is asserted: 1. That frequent shifting of the mixer causes too much lost time, and 2. That the principal item of labor cost in street work is the conveying of materials to and from the mixer, and this item is the same whether hand or machine mixing be employed. The records of machine mixer work given elsewhere in this chapter go far, in the opinion of the authors, toward disproving the accuracy of both assertions. If the machine used and the methods of work employed are adapted to the conditions of street work, machine mixing can be employed to decided advantage. A continuous and large output is demanded in a mixer for street work. The perfection of the mixing is within limits a minor consideration. This at once admits for consideration types of mixers whose product is classed as unsuitable for reinforced concrete work, and also admits of speeding up the output of the better types to a point beyond that at which they turn out their most perfect product. Keeping these facts in mind, either of the following two systems of work may be employed. 1. Traction plants which travel with the work and deposit concrete in place, or so nearly in place that little shoveling is necessary. 2. Portable plants which are set up at wide intervals along the work, and which discharge the concrete into carts or dump wagons which distribute it to the work. The secret of economic work with plants of the class cited first is the distribution of the stockpiles so as practically to eliminate haulage from stockpile to mixer. The mixer backs away from the work, its discharge end being toward the work and its charging end away from it. Then deposit the materials so as to form a continuous stockpile along the center of the street. The mixer moving backward from the completed foundation keeps close to the materials, and if the latter are uniformly distributed in the pile, the great bulk of the charging is done by shoveling direct into the charging bucket. The point to be watched here is that the shovelers do not have to carry the materials. Separate stockpiles within moderate hauling distance by wheelbarrows are a far more economic arrangement than a continuous pile so irregularly distributed that much of the material has to be carried even a few paces in shovels. Economic work with plants of the second class depends upon efficient and adequate means of hauling the mixed concrete to the work. The plant should not be shifted oftener than once in 1,000 to 2,000 ft, or, say, 4 city blocks. This does away with the possibility of wheelbarrow haulage. Large capacity hand or horse carts must be employed. With 6 ft, hand carts such as the Ransom cart, a haul of 500 ft, each way from the mixer is possible, and with horse carts such as the Briggs, this economic distance is increased to 1,000 ft, each way from the mixer. The mixer must be close to the stockpile, and it will pay to make use of improved charging devices. A 6-in foundation for 2,000 ft of 30 ft. Street calls for 667 ids of concrete, and if both sides are curbed at the same time, 100 ids more are added, or 767 ids. In all, where intersecting streets are to be paved in both directions from the mixer plant, these amounts are doubled. A very small saving per cubic yard, due to mechanical handling of the materials to the mixer, amounts to the interest on a considerable investment in such plant. A point that should not be forgotten is that carts such as those named above spread the concrete in dumping so that little or no shoveling is required. Foundation for Stone Block Pavement, New York, N.Y. Mr. G. W. Tilson, in Street Pavements and Paving Materials, p. 204, gives the following data on the cost of granite block pavement in New York City in 1899. The day was 10 hours long. Concrete gang per day. Per SQ, YD. Per Q, YD. 1 foreman $3, $000, $01250, 075 8 mixers on 2 boards at $1, 2510, 000, 04160, 254 wheeling stone and sand at $1, 25 5, 000, 02080. 125 1 carrying cement and supplying water at $1, 25 1, 25 0, 00510, 031 1 ramming at $1, 25 1, 25 0, 00510, 031. Total 240 SQ ids, 40 Q ids, $20, $50, $08510, 512. The concrete was shoveled direct from the mixing boards to place. Cost 1 to 2 to 4 concrete per Q, YD. 1/3 BBLS. Natural cement at $0, $91. 20 95 Q, YD. Stone at $1, 25 1, 19 37 Q, YD. Sand at $1, 000, 37 labor 0, 51 $3, 27 inlaying 5,167 SQ. Ids of granite block pavement on one job in New York City in 1905, the author's records show that one laborer mixed and laid 3 ids of concrete per day in a 6-in foundation. This is a very small output. The work was done by contract and the labor cost was as follows. Item: total per SQYD per QYD, 28.5 days, foreman at $3, $50.99, $75 $01930, 118 399 days, laborers at $1, 75 698, 25 1351 826, $798, $000, $1544, $944. The average day's wages was $1.86, so that the labor cost was about 0.5 of a day's wages per cubic yard of concrete. Foundation for pavement, New Orleans, L.A. Mr. Alfred E. Harley states that in laying concrete foundations for street pavement in New Orleans, a day's work in running 3 mixing boards covering the full width of the street averaged 900 ids, 6-ins, thick, or 150 ids, with a gang of 40 men, with wages assumed to be 15 CTS per hour. The labor cost was CTS per YD. 6 men wheeling broken stone, 6 3 men wheeling sand, 3 1 man wheeling cement, 1 2 men opening cement, 2 7 men dry mixing, 7 8 men taking concrete off, 8 3 men tamping, 3 3 men grading concrete, 3 1 man attending run planks, 1 3 water boys, 1 2 extra men, and 1 foreman. 4. Total labor cost 39 CTS. Foundations for street pavement, Toronto, Canada. The following cost of a concrete base for pavements at Toronto has been abstracted from a report, 1892, of the city engineer, Mr. Granville C. Cunningham. The concrete was 1 to 2 a 7.5 Portland, 2,430 ids were laid, the thickness being 6-ins, at the following cost per cubic yard: 0.77 BBL. Cement at $2, 78 $2, 14 76 YD. Stone at $1, 91 1, 45 27 YD. Sand and gravel at $0, 80 22. Labor 15 CTS per HR 103, total $4. 84. Judging by the low percentage of stone in so lean a mixture as the above, the concrete was not fully 6-ins thick as assumed by Mr. Cunningham. Note that the labor cost was 1.5 to 2 times what it would have been under a good contractor. Miscellaneous examples of pavement foundation work. The following records of pavement foundation work are taken from the note and time books of one of the authors. Case 1. Laying 6-in. Pavement foundation. Stone delivered and dumped upon 2-in. Plank laid to receive it. Sand and stone were dumped along the street, so that the haul in wheelbarrows to mixing board was about 40 ft. 2 gangs of men worked under separate foremen, and each gang averaged 4, 5 ids concrete per hour. The labor cost was as follows for 45 ids per gang per day per YD. 4 men filling barrows with stone and sand ready for the mixers, wages 15 CTS per hour, $6, $000. 13 10 men wheeling, mixing, and shoveling to place 3 or 4 steps, wages 15 CTS per hour, 15, $000. 33 2 men ramming, wages 15 CTS per hour, 3, $000. 071 foreman at 30 CTS per hour, and 1 water boy, 5 CTS, 3, 50 008. Total $27, $50. 61 Case Roman 2. Sometimes it is desirable to know every minute detail cost, for which purpose the following is given. Per coup, YD, days labor, cost. 3 men loading stones into barrows $0. $0.60, 09. 1 man loading sand into barrows 0. 0.20. 0.32 men ramming 0. 0.40. 0.61 foreman and 1 water boy equivalent to 0. 0.35. 0.5 wheeling sand and cement to mixing board 0. 0.20. 0.3 wheeling stone to mixing board 0. 0.26. 0.49 men mixing mortar 0. 0.13. 0.2 mixing stone and mortar 0. 0.49. 0.7 placing concrete walking 15 ft. 0.72. 11 total $0. 335 $0. 50 in one respect. This is not a perfectly fair example, although it represents ordinary practice, for the mortar was only turned over once in mixing instead of 3 times, and the stone was turned only twice instead of 3 or 4 times. Water was used in great abundance, and by its puddling action probably secured a very fair mixture of cement and sand, and in that way secured a better mixture than would be expected from the small amount of labor expended in actual mixing. About 9 CTS, more per coup, YD, spent in mixing would have secured a perfect concrete without trusting to the water. Case Roman 3. 2 gangs, 34 men working under separate foremen averaged 600 SQ. IDs, or 100 coup. IDs of concrete per 10-hour day for a season. This is equivalent to 3 coup. IDs per man per day. The stone and sand were wheeled to the mixing board in barrows, mixed and shoveled to place. Each gang was organized as follows per day, per coup, YD. 4 men loading barrows $6. $0.00. 12 9 men mixing and placing 13. 50 0. 27 2 men tamping 3. 0.00. 0.6 1 foreman 2. 50 0. 0.5. Total $25. $0.00. 50 These men worked with great rapidity. The above cost of 50 CTS per coup, YD, is about as low as any contractor can reasonably expect to mix and place concrete by hand in pavement work. Case Roman 4. 2 gangs of men, 34 in all, working side by side on separate mixing boards, averaged 720 SQ. IDs, or 120 coup. IDs per 10-hour day. Each gang was organized as follows per day, per coup, YD. 6 men loading and wheeling $9. $0.00. 15 8 men mixing and placing 12. $0.00. 22 men tamping 3. $0.00. 0.5 1 foreman 3. $0.00. 0.5 total $27. $0.00. 45 Instead of shoveling the concrete from the mixing board into place, the mixers loaded it into barrows and wheeled it to place. The men worked with great rapidity. Mr. Irving E. Howe gives the cost of a 6-in. Foundation of 1 to 3 to 5 natural cement at Minneapolis, Min, in 1897 as $2.80 per coup, YD, or $0. 467 per SQ, YD. Cement cost 76 CTS. Per barrel and stone and sand cost delivered $1, 15 and 30 CTS, respectively. Mixers received $1.75 per day. Mr. Niles Merriweather gives the cost of materials and labor for an 8-in. Foundation constructed by day labor, probably colored at Memphis 10. In 1893 as follows per SQ. YD. Natural cement at $0. 74 per BBL $0, 195 sand at $1, 25 per Cu, YD 0, 0.75 stone at $1, 87 per Cu, YD 0, 355 labor mixing and placing 0, 155 total $0. 780 labor was paid $1, 25 to $1, 50 per 8-hour day and 1.16 BBLS of cement were used per cubic yard of concrete. The cost of materials, as will be noted, was high, and the labor seems to have been inefficient. Foundations for brick pavement, Champaign, Ill. The concrete foundation for a brick pavement constructed in 1903 was 6 inches thick. The concrete used was composed of 1 part natural cement, 3 parts of sand and gravel, and 3 parts of broken stone. All the materials were mixed with shovels and were thrown into place from the board upon which the mixing was done. The material was brought to the steel mixing board in wheelbarrows from piles where it had been placed in the middle of the street, the length of haul being usually from 30 to 60 ft. The foundation was 6 inches thick, and it cost as follows for materials and labor. Cost per Cu, YD, 1, 2 BBLS. Cement at $0, 50 $0, 600 0, 6 Cu, YD. Sand and gravel at $1 0, 600 0, 6 Cu, YD. Broken stone at $1, 40 0. 846 men turning with shovels at $2 0, 0.84 men throwing into place at $2 0, 0.53 2 men handling cement at $1, 75 0, 0.23 1 man wetting with hose at $1, 75 0, 0.12 2 men tamping at $1, 75 0, 0.23 1 man leveling at $1, 75 0, 0.12 6 men wheeling stone at $1, 75 0, 0.74 men wheeling gravel at $1, 75 0, 0.47 1 foreman at $4 0, 0.27 $2, 387. This is practically 40 CTS per SQ, YD, or $2, 40 per Cu, YD, of concrete for materials and labor. It is evident from the above quantities that a cement barrel was assumed to hold about 4.5 Cu, FT. Hence the cement was measured loose in making the 1:3:3 concrete. The accuracy of the quantities given is open to serious doubt. It will also be noted that the labor cost of making and placing the concrete was only 35 CTS per Cu, YD, wages being nearly $1, 85 per day. This is so remarkably low that some mistake would seem to have been made in the measurement of the work. The authors do not hesitate to say that no gang of men ever made any considerable amount of concrete by hand at the rate of 5.75 Cu, IDS, per man per day. Fig. 112. Foot continuous mixer arranged for pavement foundation work. Foundation construction using continuous mixers. The following are records of 2 jobs of pavement foundation work using continuous mixers with 1-horse concrete carts in one instance and wheelbarrows in the other instance. The mixer used was the foot mixer. As arranged for the work being described, it is shown by Fig. 112. One particular advantage of this and similar mixes for street work is that no proportioning or measuring of the materials is required of the men. The mixes are provided with an automatic measuring device, by means of which any desired proportion of cement, sand, and stone is delivered to the mixing trough. The mixer is mounted on trucks, and the hoppers that receive the sand and stone are comparatively low down. The sand can be wheeled in barrows up a run plank and dumped into a hopper on one side of the mixer, and in like manner the gravel or broken stone can be delivered into a hopper on the other side. The cement is delivered in bags or buckets to a man who dumps it into a cement hopper directly over the mixer. All that the operator needs to attend to is to see that the men keep the hoppers comparatively full. The records of work on the two jobs mentioned are as follows. Fig. 113. Briggs cart distributing concrete for pavement foundation. Job I. The sand was delivered from the stockpile by a team hitched to a drag scraper and was dumped alongside the mixer where two men shoveled it into the hopper. On the same job, the concrete was hauled away from the mixer in Briggs concrete carts. With a gang of 30 men and 2 to 4 horses hauling concrete in Briggs carts, the contractor averaged 1,200 SQ, ids, or 200 ku, ids, per day of 10 hours, with wages of laborers at 15 CTS. Per hour and a single horse at the same rate, the cost of labor was 26 CTS. Per ku, YD, or less than 4.5 CTS, per SQ/YD of concrete base 6 ins thick. The coal was a nominal item and did not add 1 CT per ku/YD to the cost. In this case, the mixer was set up on a side street, and the concrete was hauled in the carts for a distance of a block each way from the mixer. At first, 4 carts were used, but as the concreting approached the mixer, less hauling was required, and finally only 2 carts were used. An illustration of a Briggs cart is given by Fig. 113. It is hauled by 1 horse, which the driver leads, and is dumped by an ingenious device operated from the horse's head. The cart dumps from the bottom and spreads the load in a layer about 8 or 9 ins thick, so that no greater amount of shoveling is necessary than when barrows are used. It took about 20 seconds for the cart to back up and get its load and about 5 seconds to dump and spread the load. Job Roman II. In this job, the mixer was charged with wheelbarrows, and wheelbarrows were also employed to take the mixed concrete to the work, the mixer being moved forward at frequent intervals. The stockpiles were continuous, sand on one side of the street and stone on the other side. A 1 to 3 to 6 Portland cement concrete was used, a very rich mixture for a 6-in. Foundation. The organization of the working gang was as follows. Men loading and wheeling gravel, 8 men assisting in loading gravel, 2 men dumping barrows into hopper, 1 man loading and wheeling sand, 3 men dumping barrows into hopper, 1 man wheeling concrete in barrows, 7 men spreading concrete, 3 men tamping concrete, 2 men pouring cement into hopper, 1 man operating mixer, 1 man shoveling spilled concrete, 1 man opening cement bags, 1 engineer, 1 total men in gang 32. The average day's output of this gang was 150 ku, ids, or 900 SQ, ids, in 8 hours, but on the best day's work the output was 200 ku, ids, or 1,200 SQ, ids in 8 hours, which is a remarkable record for 32 men and a mixer working only 8 hours. The following is the labor cost of 8,896 SQ, ids of 4.5 in. Concrete foundation for an asphalt pavement constructed in New York City in 1904. Item, per SQYD, foreman at $3, 75 $0, 0.30 laborers at $1, 50 0, 242 teams at $5 0, 0.40 steam engine at $3, 50 0, 0.28, total $0. 340. The concrete was a 1 to 3 to 6 mixture and was mixed in a foot mixer. These costs are compiled from data collected by the authors. Foundation construction for street railway track using continuous mixers. The following account of the methods and cost of constructing a concrete foundation for street railway track at St. Louis, Mo. is compiled from information published by Mr. Richard McCulloch. The work was done by day labor by the United Railways Co. in 1906. Figure 114 shows the concrete construction. A 1:2, a 6, a half Portland cement broken stone concrete mixed by machine was used. Fig. 114. Concrete foundation for street railway track. The material for the concrete was distributed on the street beside the tracks in advance of the machine, the sand being first deposited, then the crushed rock piled on that, and finally the cement sacks emptied on top of this pile. The materials were shoveled from this pile into the concrete mixing machine without any attempt at hand mixing on the street. Great care was taken in the delivery of materials on the street to have exactly the proper quantity of sand, rock, and cement, so that there would be enough for the ballasting of the track to the proper height and that none would be left over. Each car was marked with its capacity in cubic feet, and each receiver was furnished with a table by which he could easily estimate the number of lineal feet of track over which the load should be distributed. The concrete mixing machines were designed and built in the shops of the United Railways Co. 3 machines were used in this work, 1 for each gang. The machine is composed of a Drake continuous worm mixer, fed by a chain dragging in a cast iron trough. The trough is 36 ft long so that there is room for 14 men to shovel into it. Water is sprayed into the worm after the materials are mixed dry. This water was obtained from the fire plugs along the route. In the first machine built, the Drake mixer was 8 ft long. In the 2 newer machines, the mixer was 10 ft long. Both the conveyor and the mixer were motor-driven, current being obtained for this purpose from the trolley wire overhead. 2 types of machines were used, one in which the conveyor trough was straight and 45 in, above the rail, and the other in which the conveyor trough was lowered back of the mixer, being 25 in, above the rail. The latter type had the advantage of not requiring such a lift in shoveling, but the trough is so low that a motor truck cannot be placed underneath it. In the high machine, the mixer is moved forward by a standard motor truck under the conveyor. In the low machine, the mixer is moved by a ratchet and gear on the truck underneath the mixer. A crew of 27 men is required to work each machine, and under average conditions concrete for 80 lin. ft of single track amounting to 22 cu ids can be discharged per hour. The costs of the concrete materials delivered per cubic yard of concrete were: cement per barrel $1.70, sand per cu yd $0, 675, and stone per cu yd $0, 425. The cost of the concrete work per cubic yard and per lineal foot of track was as follows: item per lin, ft per cu yd, concrete materials $0, 791 $2, 92 labor mixing and placing 0, 71 0, 26. Total labor and materials $0, 862 $3. 18 foundation construction using batch mixers and wagon haulage, St. Louis, Mo. The following record of the method and cost of laying a concrete foundation for street pavement using machine mixing and wagon haulage is given by Mr. D. A. Fisher. The foundation was 6 ins thick. The gravel was dumped from wagons into a large hopper, raised by a bucket elevator into bins, and drawn off through gates into receiving hoppers on the charging platform where the cement was added. The receiving hoppers discharged into the mixers, which discharged the mixed concrete into a loading car that dumped into wagons, which delivered it on the street where wanted. The longest haul in wagons was 30 mins, but careful tests showed that the concrete had hardened well. The wagons were patent dump wagons of the drop-bottom type. Mr. Fisher says, "You may consider the following figures a fair average of the plant referred to, working to its capacity. To these amounts, however, must be added the interest on the investment, the cost of wrecking the plant and the depreciation of the same, superintendents and the payroll that must be maintained in wet weather. I am assuming the street as already brought to grade and rolled. With labor at $1, 75 per day of 10 hours, teams at $4, engineer and foreman at $3 and engine at $5 per day, concrete mixed and put in place by the above method costs. Per coup, YD, to mix $0, 12 to $0, 15 to deliver to street 0, 10 to 0, 14 to spread and tamp in place 0, 08 to 0, 11, total $0, 30 to $0, 40 the mixers are no, 2.5 Smith sold by the Contractors Supply Co., Chicago, IL and a half YD. Cube sold by Municipal Engineering and Contracting Co., Chicago. The above figures are on the basis of a batch every 2 minutes, which is easily maintained by using the loading car, as by this means there will be no delay in the operation of the plant owing to the irregularity of the arrival of the teams. My experience leads me to believe that a better efficiency can be obtained by using mixes of 1 coup, YD, capacity, and that the batch mixer is the only type of machine where any certainty of the proportion of the mixture is realized. Fig. 115. Chicago improved cube traction mixer for pavement foundation construction using a traction mixer. In laying a 6-in foundation for an asphalt pavement in Buffalo and Y, an average of 100 SQ, IDs, or 16, 6 coup, IDs, of concrete in place was made per hour using the traction mixer shown by Fig. 115. This mixer was made by the Municipal Engineering and Contracting Co. of Chicago, IL, and consisted of one of that company's improved cube mixers operated by a gasoline engine and equipped with the regulation mechanical charging device, and also with a swinging conveyor to deliver the mixed concrete to the work. The feature of the apparatus in its application to paving work is the conveyor. This was 25 ft, long and pivoted at the mixer end so as to swing through an arc of 170 degrees. The mixer discharged into a skip or bucket traveling on the conveyor frame and discharging over the end, spreading its load anywhere within a radius of 25 ft. In operation, the mixer traveled along the center of the street, backing away from the finished foundation and toward the stock pile, which was continuous and was deposited along the center of the street. The bulk of the sand and stone was thus shoveled direct into the charging bucket, and the remainder was wheeled to the bucket in barrows. As the charging bucket is only 14 ins high, the barrows could be dumped directly into it from the ground. The gang worked was 17, including a foreman and 1 boy, and with this gang 100 SQ, IDs of 6 in. Foundation was laid per hour, assuming an average wage of 20 CTS. An hour the cost of mixing and placing the foundation concrete was 3, 4 CTS per SQ, YD, or 20, 4 CTS per coup, YD, for labor alone. Foundation construction using continuous mixer. The foundation was 6 ins, thick for an asphalt pavement, and was laid in Chicago, IL. The concrete used was exceptionally rich for pavement foundation work, it being a 1 to 3 to 6 Lehigh Portland cement broken stone mixture. The mixing was done by machine, a mixer made by the Buffalo Concrete Mixer Co., Buffalo N.Y. being used. This mixer was equipped with an elevating charging hopper and was operated as a continuous mixer. The mixer was mounted on wheels and was pulled along the center of the street ahead of the work with its discharge end toward the work. Moves of about 25 to 30 ft were made, the mixer being pulled ahead for this distance each time that the concrete came up to its discharge end. The stock piles were continuous, sand on one side and stone on the other side of the street. Cement was stored in a pile at each end of the block. All materials were wheeled from stock piles to mixer in wheelbarrows. The men wheeling sand and stone loaded their own barrows, wheeled them to the mixer, and discharged them directly into the elevating hopper. No runways were used, the barrows being wheeled directly on the ground. The cement was brought in barrows, 2 or 3 bags being a load, and dumped alongside a cement box which was located close to and at one side of the elevating hopper. A man untied the bags and emptied them into the cement box, and another man scooped the cement out of the box in bucketfuls and emptied it over the sand and stone in the elevating hopper. The mixer discharged onto a sheet iron shoveling board, and the concrete was carried in shovels from shoveling board to place, the length of carry being a maximum of 25 to 30 ft. 2 men were required to pull down the cone of concrete at the discharge end of the mixer and to keep the stone from separating and rolling down the sides. The gang was organized as follows. No. Men, loading and wheeling, stone 10 loading and wheeling sand 3 to 4 loading and wheeling cement, 2 untying and emptying cement bags, 1 charging cement to hopper 1 operating mixer and hopper 1 pulling down, and tending discharge 2 carrying concrete in shovels 8 spreading concrete 2 tamping concrete 2 sweeping concrete 1 general laborers 3 foreman 1 watchman 1 timekeeper 1. Total gang 40. This gang averaged 1,000 SQ. IDs of 6 in. Foundation per 10-hour day, a maximum of 1,400 SQ. IDs was laid in a day. We have thus an average of 167 Ku IDs and a maximum of 234 Ku IDs of concrete foundation mixed and placed per 10-hour day. At an average wage of $2 per day, the average labor cost of mixing and placing concrete was 48 CTS per Ku YD, or 8 CTS per SQ YD of 6 in. Foundation. It was stated that the gang was larger by 3 men than was ordinarily used owing to certain extra work being done at the time that the above figures were collected. Taking out 3 extra men and the timekeeper and watchman, we get 34 men actually working in mixing and placing concrete. This reduced gang gives us a labor cost for mixing and placing of about 41 CTS per Ku YD, or 8 CTS per SQ YD of 6 in. Foundation. Foundation construction using a batch mixer. The following figures are an average of several jobs using a ransom a half Ku YD. Mixer for constructing 6 in. Foundations. The mixer was moved 1,000 FT at a time and the work conducted 500 FT in each direction from each station. The concrete materials were delivered from stock pile to mixer in wheelbarrows, and the mixed concrete was hauled to the work in 2-wheeled ransom carts. Run planks were laid for the carts, and 1 man readily pushed a cart holding 6 Ku FT. The men had to work fast on the long haul but had an easy time when the haul was short. The organization of the gang was as follows, wages being $1, 50 per day, 10 men loading and wheeling stone $15, 004 men loading and wheeling sand 6, 002 men handling cement 3, 001 firemen 2, 001 man dumping mixer 1, 55 men wheeling carts 7, 53 men spreading and ramming 4, 51 foremen 3, 50, total wages per day $43. 00 This gang averaged 1,080 SQ. IDs of 6 in. Foundation or 180 cu. IDs of concrete in place per day, which gives a labor cost of 24 CTS per cu. YD or 4 CTS per SQ. YD for mixing and placing. Chapter 43. Next to pavement foundations, the most extensive use of concrete in street work is for cement walks and concrete curb and gutter. Usually the mixing and placing of the concrete is hand work, practically the only exceptions being where pavement base, curbing, and sidewalks are built all at once, using machine mixers. The same objections that have been raised to machine mixers in laying pavement foundation are raised against them for curb and walk construction, and owing to the much smaller yardage per lineal foot of street in walk and curb work, these objections carry more force than they do in case of paving work. Another argument against the use of mixers is that both walk and curb and gutter work involve the use of forms and the application of mortar finish, the placing of which are really the limiting factors in the rate of progress permissible, and this rate is too slow to consume an output necessary to make a mixer plant economical as compared with hand mixing where so much transportation is involved. Concrete sidewalk and curb work are essentially hand mixing work. They, therefore, involve a careful study of the economies of hand mixing and wheelbarrow haulage, which are fully discussed in Chapter II. Cement sidewalks. Sidewalk construction consists in molding on a suitably prepared sub-base a concrete slab from 3½ to 7½ ins, thick, depending on practice, and finishing its top surface with 1/2 to 1½ in. Wearing surface of cement mortar. General method of construction. The excavation and preparation of the subgrade call for little notice, beyond the warning that they should never be neglected. The authors have seen many thousands of feet of cement walk laid in the Middle West in which the sub-base was placed directly on the natural sod, often covered with grass and weeds a foot high. Such practice is wholly vicious. The sod should always be removed, and the surface soil excavated to a depth depending upon the climate and nature of the ground and the foundation bed well tamped. From 4 to 6 ins. Depth of excavation will serve where the soil is reasonably hard and there are no heavy frosts. With opposite conditions, a 12 in. Excavation is none too deep. The thickness of the broken stone, gravel, cinder, or sand sub-base should likewise be varied with the character of the soil, the conditions of natural drainage, and the prevalence of frost. In well-drained sandy soils, 6 to 8 ins of sub-base are sufficient, but in clayey soils with poor natural drainage, the sub-base should be from 10 to 12 ins, thick at least. The local conditions will determine the thickness of sub-base necessary, and in places it may be desirable to provide by artificial drainage against the accumulation of water under the concrete. Tile drains are better and cheaper than excessively deep foundations. The thorough tamping of the sub-base is essential to avoid settling and subsequent cracking of the concrete slab. This is a part of sidewalk work which is often neglected. Portland cement concrete, sand and broken stone or gravel mixtures in the proportions of 1 to 3 to 5 and 1 to 3 to 6 are used for base slabs. For walks up to 7 ft. Wide the slab is made 3½ ins, thick for residence streets and 4½ to 5 ins, thick for business streets. For wider walks the thickness is increased to 7 ins. for 8 ft, width and 7½ ins, for 9 to 10 ft. Width, roughly the thickness of the walk in inches, base and top together, is made about equal to its width in feet. The concrete is deposited in a single layer and tamped thoroughly, either in separate blocks behind suitable forms or in a continuous slab which is, while fresh, cut through to make separate blocks. For walks up to 8 ft. Wide, the slab is divided by transverse joints spaced about the width of the walk apart. But for the wider walks, the safety of this division depends upon the thickness of the base. An 8 ft. walk with a 5 in. Base can safely be laid with joints 8 ft. apart, but if the slab is only 4 ins, thick it had better be laid in 4 times 4 ft. Squares. The mode of procedure in base construction is as follows. The sub-base being laid, side forms held by stakes are placed as shown by Fig. 116. With the top edges of the boards exactly to the grade of the top surface of the finished walk. The concrete is then deposited between these side forms and tamped until it is brought up to the level marked by the template A. If the plan is to deposit the base in sections, transverse plates of to 1/4 in. Steel are set across the walk between the side boards at proper intervals and the concrete tamped behind them. Sometimes the concreting is done in alternate blocks. When the steel plate is withdrawn, an open joint is left for expansion and contraction. Where the plan is to lay the base in one piece which is afterwards cut into blocks, the cutting is done with a spade or cleaver. Fig. 116. Sketch showing method of constructing cement walks. Fig. 117. Jointer for cement sidewalk work. Portland cement mortar mixed 1 to 1½ to 1 to 2 is used for the wearing surface, and is laid from a 1/2 in to 1½ ins. Thick, depending upon the width of the walk and the thickness of the base. As a rule, the mortar is mixed rather stiff. It is placed with trowels in 1 coat usually, but sometimes in 2 coats, and less often by tamping. The mortar coat is brought up flush with the top edges of the side forms by means of the template B, and the top finished by floating and troweling. The wearing coat is next divided into sections corresponding with the sections into which the base is divided, by cutting through it with a trowel guided by a straight edge, and then rounding the edges of the cut with a special tool called a jointer and shown by Fig. 117. An edger, Fig. 118, is then run around the outside edges of the block to round them. The laying of the mortar surface must always follow closely the laying of the base so that the two will set together. Fig. 118. Edger for cement sidewalk work, bonding of wearing surface and base. Trouble in securing a perfect bond between the wearing surface and the base usually comes from one or more of the following causes. 1. Applying the surface after the base concrete has set. While several means are available for bonding fresh to old concrete as described in Chapter 24, the better practice is not to resort to them except in case of necessity, but to follow so close with the surfacing that the base will not have had time to take initial set. 2. Poor mixing and tamping of this base concrete. 3. Use of clayey gravel or an accumulation of dirt on the surface. In tamping, clayey gravel, the water flushes the clay to the surface and prevents the best bond. 4. Poor troweling, that is, failure to press and work the mortar coat into the base concrete. Some contractors advocate tamping the mortar coat to obviate this danger. Conversely, to make the surface coat adhere firmly to the base, it must be placed before the base concrete has set. The base concrete must be thoroughly cleaned or kept clean from surface dirt. The surface coat must be tamped or troweled forcibly into the base concrete so as to press out all air and the film of water which collects on top of the concrete base. Protection of work from sun and frost. Sun and frost cause scaling and hair cracks. For work in freezing weather, the water, sand, and gravel should be heated or salt used to retard freezing until the walk can be finished. It may then be protected from further action of the frost by covering it first with paper, and then with a mattress of sawdust, shavings, or sand, and covering the whole with a tarpaulin. Methods of heating concrete materials and rules for compounding salt solutions are given in Chapter Roman 7. The danger from sun arises from the too rapid drying out of the surface coating. The task then is to hold the moisture in the work until the mixture has completely hardened. Portable frames composed of tarpaulin stretched over 2 times 4 in. Strips may be laid over the finished walk to protect it from the direct rays of the sun. These frames can be readily removed to permit sprinkling. Practice varies in the matter of sprinkling, but it is the safe practice in hot weather to sprinkle frequently for several days. Moisture is absolutely necessary to the perfect hardening of cement work, and a surplus is always better than a scarcity. In California, the common practice is to cover the cement walk, as soon as it has hardened, with earth which is left on for several days. Cause and prevention of cracks. Cracks in cement walks are of 2 kinds. Fractures caused by any one of several construction faults, and which reach through the surface coating or through both surface and base, and hair cracks which are simply skin fractures. Large cracks are the result of constructive faults, and one of the most common of these is poor foundation construction. Other causes are poor mixing and tamping of the base, too large blocks for thickness of the work, failure to cut joints through work. Hair cracks are the result of flushing the neat cement to the surface by excessive troweling or the use of too wet a mixture. The prevention of cracks obviously lies in seeing that the construction faults cited do not exist. If expansion joints are not provided, a long stretch of cement walk will expand on a hot day and bulge up at some point of weakness, breaking the walk. Cost of cement walks. The cost of cement walks is commonly estimated in cents per square foot, including the necessary excavation and the cinder or gravel foundation. The excavation usually costs about 13 CTS per QYD, and if the earth is loaded into wagons, the loading costs another 10 CTS per QYD, wages being 15 CTS per HR. The cost of carting depends upon the length of haul and may be estimated from data given in Chapter Roman 3. If the total cost of excavation is 27 CTS per QYD, and if the excavation is 12 ins deep, we have a cost of 1 CT per SQFT for excavation alone. Usually the excavation is not so deep, and often the earth from the excavation can be sold for filling lots. In estimating the quantity of cement required for walks, it is well to remember that 100 SQ/FT of walk 1 in thick require practically 0.3 QYD concrete. If the concrete base is 3 ins thick, we have 0.3 times 3 or 0.9 QYD per 100 SQ/FT of walk, and by using the tables in Chapter 44, Mixture. In cement walk work, the cement is commonly measured loose so that a barrel can be assumed to hold 4.5 QFT of cement. If the barrel is assumed to hold 4.5 QFT, it will take less than 1 BBL of cement to make 1 QYD of 1 to 3 to 6 concrete, hence it will not require more than 0.9 BBL, cement 0.9 QYD, stone, and 0.45 QYD, sand per 100 SQ/FT of 3 in concrete base. The 1-in wearing coat made of 1 to 1.5 mortar requires about 3 bbls of cement per cu yd if the barrel is assumed to hold 4-5 cu ft, and since it takes 0.3 cu yd per 100 sq ft 1-in thick, we have 0.3 times 3 or 0.9 bbl cement per 100 sq ft for the top coat. This makes a total of 1.8 bbls per 100 sq ft, or 1 bbl makes 55 sq ft of 4-in walk. As the average of a number of small jobs, the author's records show the following costs per sq ft of 4-in walk, such as just described: CTS per sq ft, excavating 8 ins, deep 0.65 gravel for 4-in, foundation at $1.00 per cu yd, 1.20 0.18 bbl, cement at $2.003 60 0.009 cu yd, broken stone at $1.51 35 0.006 cu yd, sand at $1.000 60, labor making walk 1.60, total cents 9.00. This is 9 CTS per sq ft of finished walk. The gangs that built the walk were usually 2 masons at $2.50 each per 10 sha day, with 2 laborers at $1.50 each. Such a gang averaged 500 sq ft of walk per day. Cost at Toronto, Ont. Mr. C.H. Rust, city engineer, Toronto, Ont, gives the following costs of constructing concrete sidewalks by day labor. The sidewalks have a 4-in foundation of coarse gravel or soft coal cinders, thoroughly consolidated by tamping or rolling, upon which is placed a 3.5-in layer of concrete composed of 1 part Portland cement, 2 parts clean, sharp, coarse sand, and 5 parts of approved furnace slag, broken stone, or screened gravel. The wearing surface is 1-in thick, or 1 part Portland cement, 1 part clean, sharp, coarse sand, and 3 parts screened pea gravel, crushed granite, quartzite, or hard limestone. Costs are given of a 6 ft and a 4 ft walk as follows: cost of 6 ft. Sidewalk item per 100 sq ft. Labor $5.59, cement 1.66 bbls at $1.54 49, gravel 2.7 cu ids at $0.82 21, sand 0.46 cu yd at $0.80 37, water 0.05, total $10 71, cost of 4 ft. Sidewalk item per 100 sq ft. Labor $6.73, cement 2.04 bbls at $1.54 15, gravel 2.06 cu ids at $0.81 65, sand 0.49 cu yd at $0.80 39, water 0.07, total $11 99. The rates of wages and the number of men employed were as follows: 1 foreman at $3.50 per day, 1 finisher at 30 CTS per hour, 1 helper at 22 CTS per hour, 15 laborers at 20 CTS per hour. Cost at Quincy, Mass. The following costs are given by Mr. C. M. Saville for constructing 695 sq ids of granolithic walk around the top of the Forbes Hill Reservoir embankment at Quincy, Mass. This walk was laid on a broken stone foundation 12 ins thick. The concrete base was 4 ins thick at the sides and 5 ins thick at the center. The granolithic finish was 1 in thick. The walk was 6 ft wide and was laid in 6 ft sections, a steel plate being used to keep adjacent sections entirely separate. The average gang was 6 men and a team on the base, and 2 masons and 1 tender on the finish. The average length of walk finished per day was 60 ft. The cost was as follows: stone foundation per coup YD per SQ FT, broken stone for 12 in. Foundation $0, $40 0.15 labor placing at 15 CTS. Per hour 1, 50 0.56. Totals $1, $90 0.71 concrete base for a half ins. Thick 122 BBLS. Cement per coup YD at $1.53 1. 87 0.026 50 coup YD. Sand per coup YD at $1.020 51 0.0070 84 coup YD. Stone per coup YD at $1.57 1 32 0.19 labor 6 laborers 1 team 3 48 0.50 total for 90 coup. IDS $7 18 $0 102 granolithic finish 1 in. Thick 4 BBLS. Cement per coup YD at $1.53 6 12 0.19 8 coup YD. Sand at $1.0 80 0.002 lamp black 0 29 0.001 labor 2 masons 1 helper 6 36 0.16 totals $13 57 0.038 the 2 masons received $2 25 per day each and their helper $1 50 per day and they averaged 360 SQ FT per day which made the cost 1/2 CTS per SQ FT. For labor laying granolithic finish, the cost of placing the foundation stone is very high, and the cost of concrete base also runs unusually high. The reasons for these high costs are not evident. Cost at San Francisco. Mr. George P. Wetmore of the contracting firm of Cushing and Wetmore, San Francisco, gives the following figures relating to sidewalk work in that city. The foundations of cement walks in the residence district of San Francisco are 2½ ins. Thick, made of 1 to 2 to 6 concrete, the stone not exceeding 1 in. In size, the wearing coat is a ½ in. Thick, made of 1 part cement to 1 part screened beach gravel. The cement is measured loose 7 coup FT per barrel. The foundation is usually laid in sections 10 FT. Long. The width of sidewalks is usually 15 FT. The top coat is placed immediately, leveled with a straight edge and gone over with trowels till fairly smooth. After the initial set and first troweling, it is left until quite stiff when it is troweled again and polished, a process called hard finishing. The hard finish makes the surface less slippery. The surface is then covered with sand and watered each day for 8 or 10 days. The contract price is 9 to 10 CTS. Per SQ FT for a 3 in, walk 12 to 14 CTS. For a 4 in, walk having a wearing coat 3/4 to 1 in. Thick. A gang of 3 or 4 men averages 150 to 175 SQ. FT, per man per day of 9 HRS. Prices and wages are as follows. Cement per BBL, $2, 50 crushed rock per coup YD, 1.75 gravel and sand for foundation per coup YD, 1.40 gravel for top finish per coup YD, 1.75 finisher wages, best per HR, 0. 40 finisher helper best per HR, 0. 25 laborer best per HR, 0. 20 cost in Iowa. Mr. L.L. Bingham sent out letters to a large number of sidewalk contractors in Iowa asking for data of cost. The following was the average cost per square foot as given in the replies. CTS per SQ. FT cement at $2 per BBL. 3. 6 sand and gravel 1. 5 labor at $2. 30 per day average 2. 2 incidentals estimated 0, 7 total per SQ, FT8. 0 This applies to a walk 4 ins, thick, and includes grading in some cases, while in other cases it does not. Mr. Bingham writes that in this respect the replies were unsatisfactory. He also says that the average wages paid were $2.30 per man per day. It will be noted that a barrel of cement makes 55½ SQ. FT. Of walk, or it takes 8 BBLS per 100 SQ FT. The average contract price for a 4-in walk was 11½ CTS per SQ FT. Concrete pavement. Concrete pavement is constructed in all essential respects like cement sidewalk. The subsoil is crowned and rolled hard, then drains are placed under the curbs. If necessary to secure good drainage, a sub-base of gravel, cinders, or broken stone 4 to 8 ins. Thick is laid and compacted by rolling. The foundation being thus prepared a base of concrete 4 to 5 ins. Thick is laid, and on this a wearing surface 2 to 3 ins. Thick. As showing specific practice, we give the construction in 2 cities which have used concrete pavement extensively. Windsor, Ontario. The street is first excavated to the proper grade and crown and rolled with a 15-ton roller. Tile drains are then placed directly under the curb line and a 6 times 16 in. Curb is constructed, vising 1 to 2 to 4 concrete faced with 1 to 2 mortar, including the 3 in. Tile drain this curb costs the city by contract 38 CTS. Per lin, FT. The pavement is then constructed between finished curbs as shown by Fig. 119, Fig. 119. Concrete pavement, Windsor, Canada. The fine profile of the subgrade is obtained by stretching strings from curb to curb, measuring down the required depth and trimming off the excess material. The concrete base is then laid 4 ins, thick. A 1 to 3 to 7 Portland cement concrete is used, the broken stone ranging from a 1/4 in to 3 ins in size, and it is well tamped. This concrete is mixed by hand, and as each batch is placed, the wearing surface is put on and finished. The 2 layers are placed within 10 minutes of each other, the purpose being to secure a monolithic or one-piece slab. The top layer consists of 2 ins, of 1 to 2 to 4 Portland cement and screened gravel, a 1/4 in to 1 in concrete. This layer is put on rather wet, floated with a wooden float and troweled with a steel trowel while still wet. Some 20,500 SQ. IDs of this construction have been used and cost the city by contract, per SQ, YD, bottom 4 in. Layer 1 to 3 to 7 concrete $0, 57 top 2 in. Layer 1 to 2 to 4 concrete 0, 32 excavation 0, 10, total $0. 99 This construction was varied on other streets for the purpose of experiment. In one case a 4 in, base of 1 to 3 to 7 stone concrete was covered with 2 ins, of 1 to 2 to 2 gravel concrete. In other cases the construction was 4 in, base of 1 to 3 to 7 stone concrete, 1½ in, middle layer of 1 to 2 to 4 gravel concrete and a 1/2 in, top layer of 1 to 2 sand mortar. All these constructions have been satisfactory. The pavement is not slippery. The cost to the city by contract for the 3-layer construction has in 2 cases been as follows. Church sent 8,000 SQ. IDs per SQ YD 4 in, base 1 to 3 to 7 concrete $0, 57 1½ in, 1 to 2 to 4 and a 1/2 in 1 to 2 mixture 0, 32 excavation 0, 10, total $0. 99 Albert and YN.STS, 400 SQ. IDs per SQ YD 4 in, base 1 to 3 to 7, concrete $0, 66 1.5 in, 1 to 2 to 4.5 in, 1 to 2 mixture 0, 39 excavation 0, 10 total $1. 15 the cost of materials and rates of wages were about as follows: Portland cement FOB, cars Windsor per BBL $2, 0.5 river sand per cu YD, 1.15 river gravel screened per cu YD, 1.25 crushed limestone a quarter to 3 ins per ton 1.15 labor per day 1.75 to 2.00. At these prevailing prices, the contractor got a fair profit at the contract price of $1.15 at 99 CTS. Any profit is questionable, according to city engineer George S. Haynes, who gives us the above records. Expansion joints are located from 20 to 80 ft apart and are filled with tar. Richmond Ind. The first concrete pavement was built in 1896, and since then it has been used extensively, especially for wide alleys and narrow streets where traffic is heavy and concentrated in small space. The method of construction has varied from time to time, but the construction shown by Fig. 120 is fairly representative. Usually a 1 to 3 to 5 concrete is used for the base, 5 ins thick, and a 1 to 2 mortar for the top coat, 1.5 ins thick. In 1904, this pavement cost the city by contract 16 CTS per SQ FT, or $1.54 per SQ YD, with wages and prices as follows: stone on the work $1.25 per cu YD, gravel and sand $0.75 per cu YD, cement $2.25 per barrel, common laborers 16.5 CTS per hour, and cement finishers 40 CTS per hour. Fig. 120. Concrete pavement, Richmond Ind, concrete curb and gutter. Current practice varies materially in constructing concrete curb and gutter. The more common practice is to lay the curb and water table in one piece, or as a monolith, but this is by no means universal practice. In much work, the curb wall and the water table slab are constructed separately, the construction joint being sometimes horizontal, where the curb wall sits on the slab, and sometimes vertical, where the water table butts against the wall. Again, it is the common practice to construct curb and gutter in sections, laid either alternately or in succession, separated by sand joints to provide for expansion and contraction. But this is not universal practice, much of such work being constructed as a continuous wall with no provision for temperature movements, except the natural breaks at driveways. All of these types of construction appear to have given reasonable satisfaction, but exact data for a final comparison are not available, so that we are forced to reason on general principles. Such a course of reasoning indicates that the best results should be expected where the curb and water table are built in one piece and in sections of reasonable length separated by expansion joints. Fig. 121. Box form for concrete curb. Fig. 122. Continuous form for concrete curb. Form construction. The form construction for curb and gutter work is determined by the general plan of construction followed, whether monolithic or two-piece construction. In monolithic construction, two types of forms are employed: sectional or box forms and continuous forms. A good example of box form is shown by Fig. 121. This form was designed for a curb 14 ins, high at the back 6 ins, high in front and 24 ins, from face of curb to outer edge of gutter, constructed in sections 7 ft long. The form, it will be observed, is a complete box, in which alternate sections of curb are molded and after having set are filled between using the same form but dispensing with the end boards which are replaced by the completed sections of curb. A fairly representative example of continuous form is shown by Fig. 122. In this construction, a continuous line of plank is set to form the back of the curb, and another line to form the face of the gutter slab, both lines being held in place by stakes. When the gutter slab concrete has been placed and surfaced, the form for the front of the curb is set as shown, and the upper portion of the curb wall concreted behind it. The method in detail of constructing curb and gutter with this type of form at Ottawa, Ont, is described in a succeeding section. Here the joints were formed by inserting a partition of boiler plate every 12 ft, which was withdrawn just previous to finishing up the surface. The sections between partitions were concreted continuously. Another method is to make the partitions of plank, concrete every other section, then remove the partition plank and concrete the remaining spaces against the previously finished work. A different method of supporting the plank forming the face of the curb wall is to clamp it to the back form, Fig. 123, spaces being inserted to keep the two their proper distances apart. The forms shown by Figs 121 to 123 are for monolithic curb and gutter. In two-piece construction where the curb wall is constructed on the finished gutter slab, practically, the same method of construction is employed as is illustrated by Fig. 122, except that no attempt is made to concrete the curb wall before the slab concrete has begun to set. The more common and the preferable method of two-piece construction is illustrated by Fig. 124. The curb proper is built first using the simple box form shown at the right hand. Then the water table is built using the completed curb as the form for the back, and a board held by stakes as a form for the front. This board is set with its top edge exactly to the grade of the finished water table so as to serve as a guide for one end of the template, the other end of which rides on the top of the finished curb wall. Forms for curves at street intersections are best constructed by driving stakes to the exact arc of the curve and bending in. Steel plate around them or bending and nailing times 1/4 in. Strips. Soaking the wood strips thoroughly will make them bend easily. The cost of form work in constructing curb and gutter is chiefly labor cost in erecting and taking down the forms. Fig. 123. Continuous form for concrete curb. Fig. 124. Form for two-piece curb construction, concrete mixtures and concreting. The curb body is usually made of a 1 to 3 to 5 or 6 concrete, and the curb finish of a 1 to 2 mortar. Portland cement is employed almost exclusively. The concrete mixture commonly used is of such consistency that thorough ramming is necessary to flush the cement to the surface. The cubical contents of combined curb and gutter of the forms illustrated will run from 3 to 5 ids per 100 ft, and about 1/8 of this will be facing mortar 1 in. Thick, thus a curb running 5 ids per 100 ft will contain per 100 ft about 0.83 yd of mortar and 4.17 ids of concrete. The usual method of concreting is to erect the forms for the back of the curb wall and the front of the gutter slab and concrete to the height of the water table clear across. Then shape the exposed top of the water table to section and place the mortar finish, and then erect the face form for the gutter wall. Bring the concrete backing and vertical face finish up together, and finally, finish the top. The finish coat is placed by troweling on the horizontal surfaces. On the vertical face of the curb wall it may be placed in any one of several ways. Frequently, the mortar coat is simply plastered against the face board and filled behind with concrete. Another method is to lay a one-in board against the inside of the form, concrete behind it, then withdraw the board, fill the space with mortar and tamp concrete and mortar to a thorough bond. The special face forms shown in Chapter Roman 8 may be used in place of the board. The securing of a good bond between the backing concrete and the mortar facing is governed by the same conditions that govern sidewalk work. Cost of curb and gutter. The cost of concrete curb and gutter is commonly estimated in cents per lineal foot. The cost of excavating, loading, and carting will run about the same per cubic yard as for sidewalks. Excavating the trench and preparing the subgrade usually runs from a half CT to 2 CTS per foot of curb, but sometimes it amounts to 3 CTS. Placing the subbase will cost for placing and tamping 1 CT per FT, to which is to be added the cost of materials. A 6-in, subbase 30 ins, wide contains 4-7 ids, tamped measure of materials per 100 FT. The amount of materials per foot depends upon the cross-section of the curb. It equals in cubic yards the area of cross-section in square feet divided by 27, and of this volume about 1/8 will be 1 to 2 mortar, and 7/8 1 to 3 to 6 concrete. The tables in Chapter Roman 2 give the amounts of materials per cubic yard of these mixtures. The product of these quantities and the cost of the materials on the ground gives the cost. The labor cost of mixing and placing, including the form work, will run from 10 to 14 CTS per foot. In round figures, curb and gutter of the section shown in the accompanying illustrations may be estimated to cost in the neighborhood of 40 CTS per lineal foot. The following sections give records of cost of individual jobs of curb and gutter construction. Cost at Ottawa, Canada. The method and cost of constructing 1,326 FT of concrete curb and gutter at Ottawa, Ont, are given in some detail by Mr. G. H. Richardson, Assistant City Engineer, in the annual report of the City Engineer for 1905. We have remodeled the description and rearranged the figures of cost in the following paragraphs. The concrete curb was built before doing any work on the roadway, and the first task was the excavation of a trench 2½ FT, wide and averaging 1 FT, 8 ins, in depth through light red sand. On the bottom of this trench there was placed a foundation of stone spalls 8 ins thick. In width this foundation reached from 3 ins, back of the curb to 6 ins, beyond the front of the water table. The curb was made 5 ins, thick and ran from 10 ins to 5½ ins in height, and the water table was 14 ins, wide and 4 ins, thick with a fall of 1¼ ins from front to back. The concrete used was a mixture of 1 Portland cement, 3 sand, 3 in, screened limestone, and 4 2-in stone. It was deposited in forms and tamped to bring the water to the face, and then smoothed with a light troweling of stiff mortar. The forms were constructed by first setting pickets and nailing to them a backboard 2 ins, thick and 12 ins, wide, and a front board 2 ins, thick and 6 ins, wide. The concrete for the water table was deposited in this form in sections, and brought to surface by straight edge riding on wooden strips nailed across the form and properly set to slope, etc. After the water table had been troweled down and brushed, a 1 × 10-in board was set to mold the front face of the curb. This board was sustained by small knee frames made of 3 pieces of 1 × 2-in Stuff, one conforming to the slope of the water table and long enough to extend beyond the front of the 2 times 6 in. Front board, a second standing plumb and bearing against the 1 times 10 in. Face board and the third forming a small corner brace between the 2 former to hold them in their proper relative positions. The 1 times 10 in. Face board, etc. was separated from the 2 times 12 in. Back board by a 5 in. Block at each end, and then braced by the knee frames every 3 or 4 ft. In this way it was possible to bring this 1 times 10 in. Board into perfect line by moving the knee braces in or out, and when correct nailing them to the 2 times 6 in. Front board, the 1 times 10 in. Face board being in position and braced and lined, the curb material was thoroughly tamped in, and when ready was troweled and brushed on the top, a small round being worked onto the top front corner with the trowel. Expansion joints were provided for by building into the curb every 12 ft, a piece of in. Boiler plate, which was afterward withdrawn and the joint filled with sand and faced over. As soon as the concrete had set sufficiently, the face board was taken down, and face of curb finished and brushed, the fillet between curb and water table being finished to 2½ ins. Radius. Circular curb and gutter of same construction was built at each corner, ½ in. Basewood being used for forms instead of 2 times 1 in. Lumber. In addition to the actual construction of curb and gutter, the cost given below includes the cleaning up of the street, spreading or removal of all surplus material from excavation, and the extension of all sidewalks out to the curbs at the corners. It was also necessary to maintain a watchman on this work, which duty, under ordinary circumstances, would be done by the general watchman. The total length built was 1,326 ft, of which 1,209 ft is straight and 117 ft curved to a 12 ft radius. The rates of wages paid were $2 for horse and cart, $1.65 for watchmen, and an average of $1.90 per day for labor, including foremen, all for 9 hours work per day. The working force consisted of foreman, finisher, handyman, 4 concrete men, and 3 laborers. The labor cost of the work was as follows. Item. Total per FT CTS PC of total. Excavation and setting boards $88.96, $7.30 laying stone foundation $43.33, $3.14 concreting $61.34, $6.20 finishing $45, $15.3, $4.15 cotting $9.85, $76.3 watchman $25.001, $89.8 clearing up $13.61, $044 extras sidewalk extensions $17, $23.1, $31.6, total $304, $33.23, $100. The cost of materials for curb and foundation were as follows. Total per lin FT CTS 171, 112 tons spalls $102, 93.7, 76 42 tons 2 in. Stone 41, 16.3, 0930, 8 tons in. Stone 42, 57.3, 2133,000 pounds. Cement 161, 7012, 1924 coup ids. Sand 19, 21, 45. Total $367, 56.27, 70. The cost of supplies and tools was as follows. 1,000 FT. B. M. 2 times 12 boards charged off $9. 25,500 FT. B. M. 2 times 6 boards charged off 4. 12 1,000 FT. B. M. 1 times 10 boards charged off 14. 25 a half in. Basewood 4. 30 a half keg 3 in. Nails 1. 42 a half keg 4 in. Nails 1. 43 pickets 3. 25 tools charged off 3. 15. Total $41. 17. This total, when divided by 1,326 lin. FT of curb gives the cost per lineal foot as about 3 CTS. We can now summarize as follows. Item, total per lin, FTPC of total. Labor $304. 33.23.43 material $367. 56.28.51 supplies 41. 17.36. Total $713. $060. 54,100 as indicated above. On more extensive work, the costs of carting, watchmen, cleaning up, and extras would be avoided. They cost on this work 5 CTS, and the work could therefore be done for 49 CTS, if no such charges were included. On such work also the charge for supplies would be lower per foot, and on any future work the labor cost could be materially lowered, this curb having been somewhat of an experiment as to method of construction. It is thought that with no charges for carting, cleaning, watchmen, and extras, and with the experience obtained, this curb could be built for about 46 CTS. The proportions adopted and the method of construction followed produce a very strong, dense, homogeneous curb and gutter. Fig. 125. Concrete curb and gutter at Champaign Ill. Cost at Champaign Ill. The following costs were recorded by Mr. Charles Apple and relate to work done at Champaign Ill in 1903. The work was done by contract at 45 CTS per lin. FT of the curb and gutter shown in Fig. 125. The concrete curb and gutter was built in a trench as shown in the cut. The earth was removed from this trench with pick and shovel at a rate of 1 coup. YD per man per hour. The concrete work was built in alternate sections 7 FT in length. A continuous line of planks was set on edge to form the front and back of the concrete curb and gutter, and wood partitions staked into place were used. The cost of the work was as follows. Item, no, of men, total wages, cost per 100 FT. Opening trench 18 times 30 in. $2 $52. 43 placing and tamping cinders 2 51. 00 setting forms, boss setter 1300. Assistant setter 1200. Laborer 1175. $36, 75 $1, 69 mixing and placing concrete, clamp man $1 75, wheelers 35 25, mixing concrete 4700, mixing finishing coat 23 50, tampers 75, finishing foreman and boss finisher 1400, assistant finisher 1300. Water boy 150. Total making concrete $14.26, 75 $7, 64 total for labor per 100 FT $12, 76 materials for 100 lin. FT. Quantity, price, Portland cement 8 1/3 BBLS, $1, 85 $15, 42 cinders 7. 5 ids, 53 75 gravel 2, 5 ids, 1002, 50 broken stone 2, 5 ids, 143, 50 sand 1, 01, 001, 00 total for material per 100 FT $26, 17 total for material and labor per 100 FT, $38. 93. This is the total cost, exclusive of lumber, tools, interest, profits, etc., and it is practically 40 CTS. Per lin, FT. In 100 lin, FT, of curb and gutter there were 6 coup ids of concrete and mortar facing, 4 coup ids, of which were concrete, hence the 9 men in the concrete gang laid 14 coup. ids of concrete per day, whereas the 4 men mixing and placing the mortar finishing laid only 2.5 cu. Ids of mortar per day, assuming that the mortar finishing averaged just 1 in. Thick. Since these 4 men, 2 mixers and 2 finishers, received $10.50 a day, it cost more than $4 per cu. YD. To mix and place the 1 to 2 mortar as compared with $1.41 per cu. YD. For mixing and placing the concrete. The concrete was built in alternate sections 7 ft long. The 3 men placing forms averaged 400 lin. ft a day, so that the cost of placing the forms was $1 per cu. YD of concrete. The 2 men placing and tamping cinders averaged 16 cu. Ids of cinders per day, or 8 cu. Ids per man. This curb and gutter was built by contract at 45 CTS per lin. ft for several jobs in which a curb and gutter, essentially the same as shown in Fig. 125 was built. Our records show a general correspondence with the above given data of Mr. Apple. Our work was done with smaller gangs, 1 mason and 2 laborers being the ordinary gang. Such a gang would lay 80 to 100 lin. ft of curb and gutter per 10 HA. Day at the following cost: 1 mason at $2, $52, 52 laborers at $1. 53.00, total $5.50. This made a cost of 5.5 to 7 CTS per lin. ft for labor, and it did not include the cost of digging a trench to receive the curb and gutter. Chapter 45. Fig. 126. Section showing lining for Capitol Hill Tunnel, Washington, D.C. Tunnel lining work is of 2 distinct classes: lining work done during original construction and relining of tunnels in service. The methods of work to be adopted and the cost of work will be different in the 2 cases. In relining work, the costs are increased by the necessity of providing for the movement of trains and by the delays due to these movements, and also by the labor of removing the old lining and often of enlarging the excavation. Comparatively few published figures are available on the cost of concrete tunnel lining, and such as exist are commonly incomplete. The common practice is to record the cost as so much per lineal foot of tunnel. This should be done, but the record should also show the cost per cubic yard of concrete in the lining. The notions of engineers vary as to the proper thickness of lining to use, and this dimension also varies with the character of the ground. 1 tunnel lining may easily contain twice as many cubic yards of concrete per lineal foot of lining as another tunnel contains. The 2 problems in form construction for tunnel work are: first, to construct the form work so that it does not interfere with train movements, and second, to construct it so that it can be taken down, transported and re-erected, and thus used over and over. The examples of practice given in the succeeding sections are the best instructions that can be laid before the reader in regard to possible ways of solving these problems, and also the problem of handling the concrete and other materials to the work. Fig. 127. Traveling derrick for constructing side and center walls, Capitol Hill Tunnel. Fig. 128. Steel forms for side walls for Capitol Hill Tunnel. Method of lining Capitol Hill Tunnel, Pennsylvania, Washington, D.C. The tunnel through Capitol Hill for the Pennsylvania approach to its new Union Station at Washington, D.C. is a 2-track double-tube tunnel 4,000 ft long through earth. Figure 126 shows the lining construction. It consists of stone masonry center wall, mass concrete inverts and side walls and a brick roof arch backed with concrete. For building the center and side walls, the traveling derrick shown by Fig. 127 was employed. This traveler moved ahead with the work on a 14 ft gate track, and it handled the stone and concrete buckets from the material cars to the workmen on the walls. In connection with the derrick in the concrete side wall, construction use was made of steel plate forms for the inside faces of the walls. These forms were made of 4 × 10 ft sections of steel plate, constructed as shown by Fig. 128, and connected together by bolting through the flanges. The steel forms were erected by hand in advance of the derrick, 20 ft, of form on each side at a time. The concrete buckets were brought into the tunnel on cars hauled by electric motors from the mixing plant at the portal, and the buckets were lifted by the derricks and emptied into the forms. The side walls were concreted to the springing line, and then the 5-ring brick roof arches were constructed on traveling centers and in 20 ft sections. The remainder of the concrete was then placed over the arches by means of the special backfilling machine, shown by Fig. 129. This machine also handled the earth used to fill behind the masonry. It consisted of a platform mounted on wheels and of the same general construction as the derrick platform. On the forward end of this platform, a stationary hoist was mounted, and behind this a belt conveyor platform. Fig. 129. Device for placing concrete backfilling for roof arch, Capitol Hill Tunnel. The latter structure was pivoted near the forward end, so that it could swing right and left on a circular track under its rear end. It carried a 30 ft hopper on its forward end, from under which a belt conveyor ascended an incline toward the rear and was carried back into the space behind the roof arch on a cantilever arm. In operating the backfilling machine, the material bucket was lifted from the car below, carried back on the trolley beam until over the hopper, and then dumped by hand into the hopper. From the hopper, the material dropped onto the conveyor belt and was carried back over the arch and dumped in place ready for tamping. The trolley beam of the hoist was so arranged that the hoisting movement was vertical until the bucket hit the trolley, and was then up and backward until the stop at the end of the trolley beam was reached. This point was directly over the hopper. Hoisting was done by a Lambert engine, driven by a 15 HP electric motor. The conveyor belt was 20 ins wide and was operated at a speed of 180 ft per minute by a 7.5 HP electric motor. The machine required 2 men to operate and was considered to save the labor of 12 shovelers. Method of constructing side walls in relining the Mullen Tunnel. The Mullen Tunnel, 3,850 ft long, on the northern Pacific Rye, about 20 miles west of Helena, Mont, had its original timber lining replaced in 1894 with a lining consisting of concrete side walls and a brick roof arch. The construction of the old and new linings is shown by Fig. 130. The method of constructing the side walls was as follows. The original timbering consisted of sets of 12 × 12 in posts carrying 5 segment arches of 12 × 12 in. Timbers joined by a half-in, dowels. For a portion of the lining, the posts carried plates on which the arches set. Elsewhere, the arches rested directly on the post tops. The arches and posts carried 4 in. Lagging filled behind with cordwood. The timber lining was removed to make place for the new work in the manner shown by Fig. 130. When there were no plates, a 7 ft Section AB was first prepared by removing one post and supporting the undermined arch ribs by struts SS. The timbering in this section was cut out and excavation made for the wall footing. 2 temporary posts FF were then set up, fastened by hook bolts L and lagged behind to make the wall form. Several of these 7FT sections were cut out at once, each 2 being separated by a 5FT section of timbering. The mortar car shown in Fig. 130 was then run alongside the sections in order, and enough 1 to 3 mortar was run by chute into each to make an 8-tin layer. As the car moved ahead to succeeding sections, enough broken stone was shoveled into the last preceding section to take up the mortar. The walls were thus built in 8-tin layers and became hard enough to support the arches in from 10 to 14 days. The arches were then allowed to take footing on the wall, and the posts of the remaining 5FT sections were removed and the concrete wall built up as for the 7FT sections. Where the posts carried wall plates, the struts SS were not needed, the wall plates supporting the undermined post as a beam. English Portland cement was used, and the concrete mixture was about 4 parts mortar to 5 parts broken stone, a very rich mixture. The average progress was about 30 FT, or 45 ku. IDs of side wall per working day. The average cost of the walls, including everything, was $8 per ku. YD of concrete. The brick arch cost $17 per ku. YD. Mr. H.C. Relf is authority for these figures. Fig. 130. Sketches showing method of lining Mullen Tunnel. Method and cost of lining a short tunnel, Peekskill N. Y. The following methods and costs of lining a double-track railway tunnel 275 FT. Longnia Peekskill N. Y. Are given by Mr. Geo. W. Lee. In presenting these data, it is important to note that while some of the methods described are applicable to so short a tunnel, they could not be used on a long tunnel. Figure 131 is a cross-section of the tunnel showing the lining. The tunnel was through rock, which stood up without timbering, and the rock section was excavated from 6 ins to 3 FT. Outside the lining, a 1 to 2 to 4 concrete using crusher-run stone below 1 in. In size was used for the lining and portal head wall coping, and a 1 to 3 to 6 concrete for the portal head walls proper. The cost of the portal head walls is included in the costs given further on. Fig. 131. Cross-section of Peekskill Tunnel showing lining. The side wall foundation trenches were first excavated from 1 to 3 FT. Deep and footing concreted and leveled up, the back of the footing being carried up against the rock and the front line to forms giving a 12 in offset to the side wall. The footings contained 200 ku. IDs of concrete. Platforms 25 FT. Square and level with the springing lines were then erected at each end of the tunnel. A derrick was placed at each platform to handle skips between it and the material tracks which ran underneath and through the tunnel, with a turnout at each end for switching back empty cars. A 60 HP portable boiler supplied steam for the derrick engines and a pump. The wall forms were built and erected in panels 12 FT. Long, these panels had 4 times 6 in. Plates and sills 4 times 4 in. Studs 3 FT. On centers and 2 in. Dressed and matched spruce sheeting. 4 panels were set up, 2 on each side, midway of the tunnel and braced to the tunnel track. Wheelbarrow runways carried on bents were built from the platforms to the forms. One from one platform to one side, another from the other platform to the opposite side. Temporary bulkheads were erected to close the ends of the forms, and they were filled. Meanwhile, carpenters were setting other panels at each end of the two first erected on each side. After 24 hours, the panels first set were taken down and moved ahead, and the processes described continued until the full length of side wall was completed. The side walls were not concreted back to the rock, back forms of 1 in. Hemlock were used, and the space remaining was filled with spalls. The side walls contained 692 ids of concrete. Arch forms were erected for 96 ft. At the center of the tunnel using 12 ft, lagging so that sections of this length could be taken down and moved ahead, 9 at each end. The lagging was first laid to a height of 3 ft above the springing line on each side, and the concrete dumped directly in place from runways laid on the lower chords of the arch ribs, which were placed 4 ft apart. When the concrete reached a height too great for direct discharge into the forms, it was dumped on the runway and passed over with shovels. On the upper portion of the ring, the concrete was first shoveled to a platform erected on the center posts of the ribs about 2 ft below the crown, and then passed in on the lagging, which was laid in 4 ft instead of 12 ft lengths at this stage of the work. As soon as each section of arch ring was completed, it was waterproofed with 6 layers of tar paper laid in hot tar and then packed behind with spalls. The arch centers were struck in a comparatively short time. In one instance, they were struck 90 hours after the last concrete was placed, and no settlement was apparent. The arch forms stuck so fast to the concrete, however, that they had to be jacked down by chiseling out the lagging so as to get a bearing on the arch concrete, and by nailing thrust blocks to the rib posts. The section was then hauled ahead by passing the main fall of the derrick through a snatch block on the first rib. When hauled clear of the lining, all but the first 3 ft of lagging on each side was removed. They were then jacked into position. The arch ring contained 932 ids of concrete, including the portal head walls 1948 ids of concrete were laid at the following costs for labor and materials. Item, total, per yd, cement at $1, 63 per bbl, $5,755, $52, 951 sand at $0, 75 per yd, 662, 94 0, 339, stone at $0, 80 per yd, 1,303, 20 0, 668 lumber mixing platforms and runways 336, 89 0, 174 ribs including hand sawing 234, 10 0, 120 backing boards 134, 44 0, 069 lagging 341, 040, 176 sheathing 268, 49 0, 137 plates, sills, studs, braces 182, 75 0, 093 coal 118, 73 0, 061 oil 16, 12 0, 008 hardware, nails, spikes, etc. 224, 39 0, 118 tools 181, 10 0, 093 freight on stone, cement, etc. 3,089, 86 1, 584 labor of all kinds 8,036, 31 4, 121, total $20,885, $86 $10, 712 method of lining Cascade Tunnel, Great Northern Rye. The Cascade Tunnel, 13,813 ft long, built in 1897 to 1900, was lined throughout with concrete from 24 ins to 3.5 ft thick mixed and placed in the following manner. It was necessary to place the lining without interfering with the transportation of materials and excavated material to and from the work ahead. The arrangement adopted to secure this end is shown by Fig. 132. A platform 500 ft long was constructed at the elevation of the wall plates. The rear end of this platform was reached by an incline, up which the cars loaded with concrete were hauled by an air hoist and cable and delivered to any point on this platform. While each 500 ft of tunnel was being concreted, the next 500 ft of platform in advance was being built with its approach incline so that there was no delay in the work. Complete concrete plants were installed at each portal, advantage being taken of the side hills of the approach into the mountain to handle as much material as possible by gravity. Each plant was equipped with a No. 6 gates crusher 40 in times 8 ft, rock screens and 16 in times 16 ft, screw concrete mixers. Large storage bins for the cement, sand, and stone were built adjacent to the mixer plant. A 1 to 3 to 5 concrete was used. The stone was crushed from the best rock, obtained in the tunnel excavation. This rock was loaded into the regular muck cars, taken to the portal by electric motors, and then dumped into other cars below the level of the muck cars. These cars were hauled by hoisting engine and cable to the crusher floor, and then dumped and sorted to avoid danger from pieces of unexploded dynamite. It was then run through the crushers, washers, and screens to the stone bin, and thence to the mixers. The mixed concrete was discharged into cars on the level of the muck car tracks, and these cars were taken by motor into the tunnel to the incline, up which they were hauled by cable and dumped on the platform. From the platform, the concrete was shoveled into the wall forms or onto the centers as desired. Fig. 132. Traveling platform used in lining cascade tunnel. The walls were concreted in alternate 12 ft sections, the weight on the timber arch thus being gradually transferred from the plumb posts to the walls. The roof arch was also built in 12 ft sections, the centers being in sections of corresponding length which were moved forward on dollies and jacked up as the work advanced. 10 sections of centering were used at each end. An average of 7 BBLS of cement were used per lineal foot of lining. The average monthly progress of lining was about 600 ft at each end. The concrete lining cost $44 per lin, ft of tunnel, done by company forces. Method of relining Hodges Pass Tunnel, Oregon Short Line Rye. The centers and side wall forms and the methods of work adopted in relining the Hodges Pass Tunnel on the Oregon Short Line Rye are explained in the accompanying illustrations. This tunnel is 1,425, 8 ft long, and when constructed in 1882 was lined with timber. The new lining consists of concrete side walls carrying a brick roof arch. Both the old and the new linings are shown in the drawings. The tunnel is through a variety of rock and clay strata, and through the soft strata an invert was required. Altogether, about 1/3 of the length of the tunnel was provided with an invert. It will be noted also that the new lining occupies materially more space than the old. This made necessary considerable excavation in enlarging the section. Fig. 133. Method of placing invert concrete. Hodges Pass Tunnel. The work of relining consisted of 3 operations, viz. the invert construction, the construction of the side walls, and the arch construction. Fig. 134. Method of constructing concrete side walls, Hodges Pass Tunnel. The form of the invert is shown in Fig. 136. It, of course, had to be constructed without entailing a break in the track, and the method adopted was as follows. The ties and ballast were removed from a section of track about 12 ft long, and in their place was substituted the timber frame shown in Fig. 133. Under the middle portion of this frame, a trench reaching clear across the tunnel and having a width of 6 to 7 ft. In the direction of the track was excavated to subgrade of the invert. The concrete was filled into this trench, formed to shape on top, and allowed to harden. The bridging frame was then taken out and the ties and ballast were replaced. Another section of track was then bridged, trenched and concreted, and so on until the length of invert required was constructed. Fig. 135. Side wall forms for plans and B. Fig. 134. The side wall construction was a more complex operation. It comprised first the removal of the old lining, the enlarging excavation, and the form erection and concreting. Two methods of performing this task were employed. Both are illustrated in Fig. 134. By the first method, designated as Plan A, the concreting was done continuously in sections of considerable length. The forms used are shown in detail by Fig. 135. By the second method, the concreting was done in alternate short panels. This method is designated Plan B on the drawings, Fig. 134. The forms used are shown in detail by Fig. 135. The only difference in the form construction for the two plans is in the connection of the posts at the top. Fig. 136. General plan of centers for roof arch, Hodges Pass tunnel. The construction of the centering for the roof arch is shown by Figs. 136 and 137, Fig. 137 giving detailed dimensions of the ribs and lagging. The center, as shown by Fig. 136 consisted of 4 ribs spaced 3 ft. On centers. Each rib consists of 2 side posts and an arch piece. The side posts on each side are connected at the bottoms by a sill and at the top by a cap. Jacks between the sill and a mud sill laid on the concrete invert or in the ditch held the center in place during arch construction. Lowering these jacks dropped the center onto trucks traveling on the mud sills. Thus the center was moved along as the work progressed, as will be noted from Figs. 134 and 135, the side wall forms carried the work only to the bottoms of the old caps. The arch center completed the concrete wall work and the roof arch. Only about 1/3 of the new lining had the brick arch, as shown by the drawings. In the remaining 2/3, the concrete was carried up much further on each side. In fact, the brickwork constituted only the top third of the arch. Fig. 137. Details of centers for roof arch, Hodges Pass tunnel. In describing the forms and centers, we have left much of the explanation to the drawings. These show all dimensions and details, and indicate in a measure the mode of procedure. The work done consisted of excavation enlarging the section, of removing the old timber lining, and of the form work, concreting and bricklaying for the new lining. All of it above convenient reach from the ground was done from a movable staging formed by a deck fixed on a flat car so as to be adjustable in height. The concrete was mixed by hand on this car platform and shoveled directly into the forms, the platform being raised as the work increased in height. The concrete used was a 1 to 3 to 5 mixture of 2 1/2 in. Broken stone. The organization of the working force is not easily stated since the work was done as the traffic permitted and varied with the conditions. Generally from 12 to 16 men were all that could be employed to advantage. Complete records of cost were kept, but they were destroyed by fire so that the only figures available on this point are the totals. These are as follows. Item, totals, per lin. FT, labor $21,129, $14. 81 materials, $13,939.9. 77, total $35,068, $24. 58, these amounts average the cost of the invert, which was required for about 1/3 of the length over the whole tunnel, relining a short tunnel. The following figures show the cost of relining with concrete a timber-lined railway tunnel. The concrete side walls were 14 ft high and had an average thickness of 2½ ft. Therefore, each side wall averaged nearly 1.3 ku ids per lin ft, and the two walls averaged 2.59 ku ids per lin ft of tunnel. The concrete was mixed 1:3:5, being, we believe, unnecessarily rich in cement. The average amount of concrete placed in the walls per day was 50 ku ids. Cost of side walls, materials per ku yd, 1.33 bbl. Cement at $2.002.66 5 ku yd. Sand at 0.18 0.90 75 ku yd. Stone at 0.55 41. Total $3. 16 labor on concrete 0.01 day foreman at $5. $0.00 $0.50 0.3 day foreman at $3. $0.00 0.90 0.3 day engineman at $3. $0.00 0.90 35 day laborer at $1. 75 61 42 total $0. 84 labor, removing timber, building farms, excavating, etc. 0.02 day foreman at $5. $0.00 10 0.05 day foreman at $3. 0.00 15 40 day laborer at $1. 75 70 47 total $0. 95 miscellaneous 0.02 day engineer and superintendent at $5. $0.00 10 false work and farms, timber and iron 0.07 tools, light, etc. 10 interest and depreciation of $1,800 plant at 20% per annum 0.09 train service 0.03 day work train at $25 0.75 summary concrete side walls per ku yd. Materials $3. 16 labor on concrete 0.84 labor removing timber etc. 0.95 train service 0.75 miscellaneous 0.34 total $6. 0.4 in the two side walls there were 2.59 ku ids of concrete per lin ft of tunnel, hence the cost of the side walls was $6. 0.4 times $2. 59 equals $15. 64 per lin ft of tunnel. The concrete arch varied in thickness, averaging from 14 to 20 ins. At the springing line to 8 to 14 ins. At the crown, the arch averaged 1-2 ku ids per lin ft of tunnel, about 20 ku ids of arch were placed per day. The arch concrete was mixed 1:3:5, and the cost was as follows. Cost of concrete arch. Materials per ku yd. 1.36 bbls. Cement $2. $0.02. 72 0.05 ku yd. Sand 0.18 0.90 75 ku yd. Stone 0.55 41 total $3. 22 8 ku ids. Dry rock backing at 0.55 $99 labor on concrete 0. 0 2-day foreman at $5, 0 10 0, 12-day foreman at 3, 0 36 0, 88-day laborer at 1, 75 1, 54 1, 0 2 total $1, 96 $2, 0 labor placing 1, 0 8 coup, IDS rock backing 0, 1-day foreman at $5, 0 $0 51-day foreman at 3, 0 15 0, 55-day laborer at 1, 75 0, 96 0, 61 total $1, $91, 16 labor removing timbers, farms, excavations, etc. 0 2-day foreman at $5, 0 10 0, 4-day foreman at 3, 0 12 0, 6-day carpenter at 2, 50 0, 15 0, 40-day laborer at 1, 75 0, 70 0, 52 total $2, 6 $1, 7 train service 0 6-day at $25 $1, 50 miscellaneous engineering and superintendents 7 false work, timber and iron, 13 tools, light, etc. 12 interest and depreciation, $1,800 plant, 20% per annum 0 9 summary concrete arch, concrete materials $3, 22 dry rock backing 1, 8 CY 0 99 labor and concrete 2, 0 labor placing 1, 8 coup, IDS, rock backing 1, 16 labor removing timber, etc. 1, 7 train service hauling materials 1, 50 engineering and superintendents 0 7 false work, timber and iron 0, 13 tools, light, etc. 0, 12 interest and depreciation plant 0 9 grand total $10. 35 It will be noted that the train service is an item that really should be considered as a part of the cost of the materials, for the cost of the sand and stone is the cost F. O. B. Cars at the sand pit and at the quarry, to which should be added the cost of hauling them to the tunnel, to wit, the train service. Summing up, we have the following as the cost per lineal foot for lining this single-track tunnel with concrete. Per lin, FT 259 coup, IDS, side walls at $6, 4 $15, 64 1 20 coup, IDS, arch at 10 33 12 40, 3 79 coup, IDS, total $9, 38 $28. 4 It should be remembered that the higher cost of the arch concrete is due in large measure to the fact that 1. 8 coup, IDS, of dry rock packing above the arch are included in the cost of the concrete. Strictly speaking, this dry rock packing should not be charged against the arch concrete, and segregating it, we have the following, per lin. FT, 259 coup, IDS, concrete side walls at $6, 4 $15, 64 1 20 coup, IDS, concrete arch at 8, 18 9 82 2 16 coup, IDS, dry rock at 0 55 1, 19 labor placing 2 16 coup, IDS, at 0 64 1, 39 total $28. 4 This is a much more rational analysis of the cost, and a still further reduction in the cost of the arch concrete might be made by prorating the train service item $1. 50 per coup, YD, concrete. At least half of this train service should be charged to the dry rock backing, for there are 25 coup, IDS of sand and broken stone to 80 coup, IDS of dry rock backing. The amount of this dry rock backing or packing varies greatly in different parts of a tunnel. In the first half of this tunnel it averaged 8 coup, IDS per lin, FT, while in the second half it averaged nearly 4 cu ids per lin, ft, method of mixing and placing concrete for tunnel lining. The tunnel known as the Burton Tunnel is located on the Jasper-French Lick extension of the Southern Rye, and about 4 miles from French Lick End. It is a single-track tunnel 2,200 ft, long with 300 ft. At one end on a 4 degrees 30 curve and 1900 ft. On tangent. The material penetrated was slate and loose rock, requiring solid timbering throughout. This timbering is shown by Fig. 138, which also shows the concrete lining. The timbering was embedded in the concrete lining. Fig. 138. Sections showing concrete lining for Burton Tunnel. The original timber lining was composed as follows: posts 10 times 12 ins and spaced 3 ft. Apart were set on 3 times 12 in, sills and carried 10 times 12 in. Wall plates which supported 10 times 12 in. Segmental arch ribs spaced 3 ft. Apart. The lagging behind the posts was 3 times 6 in. Stuff and the lagging over the arch ribs was 4 times 6 in. Stuff. The section of the concrete lining is shown by Fig. 138. It required 4,132 cu ids of concrete and 43 pounds of reinforcement per lin, ft. The concrete was a 1:2 of 5 crushed stone between 2 in and 1/4 in. Size mixture, it required 1/16 bbls of cement, 0.52 cu ids sand, and 0.92 cu ids of stone per cubic yard of concrete. The amount of reinforcement per cubic yard of concrete was 39 pounds. Fig. 139. View of mixer plant showing car tracks, Burton Tunnel. Fig. 140. View of mixer plant showing method of unloading materials, Burton Tunnel. All the concrete was mixed and handled from one end of the tunnel. The mixing plant was located in the approach cut at one end. A standard gauge main track ran through the cut, about 20 ft. In the clear to one side of this track, a trestle 500 ft. long was built, carrying an 18 ft. gauge derrick track and a narrow gauge 3 cu yd dump car track. A stiff leg derrick operating a 1 cu yd orange peel or a 1.5 cu yd clamshell Haywood bucket was mounted on a carriage traveling on the 18 ft. gauge track. The side of the trestle nearest the railway track was sheeted vertically, and the space between this sheeting and the track was floored over at track level for stock piles. Near the end of the trestle toward the tunnel and on the same side of the track was the mixer plant. This consisted of 285 cu yd bins, 1 for sand and 1 for stone, carried by a tower so that their bottoms were 25 ft. above track level. Below the bins was a charging platform pierced by a measuring hopper. Below the measuring hopper was a 1.5 cu yd cubicle mixer, and below the mixer was a 3 ft. gauge track for 1.5 cu yd Capel side dump cars. To the rear of the tower at ground level there was a 20 cu yd sand bin and a 20 cu yd stone bin set side by side with a continuous bucket elevator leading from each to the corresponding bin on the tower. The cement house was located directly across the railway track from the tower. At the side of the cement house nearest the track, there was an inclined bag elevator leading up to a bridge spanning the railway track at the level of the charging floor of the mixer plant. On this bridge ran a car for carrying bags of cement. The plant as described is shown by Figs. 139 and 140. In operation, the derrick unloaded the stone and sand cars by means of the Haywood buckets either into the bins at the feet of the bucket elevators or onto stock piles on the flooring beside the trestle. When put into stock piles, the materials had to be reloaded by derrick into the 3 YD cars on the trestle narrow-gauge track and carried by these cars to the elevator boots. The sand and stone were chuted from the tower bins directly into the charging hopper below. Here the cement bags, brought across the bridge on the car into which they were loaded directly by the bag elevator, were opened, and the cement added to the sand and stone. The charge was then dropped into the mixer, and from the mixer the batch dropped into the Capel concrete cars. In the tunnel, a traveling platform was constructed on 2 standard-gauge flat cars so coupled that a platform 100 FT, long and slightly narrower than the clear space between side wall forms, was obtained. Connecting the end of the platform toward the mixing plant was a ramp or inclined platform mounted on wheels. The Capel car tracks from the mixer were carried up the incline and the full length of the level platform. The cars were hauled to the foot of the incline by a light locomotive. A cable was then hooked to them. This cable was run through a block on the level platform, its free end coming back to the locomotive, which thus pulled the cars up the incline by moving back toward the mixer. On the level platform, the cars were pushed by hand and dumped on the floor, whence the concrete was shoveled into the forms. The platform construction deserves mention in the particular that it provided for adjusting the platform vertically. At each corner of the car, a vertical post some 7 or 8 FT high was set up. The side stringers of the platform carried 2 vertical posts at each end. These 2 posts were spaced just far enough apart to slide over the corner post, one on each side of it. A block at the top of the corner posts with the hoist line connected to the bottoms of the platform posts and the lead line going to a winch head, thus made it possible to lift the platform any distance within the height of the vertical post guide, and hold it there by blocking under the posts. The arrangement is shown roughly by the sketch, Fig. 141. There was block and tackle for each corner post, and a winch at each end of the car. The vertical movement of the platform was between 6 and 7 FT. The floor was cemented first, then the side walls, and finally the roof arch. Floor construction was begun at the portal farthest from the mixing plant. Capel car tracks were laid through the tunnel, and the concrete was dumped from them directly on the ground. The cars were hauled by a light locomotive. As the concreting advanced, the dump car track was raised and suspended from timbers across tunnel, so that the concrete could be placed under it. As fast as the floor hardened, the permanent standard gauge track was laid, and a temporary third rail placed to give also a dump car track. Fig. 141. Sketch showing telescopic support for concreting platform Burton Tunnel. When the floor had been finished, the side walls were constructed using the traveling platform and beginning at the far portal. The wall forms consisted of 4 times 6 in. Studs spaced 3 FT, apart and carrying 2 times 12 in. Lagging, a 6 times 6 in. Wailing outside the studs at about mid-height held the studs to the timbering by lag bolts reaching through the wall to the 10 times 12 in. Posts. A strip of plank nailed across wall between stud and post held the form at the top. Wall forms were erected for 100 FT, of wall at a time. These forms required about 45 FT, B.M. lumber per lineal foot of form on one side or 90 FT, B.M. for both sides. 2 sets of side wall forms or 200 FT. Of wall forming were built and used over and over again. The concrete was shoveled into the wall forms from the traveling platform, the lagging being placed aboard at a time as the work progressed upward and the platform being elevated as required, its final position being at about springing line level. When 100 ft of side walls had been completed, the traveling platform was moved ahead for another 100 ft. Section Fig. 142. Sketch showing device for removing centering ribs, Burton Tunnel. The centers consisted of 6 times 12 in. Ribs made up of 3 times 12 in. Plank. The feet of the ribs rested on folding wedges on 6 times 12 in. Wall plates supported by 6 times 6 in. Posts setting close against the finished wall. The ends of the ribs were held from closing in by 6 times 6 in. Wailings, one on each side, lag-bolted through the lining to the timbering. The centering required about 315 ft. B.m. of lumber per lineal foot of center. The method of removing the centers was novel. A flat car had erected on it a narrow working platform high enough to reach well up into the arch. Along this platform at the center was erected a sort of horse, which could be elevated and lowered by jacks. The sketch, Fig. 142, shows the arrangement. At each end and at the middle of the platform, 2 guide posts were erected and braced upright. Between these guide posts set plunger posts, which were raised and lowered by screw jacks. The 3 plunger posts carried a longitudinal timber C. The car was run under the ribs of centering to be removed, and the timber C raised by working the jacks until it came to close bearing under the ribs D. The railings and the wedges at the foot of the ribs were then removed, leaving the ribs hanging on the timber C. This timber was then jacked down to clear the lining, and the ribs rotated horizontally on the point of suspension as a pivot until their ends swung in over the platform. The car was then moved ahead to where the centers were to be used again. The ribs were rotated back to their normal position across tunnel. The timber C was jacked up, and the wedges and railings placed at the first of the ribs. The concreting on the roof arch was begun at the portal. 2 shifts were worked, and 42 ft. of arch were concreted each shift. Method and cost of lining Gunnison Tunnel. The costs are for concrete in place in the side walls and the arch of the tunnel, for a length of 440 lin. ft. The quantity of concrete considered in estimating the cost per cubic yard was 616 cu. Ids. The material was mixed and placed in a half cu. Yd. Batches, the proportion of the mixtures being 1 to 2, 2 to 4, 4. The final cost includes the labor of excavating and screening gravel and sand, the hauling of the same from the bins at the pit to the storage bins at the main shaft, the care of the chutes in the shaft, and the mixing of the concrete in the tunnel at the bottom of the shaft, the transportation of the concrete from the mixer to the traveler, the deposition of the concrete, the setting up and taking down of forms, and the cost of the cement. It does not include the construction of the gravel pit chutes that hold the screens, the building of the road from the gravel pit to the storage bins at the shaft, the concrete mixer and its installation, the traveler and its installation, the cost of material and labor in the construction of the concrete forms, the requisite power to run the machinery and other expenses of a similar nature. The gravel used for the concrete was obtained from a pit situated on top of a hill not far from the main shaft leading down to the tunnel. This gravel bed contains very closely the proper proportions of sand and gravel for the concrete aggregates. The gravel was excavated and loaded by hand into side dump cars of 35 cu. ft. capacity. These cars were run to the edge of the hill where the gravel was dumped upon a screen from which it ran by gravity, passing thence into storage bins. From the storage bins, the sand and gravel were drawn off into dump wagons having a capacity of 2 cu. Ids. and hauled a distance of 1/2 mile to a second set of storage bins located at the top of the shaft leading into the tunnel. The road from the storage bins at the gravel pit to the storage bins at the head of the shaft was downgrade. A 2-horse team could readily haul 2 ids of gravel over this road. The storage bins at the top of the shaft leading into the tunnel communicated with the measuring boxes at the bottom of the shaft by means of chutes. The measuring boxes discharged directly into tram cars. The average length of haul from the mixer to the place of deposition of concrete was about 4,500 ft. The concrete was placed in the side walls by means of a traveler, which was so operated in the tunnel as to allow the passage of the concrete trains beneath it. The traveler was 64 ft long and was provided with a slow-motion electric hoist, by which the cars containing the concrete were elevated to the top of the traveler and thence transferred to any desired position. The concrete was dumped from these cars into boxes where any remixing or tempering that was required was done, after which the concrete was shoveled directly into the forms. The entire operation of handling the materials of the concrete, it will be seen, utilized gravity to the greatest possible degree. In order to get a good average cost per cubic yard for handling gravel and sand, this analysis has been based on 5 months' operation, from November 1906 to March 1907. In these 5 months there were 4,123 ids of sand and gravel handled. The concrete considered was placed during the month of March. Below is given the distribution of the cost of the concrete as to the specified divisions of the work and as to the class of work involved in each division. Measurements taken at the mixer show that each cubic yard of concrete contained 0.74 ids of gravel, 0.445 ids of sand, and 6 sacks of Portland cement. The total of the aggregates is therefore 185 ids per cubic yard of concrete. The cement costs $0.62 per sack on the work, making a cost of $3.472 per cubic yard of concrete. Excavating and screening 4,123 ids gravel, total cost per yd gravel, foreman 66 days at $3.04 $203 $30 $0.49 labor 397 a half days at $2 56 1017 60 247 labor 116 a quarter days at $2 08 241 80 059 total $1,462 $70 $355 hauling 4,123 ids gravel and sand 2-horse team and driver 210 days at $3 $6,756 $000 183 2-horse team and driver 4.5 days at $4.18 $000 total $774 $000 188 as there were 185 ids of gravel per cubic yard of concrete. The cost of gravel per cubic yard of concrete was for excavating and screening 185 times $0 355 $0 421 hauling 185 times $0 188 0 223 total $0 644 adding to this the cost of cement $0 62 times 5 6 equals $3 472 we have $0 $644 plus $3, $472 equals $4, 116 as the cost of concrete materials per cubic yard of concrete. The cost of labor mixing and placing was as follows for 616 cu. IDS. Mixing 616 cu. IDS. Concrete total cost per cu. YD. Concrete. Superintendent 2 days at $5. 83 $1/3 11 67 $0 020 foreman 1 day at $4 54 50 007 labor 45 days at $3 04 130 72 215 labor 93 days at $2 56 238 080 381 hoist engineer 34 days at $3 52 119 68 196 total $504 65 $819 transporting 616 cu. IDS concrete superintendent 1 day at $5 83 $1/3 5 83 $009 foreman 1 day at $4 54 50 007 motorman 34 days at $3 04 103 36 175 brakeman 34 days at $2 56 87 040 135 total $200 73 326 depositing 616 cu. IDS concrete superintendent 4 days at $5 83 $1/3 23 33 038 foreman 4 days at $4 50 18 029 foreman 68 days at $3 04 200 72 326 labor 238 a half days at $2 56 610 56 991 total $852 61 $1 384 setting and moving forms superintendent 2 days at $5 83 $1/3 11 67 $0 018 foreman 2 days at $4 59 014 carpenter foreman 10 days at $5 50 080 carpenter 13 days at $3 2041 60 067 labor 49 days at $3 04 148 96 241 labor 19 days at $2 56 48 64 078 total $309 87 498 summarizing we have the following cost. Materials, cement, 6 bags at $0, 62 $3, 472 gravel excavating and screening 0, 421 hauling gravel and sand 0, 223 total materials $4, 116 labor mixing concrete $0, 819 transporting concrete 0, 326 depositing concrete 1, 394 setting and moving forms 0, 498 total labor $3, 037 grand total $7, 153 cost of concrete work in lining New York Rapid Transit subway. The costs given here refer alone to the concrete work in constructing the jack arch and steel beam lining of the original standard subway. Figure 143 shows the character of this construction. Arch panel forms were set up between the wall beams and hung from the floor beams and filled behind and above with 1 to 2 to 4 trap rock concrete. The form panels were used over and over, and the concrete was machine mixed. Common labor was paid $1.50 per 8-hour day, foremen $3, carpenters $3, enginemen $3.50, and masons $4. The costs cover 3 sections and are in each case the averages for the whole section. They are, we believe, the only itemized costs that have been published for concrete work on this road. 2-track subway. In this section of 2-track subway, there were 8,827 ids of foundation concrete and 6,664 ids of concrete in wall and roof arches. The 2 classes of work cost as follows. Fig. 143. Cross-section of New York Rapid Transit Subway. Foundations, total. Per YD. Labor mixing $4,669. 53 labor placing 5,142. 58 materials and plant 211. 02 cement, sand, stone, etc. 30,719. 48. Total $40,741. $4. 61 roof and side walls. Labor mixing $5,444. $0. 82 labor placing 5,623. 84 labor setting forms 14,746. 21 labor plastering arches 431. 06 materials and plant 1,176. 18 cement, sand, stone, etc. 23,888. 58. Total $51,308. $7. 69 averaging the work, we have 15,491 ids of concrete placed at a cost of $5.94 per YD. 4-track subway. On 2 sections of 4-track subway, the labor cost of mixing and placing concrete similarly divided was as follows. Section A. Section B. Foundations per YD. Per YD. Labor mixing $0, 97 $0, 94 labor placing 0, 96 0, 95 power 0, 14 0, 16. Total $2, 07 $2, 05 roof and side walls, labor mixing $0, 79 $0, 91 labor placing 0, 85 0, 94 labor setting forms 2, 011. 20 labor plastering arches 0, 16 0, 23 power 0, 28 0, 15. Total $4, $093, 43 Fig. 144. Traveling form for side walls, New York subway tunnels. Traveling forms for lining New York Rapid Transit tunnels. In constructing the tunnels under Park Ave and under the north end of Central Park for the New York Rapid Transit traveling centers and side wall forms were used for the concrete lining. The mixing plants were installed in the shafts and consisted generally of gravity mixers charged at the surface and discharging into skip cars running on the tunnel floor. Fig. 145. Traveling form for roof arch, New York subway tunnels. The forms used in the Park Ave tunnel are shown by Figs. 144 and 145. Those used in the Central Park Tunnel differed only in details. The method of work was slightly different in the 2 tunnels, but was substantially as follows. 3 platforms mounted on wheels were used in each set, and 2 sets were employed. Ahead came a traveler carrying the side wall forms, next came a shorter traveler carrying a derrick, and last came the traveler carrying the roof centers. The arrangement as operated in the Central Park Tunnel is shown by Fig. 146. In the Park Ave, tunnel the bridges were dispensed with, the skips being hoisted through the open-end bays of the derrick car and set directly on the cars on the center traveler. Fig. 146. Sketch plan of traveling forms, New York subway tunnels. The traveler carrying the side wall forms was set in position and blocked, the grade and line being given by the track rails, which had been set exactly for that purpose. The side wall forms differed slightly in the two tunnels, those for the Park Ave. Tunnel shown by Fig. 144 formed the vertical portion of the wall only so that when the arch forms Fig. 145 followed a space, a B was left which had to be molded by separate sector-like forms. The side wall forms for the central park work were constructed as shown by Fig. 147 being curved at the top to merge into the arch centers. In the Park Ave work, the wall studs were adjusted in or out by means of wedges and slotted bolt holes. In the Central Park work, the studs of Fig. 145 were hung by 3/4 in. Bolts from the pieces be spiked to line onto the cross braces. The bottom was then lined up by means of wedges at D. The side wall studs being lined up. The bottom lagging boards were placed and filled behind by shoveling the concrete into them direct from skip cars on the adjacent tracks on the tunnel floor. In this way, the side walls were built up to the tops of the forms. Fig. 147. Sketch showing detail of side wall forms, New York subway tunnels. As soon as the side wall concrete had set, the forms were struck, and the traveler was moved ahead and set for another section of wall. The derrick and roof arch travelers were then moved into position between the finished walls, and the arch traveler was jacked up and aligned. Skip cars coming from the mixer were run under the derrick traveler, where the skips were lifted by the derrick and set on the platform cars to be run alongside the work. The arch lagging was placed a piece at a time and filled behind by shoveling direct from the skips. As the crown was approached, the lagging was placed in short lengths and filled in over the ends, the concrete being shoveled in 2 lifts. In Fig. 145, the line CD indicates the position of the shoveling board. The centers were struck by lowering the jack-supported traveler down onto the track rails. Cost of mixing and placing subway lining, Long Island, Brooklyn, NY. The subway carrying the 2 tracks of the Long Island under Atlantic Ave in Brooklyn, New York City has a lining consisting of an invert arch 12 ins. Thick at the center, side walls 4.5 ft, thick at the base and 3 ft, thick at the top, and a roof of jack arches between steel I-beams 5 ft apart. The dimensions inside the concrete are 16 times 20 ft. A 1:8 mixture of cement, sand, gravel, and stone was used in the floor and walls, and a 1:6 mixture of the same materials in the jack arches. A bag of cement was called 1 cu ft, so that a barrel was 4 cu ft. A Haynes gravity mixer and a batch mixer were used, and careful records were kept of all quantities, general data. During 1903, about 13,880 cu ids of the 1:8 concrete were placed, 90% of which was mixed in the gravity mixer and 10% in the batch mixer. Of the 1:6 concrete, 5,320 cu ids were placed, 85% of which was mixed in the gravity mixer and 15% in the batch mixer. Gravity mixer work. During 1903, there were 16,940 cu ids of concrete mixed in gravity mixers, requiring 2,860 days labor mixing and 4,000 days labor placing. Wages were $1.50 a day, and the cost was 26 CTS, per coup YD for mixing and 33 CTS for placing, making a total of 59 CTS per coup YD. During the month of August, when 2,800 coup IDs were mixed, the cost was as low as 24 CTS. For mixing, plus 22 CTS. For placing, or a total of 46 CTS per coup YD for mixing and placing. The mixer averaged about 113 coup IDs per day with a gang of 19 men mixing and 26 men placing. The average size of batch was 0.46 coup YD. In 1904, 20,000 coup IDs were mixed in 190 days, worked with a gang of 19 men mixing. The gang placing consisted of 25 men. The cost was as follows. Item, total, per coup, YD. 2,950 days labor mixing $4,870 24 CTS. 4,760 days labor placing 7,336 CTS. A total $12,170 60 CTS. During the best month of 1904, the labor cost was 16 CTS. For mixing and 29 CTS. For placing, or a total of 45 CTS. Per coup YD. Batch mixer work. During 1903, the batch mixer mixed 2,390 coup IDs in 970 labor days mixing and 740 labor days placing at a cost of 59 CTS per coup YD. For mixing and 55 CTS per coup YD for placing, or a total of $1.04 per coup YD. During the month of June, the cost was as low as 40 CTS for mixing and 30 CTS for placing, or 70 CTS per coup YD for mixing and placing. The wages paid were $1.50 per day, and the average gangs were 11 men mixing and 14 men placing. The average batch mixed was 0.57 coup YD, and the average output was 35 coup IDs per day. During 1904, the mixer worked 153 days and averaged 46 coup IDs per day. The average size of batch was 0.44 coup YD. The average gangs were 13 men mixing and 11 men placing. The labor cost of 7,000 coup IDs was as follows. Item, total, per coup YD. 1,910 days labor mixing $3,175 45 CTS. 1,740 days labor placing 2,660 38 CTS. Total $5,835 83 CTS. Haulage. The costs given comprise in mixing, the cost of delivering the materials to the mixer, and in placing, the cost of hauling the concrete away. A Robbins belt conveyor was used to deliver materials to the gravity mixer, and this accounts, in a large measure, for the lower cost of mixing by gravity. The mixed concrete was hauled from both mixers in dump cars pushed by men. Form work. The labor cost of forms for 19,300 coup IDs of concrete placed in 1903 was $16,800 or 87 CTS per coup YD of concrete. The total labor days consumed on form work was 6,340 at $2.70 per day. The total cost of concrete in place for mixing, placing, and form work was $1.46 per coup YD. Not including lumber in forms, fuel, interest, and depreciation. Chapter 46. The construction problems in arch and girder bridges of moderate spans are simple, and with the exception of center construction and arrangement of plant for making and placing concrete, are best explained by citing specific examples of bridge work. This is the arrangement followed in this chapter. Centers. The construction of centers is no less important a task for concrete arches than for stone arches. This means that success in the construction of concrete arches depends quite as much upon the sufficiency of the center construction as it does upon any other portion of the work. The center must, in a word, remain as nearly as possible invariable in level and form from the time it is made ready for the concrete until the time it is removed from underneath the arch. And when the time for removal comes, the construction must be such that that operation can be performed with ease and without shock or jar to the masonry. The problem of center construction is thus the twofold one of building a structure which is immovable until movement is desired and then moves at will. Incidentally, these requisites must be obtained with the least combined expenditure for materials, framing, erection, and removal, and with the greatest salvage of useful material when the work is over. The factors to be taken count of are it will be seen, numerous, and may exist in innumerable combinations. Fig. 148. Center for 50 ft. Arch span supported. Fig. 149. Center for 50 ft. Arch span cocket. Centers may be classified into two types. 1. Centers whose supports must be arranged so as to leave a clear opening under the center for passing craft or other purposes, and 2. Centers whose supports can be arranged in any way that judgment and economy dictate. Centers of the first class are commonly called cocket centers, as examples of a cocket and of a supported center, and also as examples of well-thought-out center design. We give the two centers shown by Figs. 148 and 149, both designed for a 50 ft. Span segmental arch by the same engineer. The development of the center shown by Fig. 148 into the cocket center shown by Fig. 149 is plainly traceable from the drawings. In respect to the center shown by Fig. 149, which was the construction actually adopted, we are informed that 16,464 ft. B. M. were required for a center 36 ft. long, that the framing cost about $12 per m. ft. B. M. with carpenter's wages at $4 per day, and that the cost of bolts and nuts was about $1.50 per m. ft. B. M. with lumber at $20 per m. ft. B. M. This center framed and erected would cost about $35 per m. ft. B. M. As an example of framed centers for larger spans, we show by Fig. 158 the centers for the Connecticut Avenue Bridge at Washington, D.C., with costs and quantities. Other references to costs are contained in the index. A center of very economical construction is shown by Fig. 159 and is described in detail in the accompanying text. The distinctive feature of this center is the use of lagging laid lengthwise of the arch and bent to curve. Another example of this form of construction may be found in a three-span arch bridge built at Mechanicsville, N.Y. in 1903. The viaduct was 17 ft. wide overall and consisted of two 100 ft. spans and one 50 ft. span. Pile bents were driven to bedrock, the piles being spaced 6 ft. apart and the bents 10 ft. apart. Each bent was capped with 10 times 12 in timber. On these caps were laid 4 lines of 10 times 12 in stringers and 8 times 10 in posts 3 ft. apart were erected on these stringers, and each set of 4 posts across the arch was capped with 8 times 10 in timbers, the ends of which projected 3 ft. beyond the faces of the arch. The tops of these cross caps were beveled to receive the lagging which was put on parallel with the center line of the viaduct, sprung down and nailed to the caps. This lagging consisted of rough 1-in boards for a lower course, on top of which was laid 1-in boards dressed on the upper sides. Hardwood wedges were used under the posts for removing the centers. In the centers, forms and braces for the 3 arches there were used 140,000 ft/m of lumber. The structure contained 2,500 ids of concrete. Another type of center that merits consideration in many places is one developed by Mr. Daniel B. Luton, and used by him in the construction of many arches of the Luton type of reinforced concrete arch. The particular feature of this type of arch is that in shallow streams for bridges of ordinary span, the ends of the arch ring are tied together across stream by a slab of concrete reinforced to take tension. This slab is intended to serve the double purpose of a tie to keep the arch from spreading and thus reduce the weight of abutments, and of a pavement preventing scour and its tendency to undermine the abutments. Incidentally, this concrete slab, which is built first, serves as a footing for the supports carrying the arch center. As an illustration of the center, we choose a specific structure. In building a 95 ft, span 11 ft, 1-in, rise arch bridge at Yorktown, Ind. In 1905, the centers were designed so as to avoid the use of sand boxes or wedges. Ribs of 2 times 12-in pieces cut to the arc of the arch soffit were supported on uprights standing on the concrete stream bed pavement. The uprights were so proportioned by Gordon's formula for columns that without bracing they would be too light to support the load of concrete and earth filling that was to come upon them. But when braced at 2 points, dividing the uprights approximately into thirds, they would support their loading rigidly and without buckling. The design in detail was as follows. The uprights near the middle of the span were about 15 ft long and were spaced 7 ft apart across the stream and 3 ft apart across the bridge. Each upright then was to support a loading of concrete of 7 ft times 3 ft times 26 ins, and an earth fill 1 ft times 7 ft times 3 ft, or a total load of about 9,000 pounds. Applying Gordon's formula for struts with free ends, FSP equals L2I plus 125H2, where P is the total load, equals 9,000 pounds. F is fiber stress for oak, 1,600 pounds. L is length of strut in inches, and H is least diameter of strut in inches. It was found that for a length of 15 ft, a 7 times 7-in upright would be required to satisfy the formula, but for a length of 5 ft, which would result from bracing each strut at 2 points, a 4 times 4-in timber satisfied the formula. Therefore, 4 times 4-in timbers braced at 2 points were used for the longest uprights. About 30 days after the completion of the arch, the bracing was removed from the uprights, beginning at the ends of the span and working towards the middle. As the bracing was being removed, the uprights gradually yielded, buckling from 4 to 6 ins from the vertical and allowing the arch to settle about a 1/4 in at the crown. This type of center has been successfully employed in a large number of bridges. Figure 150 shows a center for a 125 ft span parabolic arch with the amount and character of the stresses indicated and with a diagram of the actual deflections as measured during the work. Fig. 150. Center for 125 ft span parabolic arch with diagram of deflections. In calculating centers of moderate span, there is seldom need of more than the simple formulas and tables given in Chapter Roman 9. when the spans become larger, and particularly when they become very large, over 200 ft. The problem of calculating centers becomes complex. None but an engineer familiar with statics and the strengths of materials and knowing the efficiency of structural details should be considered for such a task. Such computations are not within the intended scope of this book, and the design of large centers will be passed with the presentation of a single example, the center for the Walnut Lane Bridge at Philadelphia, PA. The main arch span of the Walnut Lane Bridge consists of twin arches spaced some 16 ft, apart at the crowns and connected across by the floor. Each of the twin arch rings has a span of 232 ft, and a rise of 70 1/4 ft, is 9 1/2 ft, thick and 21 1/2 ft, wide at the skewback and 5 1/2 ft, thick and 18 ft, wide at the crown. The plan was to build a center complete for one arch ring and then to shift it along and reuse it for building the other arch ring. The centering used is shown in diagram by Fig. 151. It consists of 5 parts. 1. 6 concrete piers running the full width of the bridge upon which the structure was moved. 2. A steel framework up to e.g. called the primary bent. 3. A separate timber portion below the heavy lines EI and WI. 4. The main staging included in the trapezoid EIWI. And 5. The upper trestle extending from II to the intrados. Fig. 151. Center for 232 ft. Span arch at Philadelphia, PA. The primary bent consists of 4 I-beam post bents having channel cords, the whole braced together rigidly by angles. Each bent is carried on 1 1/2 ft, times 6 in. Steel rollers running on a track of 19 times a in. Plate on top of the concrete piers. Between the primary bents and the main staging, and also between the main staging and the upper trestles are lifting devices. The mode of operation planned is as follows. When the center has been erected as shown, and the arch ring concreted, the separate stagings under KI and KI are taken down. Next, the portions under the lines IE and IW will be taken down and erected under the second arch. Finally, the remainder of the center will be shifted sidewise on the rollers to position under the second arch. Mixing and transporting concrete. The nature of the plant for mixing and handling the concrete in bridge work will vary not only with varying local conditions, but with the size and length of the bridge. For single-span structures of moderate size, the concrete can be handled directly by derricks, or on runways by carts and wheelbarrows. For bridges of several spans, the accepted methods of transport are cableways, cars and derricks. Typical examples of each type of plant are given in the following paragraphs, and also in the succeeding descriptions of the Connecticut Avenue Bridge at Washington, D.C., and of a 5-span arch bridge, cableway plants. The bridge was 710 ft, long between abutments and 62 ft wide. It had a center span of 110 ft, flanked on each side by a 100 ft, a 90 ft, and an 80 ft span. The mixing plant was located at one end of the bridge and consisted of a Drake continuous mixer, discharging 1/2 at the mixer and 1/2 by belt conveyor to a point 50 ft away so as to supply the buckets of 2 parallel cableways. The mixer output per 10-hour day was 400 ids, and the mixing plant was operated at a cost of $27 per day, making the cost of mixing alone 6¾ CTS per yd. The sand and gravel were excavated from a pit 4½ miles away and delivered by electric cars to the bridge site at a cost of 50 CTS per YD, two 930 FT. Span Lambert cableways set parallel with the bridge, 125 FT. Each side of the center axis were used to deliver the concrete from mixer to forms. The cableway towers were 70 FT. High and the cables had a deflection of 35 FT. They were designed for a load of 7 tons, but the average load carried was only 3 or 4 tons. These cableways handled practically all the materials used in the construction of the bridge. They delivered from mixer to the work 400 cu. IDs of concrete 450 FT in 10 hours at a cost of 2 CTS per cu. YD for operation. Fig 151A. Cableway for concreting bridge piers. Another example of cableway arrangement for concreting bridge piers is shown by Fig 151A. The river was about 800 FT, wide about 3 FT, deep and had banks about 20 FT, high. The piers were about 21 FT, high. The towers for the cableway consisted of a 55 FT derrick without boom, placed near the bank on the center line of the piers and well guyed, and a 2-leg bent placed in the middle of the river and held in place by 4 cable guys anchored to the river bottom. A 3/4 in steel hoisting cable was stretched from a deadman on shore, about 150 FT. Back of the derrick and followed along the center line of the piers past the derrick, just clearing it, to the bent in the middle of the river. At the top of this bent was a 16-in cable block. Through this block the cable passed down and was made fast to a weight, consisting of a skip loaded with concrete until the cable had the required tension, and a pitch of 18 to 20 FT. From center of river to anchor on shore. In order to secure the required pitch from the shore to the river bent, the boom fall of the derrick was hooked onto the cable at the foot of the mast, and then, by going ahead on the single drum hoisting engine, was raised to the mast head. This gave the cable a pitch of 18 to 20 FT, from mast head to top of bent in river. The carriage vised on the cableway consisted of 2 16-in cable sheaves with iron straps, forming a triangle with a chain hanging from the bottom point, to which was attached the 5 cu. FT capacity concrete bucket. The concrete was mixed on a platform at the foot of the mast. When ready for operation, the chain on the carrier was hooked to the bucket of concrete. The engine started, and both bucket and cable raised, the former running by gravity to the pier. The speed of descent was governed by the height to which the cable was raised on the derrick, and as the bucket neared the dumping point, the engine was slacked off and the cable leveled. The bucket was dumped by a man on a staging erected on the pier form. For the return of the bucket, the engine was slacked off, and the weight on the river bent would pull the cable tight so that the pitch would be toward the shore and the bucket could run down the grade to the mixing platform, the speed being governed as before by leveling the cable. When the piers were completed to the middle of the river, the engine and derrick were taken over to opposite side of the river, the bent being left in the middle, and the work continued. By using the extreme grade of the cable, it was found that the bucket would run from the platform to the bent 400 FT in less than 35 seconds. Fig. 152. Sketch showing car and trestle plant for concreting an arch bridge. Car plant for force-pan arch bridge. The bridge had 4 110 FT skew spans and a total length of 554 FT. The mixing plant was located alongside one abutment on a side hill so that sand and stone could be stored on the slope above. The mixer was set on a platform high enough to clear cars below. Above it and to the rear, a charging platform reached back to the stone and sand piles. Side dump cars running on a track on the charging platform took sand and stone to the mixer, and cement was got from a cement house at charging platform level. The concrete for the abutment adjacent to the mixer was handled in buckets by a guy derrick. A trestle, Fig. 152, was then built out from the mixer to the first pier. This trestle was so located as to clear the future bridge about 20 ft, and was carried out from shore parallel to the bridge until nearly opposite the pier site, where it was swung toward and across the pier. The concrete was received from the mixer in bottom dump push cars. These cars were run out over the pier site and dumped. When the first pier had been concreted to springing line level, the main trestle was extended to opposite the second pier, and the branch track was removed from over the first pier and placed over the second pier. This operation was repeated for the third pier. The last extension of the main track was to the far shore abutment, where the bodies of the cars were hoisted by derrick and dumped into the abutment forms. The derrick was the same one used for the first abutment, having been moved and set up during the construction of the intermediate piers. To construct the arches, a second trestle was built composed partly of new work and partly of the staging for the arch centers. This trestle rose on an incline from the mixer to the first pier, across which it was carried at approximately crown level of the arch. The concrete for the portion of the pier above springing line and for the lower portions of the haunches was dumped direct from the cars. For the upper parts of the arch, the concrete was brought to the pier track in two-wheel carts on push cars, and thence these carts were taken along the arch toward shore on runways. When the first arch had been concreted, the second trestle was extended to Pier 2, and the operation repeated to concrete the second arch. Hoist and car plant for 21-span arch viaduct. The double-track concrete viaduct replaced a single-track steel viaduct, being built around and embedding the original steel structure which was maintained in service. The concrete viaduct consisted of 21 spans of 26 ft, 7 spans of 16 ft, and 2 spans of 22 ft. With piers, it required about 15,000 ids of concrete. 2 ransom concrete hoists, one on each side of the original steel structure near one end, were supplied with concrete by a No. 4 ransom mixer. The mixer discharged direct into the bucket of one hoist, and by means of a shuttle car and chute into the bucket of the other hoist. The shuttle car ran from the mixer up an incline laid with 2 tracks, one narrow gauge and one wide gauge, having the same center line. The car was open at the front end, and its 2 rear wheels rode on the broad gauge rails, and its 2 forward wheels rode on the narrow gauge rails. At the top of the incline, the narrow gauge rails pitched sharply below the grade of the broad gauge rails, so that the rear end of the car was tilted up enough to pour the concrete into a chute which led to the bucket of the hoist. The sand and gravel bins were elevated above the mixer and received their materials from cars which dumped directly from the steel viaduct. The hoist buckets discharged into 2 hoppers mounted on platforms on the old viaduct. These platforms straddled 2 narrow gauge tracks, one on each side of the old viaduct parallel to and clearing the main track. These side tracks were carried on the cantilever ends of long timbers laid across the old viaduct between ties. At street crossings, the overhanging ends of the long timbers were strutted diagonally down to the outside shelf of the bottom cords of the plate girder spans. 6 cars were used, and the concrete was dumped by them directly into the forms. the fall from the track above being in some cases 40 ft. The hoists and shuttle car were operated by an 8x12 Lambert derrick engine, the boiler of which also supplied steam to the mixer engine. The concrete cars were operated by cable haulage by two Lambert 7x10 engines. The labor force employed in mixing and placing concrete, including farm work, was 45 men, and this force placed on an average 200 ids of concrete per day. Assuming wages, we get the following costs of different parts of the work for labor above. Item, per day, per yd, one timekeeper at $2, $50 2, $50 $0, 0125, one general foreman at $5 5, 000, 0250, three enginemen at $5 15, 000, 0750, one carpenter foreman at $4 4, 000, 0200, 12 carpenters at $3, 50 42, 000, 2101 foreman at $4 4, 000, 0200, 8 men mixing and transporting at $1, 7514, 000, 0700, 13 men placing concrete at $1, 7522, 750, 1137, one foreman finishing at $4 4, 000, 0200, four laborers finishing at $1, 75 7, 000, 0350, 45 men at $2, $7,120, $25 6012. It is probable that the carpenter work includes merely shifting and erecting forms and not the first cost of framing centers. No materials, of course, are included. It should be kept in mind that while the output and labor force are exact, the wages are assumed. Traveling derrick plant for Forcepan Arch Bridge. The bridge consisted of 470 ft. Arch spans and was built close alongside an old bridge which it was ultimately to replace. The approach from the west was across a wide flat. At the east, the ground rose more abruptly from the stream. Conditions prevented the use of a long spur track and also made it necessary to install all plant at and to handle all material from the west bank. A diagram sketch of the arrangement adopted is shown by Fig. 153. Fig. 153. Sketch showing traveling derrick plant for concreting an arch bridge. The track from the west approached the existing bridge on an embankment 25 ft. high. A spur track 175 ft. long from clear post to end was built on trestle as shown. The cement house and mixer platform were placed at the foot of the embankment at opposite ends of the spur track. Between the two, the slope of the embankment was sheeted with 1 in. Boards and a timber bulkhead 4 ft. high was built along the toe of the sheeting. Stone, sand, and coal were stored behind the bulkhead on the sheeting. A runway close to the bulkhead connected the cement house with the mixer platform, all materials to the mixer being wheeled in barrows on this runway. A 3/4 yd. Smith mixer was set on a platform 5 ft. above ground with its discharge end toward the stream. Beginning under this platform, a service track was carried across the flat and stream to the extreme end of the east abutment. This track consisted of 3 rails, 2 rails 4 ft. apart next to the work and a third rail 25 ft. from the first. The 4 ft. gauge provided for cars carrying concrete buckets from the mixer and the 25 ft. gauge provided for a traveling derrick, 18 lb. Rails were used and they proved to be too light, 40 lb. Rails are suggested. The derrick consisted of a triangular platform carrying a stiff-legged derrick with a 25 ft, massed and mounted on 5 wheels. The wheels were double flange 16 ins, diameter, and cost $30 each, being the most expensive part of the derrick. The derrick was made on the ground and took 4 carpenters between 3 and 4 days to build. Derrick and 350 ft. Of service track, including pole trestle across the stream, cost between $600 and $800. The derrick was moved by means of a cable wrapped around one spool of the Flory double-drum hoisting engine and leading forward and back to dead men set at opposite ends of the service track. Cars carrying concrete buckets were run out on the 4 ft. Gauge track and the buckets were hoisted by the derrick and dumped into a half-coup (YD) car running on a movable transverse track across the bridge. This transverse track was necessary to handle the concrete to the far side of the work, the derrick being set too low and the boom being too short to reach. The derrick was used to handle material excavated from the pier foundations and also to tear down the centers and spandrel forms. Some rather general figures on the cost of this bridge are given by Mr. H.C. Harrison, the contractor. They are: materials, total, 6,000 BBLS. Cement at $2. 05 $12,300 2,500 coup. IDS, sand at $0, 82,000 5,000 coup. IDS, stone at $0, 85 4,250 260 m. FTBM, lumber at $17 4,420. Total $22,970 labor. Cofferdams, excavation and pumping $3,000 forms. Falseworks and centers 2,000 mixing and placing concrete 4,000 placing reinforcement 400 removing falseworks forms etc. 1,201 coat pitch and paper 150 building plant etc. 2,250. Total $13,000. Mr. Harrison states that including plant cost, delays, floods, and incidentals, the cost per cubic yard of concrete was $8, and that excluding these items, the cost was $6 per coup. YD, cost of constructing concrete highway bridge, Greene County, Iowa. The following is the itemized cost of constructing a reinforced concrete slab highway bridge, one of several built by the Highway Commissioners of Greene County, Iowa, in 1906. The figures are given by Messrs. Henry Hogg and D.E. Donovan, the last being the foreman of the concrete gang doing the work. All bridges consist of 10 to 12 in slabs reinforced with old steel rails and of abutments and wing walls reinforced with old rods, bars, or angles selected from junk. This junk metal cost 0.6 CTS per pound, and the rails cut to length cost 1.15 CTS per pound. FOB cars. The work was done by a special gang, the men receiving $1.50 per day and board. As a rule, the footings were made 2 ft wide and as high as need be to get above the water and dirt. Before the footing concrete set steel rods, bars, or angles were placed. They were long enough to reach the height of the wall and 3 to 6 ins. Into the slab. The forms for the abutment and wing walls and for the floor slab were then erected complete before any more concrete was placed. No carpenter was employed, every man on the job having been taught to take his certain place in the work. Then, the forms being erected, every man had his particular place in the work of mixing and placing the concrete. The foreman saw that the reinforcement was properly placed and watched over the accuracy of the work generally. The concrete was allowed to set on the centers for from 30 to 40 days. The other farm work was taken down after 3 days and travel over the bridge permitted after 3 or 4 days. The concrete was mixed wet. The bridge whose cost is given was 22 ft, wide and 16 ft, span with 2 ft, wing walls. The foundations are 4 ft, deep and 2½ ft, wide. The walls on top of the foundations are 7 ft, high 18 ins, wide at the base and batted up to 14 ins. At the top for wings and 12 ins, at top for walls. The floor is 22 ft by 18 ft and 1 ft thick. The wheel guard is 12 ins, thick by 14 ins, wide and 32 ft long. The itemized cost of this bridge, containing 73 ids of concrete, is as follows. Materials total per yd 70 ids. Gravel at 70 cts $49,000 $67.26 ids. Broken stone at 70 cts 7,000,0095975 bbls. Cement at $2 $2,165 002 26037 £1,000. Steel rails at 15 cts 80 51 1,027 £1,000. Junk rails at 6 cts 6 000 0819 200 ft b m. Lumber wasted at $29 80 0794 15 pounds. Nails at 3 cts 45 0061. Labor and supplies, 2 days excavation at $14.28 000 3835. 3/4 day foundation at $14.10 000 1369. 1½ days building forms at $14.21 000 2876. 2 days filling forms at $14.28 000 3835. Hauling lumber and tools 000 1096. Hauling cement and tools 000 2465. Taking off forms 30 0315 1,000 pounds. Coal at $4 per ton 000 0274. Total cost $431 $055 9054. In round figures, the cost per cubic yard of concrete in the finished bridge was $5.90. Summarizing, we have the following cost per cubic yard of concrete in place. Item per yd. Cement $2, 26 steel 1, 22 lumber 0, 22 gravel and stone 0, 76 labor 1, 41 coal 0, 03 total $5.90. The average cost of concrete in place for all the work done in Greene County by day labor was $6.25 per yd. In the job itemized above, the bank caved in, causing an extra expense for removing the earth. The gravel used in this bridge was very good clean river gravel. Method and cost of constructing 2 highway girder bridges. The following account of the methods and costs of constructing 2 slab and beam highway bridge decks on old masonry abutments is taken from records kept by Mr. Daniel J. Howe. The first bridge was a single span 15 ft. long that replaced wooden stringers and floor that had become unsafe. The second was 2 short spans of a steel bridge that was too light for the traffic of the road, and it was torn down and moved elsewhere by the county authorities. The work was done by contract, and in each case consisted of building the reinforced floor and girders on the old masonry walls that were in good condition. While the work was going on, traffic was turned off the bridges, fords being used instead. Figure 154 shows a sketch of the cross-section of the floor and girders. In example, either girders had a depth below the floor of 12 ins, and were of the same width. In example Roman 2, the girders were 14 ins, wide and had a depth below the floor of 18 ins. The floors on both bridges were 6 ins, thick. Con bars were used for reinforcement. Fig. 154, cross-section of concrete girder bridge, example I. This bridge was but little more than 5 ft, above the stream which was shallow and not over 7 ft, wide unless swollen by floods. The bottom for several hundred feet on either side of the bridge was covered with coarse sand and gravel that had pebbles in it from the size of a goose egg down. This was taken from the stream by men with picks and shovels and hauled to the site of the work with wheelbarrows, and then screened so as to separate the gravel from the sand. As it was found that the sand was so coarse that it would take more cement than the specifications called for in a 1:2:5 mixture, some much finer sand was bought and mixed with it. For the privilege of taking the sand from the stream, $1 was paid the property owner. This was done to get a receipt and release from him, rather than as an attempt to pay royalty on the gravel and sand. This dollar is included in the cost of the labor in getting these materials. The cost of materials per cubic yard for the bridge was as given below, the mixture being as stated above. The cement cost $1, 40 per barrel delivered at the bridge, per cu. YD, steel $2, 50 gravel and sand, 75 sand bought, 30 cement $1.57 per cubic yard $5. 12. It is of interest to note the cost of the gravel and sand, as this includes the cost of digging it, wheeling it in a wheelbarrow an average distance of 100 ft, and then screening it and putting it in 2 stock piles. The proportion of bought sand used with the creek sand was 1/2. The old wooden floor and stringers had to be torn down. This was done at a cost of $1, 30 per m, ft, b, m, and furnished 60% of the lumber needed for forms. The floorboards were 3 in, yellow pine planks, and the stringers 6 times 12 in. Timbers rather heavy, but money was saved by using them. The 6 times 12 in timbers were used for props for the centering. Additional lumber was bought, delivered at the site of the bridge for $20, 84 per m, ft, b, m. In framing and erecting the forms, the carpenter had laborers helping him, he doing only carpenter's work, the laborers carrying and lifting all pieces wherever possible. The carpenter's work was about 40% of the total labor cost, which was as follows per cubic yard of concrete: tearing down old bridge $0, 08 lumber, 85 nails, 15 labor carpenter, 77 labor laborers, 96 $2. 81 The forms were torn down by laborers with the assistance of a man and his helper who were given the boards for this labor and to haul them away. This reduced this item somewhat, as it only amounted to 20 CTS per cu. YD. The cost of the forms per 1,000 feet board measure was: new lumber $20, 82 nails 1, 44 labor carpenter 7, 60 labor laborers 9, 50 tearing down 2, 00, $41. 36 All the men, including the carpenter, worked 10 hours per day and were paid at the following rates: carpenter $2, 50 sub-foreman 2, 00 laborers 1. 50 A regular foreman was not employed, but an intelligent and handy workman was given 50 CTS. Additional to lead the men and look after them when the contractor was not present. A gang of 6 men did the work of mixing and placing, and as the stock piles were close by the mixing board, no extra men were needed to handle materials. Water was secured from the stream in buckets for mixing. The mixture was made very wet. The cost per cubic yard for the entire structure was as follows. Preparing for mixing $0. 04 cleaning out forms. 06 handling steel. 03 mixing and placing 1. 15 ramming. 23 $1. 51 the cost of the contractor's expense of bidding, car fare, etc. is listed under general expense and gives a total cost per cubic yard of materials $5. 12 erecting forms 2. 81 tearing down forms. 20 labor 1. 51 general expense 2. 00 $11. 64 example Roman 2. For this bridge both the stone and sand had to be bought. The bridge floor was nearly 14 ft, above the bottom of the stream, which was shallow. The wages paid were as follows for a 10-hour day. Foreman $3. 00 laborers 1. 50 carpenters were paid $3 for an 8-hour day and time and a half for all overtime, which they frequently made. For the girders, a 1 to 2 to 4 mixture was used. The cement delivered at the bridge cost $1. 21 per barrel, there being 8 CTS. A barrel storage and 8 CTS. A barrel for hauling included in this. The sand was paid for at an agreed price per cartload delivered, which averaged $1. 34 per coup, YD. The stone was crushed so as to pass a 1.5 in ring in all directions. It was delivered at the bridge for $2. 75 per coup, YD. This makes the cost per cubic yard for materials as follows. Steel $1. 41 cement 2. 18 sand. 67 stone 2. 75 $7. 01 for the floor, a 1 to 3 to 5 mixture was used, making a cost for material of steel $1. 02 cement 1. 69 sand. 67 stone 2. 75 $6. 13 2-inch rough pine boards were used to make the troughs for the girders, while 1 in. Rough boards were used for the floors. These were all supported by 3 times 4 in. Pine scantlings. This lumber cost delivered $17. 50 per m. FT. BM. Carpenters did all the framing and erected it with the help of laborers. All the carrying of the lumber was done by laborers. This reduced the cost of the work, as the laborers' wages amounted to 1/3 of the whole cost. As soon as the forms were all in place, which was before the mixing of concrete commenced, the carpenters were discharged. The cost per cubic yard for forms was lumber $2, 82 nails, 05 labor carpenters 1, 24 laborers, 62 $4. 73 the tearing down of the forms was done entirely by laborers at a cost of 61 CTS. Per coup, YD. On concrete work, it is also advisable to keep the cost of forms per 1,000 feet board measure, so as to have such data for estimating on new work. The cost per m, FT, on this job was lumber $17, 50 nails, 30 labor carpenters 7, 65, laborers 3, 85 tearing down 3, 80, $33. 10 the concrete was mixed by hand, water being carried in buckets from the creek. 10 to 12 men were worked in the gang under a foreman, and the concrete was wheeled from the mixing board to the forms in wheelbarrows. The mixture was made wet enough to run. The cost per cubic yard for the girders in detail was as follows. Foreman $0. 41 preparing for mixing 0. 14 cleaning out forms 0. 07 handling materials 0. 30 handling and placing steel 0. 40 mixing and placing 0. 87 ramming 0. 45 $2. 64 the cost of labor for the floor was foreman $0. 28 preparing for mixing 0. 08 cleaning out forms 0. 05 handling materials 0. 14 handling and placing steel 0. 08 mixing and placing 0. 87 ramming 0. 36 $1. 86 This gives a total cost per cubic yard for the concrete in the girders in the completed bridge as follows. Materials $7. 01 erecting forms 4. 73 tearing down forms 0. 61 labor 2. 57 general expense 1. 60 $16. 52 The cost per cubic yard for the floor was materials $6. 13 erecting forms 4. 73 tearing down forms 0. 61 labor 1. 86 general expense 1. 60 $14. 93 Included with this is an item for general expense, being expenses of the contractor in bidding on the work, car fare, and other items of expense in looking after the contract. It will be noticed that a record is here given of 3 different mixtures, and that the labor cost of mixing and placing increases with the richness of the mixture. This is because it takes a greater number of batches to the cubic yard. Record has also been given of cost of preparing the mixing board and other work necessary to start and clean up each day. Also, when stock piles could not be arranged close to the mixing board, of the cost of handling the materials. These items, it will be noticed, are large enough to be considered in estimating on new work. The cost of sweeping and cleaning out the forms has also been listed, as this work is extremely important. The cost of the reinforcing steel is given in with the materials, but the labor of handling it and placing it in the forms is listed under labor. This naturally varies with the amount of steel needed, and with the con bar it will vary from 10 CTS to 75 CTS per cubic yard, as the prongs of the bar must be bent into proper position and at times straightened when bent in shipment. This cost seems large, but it is done with the ordinary labor, while with round rods a large amount of blacksmith work has to be done and a smith and his helper frequently must place them. The patent bars are all lettered and numbered as structural steel is, and can be placed under the direction of the foreman. One striking lesson can be learned from the forming. It will be noticed that the cost for common labor for handling and helping to erect the forms was much larger in example I than in example Roman II, although the bridge was higher in the latter instance. This was caused by the heavy timber that was used, and equaled an extra cost nearly 50% of the price of new lumber. It certainly speaks volumes against the use of unnecessarily heavy timber for concrete forms. In bridge work, the height of the floor above the stream to some extent governs the cost of the forms. This is made so by the extra lumber needed as props or falsework to support the forming, and also by the fact that men at some height above the ground do not work as quickly or as readily as they do nearer the ground. For high and long spans, a derrick is sometimes needed for the work of placing the centering. On these jobs, the concrete was made so wet that with the proper tamping and cutting of the concrete in the forms, the surfaces were so smooth that no plastering was needed. Molding slabs for girder bridges. The bridges carry railway tracks across intersecting streets. The slabs rest on 2 abutments and 3 rows of columns, so that there are 2 24A quarter FT spans over the street roadway and 1 10 3/4 FT span over each sidewalk. The larger slabs were 24 FT, 3 ins, long 33 ins, thick and 7 FT. Wide, each contained 16 3/4 cu. Ids of concrete and weighed 36 3/4 tons. The smaller slabs were 10 FT, 9 ins, long 17 ins, thick and 7 FT. Wide, each contained 3 65 cu. ids of concrete and weighed 7-8 tons. The weights were found by actual weighing. They make the weight of the reinforced slab between 160 and 162 pounds per ft. The concrete was generally 1 pot cement and 4 pots pit gravel. The reinforcement consisted of corrugated bars. The method of molding was as follows. Fig. 155. Arrangement of tracks and forms for molding slabs for girder bridge. Fig. 156. Form for molding slabs for girder bridge. A cinder fill yard was leveled off and tamped. Then the forms were set up on both sides of 2 lines of railway track arranged as shown by Fig. 155. The exact construction of the forms for one of the larger slabs is shown by Fig. 156. The side and end pieces were so arranged as to be easily taken down and erected for repeated use. About 100 flaws were used, and they had to be leveled up each time used as the lifting of the hardened slab disarranged them. The side and end pieces were removed in about a week or 10 days, but the slab stood on the floor 90 days, being wetted each day for 2 weeks after molding. The plant for mixing and handling the concrete was mounted on cars. A flat car had a rotary drum mixer mounted on a platform at its forward end. Beneath the mixer was a hopper provided with a deflector which directed the concrete to right or left as desired. Under the hopper were the ends of 2 inclined chutes extending out sidewise beyond the car, one to the right and one to the left, and over the slab molds on each side. Above the mixer was another platform containing a charging hopper, and from the rear of this platform an incline ran down to the rear end of the car, and then down to the track rails. A car loaded with cement and gravel in the proper proportions was hauled up the incline by cable operated by the mixer engine, until it came over the topmost hopper into which it was dumped. This hopper directed the charge into the mixer below. The mixer discharged its batch into the hopper beneath, from which it flowed right or left as desired into one of the chutes, and thence into the mold. The chutes reached nearly the full length of the molds, and discharged as desired over the ends into the far end of the mold, or through a trap over the end of the mold nearest the car. To the rear of the mixer car came a cement car provided with a platform overhanging its forward end. 2 hoppers were set in this platform, each holding a charge for 1 batch. Coupled behind the cement cars came 3 or 4 gravel cars. These were gondola cars, and plank runways were laid along their top outer edges, making a continuous runway for wheelbarrows on each side from rear of train to front of cement car. The sand and gravel were wheeled to the 2 measuring hoppers, and the cement was handed up from the car below and added. The charge was then discharged into the dump car below, and the car was hauled up the incline to the mixer as already described. 2 measuring hoppers were used so that one was being filled while the other was emptied, thus making the work continuous. The molding gang consisted of 33 laborers, 2 foremen and 1 engineman. This gang averaged 7 of the large slabs per 10-hour day, and at times made as many as 9 slabs. When molding small slabs, an average of 12 were made per day. This record includes all delays, moving train, switching gravel cars on and off, building runways, etc. The distribution of the men was about as follows: handling materials, no. Men, shoveling gravel into wheelbarrows, 9, wheeling gravel, to measuring hoppers, 9, emptying cement, into measuring hoppers, 2, handling cement, to men, emptying, 1, in charge of loading dump car, 1, on top of cement car, 1, sub-foreman, in charge, 1, mixing and placing. Engineer, 1, in charge of mixer, 1, hoeing and spreading in mold, 2, spading in Mold 2. Finishing sides of Block 2, general laborers 3 foremen in charge 1. Total men 36. This gang mixed and placed concrete for 7 blocks or 117 a quarter coup. Ids of concrete per day. Assuming an average wage of $2 per day, the cost of labor mixing and placing was 61. 4 CTS per coup, YD, or $10, 28 per slab. It is stated that the slabs cost $11, 80 per coup, YD. On storage pile, this includes labor and materials, concrete and steel, molds, loading into cars with locomotive crane, hauling cars to storage yard and unloading with crane into storage piles, and inspection, incidentals, etc. To load the slabs into cars from storage piles, transport them to the work and place them in position is stated to have cost $2 per coup. YD. The slabs were placed by means of a locomotive crane being swung from the flat cars directly into place. Fig. 157. Sections showing construction of Connecticut Ave. Bridge, method and cost of constructing Connecticut Ave. Bridge, Washington, D.C. The Connecticut Ave Bridge at Washington, D.C. consists of 9 150 ft. spans and 282 ft. spans, one at each end. All full-centered arches of mass concrete trimmed with tool-dressed concrete blocks. Figure 157 is a part-sectional plan and elevation of the bridge, showing both the main and spandrel arch construction. This bridge is one of the largest concrete arch bridges in the world, being 1,341 ft long and 52 ft wide and containing 80,000 ids of concrete. Its total cost was $850,000 or $638, 85 per lin, ft or $10, 63 per YD, of masonry. It was built by contract with Mr. W.J. Douglas as engineer in charge of construction. The account of the methods and cost of construction given here has been prepared from information obtained from Mr. Douglas and by personal visits to the work during construction. General arrangement of the plant. The quarry from which the crushed stone for concrete was obtained was located in the side of the gorge at a point about 400 ft from the bridge. Incidentally, it may be added, the fact that the contractor had an option on this quarry gave him an advantage of some $30,000 over the other bidders. The stone from the quarry was hoisted about 50 ft by derricks and deposited in cars which traveled on an incline to a Gates gyratory crusher, into which they dumped automatically. The stone from the crusher dropped into a 600 YD bin under the bottom of which was a tunnel large enough for a dump car and provided with top gates by which the stone above could be dropped into the cars. The cars were hauled by cable to the mixer storage bin and they're discharged. Sand was brought in by wagons and dumped onto a platform about 50 ft, higher than the bottom of the main stone bin. A tunnel exactly similar to that under the stone bin was carried under the sand storage platform. The sand car was hauled from this tunnel by cable to the mixer storage bin using the same cable as was used for the stone cars, the cable being shifted by hand as was desired. Cement was delivered to the mixer platform from the crest of the bluff by means of a bag chute. The mixer used was one of the Haynes gravity type. It had 4 drops and was provided with 4 mixing hoppers at the top. The concrete was made quite wet. The proportions of sand and water were varied to suit the stone according to its wetness and the percentage of dust carried by it. The head mixer regulated the proportions and his work was checked by the government inspector. From the bottom hopper, the mixed concrete dropped into a skip mounted on a car. Fig. 158. Center for Connecticut Ave, bridge elevation. To distribute the skip cars along the work, a trestle was built close alongside the bridge and at about springing line level. This trestle had a down grade of about 2%. From the mixer, derricks mounted along the centering, and on the block molding platform lifted the skips from the cars and deposited them where the concrete was wanted. The skip cars were large enough for 3 skips, but only 2 were carried so that the derricks could save time by depositing an empty skip in the vacant space and take a loaded skip away with one full swing of the boom. Altogether, 9 derricks were used in the bridge, 4 having 70 ft. Booms and 5 having 90 ft. Booms. These derricks were jacked up as the work progressed. Fig. 158. Center for Connecticut Ave, bridge details, forms and centers. The forms for wall and pier work consisted of 1 in, lagging held in place by studs about 2 ft. On centers, and they in turn supported by wales which were connected through the walls by bolts, the outer portions of which were removed when the forms were taken down. The centers for the 5 150 ft. Arches were all erected at one time, those for the 82 ft. Arches were erected separately. The 7 centers required 1,500,000 ft. B. M. of lumber or 1,404 ft. B. M. per lineal foot of bridge between abutments or 1,640 ft. B. M. per lineal foot of arch span. The centers for the main arch spans are shown in detail by Fig. 158. This drawing shows the sizes of all members and the maximum stresses to which they were subjected from the loading indicated. That is the arch ring concrete. The centers, as a rule, rested on pile foundations. 4 piles to each post were used for the intermediate posts and 2 piles for the posts in the 2 rows next the piers. Concrete foundations, however, were put in Rock Creek and on the line of Woodley Lane Bridge where it was impracticable to drive piles, as considerable difficulty was experienced in driving the piles. The ground consisting mostly of rotten rock, it is thought that it would have cost less if the contractor had used concrete footings throughout. Some of the costs of form work and centering are given. The cost of lumber delivered at the bridge site was about as follows. M. ft. B. M. Rough Virginia pine $25, dressed Virginia pine lagging 23 rough Georgia, sizes up to 12 times 12 ins. 33 rough Georgia, sizes over 12 times 12 ins. 35 rough oak lumber 35. The following wages were paid. Foreman carpenter $3. 50, carpenters $2 to $3, laborers $1, 70 with a few at $1, 50. An 8-hour day was worked. The cost of formwork is given in summary as follows, lagging per ft. Used twice, lumber at $23, $11, 50 erection $15.00, total cost erected $26. 50 studding and rough boards used in place of lagging per ft. Used twice, lumber at $25, $12, 50 erection $10.00, total cost erected $22, 50 wales per ft. Used 6 times, lumber at $36, $6.00, erection $10.00, total cost erected $16. 00. The total cost of the main arch span centers to the District of Columbia was $54,000 or $59 per lineal foot of arch span, or $37. 33 per ft. B. M. The cost of center erection and demolition was as follows. Erection below springing line per m. FT, $15 erection above springing line per m. FT. 25 demolition 5. The salvage on the centers amounted to $11 per m. FT, B, M. The spandrel arch centers were each used twice and cost per m. FT, B, M. For lumber at $25 per m. FT, $12. 50 erecting at $25 per m. FT, 25.00 moving at $5 per m. FT, 5.00 total per m. FT, 42.50. Molding concrete blocks. The bridge is trimmed throughout with molded concrete blocks, comprising belt courses, quoin stones, chain stones, ring stones, brackets, and dentils. The blocks were made of a 1:2 to 4.5 concrete, faced with a 1:3 mixture of Dragon Portland cement and bluestone screenings from in. Size to dust. They were cast in wooden molds with collapsible sides held together by iron rods. Each mold was provided with 6 bottoms, so that the molded block could be left standing on the bottom to harden, while the side pieces were being used for molding another block. The molding was done on a perfectly level and tight floor on mud sills, the perfect level of the molding platform having been found to be an important factor in securing a uniform casting. The blocks were molded with the principal showing face down and the secondary showing faces vertical. The facing mortar was placed first, and then the concrete backing. Care was taken to tamp the concrete so as to force the concrete stone into, but not through the facing. Mr. Douglas remarks that the back of the block should always be at the top in molding, since the latents or slime always flushes to the surface, making a weak skin which will develop hair cracks. In this work, the backs of the blocks were mortised by embedding wooden cubes in the wet concrete and removing them when the concrete had set. These mortises bonded the blocks with the mass concrete backing. The blocks were left to harden for at least 30 days and preferably for 60 days, and were then bush-hammered on the showing faces, some of the work being done by hand and some with pneumatic tools. Some precautions necessary in the molding and handling of large concrete blocks were discovered in this work and merit mention. In designing blocks for molding, it is necessary to avoid thin flanges or the flanges will crack and break off. Blocks molded with a 2 1/4 in. Flange projecting 1 3/4 ins. Gave such trouble from cracking on this work that a flange 5 ins. Thick was substituted. Provide for the method of handling the block so that dog or Lewis holes will not come in the showing faces. Dog holes can be made with a pick when the concrete is 3 or 4 weeks old. When it is not practicable to use dogs, 2-pin Lewises can be used. The Lewis holes should be cast in the block and should be of larger size than for granite. They should not be located too near the mortar faces. In turning blocks, it is necessary to provide some sort of cushion for them to turn on or broken arises will result. When the work will permit, it is desirable to round the arises to about a in. Radius. The following general figures of the cost of block work are available. Foreman cutters were paid $5 per day, foreman concrete workers $3 per day, stone cutters $4 per day, concrete laborers $1.70 per day, and common laborers $1.50 to $1.70 per day. Plain and ornamental blocks cost about the same, the large size of the ornamental blocks bringing down the cost. The following is given as the average cost of block work per cubic yard. Cement $1, 95 sand 0, 35 stone 1, 14 forms, lumber and making 0, 80 mixing and placing concrete 1, 50 dressing 4, 73 handling and setting 2, 0 superintendents, plant, incidentals at 25%. 312 condemnation at 5%. 0. 78 total cost blocks in place $16.37. It will be seen that the largest single item in the above summary of costs is the item of dressing. This was done, as stated above, partly by hand and partly by pneumatic tools. Hand tooling cost about twice as much as machine tooling, but its appearance was generally better. The average cost of tooling the several forms of blocks is shown by Table Roman 19. For 42,190 SQ, FT, the average cost was 26 CTS per SQ, FT, or $2.34 per SQ, YD, or $4.73 per Q, YD, of block work. This tooling was done by stone cutters and was unusually high in cost. Mass concrete work. All parts of the bridge except the molded block trim were built of concrete deposited in place. Briefly, the molded blocks were set first and then backed up with the mass concrete deposited in forms and on centers. The only features of this work that call for particular description are those in connection with the main arch ring and the spandrel arch construction. The main arch rings were concreted in transverse sections. Fig. 158 shows the size and order of construction of these sections. Back forms were necessary up to an angle of 45 degrees from the spring line, after which the concrete was made somewhat drier and back forms were not used. After sections 1, 2, 3, and 4 had been concreted, they were allowed to set, and then the struts and back forms were taken out, and the intervening sections were concreted. The large sections 6 and 7 were concreted in 5 sections each, in order to permit the taking out of the timber struts supporting the sections above. The concrete in all sections was placed in horizontal layers as a rule, and it is the judgment of the engineers in charge of this work that this is the preferable method. Table Roman 19. Showing cost of tooling concrete ornamental blocks for Connecticut Avenue Bridge. Description: 1, 2, 4½ concrete backing. 1, 3 mortar face, per cubic foot, per superficial foot of showing face. Total number stones cut, number cubic feet in each. Total cubic feet cut, cost per cubic foot, superficial feet in each. Total superficial feet. Cost per superficial foot, number super, FT to 1 cubic foot, brackets under lamps and rail posts, cap and base, 344.16, 5,500 $0, 27.10, 3,630 $0, 41.0, 66 molding, undercoping 775. 4,560 $0, 33, 2,930 $0, 47.0, 64 dentals between molding 525, 2,860 $0, 28, 4,160 $0, 14.1. 45 coping 494.61, 230,220 $0, 12, 35, 417,490 $0, 21.0, 58 pedestal 3 courses 162.27, 4,400 $0, 15.14, 2,290 $0, 29.0, 52 rail posts top and base at 296.7, 2,100 $0, 50.17, 5,100 $0, 21.2, 43 lamp posts and parapets over piers top and base, 248.22, 5,690 $0, 17.26, 6,580 $0, 15, 16 average of above, totals $2,830,419. $555,330, 1714. $843,190, 26 77 table Roman 20. Showing cost of mass concrete work per cubic yard. Transcriber's note, table split description. Cost delivered. On mixer, proportions, average yardage for days run. Cement, sand, stone, total materials. Class A in Piers 1, 2, 4.5, 151, 65 0, 39 1, 083. 12 Class A in Arches 1, 2, 4.5, 201. 65 0, 39 1, 083. 11 Class B in Piers Solid Work 136 161, 40 0, 42 1, 23 3. 05 Class B in Piers Hollow Work 136 110 1, 40 0, 42 1, 23 3. 05 Class B in Spandrel Walls 1, 3, 6, 110 1, 40 0, 42 1, 23 3. 05 Class B in Spandrel Arches 136 201, 40 0, 42 1, 23 3. 05 Class B in Abutments 136 151, 40 0, 42 1, 23 3. 05 Class C filling over Bridge 1 3, 10 145 0, 90 0, 31 1, 32 51. Description, cost of mixing and placing. Mixing, placing total mixing and placing Class A in Piers 0, 090, 21 0, 30 Class A in Arches 0, 050, 28 0, 33 Class B in Piers Solid Work 0, 090, 18 0. 27 Class B in Piers Hollow Work 0, 11 0, 36 0. 47 Class B in Spandrel Walls 0, 11 0, 40 0. 51 Class B in Spandrel Arches 0, 070, 26 0. 33 Class B in Abutments 0, 11 0, 24 0. 35 Class C filling over Bridge 0, 11 0, 28 0, 39 Description, cost of farm work, erecting, taking down lumber, total farm work, total cost per cubic yard, G Class A in Piers 0, 17 0, 050, 16 0, 38 $3, 80 Class A in Arches 0, 080, 030, 10 0, 21 3. 66 Class B in Piers Solid Work 0, 17 0, 050, 16 0, 38 3. 70 Class B in Piers Hollow Work 0, 77 0, 25 0, 64 1, 66 5. 18 Class B in Spandrel Walls 0, 85 0, 28 0, 73 1, 86 5. 42 Class B in Spandrel Arches 0, 94 0, 30 0, 86 2, 10 5. 48 Class B in Abutments 0, 10 0, 030, 12 0, 25 3. 65 Class C filling over Bridge 0, 000, 000, 000. 2. 90G add 25% to the cost here tabulated for superintendents, plant, and incidentals. Considerable difficulty was experienced in building the large arches with a concrete block, facing on account of the fact that the edges of the blocks are liable to chip off when any concentrated pressure is brought on them. In order to permit the ring of blocks to deform, as the centering settled under its load, sheet lead was placed in the joints between blocks at the points corresponding with the construction joints between sections of the mass concrete backing. The deflection of the centers at the crown was a maximum of 3 1/4 ins and a minimum of 2 1/2 ins. Table Roman 21, detail cost of engineering and inspection for different classes of work. Engineering, inspection, kind of work. Total, unit. Class A concrete, 23,500 cu. IDS $3,055. $000. 1,762. $50. 0.75 Class B concrete, 36,580 cu. IDS 3,658. 000. 10 1,646. 10 0.45 Class C concrete, 2,150 cu. IDS 107. 50 0.553. 75 0.25 Class D concrete, 6,250 cu. IDS 1,875. 000. 34,687. 50 75 1000 m FTB m centering 1000 001 440 000 44 cement 73,000 barrels 365 000 005 730 000 01 earth filling 50,000 cu. IDS 1,000 000 02 500 000 01 The centering of the main arches was not struck until the spandrel arches and all the work above the main arches to the bottom of the coping had been completed. The first and third spandrel arch on each side of the piers was made with an expansion joint in the crown, to permit further of the adjustment of the portion of the masonry above the backs of the main arches. The crown of the middle arch of each set of spandrel arches was left unconcreted until the center of the main arches had been struck. It may be noted here that the expansion joints in the first and third arches were carried up through the dentils and coping, and observations show that these joints are about larger in winter than in summer. The cost of the mass concrete work is shown in Table Roman 20. These figures are based on the wages already quoted and the following: foreman riggers $4, 50, riggers $1, 50 to $1, 75 and $2, skilled laborers $2, engineers $3, 50. The detail cost of engineering and inspection is shown in Table Roman 21. Arch bridges Elkhart End. At the new Elkhart End, yards of the Lake Shore and Michigan Southern Rye. The tracks are carried over a city street by concrete arches 40, 60, and 160 ft. long. These arches all have a span of 30 ft, a height of 13 ft, and a ring thickness at crown of 28 ins. The reinforcement consists of arch and transverse bars. The arch bars are spaced 6 ins. On centers 2½ ins. From both extrados and intrados, and the transverse bars are spaced 24 ins. On centers inside both lines of arch bars. The proportions of the concrete were generally 1 cement, 3 gravel, and 6 stone. The gravel was a material dug from the foundations and was about 50%, sand and 50%. Gravel ranging up to the size of pigeons' eggs. The concrete was machine mixed and was mixed very wet. The work was done by the railway company's forces, and Mr. Samuel Rockwell, assistant chief engineer, gives the following figures of cost, total, per cu, YD, temporary buildings, trestles, etc. $752. $33 15 machinery, pipe fittings, etc. $416. 34 08 sheet piling and boxing 1006. 12 21 excavation and pumping 1619. 74 33 arch centers and boxing 3,528, 92 0, 73, total $7,323, 45 $1, 50 concrete masonry, cement 8,860, 55 1, 84 stone 1,788, 50 0, 36 sand 240, 0 0 0, 05 drain tile 103, 030, 02 labor 8,091, 41 1, 68, total concrete $19,083, 49 $3, 95 steel reinforcing rods $3,028, 39 $0, 63 engineering, watching, etc. 508, 40 0, 11, grand total 4,833 coup. IDS, concrete, $29,943, 73 $6, 19 arch bridge, Plainwell, Mitch. The following figures of cost of a reinforced concrete arch bridge are given by Mr. P. A. Cartwright. The bridge crosses the Kalamazoo River at Plainwell, Mitch, and is 446 ft, long overall with 7 arches of 54 ft, span and 8 ft, rise. The arch rings were reinforced with 4 in, 6 lb, channels bent to a radius of 70 ft, and spaced 9 ft C to C. The contract price of the bridge was $19,900. The concrete was made of Portland cement and a natural mixture of sand and gravel in the proportions of 1:8 for the foundations, 1:6 for arches and spandrel walls, and 1:4 for the parapet wall. The proportions were determined by measure, the wagon boxes being built to hold a cubic yard of sand and gravel. A sack of cement was taken as 1 cu. ft. For foundations, the pit mixture was used without screening, stones over 4 ins in diameter being thrown out at the pit or on the mixing board. For the arches and spandrel walls, the gravel was passed over a 2-in mesh screen on the wagon box. The aggregate for the parapet walls was screened to 1 in, largest diameter. The concrete was mixed in a McKelvey continuous mixer which turned the material 8 times. The mode of procedure was as follows. The gravel was loaded upon wagons in the pit and hauled to a platform at the intake of the mixer. Half of the cement required in the concrete was then spread over the top of the load in the wagon box, and the whole was dumped through the bottom of the wagon box onto the platform and spread with shovels. The remainder of the cement was spread over the mixture, and the whole was shoveled by one man to a second man who shoveled it into the mixer. Water was added after the mixture had passed about 1/3 of the way through the mixer. The mixer delivered the concrete directly into wheelbarrows, by which it was delivered to the work. The concrete was spread in layers from 2 to 4 ins, in thickness and thoroughly rammed with iron tampers. 2 men were employed tamping for each man shoveling. The arches were concreted in 3 longitudinal sections, each section constituting a day's work. The work was done in 1903, and the concrete cost for mixing and placing, labor per day, per coup, YD, 13 men at $1, 80 $23, 40 $0, 78 engine and mixer 5, 0 0 0, 17 1 team 3, 0 0 0, 10 1 foreman 3, 0 0 0, 10 totals for labor $34, $41, 15 materials 0 65 BBL, cement at $2 $1, 30 0, 9 coup YD, gravel at $0, 50 0, 45 total for materials $1, 75 grand total $2, 90 methods and cost of constructing a 5-span arch bridge. This bridge consisted of 5 elliptical arch spans of 40, 45, 60, 87, and 44 ft, carried on concrete piers. The arch rings were 12 ins, thick at the crowns, and 18 ins, thick 5 ft, from the centers of piers, and carried 4 in. Spandrel walls, there were 1,000 ids of concrete in the arches and 600 ids in the piers. Each arch ring was reinforced by a grillage of longitudinal and transverse rods. Fig. 159. End view of center for short elliptical arch spans, forms, and centers. Figure 159 is an end view of the center arch. It consists of a series of bents 6 ft C to C, the posts of each bent being 5 ft C to C. These posts are made of 2 times 6 in. Washington fir. Upon the heads of the posts rest 2 times 6 in. Stringers extending from bent to bent. Resting on these stringers are wooden blocks or wedges which support a series of cross stringers, also of 2 times 6 in. Stuff spaced 2 ft C to C. On top of these cross stringers rest the sheeting planks, which are 1 times 6 in. Stuff dressed on the upper side and bent to the curve of the arch. This sheeting plank was not tongue and grooved, and a man standing under it after it is nailed in place could see daylight through the cracks. It looked as if it would leak like a sieve and let much of the wet concrete mortar flow through the cracks, but as a matter of fact, scarcely any escapes. Figure 160 shows a front view of a bent and indicates the manner of sway bracing it with 1 times 4 in. Stuff. Figure 161 shows the outer forms for the parapet wall or concrete hand railing, and it will be noted that the cross stringers are allowed to project about 3 ft, so as to furnish a place to fasten the braces which hold the upright studs. The inner forms for the parapet wall are shown in dotted lines. They are not put in place until all the concrete arch is built. Then they are erected and held to the outer forms by wire, and a sway braced to wooden cleats nailed to the top surface of the concrete arch. Fig. 160. Front view of center for short elliptical arch spans. Fig. 161. Form for parapet wall for arch bridge. For the 5 spans, the total amount of lumber in the centers was in round figures 28 m. ft, distributed about as follows. Item. ft b m 1 times 6 in. Sheeting 5,602 times 6 in. Longitudinal stringers 2,602 times 6 in. Cross stringers 2,602 times 6 in. Posts 4,003 times 8 in. Sills 1,501 times 4 in. Braces 3,000 outer forms for spandrel walls, 4,000 inner forms for spandrel walls, 4,000. Total 27,300. The aggregate span length of the arches was 276 ft, so that a little less than 100 ft. B. M of lumber was used for centering per lineal foot of span. The superintendent at $5 per day and 5 carpenters at $3.50 per day erected the 5 centers in 18 days at a cost of $400, or a trifle more than $14 per m. Ft. B. M. The cost of taking down the centers was $2 per m. Ft. B. M. And the lumber for the centers cost $24 per m. Ft. B. M, making a grand total of $40 per m. Ft. B. M for materials and labor. As there were 1,000 ids of concrete in the arches and spandrels, the cost of centers and forms was $1, 12 per yd. This form lumber was, however, after taking down, used again in erecting a reinforced concrete building. Assuming that the lumber was used only twice, the cost of centers and forms for these 5 arches was less than 80 cts per yd. of concrete, shaping and placing reinforcement. The 60 and 87 ft. spans were reinforced with 32 1 in, round longitudinal rods held in place by a half-in. Square transverse rods wired at the intersections. The reinforcement of the smaller spans was exactly the same except that 1 in diameter rods were used. To bend the longitudinal rods to curve, planks were laid on the ground roughly to the curve of the arch. The exact curve was marked on these planks, and large spikes were driven part way into the planks along this mark. The end of a rod was then fastened by spiking it against the first projecting spike head, and 3 men taking hold of the opposite end and walking it around until the rod rested against all the spikes on the curve. It took 3 men 2 8-hour days to bend 46,000 pounds of rods. Their wages were $2.50 each per day, making the cost of bending 0.03 CT per pound or 60 CTS per ton. It took a man 5 mins to wire a cross rod to a longitudinal rod, with wages at $2.50 per day. The cost of shaping and placing the reinforcement per ton was as follows. Item per ton. Bending rods $0, 60 shearing rods to length 0, 40 carrying rods onto bridge 0, 40 placing and wiring rods 2, 35 total $3.75 including superintendents. The labor cost was practically $4 per ton or 0.2 CTS per lb. Altogether 66,000 pounds of steel was used for reinforcing 1,000 ids of concrete or 66 pounds per yd. The cost of steel delivered was 2 CTS per lb, and the cost of shaping and placing it 0.2 CT per lb, a total of 2 CTS per lb or 2 times 66 equals $1.45 per yd of concrete. Mixing and placing concrete. A ransom mixer holding a half-yard batch was used. The mixer was driven by an electric motor. The concrete for the piers was a mixture of 1 part Portland cement to 7 parts gravel. For the arches, the concrete was mixed 1:5. The gravel was piled near the mixer, a snatch team being used to assist the wagons in delivering the gravel into a pile as high as possible. Run planks supported on horses were laid horizontally from the mixer to the gravel, so that big wheelbarrow loads could be handled. The barrows were loaded with long-handled shovels, and the men worked with great vigor, as is shown by the fact that 4 men shoveling and wheeling delivered enough gravel to the mixer in 8 HRS to make 100 ids of concrete. We have therefore estimated on a basis of 6 men instead of 4. The mixer crew was organized as follows. Per day. 6 men shoveling and wheeling $12, 2 men handling cement, 4 1 man handling water, 2 1 man dumping concrete, 2 men handling dump cars, 4 2 men handling hoisting rope, 4 men spreading and ramming concrete, 8 1 engineman, 4 1 foreman, 5 fuel. Estimated 3. Total $48. The output of this crew was 100 ids per day. The concrete was hauled from the mixer in 2 small dump cars, each having a capacity of 10 ft. The average load in each car was a quarter yd. Ordinary mine cars were used, of the kind which can be dumped forward or on either side. The cars were hauled over tracks having a gauge of 18 ins. The rails weighed 16 pounds per yard and were held by spikes at times 2½ ins. Larger spikes would have split the cross ties, which were 3 times 4 ins. Only 1 spike was driven to hold each rail to each tie, the spikes being on alternate sides of the rail in successive ties. No fish plates or splice bars were used to join the rails. which considerably simplifies the track laying. Fig. 162. Trestle for service track. 2 lines of track were laid over the bridge. The tracks were supported by light bents, the crosstie forming the cap of each bent, as shown in Fig. 162. The bents were spaced 3 ft. apart. There were 2 posts to each bent, toe-nailed at the top of the tie and at the bottom to the arch sheeting plank. 2 men framed these crude bents and laid the 2 rails at the rate of 150 lin. ft. of track per day at a cost of 4 cts per lin. ft. of track. As stated, there were 2 tracks, one on each side of the bridge, but they converged as they neared the concrete mixer, so that a car coming from either track could run under the discharge chute of the mixer. Fig. 163 shows the arrangement of the tracks at the mixer. The part of each rail from it to be 6 ft. long was free to move by bending at her, the rail being spiked rigidly to the tie at her, leaving its end at be free to move. To move the end B so as to switch the cars, a homemade switch was improvised, as shown in Figs. 163 and 164. Fig. 163. Arrangement of service tracks at mixer. Fig. 164. Improvised switch for service cars, general plan. It will be remembered that this bridge was a series of 5 arches. There was a steep grade from the 2 ends of the bridge to the crown of the center arch. Hence, the 2 railway tracks ascended on a steep grade from the mixer for about 175 ft. Then they descended rapidly to the other end of the bridge. Hence, to haul the concrete cars up the grade by using a wire cable, it was necessary to anchor a snatch block at the center of the bridge. This was done by erecting a short post, the top of which was about a foot above the top of the rails. The post stood near the track and was guyed by means of wires and braced by short inclined struts. To the top of the post was lashed the snatch block through which passed the wire rope. Fig. 165 shows this post P about 10 ft. From the post P on the side toward the mixer, another post Q was erected and a snatch block fastened to it. When the hoisting engine, which was set near the concrete mixer, began hauling the car along the track, a laborer would follow the car. Just before the car reached the post Q, he would unhook the hoisting rope from the front end of the car, then push the car past the post Q and hook the hoisting rope to the rear of the car. The car would then proceed to descend in the direction T, being always under the control of the wire rope, except during the brief period when the car was passing the post Q. Each of the 2 cars was provided with its own hoisting rope, and one engineer operating a double drum hoist handled the cars. The hoist was belted to an 8 HP gasoline engine, no electric motor being available for the purpose. Fig. 165. General plan of rope haulage system. Fig. 166. Fig. 167. Details of haulage rope guides. Where hauling is done in this manner with wire ropes, it is necessary to support the ropes by rollers wherever they would rub against obstructions. A cheap roller can be made by taking a piece of 2-in gas pipe about a foot long and driving a wooden plug in each end of the gas pipe. Then bore a hole through the center of the wooden plugs and drive a 1-in round rod through the holes, as shown in Fig. 166. The ends of this rod are shoved into holes bored into plank posts, which thus support the roller. Where the rope must be carried around a more or less sharp corner, it is necessary to provide 2 rollers, one horizontal and the other vertical, as shown in Fig. 167. When conveying concrete to a point on the bridge about 300 ft. From the mixer, a dump car would make the round trip in 3 mins, about a quarter min, of its time being occupied in loading and another a quarter min in dumping. One man always walked along with each car, and another man helped pull the wire rope back, including the cost of laying the track and installing the plant, the cost of mixing and placing the 1,600 ids of concrete was only 55 CTS per YD, in spite of the high wages paid. However, the men were working for a contractor under a very good superintendent. Summing up the cost of the concrete in the arches of this bridge, we have, per YD, 135 BBL, cement at $3 $4, 051 YD, gravel at $1 66 pounds, of steel in place at 2 CTS, 45 centers in place, lumber used once 12 labor, mix and place concrete 55, total $8. 17 The cost of the nails, wire, excavation, and plant rental is not available but could not be sufficient to add more than 10 CTS per YD under the conditions that existed in this case. Concrete ribbed arch bridge at Grand Rapids, Mich. The bridge consisted of 7 parabolic arch ribs of 75 ft, clear span and 14 ft rise. The 5 ribs under the 21 ft roadway were each 24 ins, thick 50 ins, deep at skewbacks and 25 ins. Deep at crown, the 2 ribs under the sidewalks were 12 ins, thick and of the same depth as the main ribs. Each rib carried columns which supported the deck slab. Columns and ribs were braced together across bridge by struts and webs. All structural parts of the bridge were of concrete reinforced by corrugated bars. The abutments were hollow boxes with reinforced concrete shells tied in by buttresses and filled with earth. There were in the bridge, including abutments, 884 ids of concrete and 62,000 pounds of reinforcing metal, or about 70 pounds of reinforcing metal per YD of concrete. Of the 884 ids of concrete, 594 ids were contained in the abutments and wing walls and 290 ids in the remainder of the structure. Fig. 168. Fig. 168. Details of ribbed arch bridge. Centers. The center for the arch consisted of 4 pile bents spaced about 12 ft apart in the line of the bridge. The piles were 12 times 12 in, times 24 ft, yellow pine, and they were braced together in both directions by 2 times 10 in. Planks. Each bent carried a 3 times 12 in plank cap. Maple folding wedges were set in these caps over each pile, and on them rested 12 times 12 in transverse timbers, one directly over each bent. These 12 times 12 in transverse timbers carried the back pieces cut to the curve of the arch. The back pieces were 2 times 12 in plank, 2 under each sidewalk rib and 4 under each main rib of the arch. The back pieces under each rib were X-braced together. The lagging was made continuous under the ribs, but only occasional strips were carried across the spaces between ribs. This reduced the amount of lagging required, but made working on the centers more difficult, and resulted in loss of tools from dropping through the openings. Work on the centers and forms was tiresome, owing both to the difficulty of moving around on the lagging and to the cramped positions in which the men labored. Carpenters were hard to keep for these reasons. Concrete. A 1-to-7 bank gravel concrete was used for the abutments, and a 1-to-5 bank gravel concrete for the other parts of the bridge. The concrete was mixed in a cubicle mixer operated by electric motor and located at one end of the bridge. The mixed concrete was taken to the forms in wheelbarrows. The mixture was of mushy consistency. No mortar facing was used, but the exposed surfaces were given a grout wash. In freezing weather, the gravel and water were heated to a temperature of about 100 degrees F. When work was stopped at night, it was covered with tarred felt and was usually found steaming the next morning. Cost of work. The cost data given here are based on figures furnished to us by Geo. J. Davis, Jr., who designed the bridge and kept the cost records. Mr. Davis states that the unit costs are high because of the adverse conditions under which the work was performed. The work was done by day labor by the city. The men were all new to this class of work. The weather was cold and there was high water to interfere, and work was begun before plans for the bridge had been completed, so that the superintendent could not intelligently plan the work ahead. Cost-keeping was begun only after the work was well underway. Many of the items of cost are incomplete in detail. The following were the wages paid and the prices of the materials used. Materials and supplies, no. 1 hemlock matched per m, ft, $20 no. 1 hemlock plank per m, ft, 17 no. 2 Norway pine flooring per m, ft, 19 no. 2 yellow pine flooring per m, ft, 2012 times 12 in, times 16 ft. Yellow pine per m, ft, 2912 times 12 in, times 24 ft. Yellow pine piling per m, ft. 27 maple wedges per pair 50 cts. A half-in corrugated bars per lb 2 615 cts. 3/4 in corrugated bars per lb 2 515 cts. In corrugated bars per lb 2 515 cts. Coal per ton $4. Electric power per kilowatt 6 cts. Medusa cement per bbl $1. 75 Etna cement per bbl 1.05 bank gravel per cu yd 0. 85 sand per cu yd 0. 66 carpenters per day $3 to 3. 50 common labor per day 1. 75 The summarized cost of the whole work with such detailed costs as the figures given permit of computation was as follows. General service, total, per cu yd. Engineering $451 $0. 512 miscellaneous 75 0. 084 pumping, total 110 days. Coal at $4 per ton, $210 machinery, tools and cartage 283 labor 497, total $990. This gives a cost of $9 per day for pumping. Excavation, total cost, PC, total, timber cartage, etc. $375.17. 6 tools 69.3, 3 labor at $1. 75 $1,687.79. 1. Total $2,131 100. 0 filling 5,711 cu. IDS. Total per cu. YD. Earth $1,142 0. 20 labor including riprapping 396 0. 07. Total $1,538 0. 27 removing old wing walls, total. Labor and dynamite $346. Tools and sharpening 64, total $410. Handrail 150 ft. Total per lin, ft. Material $278 $1. 85 labor 29 0. 19. Total $307 $2. 04 wood block pavement 296 SQ. IDS. Total per SQ YD. Labor 57 0. 19. Total $752 $2. 54 steel 62,000 pounds. Total per lb. Corrugated bars, freight, etc. $1,498 to 41 CTS. Plain steel, wire, etc. 75.0. 12 CTS. Blacksmithing, tools and placing 438.0. 71 CTS. Total $2,011 3. 24 CTS. Centering, total, concrete, per coup, YD. Lumber and piles, $332 $1. 14 labor, $272.0. 95, total, $604 $2. 09 total, per coup, YD. Forms, $3,312 3. 75 concrete, $5,532 6. 25. Grand total, $18,113 $20. 50 in more detail, the cost of the various items of concrete work was as follows for the whole structure, including abutments, wing walls, and arch, containing 884 cu. IDS. Form construction, total, per cu. YD. Lumber and cartage, $1,547 $1. 75 nails and bolts, $129.0. 15 tools, $110.0. 12 labor, erecting and removing, $1,526 $1. 72, total, $3,312 $3. 74 concrete construction. Materials, Etna cement at $1. 05 $1,218 $1. 37 Medusa cement at $1. 75 $499.0. 56 sand at 66 CTS. Per cu, YD, 37.0. 04 gravel at 85 CTS. Per cu, YD, 915 1. 04. Total materials, $2,669 $3. 01 mixing. Machinery and supplies, $549.0. 62 power at 6 CTS. Per kW, 52.0. 06 tools, 22.0. 02 labor, 737.0. 83 total mixing, $1,360 $1. 53 placing concrete, $609.0. 69 tamping concrete, $481.0. 54 heating concrete, apparatus and cartage, $47.0. 05 fuel, $96.0. 11 labor, $270.0. 31 total heating, $413.0. 47 grand total, $8,844 $9. 98 considering the abutment and wing wall work, comprising 594 cu. IDS. Separately, the cost was as follows. Forms, per cu, YD, materials, $1, 20 labor, 1, 09, total, $2. 29 concrete, materials, $2, 92 labor, 2, 38, total, $5. 30 heating, water, and gravel, $0. 70 grand total, $8. 29 considering the arch span, comprising 290 cu. IDS. Separately, the cost was as follows. Forms, per cu, YD, materials, $3, 70 labor, 3, 03, total, $6. 73 concrete, materials, $3, 22 labor, 3, 57 total, $6. 79 grand total, $13. 52. Chapter 47. Culvert work is generally located on the line of a railway or a highway, so that the facilities for getting plant and materials onto the work are the best. And as culverts are in most cases through embankment, under trestle or in trench below the ground level, the advantage of gravity is had in handling materials to mixer and to forms. Ordinarily, individual culverts are not long enough for any material economy to be obtained by using sectional forms, unless these forms are capable of being used on other jobs, which may occasionally be the case where standard culvert sections have been adopted by a railway or by a state highway commission. Various styles of sectional forms for curvilinear sections are given in Chapter Roman 21, and centers suitable for large arch culverts are discussed in Chapter Roman 17. Figure 169 shows an economic form for box sections. It can be made in panels or with continuous lagging, as the prospects of reuse in other work may determine. For curvilinear sections of small size, some of the patented metal forms have been successfully used. Box culvert construction, C, B, and QRR. Mr. L.J. Hotchkiss gives the following data. Box sections of the type shown by Fig. 169 are used mostly. They range in size from single 4x4 FT to double 20x20 FT and triple 16x20 FT boxes. These boxes are more simple in design and construction than arches, and for locations requiring piles, they are less expensive. The form work is plain, and the space occupied is small as compared with arches, so that excavation, sheeting, and pumping are less, and the culvert can be put through an embankment or under a trestle with less disturbance of the original structure. Finally, less expensive foundations are required. For small jobs where it does not pay to install a power mixer, a hand power mixer mounted on a frame carried by two large wheels has been found at least as efficient as hand mixing, more convenient and easier on the men. The machine is turned by a crank driving a sprocket chain. It is charged at the stock piles and then hauled to the forms to be discharged. Local conditions determine the capacity of power mixer to be used. Difficulties in supplying material or in taking away the concrete may readily reduce the output of a large machine to that of one much smaller, and the small machine is cheaper in first cost and in installation and operation. Where the yardage is sufficient to justify the installation of equipment for handling the materials and output of a large mixer, it is found preferable to a small one, as the increase in plant charges is not proportionately so great as the increase in the amount of concrete handled. Again, it may occur on a small job that the concrete must be taken a long distance from the mixer, that a large batch can be moved as quickly and as easily as a small one, and the time consumed in doing it is sufficient for the charging and turning of a large mixer before the concrete car or bucket returns to it. Here a large mixer, while it may stand idle part of the time, is still economic. Fig. 169. Box culvert and form C, B, and QRR. The plant layouts vary with the local conditions, as the following will show. In one case of a culvert located under a high, short trestle, the following arrangement of plant was employed. A platform located on each side of the approach embankment about 8 ft. Below the ties was built of old bridge timbers. A track was laid on each platform and ran out over a mixer located on the end slope of the embankment. 2 mixers, one for each platform, were used. From each mixer, a track led out over the culvert form, and a track along the top of this form ran the full length of the culvert. Gravel and sand were dumped from cars onto the side platforms, and thence shoveled into small bottom dump cars, which were pushed out over the mixer and dumped directly into it. Cars on the short tracks from mixers to culvert form took the mixed concrete and dumped it into the distributing cars traveling along the form. The cars were all hand-pushed. An entirely different layout was required in case of a long box culvert located in a flat valley some 600 ft from the track. A platform was built at the foot of the embankment with its outer edge elevated high enough to clear 2 tracks carrying 5 yd dump cars. The sand and gravel was dumped from cars onto the side of the embankment, running down onto the platform so that scraper teams moved it to holes in the platform where it fell into the dump cars. These cars were hauled by cable from the mixer engine and dumped at the foot of an inclined platform leading to a hopper elevated sufficiently to let a 1.5 yd dump car pass under it. A team operating a drag scraper by cable moved the material up the inclined platform into the hopper, whence it fell directly into the car to which cement was added at the same time. The charging car was then pulled by the mixer engine up another incline, at the top of which it dumped into the mixer. The concrete car was hauled up another incline to a track carried on the forms and reaching the full length of the culvert work. The placing of the reinforcement is given close supervision. When a wet concrete is used, it is found necessary to securely fasten the bars in place to prevent them being swept out of place by the rush of the concrete. A method of supporting the invert bars is shown by Fig. 169, 2 times 2 in. Stakes are large enough, and they need never be spaced closer than 6 ft. The longitudinal bars are held on the stakes by wire nails bent over, and the transverse bars are wired to them at intersections by stove pipe wire. The vertical wall bars are placed by thrusting the ends into the soft footing concrete and nailing them to a horizontal timber at the top. The horizontal wall bars are wired at intersections to the verticals. In the roof slab, the stakes are replaced by metal chairs or by small notched blocks of concrete. The form construction is shown by Fig. 169. It is not generally made in panels, since, as the work runs, the locations of boxes of the same size are usually so far apart that transportation charges are greater than the saving due to use a second time. No general rule is followed in removing forms, but they can usually be taken down when the concrete is a week old. The boxes are built in sections separated by vertical joints, one section being a day's work. The vertical joints are plain butt joints. Tongue and groove joints give trouble by the tenons cracking off in the planes of the joints. A wet mixture is used and smooth faces obtained by spading. Arch culvert costs NC and St. L. Rye. The cost of arch culvert construction for the Nashville, Chattanooga, and St. Louis Rye is recorded in a number of cases as follows: 18 ft. Arch culvert. Mr. H. M. Jones is authority for the following data. An 18 ft. full-centered arch culvert was built by contract near Paris 10. The culvert was built under a trestle 65 ft. high before filling in the trestle. The railway company built a pile foundation to support a concrete foundation 2 ft. thick and a concrete paving 20 ins thick. The contractors then built the culvert, which has a barrel 140 ft. long. No expansion joints were provided, which was a mistake, for cracks have developed about 50 ft. apart. The contractors were given a large quantity of quarry spalls which they crushed in part by hand, much of it being too large for the concrete. The stone was shipped in drop-bottom cars and dumped into bins built on the ground under the trestle. The sand was shipped in ordinary coal cars and dumped or shoveled into bins. The mixing boards were placed on the surface of the ground, and wheelbarrow runways were built up as the work progressed. The cost of the 1900 ids of concrete in the culverts was as follows per yd. 101 BBLS, Portland Cement $2, 26,056 Cu, IDS of sand at 60 CTS, 32 loading and breaking stone, 25 lumber centers, cement house and hardware, 64 hauling materials, 04 mixing and placing concrete 1, 17 carpenter work, 19 foreman 100 days at $2.50, 13 superintendent 100 days at $5.50, 29 total per Cu, YD, $5. 29 it will be seen that only 19 Cu, IDS, of concrete were placed per day with a gang that appears to have numbered about 21 laborers who were Negroes receiving about $1.10 per day. This was the first work of its kind that the contractors had done. It will be noticed that the cost of 42 CTS per Cu, YD for superintendents and foremanship was unnecessarily high. 6 arch culverts 5 FT to 16 FT span. All these arches were built under existing trestles, and in all cases except no. 2 bins were built on the ground under the trestle, and the materials were dumped from cars into the bins, loaded and delivered from the bins in wheelbarrows to the mixing boards, and from the mixing boards carried in wheelbarrows to place. Negro laborers were used in all cases except no. 5 and were paid 90 CTS a day and their board, which cost an additional 20 CTS. They worked under white foremen who received $2.50 to $3 a day and board. In culvert no. 5 white laborers at $1.25 without board were used. There were 2 carpenters at $2 a day and 1 foreman at $2.50 on this gang, making the average wage $1.47 each for all engaged. The men were all green hands, in consequence of which the labor on the farms in particular was excessively high. The high rate of daily wages on culverts nos. 1 and 3 was due to the use of some carpenters along with the laborers in mixing concrete. The high cost of mixing concrete on culvert no. 2 was due to the rehandling of the materials, which were not dumped into bins but onto the concrete floor of the culvert and then wheeled out and stacked to one side. The cost of excavating and backfilling at the side of each culvert is not included in the table, but it ranged from 70 CTS to $2 per Cu, YD of concrete. Cost of 6 concrete culverts on the N.C. and Cent L. Rye and Cent L. Rye no. Of culvert 1, 2, 3, 4, 5, 6 span of culvert 5 FT, 7, 66 FT, 10 FT, 12 FT, 12 FT, 16 FT. Cu IDS of concrete. 210, 199, 354, 292, 406, 986 ratio of cement to stone 1, 5. 516, 515, 815, 816, 116, 5 increase of concrete over stone 16, 0% 9, 9% 6, 3% 12, 3% 8, 3% 5, 3% BBLS. Cement per Cu, YD. 1020, 91, 061, 011, 001, 09 Cu, IDS. Sand per Cu, YD. 0, 43, 0, 49, 0, 44, 0, 46, 0, 46, 0, 47 Cu, IDS. Stone per Cu, YD. 0, 86, 0. 90, 0, 95, 0, 89, 0, 94, 0, 94 total day labor, Inc. Foremen and supt. 702, 607, 784, 726, 768, 1994 Av. Wages per day, Inc. Foremen and supt. $1, 61 $1, 33 $1, 59 $1, 19 $1, 47 $1, 46 cost per Cu, YD. Cement 2, 18-1, 94-2, 27-1, 82-2, 11-2, 0-1 Sand 0, 17-0, 20-0, 18-0, 18-0, 19-0, 14 Stone 0, 52-0, 52-0, 47-0, 54-0, 47-0, 58 Lumber 0, 88-0, 43-0, 48-0, 43-0, 31-0, 57 Unload Materials 0, 23-0, 17-0, 18-0, 18-0, 16 Building Farms 1, 070, 33-0, 62-0, 47-0, 72-0, 41 Mixing and Placing 1, 59-1, 74-1, 69-1, 35-1, 23-1, 26. Total per coup YD $6, 64 $5, 33 $5, 89 $4, 97 $5, 19 $4, 97 14 FT, 9 in Arch Culvert. Mr. W.H. Wally gives the following methods and cost of constructing a 12 FT. Full Centered Arch Culvert 204 FT. Long. The culvert was built in 3 sections, separated by vertical transverse joints to provide for expansion. The end sections were each 61 FT. Long, and the center section was 70 FT. Long. Fig. 170 is a cross-section at the center. For the end sections, the height is 14 FT, 9 ins. The crown thickness is 1 FT, 9 ins, and the side walls at their bases are 5 FT, thick. The concrete was a 1 to 3 to 6 mixture, using slag aggregate for part of the work and stone aggregate for a part. The culvert was built underneath a trestle which was afterwards filled in. Mixing and handling concrete. The height of the track above the valley permitted the mixing plant to be so laid out that all material was moved by gravity from the cars in which it was shipped, until finally placed in the culvert. Sand and aggregate were received in drop-bottom cars, and were unloaded into bins in the trestle. These bins had hopper bottoms with chutes leading to a wheeling platform, which was placed between 2 trestle bents and extended over a mixer placed outside the trestle. The cement house was erected alongside the trestle at the wheeling platform level, and a chute from an unloading platform at track level to the opposite end of the house enabled the bags to be handled directly from the car to the chute, and thence run by gravity to the cement house. Sand and aggregate were chuted from the bins into wheelbarrows, wheeled about 23 FT, and dumped into a hopper over the mixer. Water was pumped by a gasoline engine from a well just below the trestle to a tank on the trestle, whence it was fed to the mixer by a flexible connection, a valve so regulating the flow that the necessary amount was delivered in the time required to mix a batch. Fig. 170. Section of Arch Culvert N, C, and Cent L. Lord Earth. The mixer was a No. 5 Chicago improved cube mixer, operated by a gasoline engine. A larger size would have been preferable since a batch required only 2/3 of a bag of cement which had to be measured, which required the services of an additional man. The mixer was in operation 194 hours and mixed 7,702 batches, 1,217 coup. Ids, or a batch every 87 seconds or 3 coup ids per hour. During the last 10 days, it mixed a batch every 78 seconds while running. The best short record made was 291 batches in 5 hours, or 1 batch every 63 seconds, this being at the rate of 58 batches equal to 9. 2 coup ids of concrete in place per hour, or nearly 1/6 coup YD per batch. It took about a half minute to mix the concrete and about the same length of time to charge and discharge the mixer. To convey the concrete from the mixer to the culvert walls, a 1 coup YD drop-bottom car was used. This car ran on 30-in gauge tracks carried on a trestle straddling the culvert walls and having its floor high enough to clear the arch. A track ran lengthwise of the trestle over each culvert wall, and a cross-track intersecting both with turntables ran to the mixer. 3 men handled the car, a round trip to the extreme end of the trestle being made in about 3 minutes. In the meantime, the mixer was discharging into a small hopper which unloaded into the car on its return. One only of the 3 sections of the culvert was built at a time, both walls being brought up together. After a point had been reached about 2 ft, above the springing on both walls, one track was removed and the other was shifted to the center of the trestle. Forms. There was used in the forms 15,000 ft, B, M of 2-in, dressed lagging for face work 21,000 ft, B, M, rough lumber for back work and old car sills for studding. No charge was made for studding except the cost of loading. The cost of the remaining lumber was $16 per M. For dressed, and $12.50 per M. For rough, a credit of 1/3 the cost was allowed for the old material recovered. The total cost of the labor of erecting the material in forms, bins, and platforms was $666. The work was done by a bridge crew of white men, the average rate of wages per man, including the bridge foreman's time, being $2.20 per day. In addition, a mason at $3.50 per day and a carpenter at $2.25 per day worked with the bridge crew in erecting forms. Cost. The cost of the 1,217 ids of concrete in the culvert was as follows. Item per coup YD 108 BBLS. Cement at $1, 72 $1, 85 0, 47 coup YD. Sand at 30 CTS 0, 14 0, 25 coup YD. Broken stone at 51 CTS 0, 13 0, 8 coup YD. Slag at 26 CTS 0, 21 lumber in forms, etc. 0, 30 miscellaneous materials 0, 05 labor unloading materials 0, 11 labor mixing and placing concrete 0, 42 labor building forms 0, 55 labor not classified 0, 18 labor excavating 40 CTS per coup YD 0. 28 labor backfilling and tearing down forms 0. 10 total $4. 32 culverts for new construction, Wabash Rye. The following data relate to culvert work carried out in constructing the Pittsburgh extension of the Wabash Rye. In 1903, all the work was done by contract. Plant I. This plant was located on a hillside with the crushing bins above the loading floor or platform which extended over the top of the mixer, so that the crushed stone could be drawn directly from the chutes of the bins and wheeled to the mixer. The sand was hauled up an incline in 1-horse carts and dumped on this floor, and was also wheeled in barrows to the mixer. The proportions used were 4 bags of cement, 4 barrows of sand and stone dust, and 7 barrows of crushed stone. A coup YD. Mixer was used and it averaged 40 coup ids per 10-hour day at the following cost for labor. Item per day per coup YD. 1 foreman $3,000, 083 men charging with barrows 450 0. 11 one-man attending engine and mixer 250 0. 062 men loading concrete barrows 3,000. 08 4 men wheeling concrete barrows 100 ft. 6000. 15 4 men ramming concrete 6,000. 15 4 men wheeling and bedding rubble stones 6,000. 15 totals $31. $000. 78 assuming 1/3 ton of coal per day at $3 per ton, we have 2 CTS. More per cubic yard for fuel. Plant Roman 2. At this plant, a Smith mixer was used with a loading floor 4 FT. Above the ground, this low platform being made possible by having a hole or sump in which the skip receiving the concrete was set. A derrick handled the skips between the sump and the work. The batch was made up of 2 bags of cement, 2 barrows of sand, and 4 barrows of stone. The output was 50 ids per day of 10 hours at the following cost. Item per day per yd. 1 man feeding mixer $1, $50. 031 mixer runner 2, $50. 051 derrick engineman 2, $50. 052 tagmen swinging and dumping 3, 000. 066 men wheeling materials 9, 000. 18 2 men tamping concrete 3, 000. 061 foreman 3, 000. 06 totals $24, $50. 49 The cost of fuel would add about 3 CTS per cubic yard to this amount. Small arch culvert costs Pennsylvania Mr. Alex. Holiday gives the following figures of cost of small concrete culvert work carried out under his direction. The culvert section used is shown in Fig. 171. This section gives a slightly larger waterway than a 36-in. Cast iron pipe. 8 culverts having an aggregate length of 306 FT were built using a mixture of Portland cement and limestone and screenings. Each culvert had a small spandrel wall at each end. The work was done by a gang of 6 men receiving the following wages. Foreman, cents per hour 27. 5 assistant, 17. 5 laborers, 15. 0 teams, 35. 0 The materials were hauled about 1 mile from railway to site of work. Cement including freight and haulage cost $1, 97 per barrel. Limestone and screenings cost 50 CTS per yd. FOB. At quarry, no freight charges are included in cost of any of the materials except cement. The cost of the 306 FT of culvert was as follows. Item, total per lin, FT per yd. Labor $443, 14 $1, 45 $3, 35 stone and screening 78, 50 0, 25 0, 60 cement 307, 53 1, 0 1 2, 34 forms 12, 0 0 0, 0 4 0, 09. Total $841. $17 $2. $75 $6. 38 Fig. 171. Small culverts Pennsylvania 26 FT span arch culvert. The culvert was 62 FT, long and 26 FT, span and was built of 1:8 and 1:10 concrete mixed by hand. The wages paid were general foreman 40 CTS, per hour foreman 25 CTS, per hour carpenters 22.5 to 25 CTS, per hour and laborers 15 CTS, per hour. The cost of the concrete in place exclusive of excavation but including wing walls and parapet was as follows, per yd 0.96 BBL. Cement at $1, $61, 535 1, 03 tons cost gravel at $0, 19 0, 195 0, 40 tons fine gravel at $0, 21 0, 085 0, 32 tons sand at $0, 36 0, 115 tools, etc. 0. 078 lumber for farms and centers 0. 430 carpenter work on farms 23 CTS. HR 0. 280 carpenter work platforms and buildings 0. 050 preparing site and cleaning up 0. 210 changing trestle 0. 085 handling materials 0. 037 mixing and laying av 15.5 CTS per HR 1. 440 total per coup. YD $4. 540 there were 1,493 coup. IDs of concrete in the work. The excavation cost $463 and the total cost was $7,243. Cost of railway culvert. The culvert was for a single-track railway and contained 113 coup. IDs of concrete and required 36 coup. IDs of excavation. The figures are given by C. Williams as follows. Cost of material. Kind and amount of material. Unit price. Cost. Stone 113, 2 tons $, $70.79, 24 sand 46, 8 IDs 55.25, 74 cement 137 BBLS. 85 116 45 total $221 43 lumber 52 50 rail and bolts 36 60 total $89 10 excavation labor 189 hours at $15.28 35 foreman 60 hours at $30.18 00 total $46 35 concrete labor 683 hours at $15,102 45 foreman 130 hours at $30.39 00 total $141 45 forms carpenters 313 hours at $225.70 42 labor 30 hours at $15,450 total $74 92 handling materials moving material 245 hours at $15.36 75 unloading material 95 hours at $15.14 25 foreman 20 hours at $36 00 total $57 00 superintendents and office superintendent 6 hours at $50.03 00 office 10 00 total $13 00 grand total $643 25 proportional costs item cost per yard concrete percent of total cost of concrete material $221 43 $1 96 7 1 laying concrete 141 45 1 25 23 6 lumber 52 50 46 08 7 rail and bolts 36 60 32 06 1 building forms 74 92 67 13 3 handling material 56 90 50 09 0 superintendent and office 13 00 12 02 2 total $5 28 100 00 excavation 46 35 1 28 a total $643 15 contractors receipts 113 IDs concrete at $5 95 $672 35 36 IDs excavation at 3010 80 total $683 15 total cost $643 15 profit 5 9% of contract price $40 00 12 FT culvert Kalamazoo Mitch a portion 1,080 FT long of a new channel built in 1902-3 for a small stream flowing through the city of Kalamazoo Mitch was constructed as an arch culvert of the form shown by Fig. 172. The concrete section is reinforced on the lines indicated by a double layer of woven steel wire fabric. The concrete was approximately a 1 cement, 6 sand and gravel mixture. Fig. 172. Cross-section of culvert at Kalamazoo, Mich. The centers were built in sections 12½ ft. Long of the form and construction shown by Fig. 173, and a sufficient number was provided to lay 12 sections of invert and 6 sections of arch. The arch centers were arranged to be uncoupled at the crown. This, with the hinges at the quarter points, permitted the two halves to be separated, and each half to be folded so that it could be carried from the rear of the work through the forms still in place, and erected again for new work. When in place, the center ribs rested on the side forms which set on the invert concrete and are braced apart by the hinged cross strut. This cross strut was the key that bound the whole structure together. The method of removing this key is indicated by Fig. 174. From his experience with these centers, the engineer of the work, Mr. Geo. S. Pearson, remarks, "In work of this kind it is very important to have the centering absolutely rigid, so it will not spring when concrete is being tamped against it, and thus weaken the cohesion of the concrete. It is also important to have the arrangement such that all the centering can be removed without straining or jarring the fresh concrete. The centers were generally removed in about 3 or 4 days after the concrete arch was in place." Fig. 173. Center for culvert at Kalamazoo, Mich. The invert concrete was brought to form by means of templates, Fig. 173, and straight edges. The side forms were then placed and braced apart by the struts, and concreting continued to the skewback plane indicated in Fig. 173. The arch form was then placed. It rested at the edges on the side forms and was further supported by center posts bearing on boards laid on the bottom of the invert. A template, Fig. 175, was used to get the proper thickness and form of arch ring. Outside forms were used to confine the concrete at the haunches, but nearer the crown they were not required. Fig. 174. Hinged cross strut for center for culvert at Kalamazoo, Mich. Much of the work was done when the thermometer, during working hours, ranged from 12 degrees to 25 degrees above zero. When the temperature was below freezing, hot water was used in mixing the concrete, and on a few of the coldest days salt was dissolved in the water. In addition, each section of the work was covered with oiled canvas as soon as completed, and the conduit was kept closed so far as was practicable to retain the heat. Concreting was never stopped on account of cold weather. Fig. 175. Template for arch ring for culvert at Kalamazoo, Mich. Account was kept of the cost of all work, and the figures obtained are given in the following tables. Labor force, materials used, and progress of work. Average progress per day in feet 18. 0 greatest number of feet laid in 1 day 28. Average number of laborers per day mixing and wheeling 10. 0.4 average number of laborers per day placing concrete 5. Average number of laborers per day setting up forms 4. 57 cubic yards of concrete mixed and wheeled per day per man 1. 96 cubic yards of concrete placed per day per man 3. 54 cubic yards of concrete per lin. FT. 0. 95 barrels of cement per lin. FT. 1. 18 barrels of cement per coup. YD. 1. 24 proportion of cement to sand and gravel 1 to 6 itemized cost per lineal foot. Sand and gravel $0. 42 cement 2. 44 mixing and wheeling concrete 0. 98 labor placing concrete 0. 47 forms and templates 0. 30 metal fabric 0. 39 setting up forms 0. 43 finishing 0. 09 tools, general and superintendents 0. 43. Total per lineal foot $5. 95 The cost per cubic yard was thus $6.26. Wages were $1.75 per day. Method and cost of molding culvert pipe, Chicago and Illinois Weston, During 1906, the Chicago and Illinois Weston, Mr. O.P. Chamberlain, chief engineer, built a number of culverts of concrete pipe with an interior diameter of 4 ft and 6 in. Shells. Fig. 176 shows the forms in which the pipe was molded. Both forms are of ordinary wooden tank construction. The inner form has one wedge-shaped loose stave which is withdrawn after the concrete has set for about 20 hours, thus collapsing the inner form and allowing it to be removed. The outer form is built in 2 pieces with 2 times in. Semicircular iron hoops on the outside, the hoops having loops at the ends. The staves are fastened to the hoops by wood screws 1¾ ins, long driven from the outside of the hoop. When the 2 sides of the outer form are in position, the loops on one side come into position just above the loops on the other side, and 4¾ in. Steel pins are inserted in the loops to hold the 2 sides together while the form is being filled with concrete, and while the concrete is setting. After the inner form has been removed, the 2 pins in the same vertical line are removed, and the form opened horizontally on the hinges formed by the loops and pins on the opposite side. The inner and outer forms are then ready to be set up for building another pipe. Fig. 176. Form for molding culvert pipe. The concrete used in manufacturing these pipes was composed of American Portland cement, limestone screenings, and crushed limestone that has passed through a 3/4 in. Diameter screen after everything that would pass through or a 1/2 in. Diameter screen had been removed. The concrete was mixed in the proportions of 1 part cement to 3 1/2 parts, each of screenings and crushed stone. All work except the building of the forms was performed by common laborers. In his experimental work, Mr. Chamberlain used 2 laborers, one of whom set the forms and filled them and the other of whom mixed the concrete. The pipes were left in the forms till the morning of the day after molding. The 2 laborers removed the forms filled the day before, the first thing in the morning, and proceeded to refill them. The average time the concrete was allowed to set before the forms were removed was 16 hours. Mr. Chamberlain believes that with 3 men and 6 forms, the whole 6 forms could be removed and refilled daily. Based on the use of only 2 forms with 2 laborers removing and refilling them each day, and on the assumption that a single set of forms costing $40 can be used only 50 times before being replaced, Mr. Chamberlain estimates the cost of molding 4 ft. Pipes as follows: 2% of $40 for forms $0, 81. 1 coup. Ids, stone and screenings at $1, 85 2, 040, 8 BBLS, cement at $2, 10 68 10 hours labor at 28 CTS. 2, 80, total per pipe $7, 32. This gives a cost of $1, 83 per lineal foot of pipe, or practically $7 per coup, YD, of concrete. The pipe actually molded cost $2, 50 per lin FT, or $9, 62 per coup, YD, of concrete. Owing to the small scale on which the work was carried on, the laborers were not kept steadily at work. The pipes were built under a derrick and loaded by means of the derrick upon flat cars for transportation. At the culvert site, they were unloaded and put in by an ordinary section gang with no appliances other than skids to remove the pipes from the cars. As each 4-foot section of this pipe weighs about 2 tons, it was not deemed expedient to build sections of a greater length than 4 ft, to be unloaded and placed by hand. On a trunk line, however, where a derrick car is available for unloading and placing the pipes, there is no reason why they should not be built in 6 or 8 ft. Sections. Chapter 48. If we set aside concrete block construction, virtually all concrete used in building construction is reinforced. Plain monolithic or mass concrete now, as in the past, is one of the secondary building materials. It is reinforced concrete building construction that is discussed in this chapter. In no class of concrete work is the contractor's responsibility for the successful outcome of the work greater than in reinforced concrete building construction. No degree of excellence in design can make up for incompetent, careless, or dishonest work in construction. This is true not merely in the general way that it is true of all engineering construction. It is true in a special way peculiar to the material. Except for the reinforcing steel, the contractor for concrete building work has no guarantee of the quality of any element of his work, except his own faithful care in performing every task that combines to produce that element. The quality of his concrete depends upon the care with which he has chosen his cement, sand, and stone, and on the perfection with which he has incorporated them into a homogeneous mixture. The quality of his beam or column, then, depends upon the care with which the concrete is placed in position with the reinforcement, and with which the supporting forms are maintained, until the member is amply strong to do without support. There is no certainty of any detail, except the certainty that is had by performing every part of the work as experience has taught that it should be performed if perfect results are to be attained. We have dwelt thus emphatically on the responsibility in concrete building work of the contractor, for the reason that in the past it has been upon the contractor that the burden of failure has been generally shifted. The construction work of buildings is divided into 1. Construction, erection, and removal of forms. 2. Fabrication and placing of reinforcement. 3. Mixing, transporting, and placing concrete. Construction, erection, and removal of forms. The stereotyped textbook statement that forms must be true to dimensions and shape, and rigid enough in construction to maintain this condition under all loads, that they have to sustain mentions only one of the factors that the constructing engineer or the contractor has to keep in mind in designing such forms. His design must be made true and rigid at the least possible cost for first construction of lumber and carpenter work. It must be made with the plan in mind of using either the same forms as a whole or the same form material several times in one structure. It must be made with a view to convenience in taking down, carrying and re-erecting the forms the second or third time. And it must be made with the object in sight of securing the greatest salvage value either in forms fit for use again, or in form lumber that can be sold or worked up for other purposes. The general conditions governing the computation and design of economic form work are discussed in Chapter Roman 9. Column forms. Concrete columns are usually square or rectangular in section, with commonly chamfered or beveled corners. The popularity of these sections is due very largely to the simplicity of the forms required. When hooped reinforcement is used, the column section is always circular or polygonal. Hollow sections, T-section, and channel sections are rarely employed, and then only for wall columns. Column forms should be made in units which can readily be assembled, taken apart, and reassembled. The number, arrangement, and size of the units are determined by the shape and size of the column and the means adopted for handling the forms. For square or rectangular columns, there will be usually 4 units of lagging, one for each side, plus the number of clamps or yokes used to bind the sides together. Yokes or clamps will seldom be spaced over 3 ft apart unless very heavy lagging is used. 2 ft. Spacing for yokes is common. For circular columns, 2 units of lagging are necessary, and this is the number commonly used. The yokes or hoops are spaced about as for rectangular columns. Metal forms can be used to good advantage for cylindrical columns. Forms for polygonal columns are difficult to construct in convenient units. Forms built complete a full story high and concreted from the top are essential where wet and sloppy concretes are used. In Europe, where comparatively dry concretes are employed, and where the reinforcement is commonly placed a piece at a time as concreting progresses, 3 sides of a rectangular form are erected full height, and the 4th side is built up as the concrete and metal are placed. This construction is now less common, even abroad, than it was, since wetter mixtures are coming to be approved by European engineers to a greater extent now than formerly. It is a time-consuming method, and with wet mixtures it has nothing to recommend it. For lagging 1 1/4 and 2 in. Plank are commonly used, with yokes spaced 2 ft. Apart, the lighter plank is amply strong and reduces the weight of the units to be handled as well as the amount of form lumber required. Fig. 177. Form for rectangular column for factory building, Cincinnati, O. Column forms should always be constructed with an opening at the bottom, by means of which the reinforcement can be adjusted and sawdust, shavings and other material cleaned out. Rectangular columns. The form shown in section by Fig. 177 was used in constructing a factory building at Cincinnati, O. 2 times 4 in. Studs at each corner carry the horizontal side lagging boards and are clamped together by yokes composed of 4 hardwood corner saddles connected around the form by a hooked rod with center turnbuckle on each side. No nails are used in assembling the parts. The same studding and yokes serve for several sizes of column, the lagging alone being changed. The lumber required for studding is 5 1/2 ft. B.m. per foot of column length. The lumber required for lagging using 1 in. Boards would be 2 2/3 ft. B.m. for a 12 in. Column and 2/3 ft. B.m. would be added for every 2 in. Increase in size of the column, about 3 1/2 ft. B.m. is required for each set of 4 corner saddles. With the studs rabbited at the mill, the carpenter work is reduced to the simple task of sawing the boards and struts to length. The form is taken down by simply unscrewing the turnbuckles. It can be erected by common labor in charge of 1 carpenter to attend to the plumbing and truing up. The form can be used over and over, and for columns of different sizes without change, except in the length of the lagging boards. The form shown by Fig. 178 was used in constructing a 9-story warehouse at St. Paul, Min. It is a design which has become almost standard with a number of large building contractors. In this construction, lagging boards the full length of the column are used and are held without nails by yokes. The yokes consist of 2 heads of wood held together by threaded rods with nuts. Between the rods and the lagging are struts or blocks serving both as spaces and to hold the lagging to plane and surface. The yoke proper is adjustable to the extent of the threaded portions of the tie rods. It is to be noticed that the lagging boards are not connected by battens or cleats. Therefore, 2 or 3 widths of stock serve for all ordinary changes in size of columns, and carpenter work is limited to sawing them to length. Furthermore, as the boards are full column length, their salvage value when removed from the forms is high. Common laborers under a carpenter foreman can assemble and erect the form for a 12-in column and using 3 times 4-in. Yokes spaced 2 ft apart and 1/4 in. Lagging this form requires about 12 ft/m of lumber per foot length of column. The column form shown by Fig. 226 for the 6-story building described in a succeeding section differs from the one described only in the details of the yoke construction. In place of the struts between the wooden heads of the yoke, a cleat is nailed across the projecting ends, which has to be pried loose every time the yoke is removed, and nailed into place again every time the yoke is put onto another form. These repeated nailings soon destroy the yoke heads. This form as constructed requires about 8¾ ft/m of lumber per foot length of 12-in column, which is 3¼ ft/m less than is required for the form shown by Fig. 177. The saving comes entirely in the yoke construction. Fig. 178. Form for rectangular column for warehouse at St. Paul, Min. The form shown by Fig. 238 is of the same general type as are the two just described, the chief difference in detail being in the yoke construction and in the forming of the lagging boards into a panel or unit for each side by means of battens. This panel construction makes a lagging unit which is more convenient to handle, but less convenient to adapt to changes in size of column. The salvage value of the lumber is also reduced by the nailing. Assuming 1/4 in lagging and a yoke spacing of 2 ft. To permit direct comparison, this form requires 10½ ft/m of lumber per foot length of 12-in column as compared with 12 ft/m for the form shown by Fig. 177 and 8¾ ft/m for the form shown by Fig. 178 as actually constructed with 2-in. Lagging the form shown by Fig. 238 requires about 14 ft/m of lumber per foot length of 12-in column. The French constructor Henry Beek uses the column form construction shown by Fig. 179. 3 sides of the forms are built full length of vertical plank, and the 4th is built up of horizontal lagging nailed on a board at a time as concreting progresses. In place of rectangular yokes, steel clamps of special form are used to hold the lagging in place. To tear down this form requires drawing the nails in the horizontal lagging and the knocking loose of the clamps. The vertical lagging is of necessity connected by battens into panels to make it possible to hold it in place by the form of clamp used. Assuming 2-in, vertical lagging with times 3-in, battens every 3 ft, and in. Horizontal lagging, this form requires about 12 ft/m of lumber for every foot length of 12-in column. This form seems to offer no particular merits to American eyes. There is practically no saving in lumber over forms with rectangular yokes, and the clamp shown, while adjustable, is not nearly so rigid and secure a bond for the lagging as is a good yoke. Fig. 179. Form used by Mr. Henry Beek for rectangular columns. Fig. 180. Form for rectangular column for a factory building, New York City. The form shown by Fig. 180 is an extreme example of nailed construction throughout, no yokes or clamps being used. It was used in constructing a factory building in New York City. Horizontal lagging nailed to vertical studs was used for all 4 sides. 3 sides were built up full height, and the 4th side was placed a board at a time as concreting progressed. This form required 7⅓ ft/m of lumber per foot length of 12-in column, which is probably about as low in lumber as column form construction can be got. The labor of tearing down and re-erecting the form would be high, as also would the waste of lumber. Nailed forms of this type are rarely used. Fig. 181. Form for T-section wall column. Fig. 182. Form for corner wall column. The form shown by Fig. 181 was used for molding T-section wall columns for a power station. It is noteworthy for its section because of the provision for molding grooves in the two sides to which the curtain walls join, and because of the manner in which 3 of the 8 sides were built up as the concreting progressed. The sides of B, C, D, E, and F, G, H were erected in full column units, and the sides C, D, E, F, and H were erected in sections 2ft, high as concreting progressed. The yokes were spaced 2ft apart, using 1/4 in. Stuff for yokes and lagging this form as built required about 16ft, b, m per foot length of column. Except for the beveling of the mold for the curtain wall recesses, the framing is all plain saw and hammer work. Fig. 183. Core form for hollow column. A corner wall column form is shown by Fig. 182, and as this was an example of hollow column work, the section of the concrete within the form is shown. Forms of this shape and of T-section are properly classed as special form work, so that the examples given here are helpful merely as indicating general methods that may be followed. This particular form required 15¾ ftb, m, of in, lagging per foot of column length, and, neglecting the special top frame, about 16 ft, b, m, of staging per foot to support the lagging. The core forms for molding the hollow spaces in the columns of this particular building are shown in Fig. 183. The cross pieces or keys carried on the in. Bolts as pivots are revolved a quarter turn to slip clear of the slots and permit the sides to close together and free the core for withdrawal. In many cases, the contractor will find it preferable to use thin sheet metal core molds or light wooden cores and leave them in place. In one case known to the authors where hollow wall columns were used as hot air ducts for a heating system, the duct was laid up of one row of bricks, encircled by the column form, and the annular space concreted around the brick duct as a core. The rare use of irregular columns makes form and core construction for them a special problem requiring special detailed estimates in each case. The channel section wall column form shown by Fig. 230 is a case in point. Here the form became practically a portable mold for duplicating columns as many times as was desired. Fig. 184. Form for large rectangular columns. As an example of form work for very large columns or pillars that's shown by Fig. 184 is particularly good. It was used for constructing 8³ ft. Square pillars for a water tank tower. The lagging consists of 4 panels made by nailing horizontal boards to vertical studs. The panels are clamped together by rectangular yokes spaced 3 ft apart. There are nearly 27½ ft, b, m, of lumber per foot length of 3 ft. Column in this form. Fig. 185. Adjustable form for rectangular columns. The form shown by Fig. 185 was used by Mr. W. Maxton in constructing a large factory building at St. Louis, Mo., and is notable for the means adopted for centering the forms and for reducing their lateral dimensions to fit them for molding the decreasingly smaller columns of the upper floors. To center the forms, the short angles are molded into the concrete so as to project slightly above the tops of the floor slab. Also, the pieces of wood C are molded into the floor slab. The form is set over the angles and lined up truly by nailing the blocks B to the blocks C. It will be noticed also that the column mold bears only at the four corners, the lagging being cut away somewhat on each side, so as to afford an opening for cleaning. The lagging for the sides of the column mold is battened together to form 4 units or panels, which are held together by iron clamps of the form shown. Lag screws are used everywhere in place of nails. The notable feature, however, is the piecing out of the lagging panels with one in. Strips, one or more of which can be ripped off on each side to reduce the size of the forms as the columns grow smaller toward the top of the building. Polygonal columns. Forms for polygonal columns require more lumber and more carpenter work and are less susceptible of ready arrangement into units than forms for rectangular columns. There is no approach to a uniform practice in their construction, and the few forms shown here are merely specific examples. Fig. 186. Form for octagonal column for factory building. The form shown by Fig. 186 was used for interior columns of octagonal section with hooped reinforcement for a factory building. This form for a 12 ft. Octagonal column 24 ins. A cross between sides requires approximately 325 ft. B.M. of lumber. The form shown by Fig. 187 was used by the same engineer in another building. It is, as will be noted, in 4 units coming apart in joints at diagonally opposite corners. This form for an octagonal column 18 in. A cross between sides required about 13 ft. B.M. of lumber per foot of column length, with yokes spaced 3½ ft. apart. The form shown by Fig. 188 was used in a large warehouse at Chicago, Ill. It will be noted from the dotted lines that one yoke clamps the sides A, the next the sides BB, and so on. This does away with triangular blocking to hold the corner boards that is used in the form shown by Fig. 187. 6 pairs of yokes were used for each column so that the yoke spacing was about 2 ft, with 2 times 6 in. Yokes and 1½ in lagging A. Form for a column 18 ins. Between sides would require some 17 ft. B.M. per foot of column length. Fig. 187. Form for octagonal column for factory building. Fig. 188. Form for octagonal column for a warehouse, Chicago, Ill. Circular columns. Circular columns have been most frequently molded in steel forms, and these are by all odds the best for general work. Made in 2 parts of sheet steel, and in sections that are set end to end one on another, a form is obtained which is easy to erect, remove, and transport. Wood forms for circular columns are rather clumsy affairs and are expensive to construct. Such a form, Fig. 190, is described in the succeeding section. Another is shown by Fig. 189. This form was used successfully for filling and encasing steel columns for a fireproof building in Chicago, Ill, and is a favorite circular form construction in Europe. It is apparent that the hooping needs to be very heavy and that the form is one that will be hard to handle and rather expensive to make. In several instances where hooped reinforcement has been used, the hooping has been wrapped with or made of expanded metal or other mesh plus work, and the concrete deposited inside the cylinder thus formed without other form work. A 6-story factory building in Brooklyn, NY, was built with circular interior columns from 28 ins to 12 ins, in diameter, reinforced by a cylinder of no 10-3 in. Mesh expanded metal, stiffened lengthwise by 4 round rods 1 in. In diameter for larger columns 2½ in. In diameter for smaller columns This reinforcement was set in place and wrapped with no 24.5 in mesh metal lath, and the cylinder was filled with concrete and plastered outside. A moderately dry concrete is essential for such construction. Fig. 189. Form for circular column. The method of molding shells with the hooping embedded described for the bush terminal factory work in another section is another way of avoiding form work of the usual type. Light steel forms, as well as the special construction noted, must be supplemented by staging to hold them in line and to carry the ends of the girder forms that are ordinarily carried by the column forms. 4 uprights arranged around the column so as to come under the connecting girders are commonly used. They are set close enough to the column to hold the form plumb by means of blocks or wedges. Ornamental columns. Forms for ornamental columns call for special design and construction. For many purposes, such as porch and portico work, the best plan is to mold the columns separately and erect them as stone columns of like character are erected. Metal forms of various patterns are made by firms manufacturing concrete block molds and can be purchased from stock or made to order. Where the column is to be molded in place, form construction becomes a matter of pattern making, the complexity and cost of which depends entirely upon the architectural form and ornament to be reproduced. The molding of ornament and architectural forms in concrete is discussed in chapter 23, and the 2 examples of ornamental column form work given here from recent work indicate the task before the builder. Fig. 190. Form for molding fluted cylindrical column. The form shown by Fig. 190 was used for molding in place fluted columns used in a courthouse constructed at Mineola, N.Y. The lagging in the form of staves forms a 24-sided polygon and is held in position by hoops and yokes. The molds for the flutes were formed by inserting screws from the outside so as to penetrate the staves and molding half-round ribs of plaster of Paris over them by means of the simple device shown. To dismantle the form, the screws were removed and the lagging taken down, leaving the plaster of Paris in place as a protection to the thin edges until the final finishing of the building. The methods illustrated by Fig. 191 were employed in molding columns in place for a church at Oak Park, Ill. The bottom portions of these columns were plain square sections molded in place in square molds. The top portions were heavily paneled. The 4 corner segments were cast in glue molds backed by wood with wires embedded as shown. After becoming hard, they were set on end on the plain column and tied and braced as shown. The side openings were then closed by wooden forms, and the interior space was filled with concrete. The surface facing for these columns was bird's-eye gravel and cement, with very little sand, mixed very dry and placed and tamped with the coarse concrete backing. Fig. 191. Form for ornamental column for church at Oak Park, Ill. Slab and girder forms. Slab and girder construction for roofs and floors is of 3 kinds. 1. Concrete slab and steel beam construction in place. 2. Concrete slab and girder construction in place. 3. Separately molded slab and beam construction. The third method of construction is distinct from the others in respect to form work as well as other details, and is considered separately in chapter 20. Slab and I-beam floors. Centers for floor slabs between steel I-beams are made by suspending joists from the beam flanges and covering them with lagging. Frequently, the joists and lagging are framed together into panels of convenient size for carrying and erecting. The construction is a simple one in either case, where slabs without haunches or plain arches form the filling between beams. Figure 192 shows an arch slab center, plain hook bolts, with a nut on the lower end passing through holes in the joists are more commonly employed. For 1 in. Lagging the joist spacing is 2 ft, for 1/2 in lagging 4 ft, and for 2 in, lagging 5 ft. Fig. 192. Form for arch slab between I-beams. Fig. 193. Form for flat slab floor between I-beams. A more complex centering is required where the slab has to be haunched around the I-beams. The center shown by Fig. 193 was designed by Mr. W. A. Etherton for the floor construction of the U.S. Post Office building erected at Huntington, Va. in 1905. The center consists essentially of the pieces A, 2 times 4 ins, for spans not exceeding 6 ft, and the 2 times 3 in, triggers B, which rest on the lower flanges of the floor beams and thus support the forms. The trigger is secured at one end to the piece by a 1 times 3 in, cleat C, and at the other end by 1 times 3 in, cleats D on either side of a, which serve also as supports for the batter boards E. The 6-penny nail F is but partly driven, and it is to be drawn before removing the forms. When the supports of the beams are not fireproofed, the cleats D extend to the bottom of the trigger B, but otherwise one cleat extends lower to secure the cross strip G. To remove the forms, draw the partly driven nail F, knock off the strip G or loosen it enough to draw the nails in B. Pull the triggers on one beam and the forms will drop. If the soffit board H is used, it is necessary first to remove the strip G. For larger beams, use the spacing blocks H as shown. For smaller beams, omit the trigger B and extend a to rest on the flange of the beam. Then to remove the form, must be cut preferably near the beam. No complete records of the cost of these forms were obtained, but the following partial information is furnished by Mr. Etherton. Considering a panel 6 ft, span by 19 ft, long on 15 in, I-beams, the lumber consisting of 1 in, boards supported by 2 times 4 in, cross pieces on 2 times 3 in, triggers spread 3 ft. On centers, soffit of beams not fireproofed, it required 1 carpenter 5 hours at 30 cts per hour to complete the panel. Figuring from this alone, I should say that 10 cts per sqyd is a fair estimate for carpenter work. In working over the forms for another floor, the 1 in, boards require more time to handle, and I should say that the saving in cost of work over the first floor would be not over 2 cts per sqyd. 2 laborers moved their scaffolding and took down the forms from 3 completed panels of 13 sq.ids, each in 1 hour. Smaller panels require a longer time per yard. Counting for the proper piling of lumber, I should allow 1 hour for 1 man to take down the forms for a 13 sq.yd panel when conditions are the best. We contracted with 2 laborers to remove the forms from the 3rd floor and roof and pile them in good shape on the ground just outside of the building for an amount averaging about 4.5 cts per sq.yd, and the men made but small wages on the contract. The lumber was used on 3 floors and the roof and the best of the 1 in, boards and all of the 2 times 4 in, and 2 times 3 in. Stuff were used on a second job. For a safe estimate based on the data secured, I should figure the cost of labor and materials for a 3- or 4-story building about as follows. Per sq.yd, lumber at $20 per 1,028 cts. Carpenter work at 30 cts. Per hour 10 cts. Labor tearing down at 15 cts. per hour 4 CTS. Total per square yard 42 CTS. Figure 194 shows an arrangement of centering between steel beams, which is novel in that it provides for molding a slab with girders. The form was used in building the roof of a locomotive roundhouse. This roundhouse was of the usual circular form and had a radial width of 80 ft. Each radial roof girder, which was an 18 in. I-beam was carried by an outside wall pier and 3 I-beam columns encased in concrete. The space between main roof girders was spanned by reinforced concrete girders and roof slab. The center illustrated was employed for molding the concrete girders and slab, and carries out the idea of making a stiff and light center for considerable spans of slab without support by staging. The truss construction of the frames supporting the girder box will be noted. Fig. 194. Form for slab and girder floor between I-beams concrete slab and girder floors. The construction of forms for this type of floor should be such that the slab centers and the sides of the girder molds can be removed without disturbing the bottoms of the girder molds. This permits the beams to be supported as long as desirable, and at the same time releases the greater part of the form work for use again. It is of advantage also to lay bare the concrete as soon as possible to the hardening action of the free air. The slabs may be similarly supported by uprights wedged up against plank caps. No very great amount of lumber is required for this staging, and it gives a large assurance of safety. It is well also to give the girder molds a camber or to crown them to allow for settling of the false work. The form shown by Fig. 195 was used in constructing girders from 14 to 23 ft, long in a factory building at Cincinnati, O. The sides are separate from the bottom, being supported at the ends by cleats on the column form and at intermediate points by struts under the yokes. The floor lagging is carried by 2 times 4 in. Stringers supported by the yokes. Uprights set under the bottom plank keep the girder supported after the sides and slab centers are removed. It will be noted that the form is given a camber of 1 in. The structural details are evident from the drawing. The form shows a method of molding a bracket for wind bracing. A simple modification fits it for molding girders without brackets. A rough computation gives 10 ft. B. M. of lumber per lineal foot of girder form as shown. Fig. 195. A girder and slab form for factory building, Cincinnati, O. Fig. 196. Girder and beam forms for factory building, Beverly, Mass. The form construction shown in Fig. 196 was employed in building the slab and girder floors for the United Shoe Machinery Co. S factory at Beverly, Mass. In these buildings, the main girders cross the building at 20 ft. Intervals and midway between the main girders is a bridging beam also reaching across the building. Floor beams span the 10 ft. Spaces between bridging beams and main girders at intervals of 3 and 4 ft. Referring first to the main girder form, tall horses are set up at 3 ft. Intervals and connected by stringers laid on the caps. These stringers carry a cross piece with a cleat at each end over each horse. The bottom boards of the mold rest on these cross pieces, and the side pieces are set up between verticals wedged tight between the cleats. The beam molds are a modification of the girder molds. The slab centers consist of panels just large enough to span the openings between beams and girders and composed of 1 in. Boards fastened together by 4 1 times 5 in. Cleats, except in attaching the quarter round and triangular moldings for fillets, no nailing is necessary in erecting and taking down the forms. Fig. 197. Girder and slab form for concrete building work. The form construction shown by Fig. 197 is one used by a large firm of reinformed concrete builders. The slab centers can be struck and the sides of the girder mold removed without disturbing the support for the bottom of the beam. This form runs quite low in lumber, requiring for a 9x12 in. Beam box including posts some 9 ft, b, m per lineal foot of box. The joists and lagging as shown require about 2 ft, b, m per square foot of floor slab. The practice is to give these girder boxes a camber of a half in 10 ft. The construction shown by Fig. 198 is designed to provide adjustability, to enable quick erection and removal and to do away with all nailing. The construction is as follows. Wooden posts carry at their tops steel T-beam crossarms knee-braced to the posts by steel straps. The crossarms carry the two jaws of a clamp, each consisting of a vertical plate and two diagonal braces, slotted so as to slide on the T-beam. A cut nail or other piece of metal driven into the slots fastens the jaws on the T-beam. The crossarms carry the bottom boards of the girder molds, and the vertical plates of the jaws support the side pieces. A blocking piece slipped between the braces carries the end of the joist for the floor slab centers. This form is the invention of Mr. W. H. Dillon and was used in constructing the 9-story, 260 x 150 ft wholesale hardware store of Farwell, Osman and Kirk Co., St. Paul, Min. Fig. 198. Girder and slab form for warehouse at St. Paul, Min. Fig. 199. Girder and slab form for factory building, New York, N.Y. The form shown by Fig. 199 was used in constructing a factory building in Long Island City, N.Y., and it is given here chiefly for the purpose of exhibiting the unnecessary complexity of form work. Comparing this form with that of nearly any of the preceding designs will bring out the point. The design, however, was one of the earlier ones to recognize the advantage of stripping the slab centers and the sides of the girder boxes without disturbing the bottom plank of the boxes or the staging. The drawing shows the independent support of the bottom board and side pieces of the girder mold on the transverse caps of the staging posts. These posts are 6 x 8 in section and are spaced from 6 to 8 ft apart. Briefly described, the bottom board is a single plank from 1 to 3 inches thick, to which the side pieces are lag screwed at the bottom. The side pieces are panels composed of 4 times in vertical boards nailed to top and bottom 2 times 4 in horizontal timbers. A third horizontal timber near the top serves as a seat for the ends of the joists carrying the slab lagging and is braced from the bottom horizontal by vertical stiffeners. The edge boards of the slab lagging are nailed to the top edges of the side pieces of the girder mold, and the tops of these side pieces are connected across the trough by strips of board. All the slab lagging boards except those at the edges of the girder molds are laid loose. In the building referred to, after the floor concrete had set about 7 days, the joists carrying the slab lagging were turned a quarter over, thus dropping the slab form about 2 inches. A few days later, the joists and lagging were taken down, and the side pieces of the girder mold were unscrewed and removed. The bottom board and staging posts were left in position about 3 weeks longer, and then dropped about 1 in. By removing fillers from the staging post caps. In another week, the bottom boards and staging posts were taken down. This construction of form and method of removing it permitted the concrete to be stripped so that the air could get at it as fast as it was safe to take the support from any part, and at the same time kept the supports in such position that they form a safety platform in case of collapse. A more important advantage is that the formed timber can be removed as fast as any part of it is free and used again. Thus, the lagging boards and joists and the side pieces for the girder molds were free for use again about every 2 weeks, and yet the main supports of the girders were undisturbed until they were fully a month old. Other examples of girder and slab forms are shown in the succeeding sections describing the construction of a 6-story building and of a garage constructed at Philadelphia, Pa. Fig. 200. Collapsible core forms for girder and slab floors. Another type of slab and girder form construction that deserves brief mention because of its variation from usual practice, and also because of its extensive use by one prominent builder is shown by Fig. 200. Cores, or inverted boxes with 4 vertical sides and rounded corners, are set side by side, with ends on stringers carried by the column forms, at intervals wide enough to enable the beam to be molded between. A plank resting on cleats on the sides of the cores forms the bottom of the beam mold. The main girders are molded in similar spaces between the ends of the cores in one panel and of those in the next panel. To permit the core to be loosened readily, it is hinged. When in place, spaces inside the core keep the sides from closing. These are knocked out, the core sides close together, and the core is removed for use in another place. Cores similar to these were used in molding the ribbed floor for the Bush Terminal Factory building, described in a succeeding section. These cores are capable of repeated use, so that while they are somewhat expensive to frame, they give a very low cost of form work, when the beam and girder spacing is arranged largely in duplicate from floor to floor. It will ordinarily be cheaper to have these cores made to pattern by regular woodworking shops and shipped to the building ready to erect. Wall forms. Wall work in modern commercial and manufacturing buildings, when we come to eliminate windows and wall columns and girders, is confined very largely to isolated curtain wall panels between windows and framework. In such buildings, therefore, wall forms consist merely of wooden panels, one for each face of the wall, constructed to fit the spaces to be walled up. Where these spaces are duplicated from bay to bay or story to story, the same form panels will serve repeatedly. For residences and other buildings having greater proportionate area of blank wall, the builder has a choice between continuous forms carried by staging and movable panel forms. Fig. 201. Continuous form for wall construction. For 1- and 2-story buildings, with the usual variation in architectural detail, panel work, and window work, the continuous form has many advantages, and the superior economy of movable panels in retaining and other plain wall work is by no means always true here. One good type of continuous wall form construction is shown by Fig. 201. The gallows frames are spaced about 6 ft. apart along the wall and connected by horizontal stringers nailed to the uprights or by diagonal bracing. Each frame may be made up of 6 × 6 in. Posts connected by 2 × 4 in. Cross struts and diagonals with bolted connections, so that the frame can be taken down and put together easily, and so that the bracing can be removed as the wall is built upward. The other details of the form work are shown by the drawing. This construction leaves a clear space for placing the concrete, and the cross pieces give support to runways. It has been successfully used in a large amount of low building work. Fig. 202. Sectional form for wall construction. Movable panel forms are of great variety in detail, but are generally of either one or the other types shown by Figs. 202 to 204. The form shown by Fig. 202 was used in constructing a church at Oak Park, Ill. For the back of the wall, it consists of continuous lagging held by 2 times 4 studs. For the face, 1 times 6 in. Lagging 12 ft. Long was nailed to 2 times 4 in. Studs to form panels. It will be noted that the ends of the studs are scoffed so as to interlock in succeeding panels. This construction also shows a method of supporting the reinforcing bars inside the form. The form shown by Fig. 203 was used in constructing a large factory building and consisted of 2 side pieces or panels 3 ft. High and 16 ft. Long, the distance between wall columns. For the first course, these were seated on the carefully leveled and rammed ground and securely braced by inclined or horizontal struts inside and outside of the building. After the concrete had set for 3 days, the molds were loosened and lifted until the lower edges were 2 ins below the top of the concrete, and there they were held by horizontal bolts through their lower edges, and across the top of the concrete by ties nailed across their tops every 3 ft, and by bracing to the falseworks supporting the column and floor forms. The cross bolts passed through pasteboard sleeves which were left permanently embedded in the wall. By starting the molds level and finishing each course level with their tops, no difficulty was had in keeping the forms plumb and to level as they were moved upward. This type of form has to be exteriorly braced to staging or adjacent column forms, etc. Fig. 203. Sectional form for wall construction, the type of movable panel form shown by Fig. 204 depends for all support on the wall alone. The sketch shows the form filled ready to be shifted upward. This operation consists in removing the bottom bolts and loosening the top bolts enough to permit the studs to be slid upward the full length of the slots. The lagging boards left free are then removed and placed on top, and the bolts are tightened, completing the form for another section of wall. Fig. 204. Movable panel form for wall construction. Fig. 205. Sullivan's plank holders for wall forms, a type of wall form construction intended to do away with studding and bracing, is illustrated by Figs. 205 and 206. In both cases, metal plank holders are used in place of studs, and practically the only difference between the two is in the shape and material of the holders. The mode of procedure is to work in horizontal courses 1 plank high around the wall, removing the bottom plank and placing it on top as each new course is begun after the first few courses have been laid. Using the arrangement shown by Fig. 205 in constructing a building 100 times 54 ft, in plan and 36 ft. High with 12 in. Walls, a height of 212 times 2 in planks was all the form work that was ever necessary at any one time, so that the amount of form lumber required for the building was 2,464 ft. B. M. plus 205 ft. B. M. of 2 times 4 in. Flooring strip or altogether 2,669 ft. B. M. or 0. 24 ft. B. M. per square foot of exterior wall surface, or 6½ ft. B. M. per cubic yard of concrete. This same form lumber with 16 additional plank was then used to construct a building 100 times 100 ft. times 16 ft. high, so that some 3,000 ft. of form lumber sufficed for 17,548 sq ft. Exterior surface of wall or for 617 cu. ids of concrete in 12 in. wall, which gives 0. 17 ft m per square foot or fa, 8 ft m per cubic yard of concrete, Fig. 206. Farrell's plank holders for wall forms, erecting forms. The organization of the erecting gang will depend very largely on the manner in which the forms have been constructed. If they have been constructed in sections which go together with wedges and clamps, common laborers, with a foreman carpenter, in charge to direct, and to line and level the work will do the erecting. But if they have to be largely built in place, carpenters are necessary for all the work except carrying and handing. There should be at least one foreman for every 15 to 20 men, and a head foreman in charge of all form work. The mode of procedure will differ for every job, but the following general directions apply to all work in greater or less measure. Clamps, bolts, and wedges, and not nails, should be used wherever possible in assembling parts of forms in erection. These devices are not only quickly and easily applied in erection, but they are just as quickly and easily loosened in taking down forms, and they can be loosened without jarring the concrete member. Lining girder forms and lining and plumbing column and wall forms is high-class carpenter work, and should be directed by competent carpenters. A column or girder which is out of line or plumb not only looks bad, but may be required to be removed and corrected by the engineer. The expense for one such correction will be many times that which would have been involved by proper care in the first place. Supports or staging for the forms should be used freely and well braced in both directions. Uprights should be set on wedges and bear against a cap piece, and on a sill piece to distribute the load. Erect, line, and plumb the column forms first. Then erect, line, and level the girder forms and set the girder staging, and finally erect and level the slab centers and their supports. Leave the foot of each column form open on one side at the bottom, so that the column reinforcement can be adjusted and connected up, and so that a clear view can be had through the form to detect any object that may have fallen into the form and become wedged. This same opening makes it possible to clean the form. Give the forms a final inspection before concreting to check line and level, to close open joints, and to tighten up clamps and wedges. Finally, clean each form and wet it down thoroughly before placing the concrete. Do this just before placing the concrete. Removing forms. Good judgment and extreme care are essential in removing centers. It goes without saying that forms should never be removed until the concrete has set and hardened to such strength that it will sustain its own dead weight and such live load as may come upon it during construction. The determination of this condition is the matter that calls for knowledge and judgment. Some cements set and harden more rapidly than others, and concrete hardens more and more slowly as the temperature falls. These and other circumstances must all be taken into account in deciding upon the safe time for removal. Many large contractors mold a cube of concrete for each day's work and leave it standing on the finished floor, exposed to the same conditions as the concrete in the forms. Examination of this sample block gives a line on the condition of the concrete in the work and on the probable safety of removing the forms at any time. In all cases, it should be the superintendent's duty to determine when to remove forms, and he should satisfy himself by personal inspection that the concrete is in condition to stand without support. It is also wise, at least as a matter of precaution, for the contractor to secure the engineer's or the architect's approval before removing any formwork. Care in removing forms is essential for the reason that green concrete is particularly susceptible to injury from shock or sudden strain. It is well, therefore, to have a separate gang always doing the work. These men will in a few days become trained under an experienced foreman, so that they will not only do the work with greater safety, but also more rapidly. This gang should, furthermore, be required to follow a regular system in its work, a system which may not be departed from without direct orders from the superintendent. An example of such a system is outlined below. The time of beginning this work of removal shall be given by the superintendent. In warm, dry weather, with other conditions favorable, removal may be begun after 7 days. Then the following schedule may be followed. At the end of 7 days, remove the sides of the column forms. This gives an opportunity to determine the soundness of the column casting, and also serves the further desirable purpose of bearing the concrete to the curing and hardening action of the air. At the end of 14 days, loosen the wedges of the posts supporting the slab centers, and drop these centers a couple of inches. Leave the centers in this position for another day, meanwhile examining the tops of the slabs to note their condition. Then remove the sides of the beam molds and the slab centers, replacing the latter with temporary uprights supporting a plank bearing against the underside of the slab. This precaution is often neglected, and with very little reason considering the importance of the safeguard thus secured. Ordinarily, the shawls need not be left in place more than a week, so that the amount of lumber thus tied up is small. At the end of 3 weeks, remove the uprights under the beam and girder molds and strip the bottom plank. In this schedule, it is assumed that the floor is free from any great load, and that no unusual loading is put upon it. If a load of any consequence is to come on the floor, the shawls and uprights should be left in place longer. No schedule of removal can be blindly followed, and that given above is certain only when the conditions are right and as stated. Fabrication and placing of reinforcement. The amount of reinforcing steel used varies from 50 pounds to 275 pounds per QYD of concrete. The highest figure will be had only in very heavy work and where very heavily reinforced raft foundations are employed, and the lowest only in one-story buildings consisting of walls and roof. A fair average is perhaps 150 pounds per QYD. The cost of fabricating and placing reinforcement will run from 1/3 CT to 1/2 CTS per pound, but the last figure is exceedingly high. 3/4 CT per pound for fabricating and placing is a reasonable labor charge. Contractors frequently have their choice whether the steel shall be fabricated into frames and placed as units or whether it shall be placed in separate bars. For girders and columns, the difference in cost of the two methods is not so very great for steel in place. When the fabrication is done in the field, the unit frames cost considerably more than separate bars to fabricate, but the cost of handling and placing them in the forms is materially less. On an average, the differences balance each other. Where the frames are made up in regular mills, unit frames generally cost less to fabricate and place than do separate bars. The use of unit frames in wall and floor slab reinforcement is generally more expensive than the use of separate bars. The chief gain that comes from the use of unit frames is the gain due to the certainty that the reinforcing bars, stirrups, etc., are all there and are properly spaced and placed. Fabrication. Fabrication includes all the work necessary to prepare the reinforcement ready to place in the forms. It amounts to very little where separate bar types of reinforcement are used. Plain bending and shearing operations comprise the whole task, where the beam or column reinforcement has to be made up into complete frames which can be handled and placed as units. This task is more complex and considerable apparatus is essential to rapid and economical work. For this reason, it is wise usually to contract with some metal working shop to assemble and connect up the various units, and to furnish them ready for installation. In many cases, these unit frame types of reinforcement are patented, and the proprietors contract to fabricate and furnish them complete according to the plans of the engineer or architect. Even where the frame construction is not so controlled, it will be economy generally to have the fabrication done at regular shops where the necessary tools and skilled workmen are had. In any case, the bars should be ordered cut to length at the mill so far as possible. Fig. 207. Rack for storing reinforcing bars. Assuming the fabrication to be done in the field, the mode of procedure will be as follows. Order the bars or rods to be shipped in bundles of corresponding sizes and lengths of pieces, with each bundle tagged with its proper shop number or mark. The bundles should weigh about 200 pounds. This is a load easily handled by 2 men, and so long as possible all handling should be done in the original package. For when once broken, it is very hard to get men to carry a full load. As received, the bars of each size and length should be stored by themselves. For ordinary bars not having long prongs, a rack of the general form shown by Fig. 207 serves the purpose excellently. When a great deal of metal must be kept stored for some time, it is wise to roof over the racks, not only to protect the metal from rain and snow, but to enable the men to work dry-shod in stormy weather. Usually it will pay to have one man whose sole duty it is to receive and check all metal, and to attend to its systematic arrangement on the racks. This same man will also direct the removal of the metal to the shop where it is bent and otherwise worked up, and can, if he is competent, earn his pay many times over in time, saved all along the line in handling and working up the reinforcement. The authors have seen enough time wasted in hauling over and rehandling metal in piles to get at what was wanted to pay for shed, racks, and the wages of a storekeeper several times during a moderate-sized job. In large work, provide the storekeeper with a schedule showing the order in which the metal is wanted for the work, so that he can arrange it in that order, and can check up his receipts from the mills and report missing items in time for the deficit to be made up before some part of the work has to be stopped because of material missing. System in receiving and storing the metal is absolutely essential to rapid and accurate work at the bending and erecting tables. The work done on the metal consists chiefly of bending. The metal can usually be bent cold, but for sizes 1/2 in and upwards some makes of bars require heating. This can be done by laying the bars side by side on the ground and arranging sticks and shavings on top of them in a strip 18 ins to 2 ft, wide across the portion where the bend is to be. Only moderate heating is usually required. Ordinary bending is a simple process and can be done with very simple apparatus. Figures 208, 209 and 210 show frequently used devices, any of which can be made by an ordinary carpenter. For heavy bars 1/2 and 2 ins, the device shown by Fig. 210, with its heavy, swinging beam, is particularly efficient. An example of more elaborate methods is had in the following description of the processes employed in fabricating girder frames and hooped column reinforcement for a large factory building. The building was 500 times 75 ft, with 6 stories and a basement built for the Bush Terminal Co., Brooklyn, NY. In 1905, 3 longitudinal rows of round columns and 2 rows of rectangular wall columns carry heavy longitudinal girders supporting floor slabs with corrugated undersides, as shown by Fig. 211, which also shows the floor slab reinforcement. About 12,000 ids of concrete and 1,000 tons of reinforcing steel were required, hence 167 pounds of steel were required for each cubic yard of concrete. The floors, however, were designed to carry a load of 800 pounds per SQ, FT. The particular feature of interest in this building was the fabrication of all the column and girder reinforcement into unit frames and cylinders in temporary workshops on the site. Fig. 208. Table for bending reinforcing bars. Fig. 209. Table for bending reinforcing bars. Fig. 210. Table for bending reinforcing bars. Fig. 211. Column and floor slab construction for factory building. The circular interior columns varying from 30 ins to 12 ins in diameter were molded in permanent shells of cinder concrete. The shells were made in sections about 30 ins long with walls 1½ ins thick, which were set one on another with mortar joints to form the column mold. In fabricating the shells, the first step was to wind a helix of steel wire on a collapsible mandrel about 4 ft long. The mandrel was set with the axis horizontal and was revolved by hand, the wire being fed on also by hand and under a slight tension. After the wire helix was completed, it was wrapped with a sheet of expanded metal, the longitudinal edges of which lapped a few inches and were tied by wire ties. The expanded metal covering was also wire tied to the helix. Each of these cylinders of expanded metal and wire was 30 ins long and formed the inner mold for making the shell. The outer mold consisted of a sheet metal cylinder in 2 parts assembled and supported by wooden yokes and framework. The 2 molds were assembled on a plank platform, one inside the other, and about a common center. The annular space was then filled with a 1:5 cinder concrete mixed moderately dry so that while it would exude slightly through the expanded metal mesh, it would not waste to any extent. After from 18 to 24 hours, the outer mold was removed for reuse, and the shell was left standing on the molding platform until safe to handle. The larger shells, 30 times 30 times 1½ ins, weighed about 150 pounds each. Fig. 212. Device for bending reinforcing rods, some 2 million pounds. Of plain round steel rods from 1/4 in to 1½ ins in diameter were required for reinforcing the concrete. For the main girders, these rods were cut, bent, and assembled into frames or trusses which were placed as units. The main rods were ordered cut to length, but the stirrup rods were ordered in lengths of 20 ft. And cut to lengths as required. The rods were brought to the work in carload lots and were stored according to lengths and sizes in racks under sheds. Another shed was provided for the steelworkers, who cut and bent the rods and assembled the girder frames ready for the workmen on the building. There were about 50 different patterns of frames required. They were made entirely by hand. For bending large-size rods, heavy compound levers were used. The lighter rods were bent by the device shown in Fig. 212. The assembling of the trusses was accomplished as shown by Fig. 213, using the steel framework of the erection shed as a staging. Across the horizontals of the framework were placed 2 false temporary top cord bars marked to the stirrup spacing of the truss being assembled. On these bars, at the spaces marked, were suspended stirrups with their lower ends hooked. The lower cord bars were then suspended in the stirrup hooks, and the whole assemblage of bars and stirrups was then clamped rigid by the lever bars and intermediate clamps. The loop ends of the stirrups were then bent by special wrenches to the position shown at 2, then closed by hammering to the position shown at 3, and finally they were wire-tied. The process was a simple one, and by adopting a regular routine, the men became so expert that 2 of them could complete many trusses in a working day. The contract price for shaping the steel and assembling it into frames was 1 CT per LB. The cost of the work to the contractor has been stated by Mr. E.P. Goodrich, engineer, Bush Terminal Co., to have been about 3/4 CT per LB. The cost of placing the steel in the building was 1/4 CT per LB. Fig. 213. Sketches showing methods of fabricating girder reinforcing frames. Placing. With unit frame reinforcement, the number, size, and location of the bars have been made certain in the shops where the frames are fabricated, so that the erector has nothing to do but to line and level up the frames in the forms, place such temporary braces as are needed to hold them true, and make the end connections with abutting frames. Such frames are usually provided with chairs to hold the bottom bars up from the form so that little bracing or none is required. With separate bar reinforcement, the erector may either place the reinforcement complete in the form by wire tying the bars to each other, to temporary braces or templates, and to the forms, or he may insert the various pieces of reinforcement in the concrete as the pouring advances, depending on the surrounding concrete, to retain them where inserted. Generally, a combination of both methods is employed. The processes in detail of placing reinforcement are particularized in several places in other sections. They will differ for nearly every job. Here, therefore, general rules only will be given. 1. See that the correct number and size of reinforcing bars, splices, and stirrups are used, and that they are spaced and placed strictly according to the working plans. 2. Bars must be properly braced, supported, and otherwise held in position, so that the pouring of the concrete will not displace them. 3. Splices are the critical parts of column reinforcement. See that the bars butt squarely at the ends and are held by pipe sleeves or wired splice bars. See that the longitudinal rods are straight and vertical. See that the horizontal ties or hooping are tight and accurately spaced. When the reinforcement is built up inside the form, one side is left open for the work. Ordinarily, the column reinforcement will be fabricated into unit frames. Then an opening in the form at the bottom to permit splicing will suffice. 4. Take extreme care that beam and girder reinforcement is placed so that the bottom bars lie well above the bottom board of the mold. Use metal or concrete block chairs for this purpose. 5. See that the end connections and bearings of beam and girder frames are connected up and have the bearings called for by the plans. 6. See that line and level of all bars and of the reinforcement as a whole are accurate. Make particularly certain that expanded metal or other meshwork reinforcement lies smooth and straight. 7. Give all reinforcement a final inspection just previous to pouring the concrete. This is particularly essential where the reinforcement is placed some time in advance of the concreting. Mixing, transporting, and placing concrete. A reinforced concrete building requires from 0, 2 to 0, 5 cu, yd, of concrete per 100 ft, of cubical volume of the building, assuming walls, floors, and roof to be all of concrete. The amount of concrete to be mixed, transported, and placed is therefore large enough even for a building of moderate dimensions to warrant close study of and careful planning for this portion of the work. A few general principles can be set down, but as a rule, there is one best way for each building, and that way must be determined by individual conditions. Mixing concrete for building work has to be of superior quality, so that no chances may be taken either in the process of mixing or with the type of mixer employed. Machine mixing and batch mixers should always be employed. Machine mixing gives generally a more homogeneous and uniform concrete than does hand mixing and is cheaper. Batch mixers are generally superior and more reliable than continuous mixers, where a uniformly well-mixed concrete is required. The capacity of the mixing plant is determined by the amount of concrete to be placed and the time available for placing it. Its division and arrangement is determined by the area of the work and the type and arrangement of the plant for transporting the materials and the mixed concrete. The following general principles may be laid down. Make the most use possible of gravity. It is frequently economy to carry all materials to the top of bins, from which point they can move by gravity down through the mixer to the hoist buckets, and where natural elevations or basement floors below street-level permit gravity handling, they should be taken advantage of. The mixing should be done as near the place of concreting as practicable. In building work, this is the point on the ground which is directly under the forms being filled. It is, of course, impracticable to secure so direct a route as this from mixer to forms, but it can be more or less closely approached. Using two mixers, for example, one at the front and one at the rear of a building cuts down the hall from hoist to forms 1/2. Other ways will suggest themselves upon a little thought. In the matter of the mixing itself, it must never be forgotten that a batch of concrete without cement which goes into a girder or column will result in the failure of that member and possibly the failure of the building. In massive concrete work, a batch without cement will not endanger the stability of the structure, but in column and floor work in buildings, it is certain disaster. Foremanship at the mixer is, therefore, highly important, and a cement man who realizes the responsibility of his task is equally important. Transporting. Transporting the mixed concrete is divided into 3 operations: delivering concrete from mixer to hoist, hoisting, and delivering hoisted concrete to the forms. The delivery from mixer to hoist may be by direct discharge into hoist bucket, by carts or wheelbarrows, or by cars carrying concrete or concrete buckets. Hoisting may be done by platform hoists or elevators, by bucket hoists, or by derricks. Handling from hoist to form may be direct in buckets, by carts or wheelbarrows, or by cars. These several methods can be worked in various combinations, and the following examples of plants show such combinations as are most typical of current practice. In any system of transportation, it is getting the concrete to the hoist, and from hoist to form that eats up the money. Hoisting makes but a small part of the total transportation cost, and moreover, the difference in cost of operation for different hoists is very small. Mr. E. P. Goodrich states that on 3 buildings the actual costs for the hoists installed and removed after the completion of the work were as follows. Platform hoist $330, bucket hoist $465, derrick $225. In figuring on the form of hoist to be adopted, the capability of the hoist for general service has to be kept in mind. Platform hoists and derricks can be used for hoisting form lumber and reinforcing steel as well as for hoisting concrete, while bucket hoists cannot be so used, except where they may be fitted with special carriages for lumber or steel. On the other hand, the bucket hoist is usually the quickest method of hoisting concrete, and it can readily be extended upward as the work progresses. The last is true also of platform hoists. The use of derricks necessitates frequent shifting for high work, or else the building of expensive staging to raise the derrick into a position to command the final height of the building. The probable costs of moving and extending must be allowed for in choosing the hoist to be used. Direct discharge of the mixer into the hoisting bucket is, of course, the ideal manner of transporting the concrete from mixer to hoist, and this can generally be obtained by planning, particularly where bucket hoists or derricks are employed. For platform hoists, direct discharge is impossible. It can be somewhat closely approached, however, where conditions permit car tracks to be laid on the floors being built, so that a car holding a batch of concrete can be run onto the platform, hoisted, and then run to shoveling boards near the forms that are being filled. The successful use of such an arrangement of car tracks is described in Chapter XX, but it was for handling concrete blocks. A direct discharge from hoisting bucket to forms is frequently possible where derricks are used for hoisting, but with bucket and platform hoists, wheeling or carting is necessary, where wheeling or carting has to be done either at the bottom or at the top of the hoist, or at both points. A great factor in the economy of work is the arranging of the operations in cycles. For example, in wheeling concrete to forms from a hopper fed by a bucket hoist, arrange the runways so that each man makes a circuit, passing by the form at one end and by the hopper at the other end, and goes and comes by a different route. The speed gained by avoiding confusion and delay saves many times the additional cost of runways, which is small. In fact, it is economy to employ a few extra men to arrange runways and keep them clean, because of the additional speed thus gained. Good organization effects more economy than special methods of hoisting as far as the labor of handling the concrete is concerned. Fig 214. Bucket hoist for building work, Wallace Lindesmith. Bucket hoists. A bucket hoist construction which has been extensively used in building work on the Pacific coast is shown by the drawings of Figs 214 to 216. Two T-bar guides made in sections connected by fish plates furnish a track for an automatic dumping bucket hoisted and lowered by steel cable from engine on the ground to head sheaves as shown. The sectional construction of the T-bar guides permits the hoist to be any height desired, it being lengthened and shortened by adding and taking out sections. The bucket is dumped automatically at any point desired by means of a tripping device attached to a chute which receives the contents of the bucket and delivers them to carts, wheelbarrows, or other receptacle. The hoist is set outside of the building with the mixer arranged, if possible, to discharge directly into the bucket. By setting the guide frame in a pit or on blocking any height of edge of bucket can be secured. The buckets are ordinarily 13.5 or 20 cu. ft capacity. It is recommended, when greater hoisting capacity is necessary, to use two hoists set side by side and operated by one cable in the same manner as double wheelbarrow cages. As the weight of one bucket counterbalances the weight of the other, the power required for hoisting is reduced. To adapt this hoist to handling form lumber, the bucket is replaced by the lumber carriage shown by Fig 216. This carriage discharges over the head of the mixer and the spring buffer shown by Fig 214 is to take the shock of the rising carriage. This buffer is omitted when concrete only is to be hoisted. In one case, this device has hoisted 520 batches of 12 cu. ft, each to the fourth floor in 8 hours or nearly 19 cu. ids per hour. In another case, 65 trips per hour were averaged to the 5th floor with a 12 coup. FT. Load each trip, this is nearly 30 coup. IDs per hour. With the lumber carriage, 8 men have unloaded 14,000 FT. B. M of 2 times 10 in, stuff from car to the 2nd floor and distributed it in 43 minutes. Or a half coup, YD, combination outfit for concrete and lumber with 40 FT. Of guide track weighs 1,750 pounds. Without the lumber carriage, the outfit weighs 1,600 pounds. This hoist is made by the Wallace Lindismith Co., Los Angeles, Cal, Fig. 215. Wallace Lindismith hoist bucket in discharging position, Fig. 216. Lumber carriage for Wallace Lindismith hoist, Fig. 217. Mixer plant with gravity feed from material bins to hoisting bucket. A popular construction for automatic bucket hoists is that shown by Figs. 217 and 218 by Mr. E. L. Ransom. The bucket is held upright by guides at its front and rear edges. To dump it, a section of the front guide is removed at the desired dumping point, which allows the bucket to overturn as shown. A friction crab hoist operated from the mixer engine runs the bucket. The mixer is located as shown. Figure 218 shows the foot of the hoist set in a pit with the mixer at surface level, but the hoist can be set on the surface and the mixer mounted on a platform. In the latter case, a charging bucket traveling from stockpile up an inclined track to the mixer platform is generally used. A hoist like that illustrated, equipped with a half coup, YD, Ransom mixer will cost about $1,500 and will deliver 15 coup, IDs of concrete per hour. Mr. F. W. Daggett gives the following figures of the cost of operation. Mixing gang, total 1 HR. 1 mixer foreman, also engineer, 25 C, $. 25 one-man charging mixer, 20 C. 21 man running hoist, 20 C. 20. 2 men wheeling sand, 17.5 C. 35 4 men wheeling and shoveling stone, 17.5 C. 71 man helping up runway, 17.5 C. 17.5 2 men carrying cement, 17.5 C. 35 gang placing cement, 1 foreman, 25 C. 25 9 men wheeling concrete, 17.5 C. 1. 57.5 3 men tamping concrete, 17.5 C. 52.5 1 man filling carts, 17.5 C. 17.5 total labor cost per hour $4. 75 fuel, etc. 50. 5. 25 this gives a cost of 35 CTS per coup YD for mixing and placing concrete. In this particular case, the mixer was charged by wheelbarrows. Frequently, the stone and sand bins can be arranged to shoot the materials directly into the charging hopper as shown by Fig. 217. In place of barrows, 2-wheeled carts of the type shown by Fig. 12 can be used. Mention has already been made of operating the charging bucket on an incline from stockpile to mixer. Such arrangements are described in Chapter 49, Fig. 218 Bucket Hoist for Building Work Ransom. In constructing a 9-story store at St. Paul, Min, the concrete was hoisted by continuous bucket elevators. A layout of the construction plant is shown by Fig. 219. In the alley near the center of the north side of the building, the surface grade was about 6 FT, above the 3rd story level. A hopper was constructed at grade and provided with 2 chutes running to the basement. These chutes discharged on opposite sides of a vertical partition separating the sand and stone bins, and by closing either chute at its top by a suitably arranged deflector plate, Either sand or stone could be dumped into the same hopper and chuted to its proper bin. Cement was brought to the work in cars over the tracks shown, and was wheeled from the cars over runways leading to the charging platforms near each mixer. Other runways connecting with these platforms provided for wheeling the sand and stone to the mixers. The runways were placed at the proper height to permit the barrows to be emptied directly into the charging hoppers. 2 Smith mixers were used, located as shown, and each discharged through a chute into one of the bucket elevator boots. There were 2 elevators which were raised 2 stories at a move as the work progressed. Each elevator discharged into a hopper holding 1.5 batches, and from these hoppers the concrete was fed into wheelbarrows and wheeled to the farms. The bucket elevators were carried no higher than the 8th floor. When this floor had been completed, the hoppers were moved down to the 5th floor and the wheelbarrows were taken to platform elevators and carried to the remaining floors and roof. Special 4 FT wheelbarrows were used for handling the concrete. A maximum of 155 ids of concrete was mixed, transported and placed in a 10-hour day with a gang of 28 men. Platform hoists. The common builder's hoist or elevator, operating single or double platforms or cages, needs no special description. The wheelbarrow, cart or car containing the concrete is run onto the platform, hoisted, and then run to the forms. The chief advantage of this device in concrete work is that it will handle all classes of material. Without any change of carriage or arrangement, it can thus be used for handling form lumber and reinforcing steel as well as for handling concrete. Fig. 219. Plan of concrete mixing and handling plant for 9-story building. Derricks. The use of derricks for hoisting in concrete building work is limited by the necessity of supporting them independently of the structure being built. The formwork or the completed concrete work cannot be utilized to carry derricks during construction. For low structures, the derrick can be set on the ground, but for high buildings, a supporting tower or staging is necessary. The arrangement of such false work can be illustrated best by specific examples. In constructing a 7-story factory at Cincinnati, concrete was mixed on the ground and hoisted by a derrick with an ATFT. Boom mounted on a tower 55 ft high. The derrick was located to one side of the building. For the lower floors, the boom swing covered so large an area that the bucket was dumped at various places, but for the upper floors it was found more economical to dump buckets into a hopper from which wheelbarrows were filled. By this plan, less time was consumed in placing the bucket, and no tag rope man was required, as the engineman could swing the boom to a certain point on the wall which would bring the bucket directly over the hopper. A Smith mixer discharged directly into derrick buckets, which rested on a track long enough to hold 2 buckets. The buckets were filled and emptied alternately by shuttling the truck and attaching first one and then the other to the derrick. In constructing an 11-story and basement office building in New York City, a 4-legged tower starting from the bottom of the excavation was erected at about the center of the lot. It was built of timber and extended upward, as the progress of the work demanded, until it overtopped the roof 11 stories above the street. The tower was square in plan, and was divided into stories corresponding approximately to the several stories of the building. A floor was constructed in the tower at each story to be used in storing materials. For hoisting a 75 ft. Boom was swung from each leg of the tower, each boom being operated by a separate engine and having a nominal capacity of 5 tons. The 4 booms covered the whole building area and were kept about 2 stories above the work by being shifted upward as the work progressed. This arrangement of derricks was used to handle the steel, lumber, and concrete, the building being built up around the tower, which was so located that its only interference with the building's structure was in the shape of square holes left in the floor slabs to accommodate the tower legs. In constructing an 8-story warehouse covering some 3 acres of ground in Chicago, the derrick plant shown by Figs, 220 to 222 was installed. Some 7,500 tons of reinforcing steel, 125,000 ids of concrete, and 4 million ft of form lumber had to be handled. Incidentally, it is worth noting that there were about 120 pounds of reinforcing steel and 32 ft/m of form lumber used per cubic yard of concrete. The controlling conditions governing the arrangement and character of the construction plant were as follows. The building, to be built entirely of reinforced concrete, was 135 ft high. Its west front abutted on the river and its south front on the street. At the north end there was some ground available for plant, and along the east front there was a strip about 20 ft wide between the building wall and the main line tracks of a railway. At best, therefore, the area outside of the building and available for plant and storage was limited, while inside the building area the contractor was confronted by the insistence of the architect that an unbroken monolithic construction be obtained as nearly as possible by reducing the floor openings for construction work to a minimum. The sketch plan, Fig. 220, shows the plant designed to meet the conditions. To get the large amount of construction material onto the work, a side track was built along the 20 ft area on the east side of the building, and another was turned into the area at the north end of the building. These side tracks handled all construction materials coming onto the work. Over the first, there were built 2 sets of storage bins for sand and gravel, and all concrete materials brought in carload lots are unloaded at these 2 points, as will be described further on. Lumber for forms and steel for reinforcement shipped in similar manner were taken by the second siding to the lumber yard and steel mill at the north end of the building. Fig. 220. Plan of concrete mixing and handling plant for large warehouse building. The raw materials, after being worked up in the mixer plants and the saw and steel mills, were distributed over the work by an industrial railway. The track system of this railway is shown by the dotted lines. It was located on the basement floor, with ramps leading to the 1 mixer plant and to the saw and steel mill tracks. The 2 main lines of track passed close to or under the elevator and stairway shaft openings in the several floors. This permitted the derrick buckets, lowered and hoisted through the shafts, to be loaded directly from the car tracks. All mixed concrete, forms and reinforcing frames were distributed by this railway to the several shafts, and thence hoisted and placed by the derrick plant. Fig. 221. Derrick for handling concrete for large warehouse building. The derrick plant consisted of 4 derricks arranged as shown by the circles in Fig. 220. The view, Fig. 221, shows the first derrick installed and illustrates the general construction quite clearly. Briefly, the derrick consisted of a vertical steelwork tower 10 ft, square and 85 ft high, within which operated a steel mast 135 ft high and carrying an 80 ft boom connected just above the tower. The mast was pivoted at the bottom and had rollers turning against a horizontal ring inside the tower at the top. It was operated by a bull wheel above the top of the tower, the turning ropes running down inside the mast to the foot block, and thence horizontally to the operating motor. The topping and hoisting lines also followed this route. The top of the tower was guyed by 4 ropes to anchorages in the basement floor. The boom commanded a circle 170 ft in diameter and could lift 150 ft above the base of the mast. The derrick was operated by a 25 HP double-drum electric hoist with a derrick swinging spool. This hoist was set on the basement floor. It will be noted that the guys are below the bull wheel so that the boom has a clear swing through a complete circle. As stated above, 4 of these derricks were employed. Together they did not cover the entire building area, but by the use of a derrick bucket so designed that it could be used as a storage bin for feeding wheelbarrows, it was found possible to keep the number of derricks down to 4. This derrick plant possessed several advantages of importance. In the first place, the derricks would handle all classes of material, concrete, forms, steel frames, equally well, and could be transferred from one class of work to the other with practically no delay. In the second place, for a large area of the building, they handled the material from the basement direct to the place it was to occupy in the work, and did it in one operation. Finally, they permitted the handling and erection of the forms and reinforcement in large units. Thus, a column form would be assembled complete at the mill, moved as a unit by car to the proper shaft, and then hoisted and set in place as a unit by the derrick. Girder forms, floor slab forms, girder and column reinforcing, etc., could be similarly assembled and handled. The derricks occupied only the area of 4 floor panels. The remainder of the area of each floor was left unobstructed for the work to be done. No materials or supplies needed be stored on the floors until they were in perfect condition to accommodate them, and not then, even so far as the prosecution of form erection and concreting were concerned. The sand and gravel for concrete were brought in by bottom or side dump gondola cars from pits located about 30 miles out on the Chicago, Milwaukee and St. Paul Rye. The cars were switched onto the main side track and unloaded under the bins which straddle this track. A receiving hopper, with its top at rail level and long enough to permit 2 cars to be unloaded at once, received the sand or gravel and distributed it through 12 gate openings onto an 18-in horizontal belt conveyor 65 ft long. This conveyor discharged into a second conveyor 133 ft long, which ran up a 22 degrees incline, extending away from the bins, and discharged onto a third conveyor 117 ft long, which doubled back on a 22 degrees incline, reaching to and over the top of the bins. This third conveyor had 2 fixed trippers and an end discharge to distribute its cargo. All 3 conveyors were operated by a 35 HP motor located at the junction of the 2 inclined conveyors, both of which were driven from the same shaft. A chain belt from the idler shaft of the first inclined conveyor to the driving shaft of the horizontal conveyor operated that unit of the plant. This belt was operated as a cross belt by reversing alternate links. No manual labor was required to handle the sand and gravel from the cars to the storage bins. The mixer arrangement at the 2 bins differed. At the No. 1 bins, the mixer was located as shown in Fig. 220, close to the bin. Chutes led directly from the sand and gravel bins to the charging hopper, and the bags of cement were stacked alongside this hopper. The mixer discharged either directly into the bucket of the first derrick or into cars for transportation on the railways. At the No. 2 bins, a belt conveyor took the concrete materials down into the basement to a mixer located close enough to one of the distribution tracks to permit it to discharge directly into the cars. Fig. 222. Special concrete bucket for large warehouse building. The derrick buckets by which the concrete was hoisted and handled to the work were of special construction. A bucket was desired which would serve several distinct purposes. It must first be able to hold a full mixer batch of material, since, with the derrick arrangement, economy in hoisting necessitated hoisting in large units, and also because storage capacity was required of the bucket for wheelbarrow work. The 4 derricks did not command the entire area of a floor. There were corners and other irregular areas outside of the circles covered by the several booms over which the concrete must be distributed by barrows or carts. A bucket large enough to supply the barrows, while a second bucket was being lowered, charged from the mixer and hoisted, was required. In the second place, a bucket was required whose contents could be discharged all at once or in smaller portion at will. Finally, a bucket was desired which could be made to distribute its load along a narrow girder form or in a thin sheet for a floor slab. To meet these requirements, the bucket shown in Fig. 222 was designed. It held 42 cu, ft, or about 1/55 cu, ids, of concrete. It had a hopper bottom terminating in a short rectangular discharge spout closed by a lever operated under cut gate, which could be opened as much or as little as desired. To the underside of the bucket, there was attached a four-leg frame in which the bucket stood when not suspended. Ordinarily, that is within the circles commanded by the derricks, the buckets were discharged suspended and directly into the forms, the character of the discharge gate permitting a thin sheet to be spread for floor slabs or a narrow girder or wall form to be filled without spilling or shock. For wheelbarrow work outside the reach of the derricks, the mode of procedure was as follows. A timber platform about 3 ft high and having room for standing 2 buckets was set just on the edge of the circle commanded by the derrick boom. 2 buckets were used. A full bucket was hoisted and set on the platform with its spout overhanging. This bucket served as a storage bin for feeding the wheelbarrows while the second bucket was being lowered, charged, and hoisted to take its place on the platform and serve in turn as a storage hopper. Placing and ramming. A wet concrete is usually used in building work except on occasions, for exterior wall work and except for pitch roof work, where a wet mixture would run down the slope. Placing and tamping are therefore essentially pouring and puddling operations. The pouring should be done directly from the barrows, carts, or buckets if possible. Dumping onto shoveling boards and shoveling makes an extra operation and increases the cost by the wages of the shoveling gang. Where shoveling boards are necessary, take care that they are placed close to the forms being filled, as it is wasteful of time to carry concrete in shovels, even for a half-dozen paces. Before pouring any concrete, the inside of the forms should be wet down thoroughly with a hose or sprinkler, if a hose stream is not available. The final inspection of forms and reinforcement just before concreting will have made certain that they are ready for the concrete, so far as line and level of forms and presence and proper arrangement of the reinforcement are concerned. But the concrete foreman must watch that no displacement occurs in pouring and puddling, and must make certain particularly that the forms are clean. In pouring columns, it is essential that the operation be continuous to the bottom of the beam or girder. It is also advisable to pour columns several hours ahead of the girders. Puddling should be thorough, as its purpose is to work the concrete closely around the reinforcement and into the angles of the mold, and to work out air bubbles. A tool resembling a broad chisel is one of the best devices for puddling or slicing. In slab and girder construction, the pouring should be continuous from bottom of girder to top of slab. Work should never be stopped off at horizontal planes. As in columns, careful puddling is essential in pouring beams. In slab work, the concrete is best compacted by tamping or rolling. A broad-faced rammer should be used for tamping wet concrete, or a wooden roller covered with sheet steel, weighing about 250 pounds, and having a 30-in face. Theoretically, concreting should be a continuous operation, but practically it cannot be made so. Bonding fresh concrete to concrete that has hardened, though it has been done with great perfection by certain methods as described in chapter Roman 24, must still be held as uncertain. Ordinarily, at least, a plane of weakness exists where the junction is made, and in stopping off work it should be done where these planes of weakness will cause the least harm. Experts are by no means agreed on the best location of these planes, but the following is recognized good practice. Work once started, pouring a column should not be stopped until the column is completed to the bottom of the girder. For beams and girders, stop concrete at center of girder with a vertical face at right angles to the girder or directly over the center of the columns. In beams connecting with girders, stop concrete at center of span or directly over center of connecting girder. Stop always with a vertical face and never with a sloping face, and never with a girder partly filled. For slabs, stop concrete at center of span or directly over middle of supporting girder or beam. Stop always with vertical joints. If for any cause work must be stopped at other points than those stated, the fresh concrete and the hardened concrete must be bonded by one of the methods described in chapter Roman 24. Constructing wall columns for a brick building. The columns, 12 in number, were constructed to strengthen the brick walls of a power station and were built as shown by Figs. 223 and 224, one at a time. The staging, 50 ft. High and 4 times 6 ft. In plan, was erected against the wall which had been shawed. A portion of the wall was cut out and forms erected and the concrete column substituted for the section of wall which was removed. The staging was then moved into position for another column. Fig. 223. Section of rectangular wall column. 2 men with sledge and drill cut out the brick work amounting to about 12 ids for each column in 15 hours at a cost of about 70 CTS per yd, including removal to the street. The cost of moving and re-erecting the scaffolding was $2.94 per each move. The character of the reinforcement is shown by Fig. 223. It was erected as the concreting progressed, the main bars being in sections 15 ft. Long, spliced with and distanced by side bars and cross bolts at the splices. Fig. 224. Staging and forms used in building column shown by Fig. 223. The concrete was hand-mixed in 6 ft. Batches at the foot of the column by 3 men with a 4th turning over and filling the buckets. The buckets, 12 ins, in diameter and 16 ins, high, were hoisted by a pulley line arranged as shown and pulled by a mule driven by a man at $1 per day for the mule and $1.50 for the man, the cost of hoisting being 25 to 40 CTS per yd, depending on the rapidity of the man inside the form. This man tamped the concrete which was emptied from the buckets by a man on the scaffolding. Each batch raised the level in the form 15 ins, and between batches a set of ties for the column rods was placed by the man during the tamping. It took from 1.5 to 2 days to concrete a column of 12 ku. Ids. The concrete was a 1 to 3, 8 to 5, 7 limestone screenings mixture, mixed wet enough to be easily pushed into the forms and worked around the reinforcement. The form construction is shown by Fig. 224. The form for one column required 650 ft. B. M. of lumber, and on an average, each form was used twice. As a matter of fact, the side strips and outside braces were used 3 times, while much of the sheathing was destroyed by being used once. The lumber for shoring cost $23 per m, FTB-M, and the light lumber for forms cost $18 per m, FTB-M. All lumber was yellow pine. All labor was Negro at 15 CTS per hour. Foremen who worked 22.5 CTS per hour. The cost of the several parts of the work compiled from records furnished by Mr. Keith O. Guthrie, engineer in charge, was as follows: concrete, cost per column, cost per ku, YD, lumber for forms $4, $81.00, 40 setting up and removing forms 11, $32.00, 95 cement 10, 17 BBLS at $2, 40 24, 42, 03 sand 5, 87 ids at $0, 95 28 0, 44 stone 8, 75 ids at $1, 35 10, 94 0, 91 mixing and wheeling 15, 73 1, 31 hoisting by mule with driver 4, 80 0, 40 handling bucket on scaffold 2, 93 0, 25 tamping inside column 2, 93 0, 25 painting with grout 3, 89 0, 32 clearing away rubbish 1, 97 0, 16 rigging etc. 2, 64 0, 21 tools 0, 59 0, 05 moving scaffold 2, 94 0, 25 moving mix board and rigging hoist 1, 62 0, 14 total cost of concrete $96, $79 $8, 07 reinforcement, cost per column, cost CTS per LB of bars, iron bars 1,034 pounds, $20, 68 $2, 00 drilling iron bars 1, 44 0, 14 setting iron bars in place 1, 23 0, 12 bolts for splicing and spacing 3, 98 0, 40 wire cross ties at 2 a CTS, LB, 1, 39 0, 14 labor forming 130 cross ties 1, 13 0, 11, total cost of iron and steel $29, 85 $2, 91 summary of cost, per column, per ku, YD. Concrete in place $96, $79 $8, 07 steel in place $29, 85 $2, 49 cutting out and removing brick 8, 36 0, 70 shoring floors and roof labor 5, 87 0, 49 ditto for lumber used 3 times 3, 44 0, 29, total $144, 31 $12, 04 Fig, 225. Girder plan for 6-story building, floor and column construction for 6-story building. The building was 91 times 112 ft, 56 columns spaced 16 ft. A pot carried the girder system shown by Fig. 225, which in turn supported a 3.5 in floor slab. The walls and partitions were not concrete. The following records were kept by the authors. Forms. The column forms were built as shown by Fig. 226. The boards were 1.5 in. Stuff surfaced on 4 sides. The yokes were spaced 2 ft. apart. The 1 times 6 in. Pieces were nailed to the 2x4 with 8D, nails with heads left projecting for easy pulling. The girder forms, Fig. 227, rested on the column forms and on intermediate posts halfway between columns. These intermediate posts were 3x4 with 4x4x12 in. Head blocks nailed to their tops and wedges under their bottoms. The girder molds were 1/2 in. Stuff and to the side pieces were nailed 1x4 in. Cleats, the bottom and side pieces were connected by ×4 in. Lag screws spaced 28 ins, apart. The floor slab stringers were carried on the 1x4 in. Cleats, they were spaced 28 ins, apart and were not nailed. Neither were the 1x6 in. Lagging boards nailed to the stringers. The point to be noted is the design and construction of the forms so that they could be put together and taken apart easily. The lumber required for forms for one floor 91 times 112 ft, or say 10,200 SQ. FT was as follows: lumber for columns FTB, M 9,000 lumber for 10 times 10 in. Beams FTB, M 7,600 lumber for 5 times 10 in. Beams FTB, M 2,700 intermediate 3 times 4 in. Posts FTB, M 1,000 lagging 1 times 6 in. Boards FTB, M 9,000 stringers 3 times 4 ins. FTB, M 4,500 total FTB. M 33,800 Fig. 226. Column form for 6-story building. In round numbers, we can say that 34,000 FTB M of lumber were used for 10,000 SQ FT of floor area, or 4 FTB M per 1 SQ FT. Enough forms were provided to erect 2 complete floors, the forms for the lower floor being removed and erected again for the second floor above, thus using all the lumber 3 times. With carpenters at $3.50 for 8 hours, the forms were framed ready for erection for $4 per M. FTB M. The lumber framed ready to erect cost them. Lumber cost per M. FTB M. $26.00. Labor framing per M. FTB M. $4.00. Total per M. FTB M. $30.00. Fig. 227. Girder and slab forms for 6-story building. Since the lumber was used 3 times, $30 divided by 3 equals $10 is the charge against each 1,000 FT. B. M. Needed to encase the concrete on a floor. There were nearly 34,000 FT. B. M. per floor, hence the cost of lumber ready for erection was $340 per floor. There were, as shown below, 200 ids of concrete per floor, so that the cost was $340 divided by 200 equals $1. 70 per yd of concrete for forms ready for erection. It took a gang of 5 men 7 days to tear down and carry up the forms for 1 floor, hence 5 times $2 times 7 equals $70 per floor, or practically $2 per M. FTB M, or $0, 35 per yd of concrete for taking down and carrying forms 2 stories. It took a gang of 10 carpenters 7 days to erect these forms, which at $3.50 per day was $245 per floor, or $7 per M. FTB M, or $1.20 per yd of concrete. The amount of concrete per floor was as follows: floor slab 3½ ins, thick 10,200 SQ, FT, 110 ids, beams 10 times 10 ins, 40 ids, beams 5 times 10 ins, 20 ids, columns 15 times 15 ins. Average 30 ids. A total concrete per floor 200 ids. A concrete mixer, a hoist, and a gang of 14 men mixed and placed the concrete for a floor in 7 days. At $2 per day for labor, this gives 14 times 7 times $2 equals $196, or say $1 per coup. YD. For mixing and placing the concrete. Reinforcement. In each of the 10 times 10 in. Beams there were 4 1 in, round rods, 2 straight and 2 bent, and stirrups of times 1 in. Straps spaced 5 ins, apart at columns and 15 ins, at the center, in each 5 times 10 in. Beam there was half as much steel as in a 10 times 10 in. Beam. The floor slab reinforcement consisted of a quarter in. Rods spaced 5 ins, apart, and 2 cross rods in 7 ft. Panel. The column reinforcement consisted of 4 rods averaging 1 in diameter. In round numbers, the amount of steel required for each floor was therefore as follows: pounds. Steel rods in 10 times 10 in. Beams 16,200 pounds. Steel rods in 5 times 10 in. Beams 4,000 pounds. Stirrups in beams 3,000 pounds. Steel rods in floor slabs 3,800 pounds. Steel rods in columns 1,400. Total pounds steel per floor 28,400. This is equivalent to 142 pounds of steel per cubic yard of concrete, or about 1% of the total volume of reinforced concrete was steel. The steel in the beams was about 3%. It required a gang of 5 laborers 7 days at $2.25 per day to bend and place the steel for each floor, or $86 for labor on 28,400 pounds of steel. This is equivalent to 0.3 CT per LB or 45 CTS per coup YD of concrete. Summary of costs. Summarizing the figures given, we have the following cost per cubic yard of concrete in floors and columns per coup YD: 142 pounds. Steel at 2.5 CTS. $3. 55 1 BBL. Cement 2, 51 coup YD. Gravel 1, 10.5 coup YD. Sand 0. 55 170 FT BM. Lumber ready to erect at $10, 1/3 of $30 1. 70 170 FT BM. Torn down at $2 0. 35 170 FT BM. Erected by carpenters at $7 1. 20 mixing and placing concrete 1. 0 shaping and placing steel 0. 45 superintendents 0. 25, total $12. 65 wall and roof construction for 1-story car barn. The barn was 50 FT, wide and 190 FT, long, divided into 3 rooms by 2 transverse partitions and covered with a 4-in, roof having a pitch of a 1/2 in per foot. The main walls were 12 ins thick and the partition walls 10 ins thick. The main room 110 FT long had 4 car tracks its whole length with pits under each and a 6-in reinforced concrete floor slab between. The floor girders, 1 under each rail, were 12 ins square, each reinforced by 3 1/3 in rods, and were carried on 12 times 12 in pillars. The total yardage of concrete was 874 cu. Ids, divided as follows: walls and foundations cu. Ids, 614 pillars and girders in track pits cu. Ids, 44 reinforced floors cu. Ids, 55 roof 160 total cu. Ids, 873 a 1 to 2 a 5 concrete was used for floors, roofs, and girders, and a 1 to 3 to 6 concrete for foundations and walls. There were 26.5 tons of reinforcing steel, or 61 pounds, per coup YD, or 0.45% of the volume of the concrete was steel. The wages paid were: foreman $2.50, blacksmith $2, engineer $1, 75 laborers $1, 50 two-horse team and driver $3, 67 one-horse team and driver $2, 92 carpenter $2. 25 carpenters worked 9 hours, all others 10 hours. Forms, carpenters framed and erected forms, and common laborers under foreman carpenter took them down. Lagging was all 2 in. Stuff and uprights 3 times 4 in. Stuff, props for roof forms were 18 ft. Round timber procured on the job, they were 6 ins. In diameter at the top and cost 50 CTS. Each 91 being used. These props are not included in the lumber listed below, but their cost is included in the costs given. No record was kept of the number of times the lumber was used, but as 54,643 ft. B. M. were bought, and about twice this much would be needed to enclose the concrete. If used only once, we will assume that all lumber was used twice. Including the props, there were about 60,000 ft. B. M. or 70 ft. B. M. per QYD of concrete. The cost of the lumber was $1,520. 86, and the cost of labor on the forms was $1,660. 60, so that the cost of forms was item per QYD per M FT per SQ FT lumber $1, $74 $13 50 $0 038 labor 1 90 14 070 041 total $3 64 $27 $57 $0 079. If the lumber had been used only once, the cost per cubic yard would have been $5. 38, and per M FT B M $41 07 concrete. A railway track was run the full length of the building upon what was eventually the 4th track of the car barn, and a ransom mixer was set up as close to the track as possible, allowing a platform to be built between it and the track. Cars were brought up to this platform, and the materials handled by wheelbarrows direct from cars to mixer. Both platform and mixer were moved twice as the work progressed. The concrete was taken by wheelbarrows on runways to the side walls. For the roof, it was hoisted by a horse by means of a mast having an arm with a 3/4 swing. The barrows were hoisted direct using a hook for the wheel and 2 rings for the handles. The cost of the concrete for materials was 1 BBL. Cement at $1. 21 per QYD. $1 33 3/4 ton sand at 75 CTS per QYD 0 55 aggregate per QYD 0 88 61 pounds steel at 1 9 CTS per QYD 1 15 lumber 70 FT BM at $27 per QYD 1 74 total per QYD $5 65. The cost of labor per cubic yard was forms per QYD $1 900 mixing per QYD 0 210 placing per QYD 0 310 finishing per QYD 0 143 handling cement per QYD 0 017 handling sand per QYD 0 104 handling steel per QYD 0 270 handling aggregate per QYD 0 222 coal at $4 25 per ton per QYD 0 010 foreman per QYD 0 133 teams and laying pipeline per QYD 0 087 total per QYD $3 406. Summarizing, we have the following cost per cubic yard. Concrete materials per QYD $2 76 labor mixing and placing concrete 1 01 forms materials and labor 3 64 reinforcement materials and labor 1 42 fuel foreman and pipeline labor 0 $23 total per coup. YD, $9.06. The cost for handling steel, making stirrups, welding, etc. was $8.90 per ton or 0.45 CT per LB. Constructing wall columns for a one-story machine shop. The building was 53 times 600 FT. Each side wall consisted of 40 columns of channel section carried on footings of channel section somewhat heavier than that of the column. The columns were spaced 15 FT on centers, and each was 7.5 FT wide, so that there were 7.5 FT spaces between columns, which were filled with 3-in curtain walls extending 7.5 FT above the floor. Figures 228 and 229 show the column and footing construction. Each column contained 125 cu FT, or 463 cu IDs of 1 to 3 to 5 1-in crushed slag concrete above the footing, and the costs given here relate only to the columns above footings. In the 80 columns there were 370 cu IDs of concrete forms. A column form is shown by Fig. 230. It contains approximately 1,000 FT, B, M of lumber. 10 of these forms were used, so that 10,000 FT, B, M of form lumber were required for 370 cu IDs of concrete, or 27 FT, B, M per cu YD of concrete. Each column had a superficial area excluding ends of about 420 SQ FT, so that 420 times 80 equals 33,600 SQ FT was the superficial area of all the columns, and 10,000 FT, B, M, divided by 33,600 SQ FT equals 0.3 FT, B, M, or say 1/3 FT, B, M, of form lumber was used per square foot of concrete enclosed. The cost of the forms per 1,000 FT, B, M, and therefore per form, was lumber 1,000 FT, B, M at $31, 75 $31, 75 labor constructing form 16, 39 total per 1,000 FT, B, M, $48, 14 Fig. 228. Channel section wall column for factory building. This gives us a cost per cubic yard of concrete for materials and labor constructing forms of $480 divided by 370 equals $1.30. And per square foot of outside wall area of $480 divided by 146 times 80 equals 4.1 CTS. The erection and taking down of the forms, owing to the weight of some of the pieces, was done by means of special derricks. The footings were brought to within a half-in of grade, and a tenon form of the exact shape of the channel section of the column was placed on top and filled with grout to a depth of 1 in. These tenons served as guides in setting the column forms and proved to be much quicker and more accurate than points. Fig. 229. Footing for wall column shown by Fig. 228. The forms were assembled on the ground and erected by a 35 FT A-frame derrick mounted on wheels. The construction is shown by Fig. 231. This derrick had a capacity of about 4 tons and carried a ransom friction crab hoist driven by a 5 H.P. Mates and Weiss kerosene oil engine. It was the practice to set a number of forms before filling any. This enabled the carpenter gang to be plumbing up the first form while the erecting gang were setting others. The forms had to be very securely guyed and braced to withstand the impact of the falling concrete. Very little trouble was had in keeping them well lined up. Fig. 230. Form for molding wall column shown by Fig. 228. 2 gangs were employed in assembling forms, and a portion of the men in each gang also shaped and placed the reinforcement and placed and tamped the concrete in the form so that no exact division of labor is possible. The organization of these gangs and the wages paid were as follows. Derrick Gang, 1 foreman at 36 CTS, per hour $3. 94 1 crabman at 30 CTS, per hour 2. 72 topmen at 27 CTS, per hour 4. 86 2 bottom men at 23 CTS, per hour 4. 14 total per 9-hour day $15. 64 assembling gang 1 boss carpenter at 47 CTS, per hour $4. 23 2 carpenters at 36 CTS, per hour 6. 48 2 carpenters at 30 CTS, per hour 5. 40 2 carpenters helpers at 25 CTS, per hour 4. 54 men forming and placing reinforcing steel and rethreading bolts at 23 CTS, per hour 8. 28 total per 9-hour day $28. 89 grand total $44. 53 these gangs assembled and erected the molds and concreted 80 columns in 22 working days, including 2 days lost on account of cold weather, so that 4 columns were completed per day of 9 hours. We can subdivide the cost as follows. Item, per coup, YD. Erecting forms and concreting $0. 81 assembling forms and reinforcement 1. 56 total $2. 37 charging the 4 men placing reinforcement and rethreading bolts to forming and placing reinforcement alone. We can figure the cost of fabrication and erection of reinforcement very closely. There were 160 pounds of reinforcing steel in each column, hence $8. 28 divided by 160 times 4 equals 1. 3 CTS was the cost per pound of forming and placing it. This includes handling. The stripping of the forms was carried on by another gang using a derrick similar to the first one described, except it could be of lighter construction as it had to handle only the separate parts of each form and not the forms assembled. The derrick shown in Fig. 232 was a 33 FT, A-frame with wheels at the bottom of each leg. It had a friction crab hoist driven by an electric motor, both of which were fastened to the derrick frame between the shear legs. Fig. 231. Derrick for erecting wall column forms shown by Fig. 230. The operation of stripping required only 4 men and the crabman. The outside flat panel was removed first and left leaning up against the concrete while the inside trough-shaped panel was pried loose and lowered onto the ground with its inside face uppermost. The side panels, being comparatively light, were stripped without the use of the derrick, and these panels were assembled on the ground with the inside piece. The derrick then picked up the outside panel again and placed it in its proper place. After the bolts were put in place, the assembled form was moved on rollers to another point in the line of columns where it was again erected. The arrangement of derricks for erecting and stripping forms is shown in Fig. 233. The gang stripping forms was made up as follows. 1 foreman at 30 CTS, per hour $2. 71 crabmen at 27 CTS, per hour 2. 43 1 topmen at 27 CTS, per hour 2. 43 2 bottom men at 23 CTS, per hour 4. 14 total per 9-hour day $11. 70 Fig. 232. Derrick for stripping wall column forms shown by Fig. 230. This gang of 5 men stripped 4 columns containing 52 ids of concrete each day so that the cost of stripping was $11. 70 divided by 52 equals 62. 7 CTS. per cu, YD, concrete. The concrete was mixed in a No. 2 ransom mixer and delivered to the work in ransom concrete carts. These carts were pushed along a runway which terminated in a slight incline under the derrick, so that their contents could be emptied into the derrick buckets. The concrete was hoisted in an ATFT, bottom dump bucket, using the derrick described above. It was necessary to stir up the concrete thoroughly with long-handled slices as it was being deposited in order to prevent segregation. This expedient combined with a wet mixture and tight molds was found to overcome this difficulty very effectually. The gang mixing and wheeling concrete was made up as follows: one mixer foreman and engineer at 27 CTS per hour $2. 43 laborers charging mixer at 18 CTS per hour 6. 48 laborers wheeling concrete at 18 CTS per hour 6. 48. Total per 9-hour day $15. 39 This gang mixed and wheeled concrete for 4 columns or 18, 52 cu. IDS. Hence the cost per cubic yard was 82, 6 CTS, with cement at $1, 60 per BBL, sand at $1 per cu, YD, and slag at $1, 10 per cu, YD. The cost of materials per cubic yard of concrete was $3, Fig. 233. Arrangement of derricks for erecting and stripping forms. Summarizing the above figures, we have the following cost per cubic yard of concrete in place. Item, per cu, YD, concrete materials $3, 00 reinforcing steel 0, 73 forms lumber and framing 1, 30 forms erecting and concreting 0, 81 forms assembling and reinforcement 1, 56 forms stripping 0, 63 mixing and wheeling concrete 0, 83 total $8, 86 constructing one-story walls with movable forms and gallows frames. In constructing the walls for an 85 times 30 FT. Factory building at Old Bridge, NJ. Mr. A.E. Budell made use of movable forms and gallows frames to construct the curtain walls and columns in one piece. Each side wall was built its full height in successive 50 FT. Lengths by depositing the concrete between 2 forms which were moved upward as the concreting progressed. Fig. 234 indicates the mode of procedure. The form was raised and lowered by means of 2 gallows frames fitted with blocks and tackle. A steel cable with a trolley affixed, extending from one frame to the other, provided a convenient mode of hoisting material to the form, and the gallows frames took the place of ladders for climbing onto the structure. No scaffolding whatever was used, and only one man was required overhead to dump the buckets and tamp the concrete into place. Fig. 234. Gallows frames supporting wall form panels for one-story building. Fig. 235. Details of wall form panel for one-story building. The 2 walls were carried up simultaneously, one form being shifted into place and filled, while the other was left in place until the concrete was sufficiently hard. It was found that 18 hours was amply sufficient to allow the concrete to set hard, after which the form was removed and lifted to a higher level. Thus the men were continuously engaged in lifting and filling first one form and then the other. The average length of time required to remove, raise and fill one form was 5 to 6 hours. Thus, 2 forms could be raised and filled almost every day. The construction of the forms and of the gallows frames is shown by Figs. 234 and 235. The cost of one set of forms and gallows frames was as follows: 320 FT, B, M of 2 times 10 in, times 10 FT, plank at $34 $10, 88 150 ft BM of 3 times 4 in, times 16 ft, spruce at $33.5, 25 135 a half ft BM, 1 times 8 in, yellow pine at $30.4, 08 335 ft BM, 1 a times 6 in, spruce at $33.11, 054 post 6 times 8 in, times 26 ft, equals 416 ft BM at $30.12, 48 4 sills 6 times 8 ins, times 16 ft, 2 caps 6 times 6 ins, times 9 ft, 4 braces 6 times 6 ins, times 16 ft, equals 490 ft BM at $30, 14, 73 pieces 3 times 10 ins, times 20 ft, equals 150 ft BM at $30 for 50, total lumber 1996, 5 ft BM. $62, 94 accessories, bolts for trussing 675 pounds, at 2 CTS. $13, 50 iron guy rope and clips 700 blocks 800 coil of 3/4 in, rope 2800, total accessories $56, 50 labor making 1 outfit, 2 men 8 days at $2, 75 per 9 HRS, $44, 00, grand total $163. 44. This sum covered the cost of forms for one side of the building 85 ft, long and containing 150 ids of concrete, hence the cost of forms was in round figures $1, 10 per yd of concrete. Each cubic yard of concrete required 1997 divided by 150 equals 13 1/3 ft, BM. Of form lumber. The concrete was a 1 to 2 a 4 a half mixture. A careful record for 15 days showed an average of 2.8 ids of concrete placed in 6 hours by a gang of 3 men. From this we can figure the cost of concrete in place to be about as follows: 2.8 ids, concrete at $3 for materials $8, 46. 3 men 6 hours at 15 CTS. 5. 67 1 foreman 6 hours at $4 per day 2.00 total per yd, $16, 07. Thus the cost of concrete in place was $16, 07 divided by 2.8 equals $5, 73 per yd. Adding the cost of forms, we get $5, 73 plus $1, 10 equals $6, 83 per yd. As the cost for labor and materials in constructing forms and mixing and placing concrete. Fig. 236. Detail of column and cantilever column footing for 4-story garage. Offsets and molding decorations were easily made, although they were quite numerous on the building in question, at least more so than would ordinarily be the case in mill building construction. The offset of 1 ft at every column was made very readily by sliding wooden shoulder pieces into place on the inner face of the form, which pieces in turn received 2 in. Faced planking, the latter being slid into place from above. Thus the entire system was collapsible, and small alterations were easily made whenever the form was shifted. Flat surfaces or offsets could be obtained at will by either removing or setting in the shoulder pieces. Molding effects were made on the front face of the wall by tacking molding strips to the form wherever necessary. The entire work was done with common labor, and the finished building presented a smooth, homogeneous surface which required very little dressing. Fig. 237. Details of cantilever girders for mezzanine floor for four-story garage. Floor and roof construction for four-story garage. The building was 53 times 200 FT and 4 stories high, with provision for 2 additional stories in the design of footings and columns. 2 rows of wall columns connected by transverse girders carrying the floor and roof slabs made a comparatively simple construction, except for a mezzanine floor carried on cantilever beams, and except for the use of cantilever footings. These 2 special details are shown by Figs 236 and 237. The amount of concrete in the building was 1,910 cu. Ids, distributed as follows. Cu. Ids. Footings, reinforced 190 columns, reinforced 450 floors and roof, reinforced 1,100 floor on ground, not reinforced 170. Total 1,910. The amount of reinforcing metal used was 237 tons, distributed as follows. Item. Tons. Pounds per cu, YD. Footings 442 columns 2090 floors and roof 175 318. A total and average 237 This is equivalent to 2%. Of steel in 1910, 170 equals 1,740 cu. Ids. Forms. The total area of concrete covered by forms, 1,740 cu. Ids. Was 94,000 SQ/FT, distributed as follows. Footings SQ/FT, 4,000 columns SQ/FT, 20,000 floors and girders SQ/FT, 70,000 total SQ/FT, 94,000 for the work, 50,000 FT. B. M of old lumber was used and 170,000 FT. B. M of new lumber was bought, the cost being as follows. 50 M FT B M at $13 per M. $650 170 M FT B M at $26 per M. 4,420 220 M FT B M at $23 $5,070. This is equivalent to 126 FT. B. M per cu YD of concrete. New forms were made for each floor except the sides of the girder molds, which were reused so far as they would fit, but the roof forms were made from lumber used for the floors. In all, no more than 20% of the form lumber was used a second time. In round figures, new lumber was required for 80,000 SQ FT of concrete. This gives a cost for lumber of 6.4 CTS per SQ FT. The construction of the column and floor forms is shown by Fig. 238, a force of 15 carpenters at $4.40 per day under a foreman at $35 per week erected and tore down forms. The carrying was done by laborers at $1.70 per day working under a foreman at $35 per week. Carpenters worked an 8-hour and laborers a 10-hour day. Forms for one floor were framed and erected in 8 to 10 days. The cost of forms for 1,740 cu. Ids and 80,000 SQ FT of concrete and per M FT B M was as follows. Item per cu YD per SQ FT per M FT. Lumber $2.90, $0.64 $23, 00 framing, erecting and removing, 2,000, 05715, 67 handling lumber 1, 10.8, 70, total $6, $000, $121.47, 37 Fig. 238. Column and floor forms for 4-story garage. The lumber had a considerable salvage value which is not allowed for in the above figures. Concrete. The concrete was a Portland cement 3/4 in. Trap rock mixture, mixed wet in 2 Chicago improved cube mixers equipped with charging buckets. The mixers were located on the ground floor, one at the rear and one at the front of the building, both discharging directly to a hoist. With a gang of 30 men at $1, 70 per 10-hour day under a foreman at $35 per week, a floor was concreted in 2 days, the columns being concreted the first day and the floor being concreted the second day. The labor cost for mixing and placing concrete and for fabricating and setting reinforcement was as follows. Item, per coup, YD. Mixing and placing concrete $1, 95 erecting and setting steel $2.05, total $4. 00 The cost of concreting includes the cost of granolithic surface for the floor slabs. The girder reinforcement was made up into unit frames and the frames were set as a unit, horses set over the molds being used to suspend and lower them into place. The cost of $2.05 per coup, YD, is equivalent to 3/4 CT per LB. Summarizing, we have the following cost for materials and labor on forms and for labor mixing and placing concrete and reinforcement. Per coup, YD. Lumber for forms $2, 90 labor on forms 3, 10 labor on concrete 1, 95 labor on steel 2.05, total $10. 00 This $10 total does not include the cost of the concrete nor of the steel. Chapter 50. This chapter deals exclusively with the methods and cost of molding and erecting separately molded wall blocks, girders, columns, and slabs. The structural advantages and disadvantages of this type of construction as compared with monolithic construction will not be considered. The data given in succeeding paragraphs show how separate piecework has been done and what it has actually cost to do it in a number of instances. Column, girder, and slab construction. European engineers have developed several styles of open web or hollow girder and column shapes, but in America, solid columns and girders have been used except in the comparatively few cases where one of the European constructions has been introduced by its American agents. Warehouses, Brooklyn, N.Y. In constructing a series of warehouses in Brooklyn, N.Y., the columns and girders were molded in forms on the ground. For molding the columns, forms consisting of 2 side pieces and 1 bottom piece were used, saving 25% in the amount of lumber required for a column form and doing away with yokes and bolts, since only simple braces were required to hold the side forms in place. It was found that the side forms could readily be removed in 24 to 48 hours, thus considerably reducing the time that a considerable portion of the form lumber was tied up. It was figured by Mr. E. P. Goodrich, the engineer in charge of this work, that this possible reuse of form lumber reduced the amount required another 50%, as compared with molding in place. Girders were molded like columns in 3-sided forms. The saving in form work was somewhat less than in the case of columns, but it was material. In general, Mr. Goodrich states, the cost of hoisting and placing molded concrete members is higher per yard than when the concrete is placed wet. That is in mass before it is hardened. Fig. 239, sketch showing forms and reinforcement for Vicentini girder. Factory Reading Pa. In constructing a factory at Reading Pa, an open or lattice web type of girder invented by Mr. Franz Vicentini and extensively used in Austria was adopted. Columns were molded in place in the usual manner with bracket tops to form girder seats. The girders were reinforced with 3 trusses made up of top and bottom cord rods connected by diagonal web rods. 1 truss was located at the center of the beam, and 1 at each side. The method of molding was as follows. The trusses were made by cutting the cord rods to length and threading the web diagonals and verticals onto them. To permit threading, the web pieces were bent. When rods were used, with an eye at each end. When straps were used, the ends were punched with holes. The work was very simple and was done mostly by boys in the machine shop of the company for which the building was being erected. The girders were molded 2 at a time in forms constructed as shown by the sketch. Fig. 239. A form consisted of a center board, 2 side boards, 2 end pieces, and the proper number of cast iron cores, all clamped together by 3 yokes. Triangular cast iron plates were screwed to the bottom boards for spaces. The side, center, and end boards were then set up and the end clamps were placed. The cast iron hollow cores, were then set over the spaces, and the form was ready for pouring. A layer of concrete was placed in the bottom of the mold, and the first side truss was placed. The concrete was then brought halfway up, and the middle truss was placed. Concreting was then continued up to the plane of the second side truss, which was placed and covered. Cores and forms were all cleaned and greased each time they were used. The cores were removed first by means of a lever device, and generally within 3 or 4 hours after the concrete was placed. The remainder of the form was taken down in 2 to 4 days and the beam removed. Kiln House, New Village, N.J. In constructing a kiln house for a cement works, 1-story columns with bracket tops and 50 ft. Span roof girders were molded on the ground and erected as single pieces. The columns, by rough calculation, averaged about 2 ids of concrete and 675 pounds of reinforcement each, or about 337 pounds of steel per cubic yard. The girders averaged, by similar calculation, 5 ids of concrete and 2,260 pounds of steel, or 452 pounds per cubic yard of concrete. The average weight of columns was thus not far from 41.3 tons, and of girders fully 11 tons. Fig. 240. Arrangement for molding 10 single bracket columns. Several combinations of arrangements were used for molding the columns and girders. For wall columns having 1 bracket, the arrangement shown by Fig. 240 was adopted. The concrete slab molding platform was covered with paper, and on this the 2 outside and the middle columns were cast in forms. When those columns had set, the forms were removed, the intervening spaces were papered, and the 2 remaining columns were cast. 10 columns, 5 sets of 2 columns in line, were cast on each base. The remaining columns were cast in combination with girders as shown by Fig. 241. The 2 outside lines of columns, 1, were molded in forms, allowed to stand until set and then stripped. Using a column surmounted by a shallow side form for one side and a full-depth side form for the other side, molds were fashioned for the 2 outside girders, nos. 2 and 3. 1 full-depth side form and the side of girder no. 2 formed the mold for girder no. 4. Girder no. 5 was then molded between girders no. 3 and no. 4. Fig. 241. Arrangement for molding 4 4-bracket columns and 4 roof girders. Fig. 242. Forms for 50 ft roof girders. The construction of the girder forms is shown by Fig. 242. This drawing shows one of the 4 main sections making up a complete form. A full-size form of this construction contained about 1,100 ft/b/m of lumber, and 3 were built, so that 3,300 ft/b/m m of form lumber were used for molding 20 girders or 33 ft. b m per cubic yard of concrete. A full-size column form contained about 225 ft. b m of lumber and 8 were constructed so that 1,800 ft. b m of form lumber were used for molding 56 columns or about 16 ft. b m per cubic yard of concrete. The following was the cost of erecting a full column form including lining, plumbing, bracing, and yoking, but excluding lumber and original construction. 1 carpenter 3 HRS at $0, 25 $0. 751 helper 3 HRS at $0, 175 0. 525 1 helper 1 HR at $0, 175 0. 175 1 to 5 boss carpenter 3 HRS at $0, 30 0. 180 total $1. 630 this gives a cost of $7. 25 per m ft b m for erecting column forms. The cost of erecting a full-size girder form including lining, plumbing, bracing, and setting 6 bolts was as follows. 2 carpenters 5 HRS at $0, 25 $2. 52 helpers 5 HRS at $0, 175 1. 75 2 laborers a half HR at $0, 15 0. 15 a quarter boss carpenter at $0, 30 0. 375 total $4. 775 this gives a cost of $4. 35 per m ft b m for erecting girder forms. The reinforcement was erected inside the forms for both columns and girders. The cost of erection for 1 column was 2 laborers 4 HRS at $0, 15 $1. 21 third foreman 4 HRS at $0, 225 0. 30 total $1. 50 this gives a cost of about 0, 22 CTS. Per pound for erecting column reinforcement including the bending of the horizontal ties or hoops. The girder reinforcement was erected by piecework at a cost of $1. 80 per girder or about 0.08 CT per pound. The concrete used was a 1:6 mixture of Portland cement and crusher-run stone, all passing a half in sieve and 10%, passing a 200 mesh sieve. No trouble was had in handling this fine aggregate. It was mixed in a ransom mixer, elevated so as to deliver the batches into cars on a standard gauge track. This track ran between the base slabs on which the molding was done. Each car held about 3 ids and discharged through a side gate and spout directly into the forms, the mixture being made so wet that it would flow readily. The company used its own cement and stone for concrete and charged up the cement at $1 per barrel and the stone at 60 CTS per cubic yard. At these prices, and assuming that a cubic yard of concrete of the mixture above described would contain about 1.25 bbl of cement and 1.5 yd of stone, we have the following cost of materials per cubic yard of concrete. 1.25 bbls of cement at $1, 25 1.5 ids, stone at $0, 60 0, 90, total $2. 15 the actual cost of mixing the concrete and delivering it to the cars was as follows. Item, per yd, 1 foreman at 20 CTS per hour $0, 0300 3 men shoveling stone at 15 CTS per hour 0675 3 men filling hopper at 15 CTS per hour 0675 1 man bringing cement at 18 CTS per hour 0.0225 one-man dumping cement at 15 CTS per hour 0.0225 9 HP at a half CT per HP hour 0.0450 superintendents repairs etc 0.0270 total $0. 28.20 the cost of hauling the concrete from mixer to forms ran about 2.7 CTS per cubic yard, so that we have a cost for concrete in place of concrete materials per QYD $2. 150 mixing concrete per QYD 0. 281 hauling concrete per QYD 0. 0.27 total cost per QYD $2. 458 the cost then per column or girder molded, assuming that it was necessary to erect a full form, was about as follows. Columns 2 Q. IDS. Concrete at $2. $46 for 92,675 pounds. Steel at 2.5 CTS. 1677 erecting steel at 0.22 CT per LB 1. 50 erecting forms 1.63 total $24. 82 girders 5 Q. IDS concrete at $2. $46 $12. 32,260 pounds. Steel at 2.5 CTS 56. 50 erecting steel at 0.08 CT per LB 1. 80 erecting forms 4.77 total $75. 37 Fig. 243. View showing method of hoisting molded columns. These figures give a unit cost of $12, 41 per QYD for molded columns and of $15, 0.7 per QYD. For molded girders, the columns were erected by a Browning locomotive crane which lifted and carried them to the work and appended them into place. To facilitate lifting the columns from the molding bed, a 1.5 in pipe 8 ins long was cast into both ends. Pins inserted into these sockets provided hitches for the tackle. The column was lifted off the molding bed and blocked up, then iron clamps were attached, one at each end, as shown by Fig. 243. A gang of 1 foreman and 14 men erected from 5 to 7, or an average of 6 columns per 10-hour day. The average wages of the erecting gang were 21 CTS per hour. The cost then of column erection was 14 times $2. 10 divided by 6 equals $5. 25 per column or $2. 63 per QYD of concrete. Fig. 244. Sketch showing sling for erecting 50 FT. Roof girders. The roof girders had 1 in. Eye bolts 24 ins. Long cast into them vertically about 4 FT. From the ends, they were lifted off the molding bed by tackle by the locomotive crane to these eye bolts and blocked up to permit the adjustment of the sling. This sling is shown by the sketch, Fig. 244, and as will be observed acts as a truss. At first it was used without the vertical, but the cantilever action of the unsupported ends caused cracks. The girders were loaded onto cars by the locomotive crane and taken to the work, where they were hoisted and placed by a gin pole. The girder erecting gang consisted of 1 foreman and 14 men working a 10-hour day at 21 CTS per hour. This gang erected 4 girders per day at a cost of 15 times $2. 10 divided by 4 equals $7. 87 per girder or $1. 57 per QYD of concrete. The cost of girders and columns in place was thus about as follows. Columns per unit per QYD, molding $25, $0012, 50 erecting 5, 25 2, 63, totals $30. 25 $15, 13 girders, molding $75, 00 $15, 00 erecting 7, $87 57 totals $82 $87 $16 57 fig 245 View showing method of handling roof slabs. In this same building, the roof was composed of 12 times 6 1/4 ft times 4 in. Slabs molded in tiers. A slab was molded, and when hard was carpeted with paper, and the form moved up, and a second slab molded on top of the first. This operation was repeated until a tier of slabs had been molded. By molding each slab with a 3 in. Overlap, as shown by Fig. 245, they could be easily separated by lifting on hooks inserted under the overhanging ends. Each slab contained 925 cu yd of concrete and about 116 3/4 pounds of reinforcement. The cost of molding one roof slab, including materials, forms, and labor, was as follows. Materials per slab per cu yd 1 bbl. Cement at $1 $1 $0.001 $0.81 0.6 tons. Stone at $0 60 636 687 116 3/4 pounds. Steel at 2 1/4 cts. 2 647 2 862 total $4 283 $4 630 forms lumber and making $0 104 $0 112.92 sq ft paper at 33 1/3 cts per 500 sq ft 0 0.55 0.59 labor erecting and removing 56.25 608 total $0 72.15 $0 779 mixing hauling and placing mixing $0 222 $0 240 hauling 0.25 0.27 placing concrete and steel 170 183 total $0 417 $0 450 general expenses housing and heating $0 700 $0 757 superintendents power etc 10% 612 661 total $1 312 $1 418 grand totals $6 73.35 $7 277 The roof slabs were raised from the casting beds by means of the locomotive crane and hooks, as shown by Fig. 245 and loaded onto cars. 8 slabs made a carload. The cars were run to the work, where the gin poles hoisted the slabs one at a time to cars running on a track built on timbers laid on top of the roof girders. A small derrick on rafters picked the slabs from the hand car and set them in place. A gang of 15 men erected from 18 to 20 slabs per 10-hour day, with average wages at 21 cts. Per hour, the cost of erection was 15 times $2. 10 divided by 19 equals $1. 66 per slab or $1. 79 per cu yd. The total cost of slabs in place was thus. Item per slab per cu yd molding $6, 73 $7, 27 erecting 1, 66 1, 79 total $8, 39 $9, 06. In studying these cost figures, their limitations must be kept in mind. Because of the character of the available data, quantities had in several cases to be estimated from the working drawings. The cost of lumber for and of framing column and girder forms is not included, but this is partly balanced at least by the assumption that each form was erected complete for each column and girder, which was not the case. as has been stated. Cost of plant is not included, nor is cost of shoring the columns until girders and struts were placed, nor are several minor miscellaneous items. Hollow block wall construction. 3 general processes of molding hollow wall blocks of concrete are employed. 1. A dry mixture is heavily tamped into a mold, and the block is immediately released and set aside for curing. 2. A liquid is poured into molds, where the block remains until hard. 3. A medium wet mixture is compressed into a mold by hydraulic presses or other means of securing great pressure. The molds used may be simple wooden boxes with removable sides or mechanical molds of comparative complexity. Generally, mechanical molds, or concrete block machines as they are commonly called, will be used. There are a score or more kinds of block machines, all differing in construction and mode of operation. None of them will be described here, but those interested may consult Concrete Block Manufacture by H. Rice, or Manufacture of Concrete Blocks and Their Use in Building Construction by H. Rice, W.M. Torrance and others. Factory Buildings, Grand Rapids, Mich. The buildings ranged from 1 to 4 stories high and altogether occupied some 74,000 ft of ground. The owners installed a block-making plant fully equipped with curing racks, 2 ideal machines, 2 national concrete mixers, 5 HP, gasoline engine, platons, tools, and a Chase industrial railway. The walls were constructed of 24-in. Square pilasters of blocks arranged as shown by Fig. 246, connected by curtain wall belt courses of single blocks. The blocks were 8 x 8 x 16 ins, and after molding the faces were bush hammered and the edges tooled. The pilasters, consisting of 4 blocks laid around an 8 x 8 in hollow space, were solidified by pouring the 8 x 8 in space and all but the 3 outside block cavities with wet concrete. The interior of the building was of regulation mill construction, and as the pilasters reached the heights for beam supports, cast iron plates with downward flanges were set in the concrete. These plates had a cast pin projecting upward to fasten the beam end. Fig. 246. Concrete block pilaster for a factory building. The materials used for the block were Sandusky Portland cement and 3/4 in. Bank gravel well balanced from fine to coarse. The blocks were molded with 1 to 3 mortar faces, the mortar being waterproofed by a mixture of Medusa waterproofing compound. All concrete was machine mixed. The men operating the block machines were paid 1 CT for each block molded so that their pay depended upon the energy with which they worked. The men handling materials and engaged in handling and curing the blocks were paid $1.75 per day. The gravel was shoveled from the railway cars onto the screens and from the screen piles to the mixers. The gang was organized as follows. Item. Per day. 8 men handling materials at $1.75, $14. 005 men operating molds at 1 CT per block 15. 001 man mixing facing mortar at $1.75. 75 2 men loading blocks onto trucks at $1.75. 350 2 men unloading blocks from trucks at $1.75. 53 men sprinkling blocks at $1.75. 25 total. 21 men molding and curing blocks, $43. 00 The average daily run was 1,500 blocks or 300 blocks per machine. This output was easily maintained after the gang got broken in. Sometimes it ran higher and sometimes lower, but the average was as given. The men operating the block machines thus earned $3 each per day. The labor cost of molding and curing per block was thus 87 CTS, as the blocks had about 25% hollow space, each block 8 times 8 times 16 ins, contained 0.45 ft of concrete. A cubic yard of concrete, therefore, made 60 blocks, so that the labor cost of making the blocks was 60 times 87 CTS, equals $1.72 per cubic yard. This cost does not include foreman's time, materials, interest, depreciation, or general expenses. It was estimated by the owners that the blocks cost them 9 CTS. A piece cured, or about $5.40 per cubic yard of concrete. This 9 CTS evidently includes materials and labor alone. Upon removal from the molds, the blocks were loaded onto cars, taken to a large shed, and there unloaded onto shelving arranged to hold 5 rows of blocks one above the other, 2 blocks opposite each other on each shelf. The blocks were left in the shed 24 to 48 hours to get the preliminary set. Then they were loaded on small cars and taken to the yard, where they were removed from the cars and stacked. They were sprinkled every day for 6 days, being kept covered meanwhile with oiled cotton cloth. The labor costs given above include molding, sprinkling, and handling the blocks up to this point. To lay the blocks, they were again loaded on cars and run to an elevator in a wooden tower outside the building. The elevator lifted the car to the floor on which the blocks were to be used, where it was run off onto a track reaching the full length of the building. The blocks were unloaded directly behind the masons. Where the walls were high enough for scaffolding, the blocks were unloaded directly onto the first scaffold, and when necessary, handed up to the scaffolds above. The masons employed were regular stone masons, receiving the regular scale of wages of $3.50 per day. The number of blocks laid by each mason was 125 per day in building pilasters and 200 per day in building plain wall. Sometimes 250 blocks per day per man were laid in plain wall work. The cost per block of laying above was thus 8 CTS. Pilasters and 75 CTS. In plain wall. This cost does not include transporting the blocks from yard or of handling them to the scaffold behind the masons, nor does it include the cost of materials and labor for mixing and delivering mortar. One of the features of this work was the method of transporting the blocks by cars. A complete system of tracks was provided covering the block plant and yard, the building sites, and the several floors of the buildings themselves. All blocks and other materials were transported by cars running on these tracks, both cars and tracks being of the type made by the Chase Foundry and Manufacturing Co. of Columbus, Ohio. Residence Quogue N.Y. The following record of methods and cost of constructing a concrete block residence is furnished by Mr. Noyes F. Palmer. A mixture of sand and pebbles was had on the site. Screening was necessary merely to sort out the odd-size stones. A mixture of 1 cement and 5 sand was really a 1 to 2 to 3 mixture, the 2 being the finest grades of sand and the 3 being various gravel sizes, none too large, none too small, so that the proportion was 2/5 fine sand and 3/5 gravel. The concrete was hand-mixed, and as the gravel had always just been excavated, it contained moisture and did not have to be wetted. The sand and gravel were mixed and turned 3 or 4 times and spread out thin, and the cement was carefully spread over them in a uniform layer. The mass was then turned 3 or 4 times until the eye could detect no difference in color. That is, each grain large enough for the eye to discern seemed to be coated with cement. After this dry mixing, water was added in a fine spray, not a deluge from a pail, but only enough to moisten the mixture. The mass was then turned 3 or 4 times. The mixture was then shoveled into the mold, no special face mixture being used, so as to about half fill it, and was then tamped by 2 men, one standing on each side of the machine. Altogether 3 layers of material were so placed and tamped, and then a shovelful of sand and cement mixture was spread over the top to permit an even strike-off. As each block was molded, it was carried on the working plate and set down on skids properly spaced to fit the marks on the plate. This is an important detail, and Mr. Palmer comments on it as follows. The writer saw inexperienced men careless about it, and who would break the backs of many blocks by not having the skids properly placed. After the blocks have been at rest for half an hour, commence to spray them with a revolving garden sprinkler, or by carefully wetting with a sprinkling pot on the center of the block only. The blocks should not be allowed to dry out for at least 10 days after removal from the working plate. The removal from the working plate can be done the morning after molding, and should never be done before, even if the block was made in the morning. In removing the green block from the skids, let there be cones of sand between the rows of blocks, and append each working plate, so as to let the end of the block come upon the sand cushion. Don't twist and turn the block, and to remove the working plate, pass a stick through the core holes in both block and plate, so that the plate will not fall when loosened. A slight rap on the center of the plate will loosen it. As soon as the blocks are appended, commence the spraying, and soak the sand underneath the block. It may seem unnecessary to dwell on these points so long, but barrels of cement and barrels of money have been wasted by neglecting to supply the hardening block with water. Curing is just as important as molding in making concrete blocks. The block construction had been detailed by the architect from cellar to roof, so that it was known beforehand how many blocks of given size were to be made. The unit of length was 32 ins. This afforded fractional parts of 8 ins, 16 ins, and 24 ins. Therefore all openings were in multiples of 8 ins. Odd sizes were made by inserting blanks in the mold box to inches or fractions of an inch if desired. This unit length was less mortar joints, while the unit of height was 9 ins, or the same as 4 ordinary bricks with joints. The floor levels were calculated in multiples of 9 ins, so that the wall could be finished all around where the beams were to be seated. This beam course was made of solid blocks. That is, no cores were used in molding them. With the machine used, no change was required to mold these solid blocks except to remove the cores. The core holes in the working plate were simply covered with pieces of tin. The shape of the block was the same, and the same materials were used. The best record in making blocks for this work was 30 blocks, 8 times 9 times 32 ins. In 1 hour, working 6 men, 3 mixing and 3 on the machine, and using 1 barrel of cement for 16 blocks. This was a record run, however, a fair average being 20 blocks per hour or 200 per 10 hours, which was the day worked. We have then the cost of making blocks as follows: 1 foreman at $2, $50 2, 55 helpers at $2.10, 13 barrels cement at $2.26, 10 coup, ids, sand and gravel at $1.10, interest and depreciation on machine 2, total for 200 blocks $50. 50. This gives a cost per block of $50. 50 divided by 200 equals 25 a quarter CTS. The displacement in the wall of each block is 1. 75 coup, FT, or the same as 30 bricks. The cost of laying blocks is the most uncertain item in the whole industry. Mr. Palmer states that he has known of instances where it cost only 5 CTS per block and of other instances where, because of the difficulty of getting help and its inexperience, it cost 15 CTS per block. In this particular building, one mason and 3 helpers laid 100 blocks per day. The building had no long walls, but it did have many turns. The cost of laying, then, was as follows. One mason at $4 4, 3 helpers at $2.06, 0 total for 100 blocks $10, 0 this gives a cost for laying of 10 CTS per block. We have, then, making 2,000 blocks $505, laying 2,000 blocks 200, total $705. This gives a cost of 35 1/4 CTS per block for making and laying. The use of a derrick for laying the blocks proved a considerable item of economy in this work. This derrick cost $50 and 2 men could mount and move it on the floor beams. It had a boom reaching out over the wall and was operated by a windlass, a plug and feather to fit the center 6-in hole in the block was used for hoisting the blocks. By this means, blocks only 7 days old were laid without trouble. It may be noted that the walls were kept drenched with water to make sure that the blocks did not dry out until they were at least 28 days old. In laying the blocks, a thin lath was used to keep the mortar back about 1 inch from the face. This precaution will prevent much labor in cleaning the walls from mortar slobber. 2-story building, Albuquerque, NM. The following record of cost of making 9 times 10 times 32-in hollow blocks in a Palmer machine and of laying 2,000 of them in 2-story building walls is given by Mr. J. M. Ackerman. Sand cost 60 CTS per cu, YD, and cement cost $3 per barrel. Lime cost 30 CTS per bushel. 1 barrel of cement made 20 blocks using a 1:4 sand mixture. In making 2,000 blocks, about 100 blocks, or 5%, were lost by blocks breaking in hauling from yard to building or by cutting blocks to fit the work. The blocks were molded by piecework for 5 CTS per block, all materials, tools, and plant being supplied to the molders. 3 men with 1 machine made from 100 to 150 blocks per day. The cost was as follows. Item, per block. Cement at $3 per BBL, $0. 15 molding at 5 CTS per block 0. 0.5 sand at 60 CTS per cu, YD, 0. 0.3 carting yard to building 0. 0.2 lime and sand for mortar 0. 0.3 laying in wall 0. 10 loss in making and cutting 0. 0.1 total $0. 39 as each block gave 9 times 32 equals 288 SQ. Ins, or 2 SQ. FT, of wall surface, the cost of the wall per square foot was 19.5 CTS. Assuming 40%, hollow space, each block contained 1 cu, FT of concrete, which cost 23 CTS, or $6, 21 per cu, YD, for materials and molding. Blocks in the wall cost $10, 55 per cu, YD of concrete. General cost data. The following data are given by Prof. Spencer B. Newberry. The average weights of 3 sizes of hollow blocks are as follows. Size ins PC hollow space. Weight pounds. 8 times 9 times 32 33 1/3 120 10 times 9 times 32 33 1/3 150 12 times 9 times 32 33 1/3 180. Costs of materials are assumed as follows. Item, per 100 pounds. Cement at $1. 50 per BBL, $0. 40 hydrated lime at $5 per ton, $0. 25 sand, gravel, or screenings at 25 CTS per ton $0. 0.12 mixed in batches of 750 pounds, sufficient for 6 8-in or 4 12-in. Blocks. The cost of materials per batch and per block will be for a 1 to 4 mixture as follows. Item per batch: 8-in block, 12-in block, 150 pounds, cement $0, 60 $0, 10 $0, 15 600 pounds, sand 0, 0.72 0, 0.12 0, 0.18, total $0, 672 $0, 112 $0, 168 in general. A factory producing 608 tin blocks per day will require 25 men to operate it, at an average wage of $1.80 per day. The following is considered as a fair estimate of cost. Item per day, per block. Materials for 600 blocks $60 $0. 10 25 men at $1.80 45 0. 0.75 repairs 10 0. 0.17 office and miscellaneous 20 0. 0.34 total $135 $0. 226. This gives for 8 times 9 times 32 in blocks a cost of about $6.78 per cu yd of concrete for materials and molding, or of 11.3 CTS per SQ FT of face. Mr. L. Bingham gives the following as the average cost per square foot of face for 10-in wall from data collected from a large number of block manufacturers operating in Iowa in 1905. Cement at $1.60 per BBL, 4.5 CTS, sand 2.0 CTS, labor at $1.83 per day, 3.8 CTS, at total cost per square foot 10.3 CTS. Assuming 1/3 hollow space, the cost for materials and molding was $5.05 per cu yd of concrete, not including interest, depreciation, repairs, superintendents, or general expenses. Chapter 51. Aqueducts and sewers in concrete are of 3 kinds. 1. Continuous monolithic conduits. 2. Conduits laid up with molded concrete blocks. And 3. Conduits made up of sections of molded pipe. Block conduits and conduits of molded pipe are rare in America compared with monolithic construction. Examples of each are, however, given in succeeding sections, where forms, methods of molding, etc. are described. The following discussion refers to monolithic construction alone. Forms and centers. Forms and centers for conduit work have to meet several requirements. They have to be rigid enough not only to withstand the actual loads coming on them, but to keep from being warped by the alternate wetting and drying to which they are subjected. They have also to be constructed to give a smooth surface to the conduit. To be economical, they have to be capable of being taken down, moved ahead, and re-erected quickly and easily. The carpenter costs run high in constructing conduit forms, so that each form has to be made the most of by repeated use. 3 different constructions of traveling forms are described in the succeeding sections. For small work, such forms appear to offer certain advantages, but for conduits of considerable size, their convenience and economy are uncertain. The experience with the large traveling form employed on the Salt River irrigation works in Arizona was, when all is said, rather discouraging. The authors believe that for work of any size where the concrete must be supported for 24 hours or more, forms of sectional construction will prove cheaper and more expeditious than any traveling form so far devised. No class of concrete work, perhaps, offers so good an opportunity for the use of metal forms as does conduit work. The smooth surface left by metal forms is particularly advantageous, and there is a material reduction in weight and a large increase in durability due both to the lack of wear and to freedom from warping. Steel forms of the Blaw type shown by Fig. 247 have been used for conduits up to 25 ft in diameter. The form illustrated Fig. 247 was for 12 ft, 3 in. Sewer. In this case, a roof form alone was used, but full circular and egg-shaped forms are made. The Blaw collapsible steel centering Co. of Pittsburgh, Pa. make and lease steel forms of this type. Fig. 247. Blaw collapsible steel centering for conduit construction. Sectional wooden forms for conduits of large diameters are shown by the drawings in several of the succeeding sections. Figures 248 and 249 show such forms for small diameters. The form shown by Fig. 248 is novel in the respect that after being assembled, a square timber was passed through it lengthwise, occupying the holes B and having its ends projecting and rounded to form gudgeons. The form was mounted with these gudgeons resting on horses, so that it could be rotated and thus wound with a narrow strip of thin steel plate. Thus sheathed, the form was lowered into the trench, and the concrete was placed around it. When the arch had been turned, the wedges were driven in until the ribs C dropped into the slots and clear of the steel shell. The arch form was then pulled out, and finally the invert form, leaving the steel shell in place to hold the concrete until hard. The strip of steel was then removed by pulling on one end, until it unwound like cord from the inside of a ball of twine. Steel strip 6 ins, wide and 1/24 in, thick were used successfully in constructing a 5 ft, egg-shaped sewer in Washington, D.C. The forms were made in sections 16 ft long and were taken out as soon as the concrete had been placed. Fig. 248. Sectional steel-wrapped wooden form for conduit construction. Fig. 249. Invert form for conduit construction. The form shown by Fig. 249 is an invert form used in constructing the sewer shown by Fig. 249, built at Medford, Mass. in 1902 by day labor. The concrete was 1 to 3 to 6 gravel. The forms for the invert were made collapsible and in 10 ft lengths. The two halves were held together by iron clamps and hook rods. The morning following the placing of the concrete, the hook rods were removed and turnbuckle hooks were put in their places, so that by tightening the turnbuckle, the forms were carefully separated from the concrete. The concrete was then allowed to stand 24 hours when the arch centers were set in place. These centers were made of times 1/2 in, lagging on 2 in, plank ribs 2 ft, apart and stringers on each side. Wooden wedges on the forward end of each section supported the rear end of the adjoining section. The forward end of each section was supported by a screw jack placed under a rib 2 ft from the front end. To remove the centers, the rear end of a small truck was pushed under the section about 18 ins. An adjustable roller was fastened by a thumb screw to the forward rib of the center. The screw jack was lowered, allowing the roller to drop on a run board on top of the truck. The truck was then pulled back by a tail rope until the adjustable roller ran off the end of the truck, whereupon the truck was pulled forward, drawing the center off the supporting wedges of the rear section. Each lineal foot of sewer required 1/4 cu. ids of excavation, which cost 74, 2 cts per foot, and 1 cu. ft of brick arch, which cost $12.07 per cu. yd, or 44, 2 cts per lineal foot of sewer. The invert required 4 cu. ft of concrete per foot, which cost as follows: item per cu. yd, Portland cement at $2.50 15 per BBL, $2, 292 labor mixing and placing 3, 0, 17 cost of forms 0, 187 labor screening gravel 0, 471 cotting 0, 592 miscellaneous 0, 146 total $6. 705 the cost of the invert was thus $1.002 per lin. FT of sewer. Collapsible metal forms for manholes and catch basins are made by several firms which make block and pipe molds. A cylindrical wooden form construction is shown by Fig. 250. The outside form consists of 3 segments of a cylinder made of 2 lagging bolted to hoops. Bent lugs on the ends of the hoops were provided with open top slots and were bolted together through 1 times in. Bars which extended the full length of the form between lugs. The assembled form was collapsed by pulling up on the bars, thus lifting the bolts out of the slots. The inner mold is also made in 3 sections with strap hinges at 2 of the joints, and at the 3rd joint a wedge-shaped stave. The other details are shown by the drawing. To mold the top of the basin, 2 cone-shaped forms are used, an outer form made in 1 piece and an inner form made in sections. Some 26 catch basins were built in Kenny Park, Hartford, Conn, by Mr. H. G. Clark, at a cost of $7 apiece for concrete in place, and there was closely 1 coup. YD of concrete in each. Fig. 250. Form for circular catch basin or manhole, concreting. Except for pipes of small diameter, the concreting is done in sections, each section being a day's work. Continuity of construction has not proved successful, except for pipes of moderate size, in the few cases where it has been tried. Examples of continuous construction methods are given in succeeding sections. Methods of molding and laying cast concrete pipe are also best shown by the specific examples given further on. In concreting large diameters, the work may be done by molding successive full barrel sections, or by molding first the invert, and then the roof arch, each in sections. The engineer's specifications generally stipulate which plan is to be followed. Construction joints between sections are molded by bulkhead forms framed to produce the type of joint designed by the engineer. The most common type is the tongue and groove joint. Fig. 251. Cross-section of Pinto Creek irrigation conduit. For small diameters built with traveling forms, a comparatively dry concrete is essential. But when the centers are left in place until the concrete is set, a wet mixture is preferable, as it is more easily placed and worked around the reinforcement in the thin shells. Mixes are commonly specified even for small work, because of their generally more uniform and homogeneous product. Portable mixers hauled along the bank and discharging into the forms through chutes furnish a cheap and rapid arrangement where the section being built has a considerable yardage. The examples given in succeeding sections present various methods of mixing and placing concrete in conduit work. Fig. 252. Traveling form for Pinto Creek conduit. Reinforced conduit, Salt River Irrigation Works, Arizona. The pipe had the cross-section shown by Fig. 251, and formed a siphon carrying water under the bed of a creek. The concrete was a 1:2 of 4 fine gravel mixture, mixed by hand on boards 150 ft. Apart along the line. The shell was reinforced as shown. The forms consisted of an outside form constructed as shown by Fig. 251 by inserting 2 1/2 in times 5 1/2 ft. lagging strips in the metal ribs. The inside form was designed to permit continuous work by moving the form ahead as the concreting progressed. It consisted, as shown by Fig. 252, of an invert form on which an arch form was carried on rollers. The invert form was pulled along by cable from a horsepower whim set ahead, being steered, aligned and kept to grade by being slid on a light wooden track. It had the form of a long half-cylinder, with its forward end beveled off to form a scoop-like snout. The arch center consisted of semicircular rings 2 ft. long, set one at a time as the work required. Each ring, when set, was flange-bolted to the one behind, and each was hinged at 3 points on the circumference to make it collapsible. In operation, the invert form was intended to be pulled ahead, and the arch rings to be placed one after another in practically a continuous process, so that the arch rings might continue supported after the invert form was drawn out from under them. Invert plates similar to the arch plates were inserted one after another in place of the shell of the invert form. The plan provided very nicely for continuous work, but continuous work was found impracticable for all but about 2,500 ft. of the 6,000 ft. of conduit built. The reason for this seems to have been, at least in a great measure, the slow-setting cement made at the cement works established by the government at Roosevelt. In building the first 300 ft. of conduit, a commercial cement was used and a progress of 120 lin. ft. of pipe per 24 hours was easily made. This work was done in June. Later, but still in warm weather, using the government cement and 70 ft. of arch plates, not more than 70 ft. of pipe could be completed in 24 hours. If the plates were taken down sooner, patches of concrete fell out or peeled off with them. As the weather grew colder, this difficulty increased, until finally the idea of continuous work was abandoned, and for some 3,500 ft. of conduit only 1 8-hour shift per day was worked. In December and January, the plates had to remain in place 3 days, so that the progress was only 24 ft. per day. In warm weather, this rate was increased to 40 ft. per day. Costs were kept on 2 sections of one of the lines, and the figures shown in the accompanying table were obtained. A gang consisted of a foreman at $175 per month, a sub-foreman at $3.50 per day, and the following laborers at $2.50 per day, 1 bending the reinforcement rings, 2 placing the reinforcement, 4 taking down, moving, and erecting the stationary plates, 4 placing the concrete and outside lagging, 2 wheeling concrete, 6 mixing concrete, 1 wheeling sand and gravel, 1 watering the finished pipe, 4 laying track for the steering apparatus, moving the superstructure and hangars, mixing boards, runways, etc., 1 pointing and finishing inside the pipe, and 1 on the whim and doing miscellaneous work. The labor was principally Mexican and only fairly efficient. It is important to note that the costs given in the table are labor costs only of mixing and placing concrete and moving forms. They do not include engineering, first cost of forms, concrete materials, reinforcement, or grading. Wages per day. May 06, 714 lin, ft. Cost. July 06, 1009 lin, ft. Cost per lin, ft per coup, yd. 4 men laying track for steering alligator $5. $0071, 48, $43, 98 $0, $06700. 16 4 men moving and erecting superstructure 5, 299, 94 358, 44 0, 38 21 0, 93 4 men moving plates 10, 202, 50 253, 44 0, 26 46 0, 65 repairs to alligator 58, 52, 50 0, 03540, 081 man bending rings 2, 50 32, 87 59, 87 0, 05380, 13 2 men placing reinforcement 5, 00 126, 94 138, 13 0, 15 38 0, 38 12 men mixing and placing concrete 30, 00 709, 68 949, 74 0, 96 31 2, 34 1 man watering finished pipe, 2, 50 45, 00 78, 27 0, 07160, 17 1 man painting and brush coating inside 2, 50 96, 50 117, 37 0, 12 41 0, 31 blacksmiths work 30, 00 25, 000, 03190, 081 man Wim 2, 50 23, 87 28, 75 0, 03060, 071 man screening and hauling sand and gravel 2, 50 183, 13 300, 000, 28040, 68, Total $1,880, 41 $2,335, 49 $2, 45 84 $5, 98 conduits, Torresdale filters, Philadelphia, PA. At the Torresdale plant of Philadelphia filtration system, the clear water conduits are reinforced concrete. The following description is composed from information furnished the authors in 1904 by the Bureau of Filtration, Mr. John W. Hill, then chief engineer. The lengths of the several conduits are as follows: 576 ft of 7½ ft, 782 ft of 8 ft, 1,050 ft of 9 ft, and 1,430 ft of 10 ft. Horseshoe conduit. All sizes of conduit have the same cross-sectional form, the cross-section of the 9 ft. Conduit is shown by Fig. 253, and all are reinforced by expanded metal arranged as indicated. The concrete is a 1 to 3 to 5 3/4 in stone mixture. The conduits were first designed with circular sections, but before construction had been begun on these plans, experience had been obtained in building a circular sewer that made a change to the horseshoe section appear desirable. In the circular sewer work, great difficulty had been found in properly placing and ramming the concrete in the lower quarters of the circular section. Fig. 253. Section of 9 ft. Conduit, Philadelphia filter plant. Forms. The forms used for the several sizes of conduit were all of the same general type, but improvements in detail were made as successive sizes were built. The last form to be designed was that for the 9 ft. section, and this was the best one. It is shown by Fig. 254. The forms were built in sections from 12 ft. to 13½ ft. long. They were covered with No. 27 galvanized sheet iron, and this covering was found of advantage both in giving a smooth finish and in prolonging the life of the centers. The important feature is the construction in sections which could be set up and broken down by simply inserting and removing the connecting bolts. 3 sets of forms were made for each size of conduit. Fig. 254. Form for 9 ft. Conduit, Philadelphia filter plant. Procedure of work. The first operation in building a section of conduit was to set to exact line and grade and the length of the form in advance of the finished work, the bulkhead shown by Fig. 255. In this space, the invert concrete was deposited and formed to a plane 1 in. Below the finished invert bottom, the 2 bottom sections of the form were then assembled and located by bolting one end to the last preceding form and inserting the other end into the bulkhead. About 2 tons of pig iron were then placed on the invert form to keep it from floating, while the liquid granolithic mixture was being poured into the 1 in. Space between the form and the invert concrete. In building up the sides, a facing form was used for placing the granolithic finish. This consisted of boards of sheet steel ribbed transversely on one side with 3/4 in pipe, and on the other side with 1/2 in pipe. 2 boards were used on each haunch, slightly lapping in the center as follows. The board was placed with the small ribs against the form, and the larger ribs kept the expanded metal just 3 ins from the face of the form. A 6 in depth of concrete was placed between the metal board and the outside form or planks, then 6 ins of granolithic was poured into the 1 in. Space between the center and the board, and finally the board was raised 6 ins, and the concrete and granolithic mixture tamped together. With the board in its new position, another layer of concrete and granolithic was placed. Toward the crown, the granolithic mixture was made stiff and simply plastered onto the mold. The expanded metal was cut into sheets corresponding to the length of the sides of the form and lapped 6 ins. In all directions, the bulkhead having a slot as shown to permit the metal to project 6 ins from the face of the concrete in order to tie 2 sections together, and also having a rib which formed a mortise in the face of the shell of concrete to key it to the succeeding section. Fig. 255. Bulkhead form for conduits, Philadelphia filter plant. All the conduits were built in sections from 12 ft to 13.5 ft long, and there was very little, if any, difference in the labor required to build a section in from 8 to 10 hours of any of the 3 sizes. 1 foreman and 18 men on the top of the trench mixed and handled the concrete and granolithic mortar, while 1 foreman, 1 carpenter, and 7 men in the trench set the forms and placed and rammed the concrete for 1 section in generally 8 hours. About 1/3 of the concrete for the whole work was mixed in a portable cubical mixer of a 1/2 cu. yd capacity, and the remainder was mixed by hand. Owing to the relatively small amount of concrete used per day, about 20 cu. ids, it was found that there was practically no difference in the cost of machine mixing and of hand mixing. The 9 ft conduit, as an average of the 3 sizes, contained 20 cu. ids of concrete, 1,200 sq. ft of expanded, and required 125 bags of cement for a section 13.5 ft long. The cost of the work, excluding excavation and profit, but including forms, metal, concrete materials, and labor, was about $10, 50 per cu. yd. Conduit, Jersey City water supply. In constructing the 8.5 ft reinforced concrete conduit for the Jersey City water supply, use was made of forms without bottoms. Each form was made of segmental sections 12.5 ft long of wood covered with sheet steel. They were set end to end in the trench, resting on 6 in concrete cubes which were finally permanently embedded in the invert concrete. In each form there was a scuttle about 2 ft square at the crown, and the bottom was open between the curves of the invert haunches. The form being set and greased and the reinforcement placed, the concrete was deposited on the outside and forced by means of tamping bars down the curve of the invert haunches until it filled the whole space between the form and the earth, and appeared at the edges of the bottom opening in the form. Concrete was then thrown through the scuttle, and the invert screeded into shape. The concreting of the sides and crown of the arch was then completed, using outside forms except for about 5 ft. Of the crown, the scuttle, of course, being closed by a fitted cover. The centers were left in place about 48 hours. The concrete was a 1 cement 7 sand and run of the crusher 2-in. Broken stone mixture, and was made so wet that it would flow down an incline of 1:8. The mixing was done in portable ransom mixers, set on the trench bank alongside the work and discharging by chute into dished shoveling boxes provided with legs to set on the erected forms. Coal scoops were used in shoveling from the box into the forms, and were found superior to shovels in keeping the relative proportions of water and solids constant. Twin-tube water conduit at Newark, N.J. In constructing the Cedar Grove Reservoir at Newark, N.J., 2 conduits side by side were built across the bottom from gate house to tunnel outlet. A section of one of the conduits showing the form construction and the arrangement of the reinforcement is given by Fig. 256. The concrete was a 1 to 2 to 5 1/2 in. Stone mixture and the reinforcement was No. 10 3-in. Mesh expanded metal. The method and cost of construction are given as follows by Mr. G. C. Woolard, the engineer for the contractors. Fig. 256. Conduit for Cedar Grove Reservoir, Newark, N.J. The particular thing that was insisted upon by both Mr. M. R. Sherrard, the chief engineer of the Newark Water Department, and Mr. Carlton E. Davis, the resident engineer at Cedar Grove Reservoir, in connection with these conduits, was that they be built without sections in their circumference, that the whole of the circumference of any one section of the length should be constructed at one time. They were perfectly willing to allow us to build the conduit in any length section we desired, so long as we left an expansion joint occasionally which did not leak. The good construction of these conduits was demonstrated later, when the section stood 40 pounds. Pressure to the square inch, and in addition, I may say that these conduits have not leaked at all since their construction. This shows the wisdom of building the conduit all round in one piece, that is, in placing the concrete over the centers all at one time, instead of building a portion of it, and then completing that portion later, after the lower portion had had an opportunity to set. The centers which I designed on this work were very simple and inexpensive, as will be gathered from the cost of the work, when I state that this conduit, which measured only 0.8 cu yd of concrete to the lineal foot of single conduit, cost only $6, 14 per cu yd, built with Atlas cement including all labor and forms and material and expanded metal. The forms were built in 16 ft. Lengths, each 16 ft. Length having 5 of the segmental ribbed centers, such as are shown in Fig. 256, viz. 1 center at each end and 3 intermediate centers in the length of 16 ft. These segments were made by a mill in Newark and cost 90 cts a piece, not including the bolts. We placed the lagging on these forms at the reservoir, and it was made of ordinary 2x4 material, surfaced on both sides, with the edges beveled to the radius of the circle. These pieces of 2x4 were nailed with 210D nails to each segment. The segments were held together by 4.5 in. Bolts, which passed through the center, and 1.5 in. Wooden tie block. There was no bottom segment to the circle. This was left open, and the whole form held apart by a piece B of 3 times 2 spruce, with a bolt at each end bolted to the lower segment on each side. The outside forms consisted of 4 steel angles to each 16 ft, of the conduit 1 on each end and 2 back-to-back in the middle of each 16 ft. Length. These angles were 2 times 3 with the 2 in side on the conduit and the 3 in side of the angle had small lugs bolted on it at intervals to receive the 2 times 12 plank, which was slipped down on the outside of the conduit as it was raised in height. The angles were held from kicking out at the bottom by stakes driven into the ground and held together at the top by a 2½ in tie rod. The conduit was 8 ins, thick save at the bottom where it was 12 ins. The reason for the 12 ins at the bottom was that the forms had to have a firm foundation to rest on, in order to put all the weight required by the conduit on them in one day or at one time without settling. We therefore excavated the conduit to grade the entire length and deposited a 4 in layer of concrete to level and grade over the entire length of the conduit line. This gave us a good, firm foundation, true and accurate to work from, and this is the secret of the good work which was done on these conduits. If you examine them, you will say that they are one of the neatest jobs of concrete in this line that has been built, especially with regard to the inside, which is true, level, and absolutely smooth. The authors can confirm this statement. When the conduit is filled with water, it falls off with absolutely no point where water stands in the conduit, owing to its being out or the proper amount of concrete not being deposited. The centers were placed in their entirety on a new length of conduit to be built, resting upon 4 piles of brick, 2 at each end as shown. The first concrete was placed in the forms at the point marked X, and the next concrete was dropped in through a trap door cut in the roof of the conduit form at the point marked Y. This material was dropped in to form the invert, and this portion was shaped by hand with trowels and screeded to the exact radius of the conduit. The concrete was then placed continuously up the sides, and boards were dropped in the angles which I have mentioned, and which served as outside form holders till the limit was reached at the top, where it was impossible to get the concrete in under the planking and thoroughly tamped. At this point the top was formed by hand and with screeds. Each 16 ft. length of this conduit was made with opposite ends male and female respectively. That is, we had a small form, which allowed the concrete to step down at one end to 3 ins in thickness for 8 ins. Back from the end of the section, and on the other end of the section it allowed it to step down to 3 ins in thickness in exactly the opposite way, making a scarf joint. This was not done at every 16 ft. length unless only 16 ft. were placed in one day. We usually placed 48 ft. a day at one end of the conduit with one gang of men. This was allowed to set 24 hours, and whatever length of conduit was undertaken in a day was absolutely completed, rain or shine, and the gang next day resumed operations at the other end of the conduit on another 48 ft. length. This was completed, no matter what the weather conditions were, and towards the close of this day the forms placed on the preceding day were being drawn and moved ahead. The method used in moving these forms ahead for another day's work is probably one of the secrets of the low cost of this work, and it is one which we have never seen employed before. The bolt atta Fig. 256 was taken out and the tie brace be thrown up. We had hooks at the point C. A turnbuckle was thrown in, catching these hooks, and given several sharp turns, causing the entire form to spring downward and inwards, which gave it just enough clearance to be carried forward, without doing any more striking of forms than pulling the bolt atta. This method of pulling the forms worked absolutely satisfactorily and never gave any trouble, and we were able to move the forms very late in the day and get them all set for next day's work, giving all the concrete practically 24 hours set, as we always started concreting in the morning at the furthest end of the form set up and at the greatest distance from the old concrete possible in the 48 FT. Length, as the furthest form had of course to be moved first, it being impossible to pass one form through the other. 16 FT sections of these forms were built, and 3 were used each day on each end, as shown by the diagram MN Fig. 256, which gives the day for the month for the completion of each of 7 48 FT sections. A gang of men simply shifted on alternate days from end to end of the conduit, although several sections were in progress at one time. And of course, finally, when a junction was made between any division, say of 1,000 FT, to another 1,000 FT, one small form was left in at this junction inside of the conduit, and had to be taken down and taken out the entire length of the conduit. The centers for a 16 FT. Length of this conduit cost complete for labor and material $18. 30, but they were used over and over again, and after this conduit was completed, they were taken away for use at other points, so that the cost is hardly appreciable, and the only charge to centers that we made after the first cost of building the centers was on account of moving them daily. Part of this conduit was built double, 6 FT. Conduits and part single, the only difference being that where the double conduit was built, 2 forms were placed side by side, and not so much was undertaken in one day. These conduits, when completed and dried out, rung exactly like a 60-in cast iron pipe when anyone walked through them or stamped on the bottom. Mr. Woolard gives the following analysis of the cost per cubic yard of the concrete steel conduit above described, per cu, YD. 1. A 3 BBL. Cement $1, 43.10 cu, FT. Sand 0, 35.25 cu, FT. Stone 1, 1026 SQ, FT. Expanded metal at 3 CTS, 0. 78 loading and hauling materials 2000 FT. To the mixing board team at $4. 50, 0. 50 labor mixing, placing, and ramming 1. 38 labor moving forms 0. 60, total $6. 14 wages were 17.5 CTS per HR for laborers and 50 CTS per HR for foremen. The concrete was 1 to 2 to 5, a barrel being assumed to be 3, 8 cu, FT. The concrete was mixed by hand on platforms alongside the conduit. The cost of placing and ramming was high on account of the expanded metal, the small space in which to tamp, and to the screeding cost. When forms were moved, they were scraped and brushed with soft soap before being used again. From Mr. Morris R. Sherrard, Engineer and Superintendent, Department of Water, Newark, N.J., we have received the following data which differ slightly from those given by Mr. Woolard. The differences may be explained by the fact that the cost records were made at different times. Mr. Sherrard states, Sept. 26, 1904, that each batch contains 4 cu, FT of cement, 8 cu, FT of sand, and 20 cu, FT of stone, making 22 cu, FT of concrete in place. 1 bag of cement is assumed to hold 1 cu, FT. He adds that a 10-hour day's work for a gang is 63 lin, FT of single 6 FT, conduit containing 47, 4 cu ids of concrete and 1,260 SQ FT of expanded metal. This is equivalent to 3/4 cu YD of concrete per lin, FT. The total cost of material for one complete set of forms 64 FT. Long was $160, and there were 7 of these sets required to keep 2 gangs of men busy, each gang building 63 lin ft of conduit a day. Since the total length of the conduit was 3,850 ft, the first cost of the material in the forms was 18 cts per lin ft, cost of labor on 6 ft. Conduit per day per coup, YD, 1 foreman on concrete $3, $35 071 water boys 0, 75 001 11 men mixing at $1, 75 19, 25 0, 39 5 men mixing at $1, 57, 50 0, 16 4 men loading stone at $1, 45, 60 0, 12 4 men wheeling stone at $1, 45, 60 0, 12 2 men loading sand at $1, 42, 80 0, 06 2 men wheeling sand at $1, 42, 80 0, 06 1 man placing concrete at $1, 75 1, 75 0, 046 men placing concrete at $1, 59, 000, 19 2 men supplying water at $1, 53 000, 06 1 man placing expanded metal at $2, 2 000, 04 1 man placing expanded metal at $1, 51 50 03 total labor on concrete $64, $91, 35 cost of labor moving forms per day per coup, YD. 4 carpenters placing forms $13, $000, 27 2 helpers placing forms $4, $000, 08 1 carpenter putting up boards for outside forms $2, 75 0, 06 1 helper putting up boards for outside forms $2, 25 0, 05 2 helpers putting up boards for outside forms $3, 50 0, 07 1 team hauling timber $4, 50 0, 09 1 helper hauling lumber $1, 75 0, 04 total labor moving $31, 75 $0, 66 It will be noted that it required 2 men to bend and place the 700 pounds, or 1,260 SQ, FT, of expanded metal required for 63 lin, FT, of conduit per day, which is equivalent to a half C per LB, or 3 CTS, per SQ FT, for the labor of shaping, placing, and fastening the metal. Circular sewer, South Bend, Indiana. In building 2,464 FT of 66 in. Circular reinforced concrete sewer at South Bend, Ind. In 1906, the method of construction illustrated in Figs. 257, 258, and 259 was employed. The sewer has a 9-in shell buttressed on the sides and is reinforced every 12 ins by a 3/16 times 1 in peripheral bar in the sides and roof and 3 ins in from the soffit. Each bar is composed of 3 pieces, 2 side pieces from 15 ins below to 6 ins above springing lines, and a connecting roof bar attached to the side bars by cotta pins. 2 grades of concrete were used, a 1 to 3 to 6 bank gravel concrete for the invert and a 1 to 2 to 4 bank gravel concrete for the arch. The invert was given a half-in, plaster coat of 1-to-1 mortar as high as the springing lines. Fig. 257. Form for South Bend sewer first stage. Fig. 258. Form for South Bend sewer second stage. Fig. 259. Form for South Bend sewer third stage. Forms and concreting. In constructing the sewer, the trench was excavated so as to give a clearance of 1 ft on each side and was sheeted as shown by Fig. 257. The sewer was built in 12 ft. Sections as follows. The bottom of the trench was shaped as nearly as possible to the grade and shape of the base of the sewer. 4 braces to each 12 ft. Section were then nailed across the trench between the lowest ranges on the trench sheeting. A partial form consisting of a vertical row of lagging was set on each of the outside lines of the sewer barrel as shown by Fig. 257. Each section of this lagging was held by stakes driven into the trench bottom and nailed at their tops to the cross braces as shown by Fig. 258. A template for the invert was then suspended from the cross braces by pieces nailed to the 4 ribs of the template and to the cross braces as shown by Fig. 257. The concrete was now placed and carried to the top of the template, which was then removed. The side pieces of the reinforcing bars were then set and fastened as shown by Fig. 258. The side forms extending up to the springing lines were then placed. They were held in position by braces nailed to their ribs at the tops, and by other braces fitting into notches in the ends of their ribs at the bottom. The concrete was then carried up to the springing lines. The arch centers in 2 pieces were placed. The arch bar of the reinforcement was placed, and the extradose forms erected up to the 45 degrees lines, all as shown by Fig. 259. The placing of the arch concrete completed the sewer barrel. The outside forms and bracing were removed about 24 hours after the completion of the arch, and back filling the trench was begun immediately. But the inside forms were left in place for 2 weeks. They were then removed by the simple process of knocking out the notched braces, by building several lengths of invert first and following in succession by the side wall construction and then by the arch construction. The form erection and the concreting proceeded without interruption by each other. It was also found that, by making bends in the form of polygons with 10 ft. sides instead of in the form of curves, there was a material saving in expensive form work. To overcome the friction of the angles in such bends, an additional fall was provided at these places. All concrete was made in a Smith mixer mounted on trucks so that it could be moved along the bank of the trench and discharging into a trough leading to the work. Labor force and cost. With a gang of 12 men from 24 to 36 ft. of sewer was built per 10-hour day, working only part of the time on actual concreting. The disposition of the force mixing and laying concrete and the wages were as follows. Item, per day, 6-wheelers at 18, 5 CTS, per hour $11, 10 one mixer at 22, 5 CTS, per hour 2, 25 one dumper at 18, 5 CTS, per hour 1, 85 4 places at 22, 5 CTS, per hour 9, 0, total $24, 20 there were 0, 594 cu yd of concrete per lineal foot of sewer, and its cost is given as follows. Item, per cu yd, cost of gravel $0, 774 cost of sand 0, 36 cost of cement 1, 50 cost of steel reinforcement 0, 84 cost of labor mixing and placing concrete 1, 0, 94 cost of moving forms, templates, etc. 0, 757 cost of forms, templates, etc. 0, 589 cost of finishing, plastering, etc. 0, 639 cost of tools and general expenses 0, 841, total $7, 394. Sewer invert, Haverhill, Mass. In constructing sewers with concrete inverts at Haverhill, Mass. In 1905, use was made of the traveling form or mold shown by Fig. 260. The form consists of an inner and an outer shell, the annular space between which forms the mold. In operation, the annular space is filled with concrete. Then the outer shell is pulled ahead from underneath, leaving the inner shell in place. A second inner shell is then adjusted to the outer shell in its new position. The annular mold is concreted, and the outer shell again pulled ahead. Continued repetition of the operations described completes the invert. The merit of the device lies in the fact that the inner shell is not moved until the concrete has attained some degree of rigidity. When, in such devices, the inner mold is slid ahead on the green concrete, it is likely so to drag forward the material that a rough and pitted surface results. Mold construction. Referring to the drawings of Fig. 260, is the outer mold of sheet steel bent to the required shape of the outer surface of the conduit to be constructed. A rib, or angle B, is riveted to the inside of the mold at its front end, and a diaphragm C of plank is securely fastened to the rear side of the rib. The opposite or rear end of the mold is open. Angles D forming tracks are riveted inside the mold a short distance below the edges and reaching their full length. The inner mold comprises a steel shell E curved to the form of the inside of the conduit. Inside this steel shell is a reinforcing lagging, and at each end there is a wooden diaphragm F. Passing through both end diaphragms and having its ends flush with the end planes of the mold is a timber G. Rearward projecting lips E are secured to the lagging at the rear end of the mold and on each side of the timber G. The diaphragms F have each two arms F which project horizontally beyond the surface of the inner mold and engage the tracks D. Locking dogs H are pivoted to the arms F so as to hook under the track angles D and hold the inner form from rising. Setting on the inner mold is an inverted V-shaped deflector I. Its edges are flush with the sides of the mold, and its purpose is to facilitate the placing of the concrete. There is also a movable diaphragm K, fitting loosely inside the outer mold and bearing against the end of the inner mold E. The length of the inner mold E is about 1/2 that of the outer mold A. As a rule, several inner molds are provided with one outer mold. Fig. 260. Traveling invert form for sewer construction. Mode of operation. In using the device, describe the outer mold as first placed in the trench with its rear end at the end of the trench. An inner mold E is then suspended on the tracks of the outer mold and locked therein by the dogs H, with its rear end flush with the rear end of the outer mold. The partition K is then placed in position against the forward end of the inner mold, and a jack J of any suitable form is interposed between diaphragms K and C, the jack being extended sufficiently to press diaphragm K firmly against the front end of the inner mold. The deflector I is next placed in position on the inner mold, and the concrete is forced down with an iron rammer between the two molds, so as to fill completely the annular space. The deflector aids in directing the concrete into this space, as will be obvious. After the mold has been filled and the concrete compacted as much as possible, the jack is operated to separate the diaphragms K and C, and as the partition K is pressed against one end of the mass of concrete which has been laid, the opposite end of which abuts against the end of the trench, it follows that any backward movement of the diaphragm K will compress the concrete. This movement will be practically inappreciable in distance, but enough to compact thoroughly the concrete and fill any voids. The action of the jack will also push forward the diaphragm C and the outer mold A, the latter being withdrawn from beneath the inner mold and the newly laid concrete, the tracks D of the outer mold being drawn from beneath the arms F of the inner mold, leaving the latter behind resting on the freshly laid concrete. Further compression of the concrete after it has been left by the outer mold will fill the spaces between the inner mold and the surface of the trench. The outer mold is moved forward in this manner a distance equal to the length of the inner mold, and then the diaphragm K is drawn forward and another inner mold is lowered into the outer mold exactly as was the first one. The jack is then placed, the concrete deposited, and the outer mold again advanced exactly as before. As the outer mold advances, the inner molds become disengaged one after another and are set ahead. In practice, enough inner molds are provided to enable the concrete to harden sufficiently to keep its position when it becomes necessary to take up successively the rearmost molds and place them ahead. Haverhill Sewer Work. The work at Haverhill, Mass., previously mentioned in which the form just described was used, was a 24-in. circular sewer with 6-in walls. The outer form was 36 ins in diameter and 6 ft, 2 ins long. The inner form was 24 ins in diameter and 3 ft long. Angle B was 3 ins, and the track angles D were 1/2 ins. Diaphragm K was made of 2 thicknesses of 3 in. Plank and diaphragm C of 1 thickness of 3 in. Plank, the other diaphragms were of 2 in. Plank. The shells of the molds were of A/4 in. Steel plate. The jack was an ordinary screw jack. 8 inner molds were used. The form used at Haverhill was built by the city carpenter, the metal portions being made in a boiler shop. Its cost was not ascertained, but was, it is thought, about $75. The concrete used was a 1 to 3 to 5 stone mixture, with cement costing $2 per barrel, sand $1, 50 per load of 36 cu ft, and stone $2, 50 per load of 36 cu ft. The men were paid 25 CTS per hour. Records kept on 265 ft. Of invert, or theoretically 19, 3 cu ids of concrete gave the following figures per lin, ft per cu yd. Labor, setting and moving forms 42 hours at 25 CTS, $0, $050. 67 labor mixing, placing and wheeling concrete 179 hours at 25 CTS, 0, 16 to 19. Total labor cost $0, 21 $2, 86. With the ordinary 1 to 3 to 5 mixture, the cost of materials would run about as follows per cu yd. Cement 0, 96 bbl at $2, $1, 92. Sand 0, 47 cu yd at $1, 13 0, 53. Stone 0, 78 cu yd at $1, 88 1, 47. Total cost materials $3, 92. 2 men were worked in the trench, one alternately ramming the concrete into place and working the jack, and the other shaping the trench ahead and assisting in bringing the rear forms ahead. The form described was invented by Mr. Robert R. Evans of Haverhill, Mass., and has been patented by him. 29 ft. Sewer, St. Louis, Mo. The following account of the method and cost of constructing 162 ft. a very large sewer section at St. Louis, Mo. is compiled from information furnished by Mr. Curtis Hill. The cross-section of the sewer is given by Fig. 261, which also shows the arrangement of the reinforcing bars. Johnson corrugated bars, old style, are used for reinforcement. The sections of the various reinforcing bars are longitudinal bars 0, 18 sq, in, invert bars 0, 7 sq, in, and arch bars 0, 7 sq, in. The spacing of the bars and the arrangement of the splices are indicated on the drawings of Fig. 261. All splices have a lap of 36 ins. Some gravel concrete has been used in the invert, but most of the concrete has been crushed limestone and Mississippi River channel sand. The proportions were 1:3:6 in the invert and 1:2:5 in the arch. The arch was computed by Prof. Green's method. The ultimate strength of concrete in compression was taken as 2,000 pounds per SQ in, and the working strength at 500 pounds per SQ in. The elastic limit of the reinforcing bars was taken at 50,000 pounds. Fig. 261. Harlem Creek Sewer, St. Louis, Mo. The trenching was done by wheel scrapers to the amount of waste. Then a cableway was erected spanning the entire length of the section and the remainder of the material taken out. The last 4 or 5 ft in depth were in limestone, and the excavated rock was taken by cableway to dump carts, which took it to the crusher, and returned with crushed rock to be used for concrete. This rock foundation was taken advantage of to reduce the amount of invert concrete. In constructing the sewer proper, the invert was first concreted to template to the height shown in Fig. 262. The arch forms were then placed as shown in Fig. 262 and the roof arch concreted. Both templates and arch forms were constructed of wood. The arch forms were moved ahead on iron rails and jacked into place. The ribs were 2 × 10 in pieces and were spaced 4 ft. On centers, the lagging was 2 in tongue and grooved stuff and was smeared with crude oil. The reinforcing bars shown in Fig. 261 were bent to proper radius by means of a wagon tire bender and were held in place by templates. The concrete was all mixed by 2 Chicago improved cube mixers operated by electric power. Fig. 262. Center for Harlem Creek Sewer. The cost records of constructing the section of 29 ft. Sewer so far built are not susceptible of complete analysis, but the following figures can be given. The prices of materials were as follows. Cement per barrel $1, 80 sand per cubic yard 0, 75 broken stone per cubic yard 1, 0 reinforcing bars per pound 0, 2 vitrified brick per 1,012, 0 the wages paid different classes of labor were, per hour, firemen $0, 50 laborers 0, 175 laborers 0, 20 laborers 0, 25 laborers 0, 28 laborers 0, 30 25 bricklayers 0, 66 2/3 helpers $0, 25 carpenters 0, 55 engineers 0, 50 timekeepers 0, 25 watchmen 0, 175 hostlers 0, 175 teams 0, 60 taking up the several items of work in order. The excavation amounted to 21,400 ku ids, of which 1,400 ku ids were rock excavation. The cost of excavation was as follows total, per ku yd, earth. Excavation $7,640 $0. 38 earth bracing 2,000 0, 10 rock excavation 1,401, 0 rock dynamite tools etc. 560 0, 40 the cost of crushing the excavated rock and returning it to the mixer was $1 per ku yd. The cost of the concrete work was as follows per ku yd, 1, 30 bbl. Cement at $1, $82, 34, 044 ku yd, sand at 75 cts, 0, 33 1 ku yd, broken stone at $1 1, 0 total concrete materials $3. 67 there were 1,600 ku. IDS of concrete placed at a cost of for total per coup YD. Mixing and placing $1,180 $0. 7375 forms 2001. 25 moving forms 400 0. 25 total for forms and labor $3,580 $2. 2375 for reinforcing the concrete 86,600 pounds of steel, or about 55 pounds, per coup YD, were used. The cost of placing and bending this steel was as follows: total per LB, cost of placing $172 0. 1986 CT, cost of bending $52.06 CT. We can now summarize the cost of the concrete work proper of this sewer as follows: items per coup YD. Cement, sand, and stone $3, 67.55 pounds. Steel at 2 CTS. 1. 10 forms, labor and materials 1. 25 mixing and placing concrete labor 0. 74 placing steel at 0. 1986 CT per LB 0. 11 bending steel at 0. 06 CT per LB 0. 03 moving forms 0. 25 total labor and materials $7. 15 to get the total cost of the sewer proper, we must add the cost of the vitrified brick invert paving. There were 71 coup IDS of this paving, and its cost was as follows: per coup YD 0. 6 BBLS. Cement at $1, $81. 080 25 coup YD. Sand at 75 CTS 0. 19,450 bricks at $12 per M. 5. 40 labor laying 71 coup IDS at $180. 33 2 54 total $9. 21 None of the preceding figures includes the plant charges. The plant cost $12,000, and the cost of running it during the work described was $2,000. In explanation, it should be noted that the plant served for building some 1,340 lin. FT of 27 FT. Sewer as well as for the section described. Sewer at Middlesborough, Kai. In constructing an oval sewer 4 FT, high at Middlesborough, Kai, 2 steel forms in 10 FT. Sections were used, as shown in Fig. 263 T iron ribs were spaced 5 FT, apart, fastened together at the top by longitudinal angle irons and at the bottom by a sheet of steel 22 ins, wide, forming the bottom of the invert. The lagging for the sides consists of movable 5 FT, lengths of channel iron, secured by sliding bolts. After the bottom of the trench has been roughly shaped with concrete, a 10 FT. Section of invert forms is lowered and suspended by the cross beams, and the space beneath packed with concrete. Then a channel iron is slid into place and bolted, and concrete packed behind it, and so on until the invert is made. The next 10 FT section is then built while the first is hardening. Upon the completion of the second section, the channel iron sides of the first section are removed, and then the rib framework is lifted out. Wood arch centers are then put in place, and an inch of 1/2 plaster spread over the lagging before placing the concrete for the arch, which is 6 ins. Thick. Fig. 263. Invert form for sewer construction. The cost per 100 FT of this sewer was as follows: prices being assumed for cement and labor. Bottom concrete. Cost per 100 FT. 18. 5 BBLS. Cement at $1, $50.27. 75 2. 7 coup IDS. Sand at $1, 002. 7015 coup IDS. Stone at $1, 0015. 0017 days labor at $1, 5025. 5025. 25 BBLS. Cement at $1, 5037. 85 7. 5 coup ids, sand at $1.007, 50-22 days labor at $1, 50-33, 00 sewer arch, 26 BBLS. Cement at $1, 50-39, 003, 9 Ku, ids, sand at $1, 003, 90-13, 6 Ku, ids, stone at $1, 0013, 60-21 days labor at $1, 50-31, 50, cost per 100 FT, $237, 30 Fig, 264. Sewer at Cleveland, Ohio. Intercepting sewers, Cleveland, O. An intercepting sewer some 3.5 miles long of the form and construction shown in Fig. 264 was built at Cleveland, Ohio in 1904. The construction consists of a plain concrete invert lined with 2 courses of shale bricks, and having 2 rows of anchor bars set in the side walls so that the bars of one row are staggered with respect to those of the other row. The anchor bars are 2 in steel and are spaced 30 ins, apart in each row. To the anchor bars are bolted arch reinforcing bars arranged as shown, and these arch bars have bolted to them 8 lines of 1 at times in. Longitudinal bars. A natural cement concrete is used for the invert and side walls. The arch is Portland cement concrete of normally a 1 to 3 to 7.5, 1.5 in, screened stone mixture, but where the voids in the broken stone exceeded 40%. It is a 1 to 3 to 6 mixture. The invert bricks are laid in Portland cement mortar, and the arch has a mortar lining and is waterproofed with 1 in of mortar on top. Forms. Separate forms were used for the invert and for the arch ring. Regarding these, the engineer, Mr. Walter C. Palmley, remarks, one of the first forms used in the sewer was like a piece of segmental arch centering inverted, and with the lagging nailed fast to the ribs. The trouble with this form is that it is difficult to tamp concrete under the bottom portion of the form, and hence a very rough surface is produced. Much better results were obtained by omitting the lagging boards on the bottom, and at the sides till a point was reached where the inclination of the concrete surface was about 45 degrees. The concrete for the bottom could then be worked down between the ribs, thorough tamping done, and a good surface obtained. The ribs serve as a guide, so that the workman produces the proper shape. From this point up to the vertical, good results can be secured with the ribs attached to the lagging. Some contractors found it more convenient to use ribs that were connected with each other by a skeleton framework only, and then to slip the lagging in, 1 piece at a time. For some of the sewers, in which the brick lining was not carried quite up to the spring line, a separate side form of skeleton ribs and loose lagging was set upon brace legs bearing on the bottom of the invert. This form carried the concrete from about 2 ft, below to about 2 ft, above the springing line. The arch ribs then became segmental and rested upon the middle braces. This method has the advantage of using ribs that are lighter and more easily handled than those that are semicircular. For arch centering, it is necessary and convenient to use independent ribs and loose lagging, for the centers can then be carried forward piecemeal, the falsework upholding the green arch, and re-erected at the advance end of the work. In these matters, each contractor prefers to use his own ingenuity, and so long as the work is properly built, the engineer can well give him considerable latitude as to use of methods. One thing, however, the engineer must insist upon, that all centering and falsework be as nearly rigid as possible. Even a slight settlement of the centers at the crown under the load of concrete and backfill will cause the arch to kick out at the quarters, and if the green concrete arch is not cracked at the crown, it will be crushed on the inside, about halfway between the crown and springing line. A reinforced arch is no more immune to this danger than is a plain concrete arch. However, with a few days of hardening, although the damage may be serious, the danger of actual collapse is less. A point to be guarded against, especially in reinforced construction, is any foolish act on the part of contractor or workman, due to his overconfidence in the strength of the structure because it contains embedded steel. The mode of procedure in constructing the arch ring was to erect the centers with lagging complete. The lagging was then covered with building paper waterproofed with paraffin. The arch reinforcing bars were then bolted to the anchor bars and the longitudinals connected up. The lining of Portland cement mortar was first laid on the lagging. Before this mortar had set, concrete was rammed in between it and the sheeting to a height of 18 ins. Above the springing line, and then the remainder of the concrete placed without outside forms. The top of the arch ring was finally finished with a 1-in mortar coat. In regard to the concrete, Mr. Palmley remarks, concrete will flush up to the forms and produce a better surface, and the voids in the stone will be much better filled if it is so wet as to require but little tamping. Moreover, there is less danger of obtaining a weak, porous wall should a workman neglect thorough tamping, than there is where only a moist mixture is used. It is also to the contractor's interest to use wet concrete, for much less labor is required in mixing and placing it. Small broken stone or gravel is preferable in concrete for sewers, the walls being comparatively thin unless there be a considerable excess of mortar. If coarse stones are used, the concrete will be honeycombed with voids. The stones should be well graded in size from large to fine, but the largest fragments should not exceed 1/2 ins, in greatest dimension. Cost. A number of records of cost of constructing short sections of the sewer described are given by Mr. Palmley as follows. Labor placing anchor bars. Per day. 1 man at $3, $53. 51 man at $1, 75 1. 75 4 hours carrying steel at 20 CTS. 0. $86. 05 The anchor bars were placed for 40 lin. FT of sewer, or about 1,504 pounds, of metal at a cost of 0.4 CT per LB. The concreting gang for the sides consisted of 5 men wheeling and mixing at $1, 75 $8, 75 1 man tamping 1, 75 2/3 time man lowering brick and concrete at $2, 25 1, 51 man carrying concrete 1, 75 $13. 75 This gang built the side wall for 40 FT of sewer daily, or 13 ku. IDS, cost of labor per ku, YD, was therefore $1.06. The concrete was tamped behind the brick lining as the latter was built up by the mason. Cost of single ring brick lining at sides, 2 masons at 70 cents per hour, $1. 21 man mixing mortar 2. 25 1/3 time man lowering at $2, 25 0. 75 3 men wheeling sand, filling buckets and dumping 5, 25, total labor for 40 lin. FT of sewer $19, 45 quantity of brick masonry laid ku, YD, 6, 38 labor per ku, YD, 3.05 An account was kept of labor performed on 85 lin. FT of arch work, or 14 1 to 6 FT. Daily, the force was as follows. 1 man putting mortar lining on centering $1. 75 2 men mixing mortar, screening and wheeling sand 3. 51 man tamping concrete 1. 75 8 men on mixing board at $1. 75 14, 00, $21.00 no. Coup YD. Placed daily 25.64 labor per coup YD. 0. 82 placing centering and arch bars, 2 men at $1. 75 $3. 51 man at $3. 53. 50 $7.00 costs for 14 1 to 6 FT. Daily $0. 49 per lin. FT. As nearly as could be judged, about 2/3 of the labor was used in erecting the centering and 1/3 in putting the steel in place. The amount of steel placed daily was 785 pounds, at cost therefore of 0.3 of a cent per lb, and the cost of erecting and moving centers $0.33 per lin, ft, of arch. Another record of 39.27 ft. On a curve gave for the cost of the brick work at sides the same result as above, but the inspector's record of men working on concrete backing at sides showed a less cost, as follows: 4 men mixing at $1. 75 $7.00 2/3 time man lowering at $2. 25 1. 51 man in bottom 1. 75 $10. 25 they placed 12 7 coup YD at a cost of $0. 81 per coup YD. This figure probably more nearly represents the average cost than the $1. 0.6 reported in the first instance. The cost of placing the anchor bars on straight sewer representing average progress at another time was found to be 1 man $3. 51 man 1. 75 $5. 25 they placed the steel for 44 ft. of sewer or 1,650 lb at a cost of 0.32 of a cent per lb. Further notes for 6 days' work, when it seemed to represent as nearly as possible the general average for the whole were: labor on arch concrete. Daily progress was 13 1 to 6 ft. The force employed was 7 men making concrete at $1. 75 $12. 25 1 man plastering the center 1. 75 1 man mixing mortar 2. 0 1 man tamping 1. 75 $17. 75 on straight arch work they placed 24. 1 coup YD. Daily at a cost of $0. 74 per coup YD. In 3 days' work on a curve, the same gang placed 26 37 coup YD. Daily at a cost of $0. 675 per coup YD. On centering and steel for arch, 3 men kept up with the regular progress of the arch concreting gang. The cost, therefore, is 1 man $3. 52 men at $1. 75 3. 50 $7. 0 they averaged 13 ft daily, or at a total cost of about $0. 54 per lin ft of sewer. 2/3 of this labor was on the centering, or $0. 36 per lin ft of arch. $0. 18 per lin ft placed the steel ready for embedding, or about 55 5 lb per ft of arch at a cost of 0.32 of a cent per lb. For the double ring brick lining at the bottom, the regular daily rate of progress was 28 ft, or 15 coup YD. With 2 bricklayers $11, 25 men at $1, 75 8, 75 1 man at $2, 25 2, 25 $22, 20, or at a cost of $1. 98 per coup YD. This is given only because it is of interest in connection with the cost of the concrete. Other observations on cost of placing steel skeleton and concrete did not vary materially from the figures given. It will be observed that no charge for superintendents or anything for the general expenses is included in the estimates of cost. These charges were, of course, impossible to obtain. On another contract with machine mixing as high as 36 lin. FT of 13 FT, 6 in. Arch were built in a day, but no data as to cost were taken, though it was evidently less than for the work with hand-mixed concrete. Reinforced concrete sewer at Wilmington, Del. Records of a notable job of sewer construction at Wilmington, Del. In 1903 are furnished by Mr. T. Chalkley Hatton. The sewer was built by day labor for the city. Its cross-section at various points is shown by Fig. 265. The cross-section of sewers in trenches deep enough to cover the arch are marked deep cutting. The sections where the arch projects above the ground surface are marked light cutting. The section through the marsh was 700 FT, long, the cutting being 8 FT deep, and at high tide the marsh was flooded 1 to 4 FT. The material was a soft mud that would pull a tight rubber boot from a workman's foot. The cost of this marsh excavation, including cofferdams, under-draining, pumping, etc., was $4. 60 per coup YD for 1,100 FT. The 9 1/4 FT. Sewer was through a cut 22 to 34 FT deep, the material being clay underlaid by granite. A Carson-Lidgerwood cableway was used, although the crown of the arch was but 8 ins. Thick. It withstood the shock of dumping 1 coup. YD, buckets of earth and rock from heights of 3 to 10 FT, and the weight of 25 FT. Of loose filling caused no cracks in the concrete. Concrete was placed in 4 in. Layers, the depth of the lagging and well rammed, since it was found that wet concrete left small honeycombed spaces on the inner surface. Concrete for the invert was 1 to 2 to 6, the stone being 1 1/2 in, and smaller, and the sand being crusher dust. The arch was 1 to 2 to 5, the reinforcing metal used in the 9 1/2 FT. Sewer was no. 6 expanded metal 6 in, mesh in sheets 8 times 5 1/2 FT, supplied by Merritt & Co. of Philadelphia. A single layer was placed around the sewer 2 ins. From the inner surface, its position being carefully maintained by the men ramming, and with but little difficulty as the sheets were first bent to the radius of the circle. Each sheet was lapped 1 mesh 6 ins over its neighbor at both ends and sides, and no sheets were wired except the top ones, which were liable to displacement by men walking over them. Fig. 265. Cross-sections of sewer at Wilmington, Del. The metal used on the rest of the work was a wire-woven fabric furnished by the White Easton Townsend Co. of New York. This fabric comes in rolls 5 1/2 FT, wide and 100 FT to the roll. The wire is no. 8, with a 6 times 4 in. Mesh. This fabric was placed by first cutting the sheets to the required length to surround the sewer entirely, embedding it in the concrete as fast as concrete was placed, in the same manner as was done with the expanded metal except over the center where, on account of its pliability, the fabric was held the proper distance from the lagging by a number of 2 in. Blocks which were removed as the concrete was placed. The wire cloth, being all in 1 sheet, can be placed a little more expeditiously than expanded metal, but on the other hand, the expanded metal holds its position better in the concrete, since it is more rigid. We quote now from Mr. Hatton's letter. The major portion of concrete was mixed by machine at a cost of 66 CTS. Per yard, including wheeling to place, coal, and running of mixing machine, wages being $1. 50 per day of 8 HRS. Stone was delivered alongside of machine, and all material had to be wheeled in barrows upon the platform, and after mixing to the sewer. Placing and ramming concrete around the forms cost 39 CTS. Per coup, YD, additional. Setting forms in invert cost 2 CTS. per coup, YD, setting centers 7 CTS, per coup, YD. Cost of setting forms and centers includes placing steel metal. Each lineal foot of 9 a quarter FT. SUA contained 1 coup, YD, of concrete, although the section only calls for 0.94 coup, YD. The excess was usually wasted by falling over sides of forms or being made too thick at crown. This yard of 1 to 2 to 5 concrete cost in place as follows, record taken as an average of several days run. Cement 1, 31 BBLS at $1, $31. 703 stone 0, 84 coup, IDS at $1, 21 1. 0, 16 stone dust 0, 42 coup, YD at $1, 21 0. 508 labor at 18 3/4 CTS. Per hour 0. 987 labor setting forms and setting metal 0. 0.45 cost of forms distributed over 1,800 FT of SUA 0. 0.8240 SQ, FT, expanded metal at 4 1/4 CTS. 1. 700 labor plastering invert 0. 0.70 cost per FT or per coup. YD $6. 111 the forms for the invert were made of 2 in. Rough hemlock boards cut out 4 ins, less diameter than the diameter of the SUA except for 18 ins, at the bottom of the form which coincided with the inside form of SUA. The bottom of the SUAs was laid to the bottom of this form before it was set. Then the lagging, consisting of 2 times 6 in, times 16 FT. Hemlock planed was placed against each side of the form, one at a time, and the concrete brought to the line of this top in 6 in. Layers until the whole invert was finished. These forms were set in 16 FT. Sections, 5 to each section. The centers consisted of 7 ribs of 2 in. Hemlock upon which was nailed 1 1/2 in. Lagging, 2 ins. Wide, tongued and grooved, and were 16 FT. Long, non-collapsible, but had 1 wing on each side, 9 ins. Wide, which could be wedged out to fit any inaccuracies in the invert. We used 4 of these centers, setting 2 at each operation, and worked from 2 ends. We left the centers in for 18 hours before drawing. The cost of the concrete on the smaller SUAs was the same as are the larger SUAs, but the steel metal cost less, as it was wire-woven metal that cost 2 1/2 CTS. Per SQ, FT. It was much easier handled and cut to no waste as it came in long rolls and was very pliable. After training our men, which occupied about 1 week or 10 days, we had no difficulty in getting the concrete well placed around the metal, preserving the proper location of the latter, which, however, bore constant watching, as a careless workman would often take the temporary supporting blocks and allow the metal to rest against the wooden center, in which case the metal would show through the surface inside of the SUA. The metal was kept 2 ins, away from the inside forms and the arch. To keep it at this location, we had several 2 in. Wooden blocks cut which were slipped under the wire or expanded metal, and as soon as some concrete was pushed under the wire at this point, the block was removed. After the forms were removed, the invert needed plastering, but the arch was practically like a smoothly plastered wall, except where it joined the invert, where it frequently showed the result of too much hurry in depositing the first loads of concrete on the arch. We remedied this by requiring less concrete to be deposited at the start, thus giving the rammers time to place the material properly. An interesting result was obtained in the smoothness of the inside surface by using a mixture of different sized stones. When 3/4 in, stones or smaller were used in the arch, the inside was honeycombed, but where 1 to 1 1/2 in, stones nothing smaller were used, the inside was perfectly smooth, and the same was true of the invert, showing that the use of larger stones is an advantage and secures more monolithic work. When the run of the crusher from 1/2 to 3/4 in stones was used, the work was not at all satisfactory. The difference in cost of mixing by hand and machine is practically nothing on this kind of work, as the moving of the machine to keep pace with the progress of the work equals the extra cost of mixing by hand when the mixing can be done close to the point where the cement is being placed. The total cost of the sewers, including excavation, etc., was cost per lin, ft. 9/4 ft. Sewer through marsh $32.009/4 ft. Sewer and cut averaging 24.5 ft. 24.006/2 ft. Sewer and cut averaging 12 ft. 10.005 ft. Sewer and cut averaging 11.5 ft. 6.70 sewer with monolithic invert and block arch. The following records of construction for a sewer built at Coldwater, Mich. in 1901 are given by Mr. H. V. Gifford. The sewer had a monolithic invert and a block arch. The sewer was circular, having an inner diameter of 42 ins. The thickness of the invert and the arch alike was 8 ins. Figure 266 is a cross-section. The concrete was one of Portland cement to 6 of gravel. There were 11 concrete blocks in the ring of the arch, each block being 24 ins, long 8 ins, thick 8 ins, wide on the outside of the arch, and 5 3/4 ins, wide on the inside of the arch. A block weighed 90 pounds, which was too heavy for rapid laying. Blocks 18 ins. Long would have been better. Some 8,500 blocks were made. Molds were of 2 in. Lumber lined with tin, for after a little use it was found the concrete would stick to the wood when the mold was removed. The 4 sides of the mold formed the extrados, the intrados, and the 2 ends of the block, the other 2 sides being left open. When put together, the mold was laid upon a 1 in board, 12 times 30 ins, reinforced by cleats across the bottom. The sides of the molds were held together with screws or wedge clamps. When the blocks had set, the sides of the molds were removed, and the blocks were left on the 12 times 30 in boards for 3 days, then piled up, being watted several times each day for a week. A gang of 14 men made the blocks, 2 screening gravel through 1 in mesh screen, 4 mixing concrete, 4 molders, 3 shifting and watering blocks, and 1 foreman. With a little practice, each molder could turn out 175 blocks a day, and since each block measured 3/4 cu. ft, the output of the 14 men was 19.5 cu. ids a day. Mr. Gifford informs us that the wages were $1.50 a day for all the men except the foreman. The daily wages of the 14 men were $22, so that the labor of making the blocks was $1.10 per cu. yd. Fig. 266. Sewer with monolithic invert and block arch, each batch of concrete containing a half bbl of Portland cement costing $1.35 per bbl made 18 blocks. 1 bbl per cu. yd. Since the gravel cost nothing except the labor of screening it, the total cost of each block was 11 to 12 cts, which includes 0.85 cent for use of molds and mold boards, which were an entire loss. At 12 cts per block, the cost was $4.32 per cu. yd. The contract price was $3 per lin. ft of this sewer, as against a bid of $3.40 per ft for a brick sewer. When the trenching had reached to the level of the top of the invert, 2 rows of stakes were driven in the bottom, stakes being 6 ft apart in each row, and rows being a distance apart a quarter in, greater than the outer diameter of the sewer. These stakes were driven to such a grade that the top of a 2x4 cap or runner set edgewise on top of them was at the proper grade of the top of the invert. The excavation for the invert was then begun, and finished to the proper curve by the aid of a template drawn along the 2x4 runners. In gravel, it was impossible to hold the true curve of the invert bottom. Concrete was then placed for the invert. To hold up the sides of the invert concrete, a board served as a support for the insides, but regular forms were more satisfactory in every respect except that they were in the way of the workmen. A form was tried, its length being 6 ft. It was built like the center for an arch, except that the sheeting was omitted on the lower part of the invert. It was suspended from the crosspieces resting on the runners. After the concrete had been rounded in place, the form was removed and the invert trued up. This form worked well in soil that could be excavated a number of feet ahead, so that the forms could be drawn ahead instead of having to be lifted out. But in soil, where the concreting must immediately follow the excavation for the invert, the form is in the way. The invert was trued up by drawing along the runners a semicircular template having a radius of 21½ inches. Then a ½ coat of 1 to 2 mortar was roughly troweled on the green concrete. Another template having a 21 radius was then drawn along the runners to finish the invert. When the plaster had hardened, 2 courses of concrete blocks were laid on each shoulder of the invert, using a 1 to 2 mortar, the a-quarter part being lime paste. The lime made the mortar more plastic and easier to trowel. Then the form for the arch was placed, and as each 8 ft section of the arch was built, a grout of 1 to 1 mortar was poured over the top to fill the joints. Earth was thrown on each shoulder and tamped, and the center moved ahead. Common laborers were used for all the invert work, except the plastering, which was done by masons who were paid 30 CTS per HR. Masons were also used to lay the concrete blocks in the arch. Mr. Gifford states that 2 masons would lay at the rate of 100 lin. ft of arch per day if enough invert were prepared in advance. As there were 11 blocks in the ring of the arch, this rate would be equivalent to 7½ cu. Ids of arch laid per mason per day. Fig. 267. Concrete block manhole. Cost of block manholes. The following costs of constructing concrete block manholes for electric conduit at Rye N.Y. were recorded by Mr. Hugh C. Baker, Jr. The arrangement of the blocks, their size and shape, and the dimensions of the completed manholes are shown by Fig. 267. The blocks were molded of 1 to 2 to 5 3/4 in. Broken stone concrete in 30 wooden molds made by a local carpenter at a cost of from $3.50 to $12 each. The concrete was placed in the molds very wet, with very little tamping, and was allowed to set for 7 days before the blocks were moved to the work. The molds were left in place from 24 to 36 hours. With the facilities at hand, 6 complete sets of top blocks were made each day by 4 men. When no wall blocks were being made and half a set, 15 wall blocks and 2 sets of top blocks were made each day by 4 men. The cost of the block manholes complete was as follows per manhole: 30 wall blocks, 2½ cu. Ids, $21. 006 cover blocks, 1½ cu. Ids, reinforced for 27 I-beams for cover in place 5, 40 supervision, freight hauling 5, 6 tons concrete 9, 38 labor placing cover 3 HRS at 15 CTS, 0, 45 labor placing walls 20 HRS at 15 CTS, 3, $00 total exclusive of iron cover $43. 50 cement pipe constructed in place. In constructing A10, cement sewer for the Foster Armstrong Piano Co. S works at Rochester, N.Y. A gang of 7 men averaged 300 ft of pipe per 10-hour day using a ransom pipe mold. The mold is shown by Fig. 268. It is made of sheet steel with an inner core 10 ft long, the front end of which is surrounded with a sheet steel shell that serves as an outer form for the pipe. The mortar, mixed rather dry, was packed into the annular space between core and shell by one man using a short wooden rammer. A second man kept the mold slowly moving forward by operating the lever, which by means of a ratchet and drum winds up a wire rope stretched ahead to a deadman in the trench bottom. As the mold moves ahead, it leaves behind it the cement pipe. A third man carefully filled under the invert and over the haunches of the green pipe with earth to give it support. The following was the itemized cost per day: 300 ft of pipe laid, 6 men at $1. 70 per 10-hour day, $10. 21 foreman 3, 003 BBLS. Cement at $1, 25 3, 75 3, 3 Ku. IDS. Sand at 85 CTS. 2, 80 water 0, 15, total for 300 Lin. FT, $19, 90. This is equivalent to 663 CTS per Lin. FT of pipe, Fig. 268. Ransom continuous mold for concrete pipe construction. In trans. C. E. Vol. 31, 1894, p. 153. James D. Schuyler gives the cost of cement pipe made by the Ransom system for the Denver Water Works. There is a wrought iron shell of the size of the inner diameter of the pipe forming the inner mold. To this shell is attached a leader and saddle of larger diameter forming the outer mold. These molds are drawn slowly along the trench by a cable and horse whim, and the concrete is shoveled continuously into the core space between the molds and rammed on a long incline. The top half or arch of the pipe is supported by sheet iron plates, 2 ft wide, placed one after another on the forward end of the mold, and being clamped together at the top and sides, remain in position after the mold is slid out from under them. After the mold has passed along, these iron plates are supported by upright sticks and by horizontal clamping rods. The plates are left in place for 24 to 48 HRS. The concrete, made 1 to 3.5, river sand and gravel, was machine mixed. A gang of 30 men mixed, wheeled, shoveled, and tamped the concrete, attended to the plates, cleaning and greasing them, etc. This gang would make short runs at the rate of 900 Lin. FT of pipe a day, but counting stoppages, the average rate was 300 FT a day. The inner diameter of the pipe was 38 ins, and its bottom was molded flat for a width of 18 ins. The concrete shell was 2.5 to 3 ins thick. The pipe was washed with pure cement grout, applied with brushes after removing the iron plates. With cement at $3, 75 per BBL, gravel at $1, 25 per Ku, YD, and labor at $1, 75 to $2 per day. The cost of this pipe was $1, 35 to $1.50 per FT. After the gang was well organized, pipe sewer St. Joseph, Mo. In constructing extensions to 36 in, 42 in, 48 in, and 72 in. Sewers at St. Joseph, Mo. Reinforced concrete pipe of the form shown by Fig. 269 was employed. The thickness of shell for the various sizes was 4 ins, 4.5 ins, 5 ins, and 7 ins. All sizes were made in 3 ft lengths, one end of which is rebaited and beveled to form a spigot, and the other end of which is chamfered on the inner edge to receive the bevel of the spigot. This jointing leaves a circumferential groove, into which the hooked ends of the longitudinal reinforcing bars project in such a way that a circular hoop can be threaded through them to connect successive lengths. The reinforcement is of the same form for all sizes of pipe, but 7 longitudinals were used in the 72-in size and 5 for all smaller sizes. The circumferential bars were in all cases spaced 1 9-ins from each end. The pipe, as described, is the standard pipe made by the Reinforced Concrete Pipe Co. of Jackson, Mich., and is covered by patents. The practice of this company is to manufacture the pipe itself on the ground and furnish it to the contractor. It does not contract to build sewers, nor does it dispose of rights to manufacture to contractors. Fig. 269. Jackson Concrete Sewer Pipe. Pipe molding. The pipe is molded endwise. A bottom plate so shaped as to form the hub or receiving end of the pipe is set up. On the upper or inner flange of this cast iron bottom plate is set the core defining the inside diameter of the pipe. This core is in 4 segments of sheet steel. The longitudinal reinforcing bars are next inserted in slots in the bottom plate, and the outside form of sheet steel is then set up on the lower and outer flange of the bottom plate. Spacing clips on the top edge of the outer shell hold the tops of the reinforcing bars in position. The concrete is then shoveled into the annular mold and tamped until it reaches the level for the first circumferential reinforcing bar. This is then placed by removing the spacing clips, threading the hoop over the longitudinal bars, and sliding it down to position. Filling and tamping then proceeds until the second hoop is to be placed. This is placed exactly like the first, and filling and tamping then proceeds until the mold is filled. At the St. Joseph work a 1 to 2 to 3 mixture with crushed limestone aggregate ranging from pea size to 1 in. Stone was used. The molding was done in tents which were heated by coke fires in salamanders in freezing weather. Pipe laying. In laying, the pipes are handled and lowered into position just as a cast iron water pipe. Successive lengths are placed by inserting the spigot ends into the chamfered hub ends, and then threading the tie hoop through the hooked ends of the projecting longitudinal reinforcing bars. A strip of galvanized iron is then passed under the pipe and bent up so as to girdle the circumferential groove except for a space at the top. The groove is then pawed with a wet 1 to 2 cement mixture, which, when hardened, completes the joint. Cost of molding small cement pipe. Mr. Albert E. Wright gives the following account of the method and cost of molding and laying 6 to 12 in. Cement pipe for irregular work at Irrigan, or. The pipe was 6 to 12 ins. Inside made of Portland cement and clean, sharp sand of all sizes up to very coarse. The mortar was mixed rather dry but very thoroughly using 14. 1 cu. ft. of sand to 1 bbl of cement, or very closely a 1 to 4 mixture. From 6 to 7 buckets of water were used to each barrel of cement, except for the 6-in pipe, for which the mortar had to be made somewhat stiffer in order to remove the inner form, which was not made collapsible as in the larger sizes. The forms were sheet iron cylinders with a longitudinal lap joint that could be expanded after molding the pipe, and removed without injuring the soft mortar. The inner form was self-centering, so that there was little variation in the thickness of the pipe. 4 men were required in making cement pipe by hand. One mixed the mortar and wheeled it to the place of work. Another threw it into the form a little at a time with a hand scoop. A third rammed it with a tamping iron, and a fourth kept the new pipe sprinkled, and applied a coat of neat cement slurry to the inside when it was sufficiently hard. In molding, the form of the bell at the bottom was secured by an iron ring that was first dropped into the form, and the reverse or convex form at the top was made with a second ring. While still in its form, the pipe was rolled or lifted into its place in the drying yard, and the form was then carefully removed. A very slight blow in removing the form would destroy the pipe, and a considerable number, especially of the larger sizes, collapsed in this way and had to be remolded. To avoid handling, the pipe was stacked on end a few feet from the place of mixing, the form being moved as the yard filled with pipe. One crew of 4 men could make about 250 joints or 500 ft of pipe a day. As soon as hard enough, the pipe was turned end for end, and was then kept wet for several weeks before being laid. The coating of neat cement on the inside was applied with a short whitewash brush, and was a small item in the cost. In laying, the trench was carefully finished to grade in order to have the joints close nicely, and the ends were well wet with a brush. The mason then spread mortar, mixed 1 to 2 on the end of the pipe, and laid a bed of mortar at the bottom of the joint. He then jammed the section into place and swabbed out the inside of the joint with a stiff brush to ensure a smooth passage for the water. A band or ring of mortar was spread round the outside of the joint as an additional reinforcement. 1 barrel of cement would joint about 300 sections of pipe. The materials cost as follows: Portland cement per BBL, $4. 45 labor per day, $2. Foreman per day, $2. 50 to $3. Hauling per load mile, 1 coup. YD. 20 CTS. Sand free at pit, water free. The pipe was all of a 1 to 4 sand and cement mortar, and the amount of cement in 1 foot of pipe was arrived at by assuming that where the sand has voids in excess of the cement used, the mortar will occupy 1. See Chapter Roman 2 times the space of the dry sand, which yields the following formula, where C equals cost per BBL of cement or $4, 45. N equals Q FT in 1 BBL. Taken at 3.5 here. S equals ratio of sand to cement or 4. D equals inside diameter in inches. T equals thickness of pipe in inches. L equals length of pipe considered, or 1 FT, here. Then, C times L times pi times DT plus T2, cement cost per foot equals A. N times S times 1. 1 times 144, which gives here equals 4. 45 times 1 times 3. 142 DT plus T2 equals 0. 00631 DT plus T2. 3. 5 times 4 times 1. 1 times 144, this gave the following cement costs per lineal foot. Diameter ins, thickness ins, cost per foot. 6 1 a quarter $0. 05718 a quarter 0. 0730 10 1 0. 0998 12 1 a half 0. 1278. The sand cost was based on 15 CTS per cubic yard for loading and a haul of 2 miles of 1 coup. YD. To the load, making 5 trips per day at $4 for man and team. It bears a constant ratio to cement cost, being 2% of the cement cost. The labor cost of making was based on the foreman's estimate that a foreman, tamper, mortar mixer, and water man should finish 250 joints a day of 6 or 8 in. Pipe. For the 10 and 12 in. Pipe, the labor was assumed to be greater in proportion to the material. The foreman was taken at $3, 1 man at $2, 50 and 2 at $2. The cement for painting the inside was neglected. Hauling the pipe to place was taken at twice the cost of hauling the sand per mile, and a haul of 4 miles was assumed. The cost of laying was based on a foreman's estimate of 2 CTS per foot for trench, and that 1 man to lay. 1 man to plaster the joints, 1 helper and 1 man to backfill would lay 600 FT per day of 6 or 8 in pipe. The larger sizes were assumed to cost more in proportion to their material. These various costs gave the following results for small size pipe. Cost per foot for 6 in pipe, 8 in pipe, 10 in pipe, 12 in pipe. Cement $0, $0.57 $0, $0.73 $0.99 $0, 128 sand 0, 0060, 0080, 011 0, 014 labor 0, 019 0, 019 0, 026 0, 034 hauling 0, 024 0, 032 0, 044 0, 056 laying 0, 024 0, 024 0, 032 0, 042 trench 0, 020 0, 020 0, 020 0, 020 totals $0, $15 $0, $176 $0, $232 $0, 294. The above costs show that the pipe in place costs about twice as much as pipe in the yard, even with cement at $4. 45. Fig. 270. Bordenave pipe for Swansea, England Water Works. Molded pipe water main, Swansea, England. As a good example of foreign practice in molded pipe conduit work, a water main constructed at Swansea, England, has been selected. This pipeline had to operate under a head of 185 FT. It was constructed under the patents of the French engineer, Mr. R. Bordenave, who has built many miles of the same type of conduit on the continent. Fig. 270 shows the construction of the pipe, the drawing being a part longitudinal section through the shell at the joint. The pipe consists of an inner and an outer reinforcement separated by a sheet steel tube and all embedded in a 1-to-2 mortar. Both inner and outer reinforcements consists of longitudinal bins of cruciform plus section wound by a spiral bar of the same section wired to them at every intersection. Only the outer reinforcement and the steel tube are considered in calculating the strength of the pipe, the inner reinforcement being considered as simply supporting the mortar. Fabrication of reinforcement. The steel tube is made of 1 mm, 0.04 in. Thick sheets of steel bent to a cylinder and jointed longitudinally by welded butt joints, welded by a blowpipe using acetylene and oxygen. Tests of this welded joint by R.H. Wyrill, Waterworks engineer, Swansea, showed it to be quite as strong as the unwelded steel cut from the shell. The circumferential joints of the tube were made by turning up the edges of the sheets and welding them. This gives a flexible, watertight joint. The tube was made in lengths of 9 FT, 9.5 ins, and its ends were turned up all around. Just back from the turned-up ends, a vertical sheet steel collar was welded to the tube to form a strip end for the external coating. These details are shown in Fig. 270. When the tube for a length of pipe is completed, the inside shell reinforcement previously made is slipped into it, and the outside shell reinforcement is formed on it as a mandrel, as shown by Fig. 271. Fig. 271. Applying external reinforcement to Bordenave pipe. Fig. 272. Casting Bordenave pipe at Swansea, England. Molding. When the 3 positions of the steel skeleton were completed, as shown by Fig. 271, they were set on curved wooden curbs made to the exact shape necessary to center them and preserve the correct thickness of cement coating. A collapsible core was lowered into position in the inside, and a two-part sheet steel mold was erected outside. The space between core and mold was then poured with a thin mortar of 1 part Portland, cement to 2 parts clean river sand. During the process of pouring, the outer steel mold is sharply struck with wooden mallets to facilitate the escape of air bubbles. The mortar was mixed on an elevated traveling platform which is shown in Fig. 272, which also shows a completed pipe, a core being withdrawn, a filled mold, and a section of reinforcement set up. The difficult feature of the molding process was found to be the determination of the time for withdrawing the core and removing the exterior mold. The time of setting of the mortar was different in warm and in cool weather and varied with the wetness of the mixture, the brand of cement, etc. By using a single brand of cement that ran very uniform in quality and time of setting, it was possible, however, for the workmen, after a little practice, to gauge very accurately the correct time for